Artificial intelligence has spent years solving one problem by buying more hardware, more GPUs, more memory, more power, larger data centers, faster networking, and increasingly expensive cooling systems. But Chinese researchers at Peking University say they have demonstrated another path. Instead of making one processor dramatically more powerful, they connected several modest processors with light and redesigned the neural network so every chip could work at the same time. The result was extraordinary. Their hybrid optical system completed a distributed artificial intelligence inference task nearly 149 times faster than a commercial GPU. Even though the combined processors provided only about 1/9 of the GPU's theoretical computing capacity. The system processed 1,000 images in 105.16 microseconds. The GPU needed 15.643 milliseconds for the same workload. The Chinese system was not powered by a magical all-optical processor. It did not train a giant language model, and it did not replace NVIDIA's most advanced accelerator. The computing was still performed electronically on 5 programmable FPGA chips. What changed was the connection between them. Each processor was linked through custom silicon photonic transceivers capable of 400 gigabits per second and a 16 by 16 optical switch that routed information using light instead of conventional electronic switching. That allowed the 5 stages of a neural network to operate like an assembly line. While one chip processed the first layer of a new image, the next chip processed the second layer of an earlier image, and the remaining chips worked on later stages simultaneously. The processors stopped waiting for one another. They stopped repeatedly moving intermediate data into distant memory, and nearly all of their available computing capacity was finally used. The question is not whether China has built a chip that is simply 100 times more powerful than every NVIDIA GPU. It has not. The real question is more important. What happens if the biggest limitation in artificial intelligence is no longer calculation but the time and energy wasted moving data between calculations? Because if light can remove that bottleneck, the future of AI may depend less on purchasing more GPUs and more on connecting the chips we already have far more intelligently. The bottleneck nobody sees. A modern AI accelerator can perform trillions of mathematical operations every second, but raw arithmetic is only one part of the job. Before a processor can calculate, it needs data. It needs model weights, input information, intermediate feature maps, instructions, and results produced by earlier stages. All of that information must move between memory, processors, network devices, and sometimes separate servers. The physical movement of data creates delay. It also consumes energy. A processor may be capable of an enormous theoretical performance, yet achieve only a fraction of that performance if its computing units spend time waiting for information. This is often described as the memory wall or communication wall. The industry's normal response is to build faster memory and wider electrical connections. High bandwidth memory places stacked DRAM beside an accelerator. Advanced packaging shortens the distance between chiplets. NVLink, InfiniBand, Ethernet, and other systems connect processors inside and between servers. These technologies are powerful, but they cannot completely escape the physical limits of electrical signaling. As data rates increase, electrical links lose more energy, generate heat, become harder to route, and require additional circuitry to recover and correct signals. The problem becomes even more difficult when an AI workload is divided among several processors. One processor may finish its assigned calculation and then wait while data travels to the next processor. If every stage operates sequentially, adding more chips may increase theoretical capacity without producing an equivalent increase in real performance. The Peking University team attacked this problem from 3 directions at once. They changed the interconnect, they changed the processing architecture, and they changed how the neural network algorithm was divided across the hardware. That combination is why the result matters. What the researchers built. The experimental system contains 3 main pieces. The first pieces are 5 field programmable gate arrays, commonly called FPGAs. An FPGA is a chip whose internal logic can be reconfigured after manufacturing. Unlike a fixed processor designed for one permanent architecture, an FPGA allows engineers to create custom data paths, processing units, buffers, and interfaces for a specific task. FPGAs are widely used in telecommunications, industrial systems, autonomous vehicles, aerospace equipment, data centers, and hardware prototypes. They are not automatically faster than GPUs. Their advantage is flexibility. Engineers can organize the hardware around one workload instead of forcing that workload through a general architecture. In this experiment, each FPGA handled one layer of a 5-layer convolutional neural network. The second component is a custom silicon photonic transceiver attached to each processing chip. The FPGA produces electrical data. The transceiver converts that data into optical signals, sends it through the network, receives incoming light, and converts it back into electrical form for the next processor. Each transceiver provided a 400 gigabit per second optical input and output interface. The third component is a non-blocking 16 by 16 optical switch. A non-blocking switch can connect available inputs to outputs without forcing one route to interfere with another. The device was manufactured on a silicon planar lightwave circuit platform. It operated around a wavelength of 1,300 nanometers and produced total optical loss of no more than 5 decibels across a broad spectral range. The network transmitted data at 400 gigabits per second, without errors and without optical amplification during the test. Together, these parts formed a reconfigurable optical fabric, capable of connecting as many as 16 processing chips. The researchers used 5 processors for the demonstrated AI workload, but the central switch provides room for a larger system. In theory, 16 400 gigabit links would provide up to 6.4 terabits per second of aggregate switching bandwidth, although the actual system remains limited by the input and output capabilities of the attached processors. How the optical pipeline works. The most important innovation is not simply replacing a copper cable with fiber. The researchers created what they call optical pipeline parallelism. Imagine a factory assembling a product in 5 stages. If one worker completes every stage alone, the next product cannot begin until the previous product is finished. Adding 5 workers does not help if all 5 still wait for the same product and work one after another. A pipeline changes the process. The first worker completes stage 1 and passes the product to the second worker. The first worker immediately begins stage 1 on the next product. Soon, all 5 workers are active simultaneously, each handling a different stage of a different product. After the pipeline fills, completed products emerge continuously. The Chinese system applied this idea to neural network inference. The 5-layer image denoising network was divided across 5 FPGAs. The first FPGA performed the first convolutional encoder stage. Intermediate feature maps moved directly from one FPGA to the next through the optical network. Each processor used local on-chip memory to buffer incoming data and digital signal processing units to execute its assigned convolution. Because each layer remained permanently deployed on its own FPGA, the system did not need to repeatedly load new kernels, store every intermediate result in external memory, and then retrieve that result for the next layer. Once the pipeline was filled, all 5 processors worked concurrently. This is where the enormous latency advantage came from. The optical link provided enough throughput to keep the pipeline moving, while the specialized hardware mapping prevented the processors from becoming idle. The demonstration. The researchers tested the architecture using a 5-layer convolutional neural network trained to remove noise from images in the Fashion MNIST dataset. Fashion MNIST contains simple grayscale images of clothing items. For the experiment, each image had a resolution of 32 by 32 pixels. Every pixel was represented using 32-bit floating point precision, giving 32,768 bits per image. Each network layer used a 5x5 convolutional kernel, followed by a rectified linear unit activation. The feature maps were reduced to 28 by 28 pixels during convolution and then padded back to 32 by 32. The model was trained offline before being deployed onto the FPGAs. That distinction is important. The optical system demonstrated inference, meaning it used an already trained model to process new inputs. It did not perform the much more demanding process of training the model from the beginning. The researchers sent 1,000 images through the completed pipeline in batches of 10. The total measured latency was 105.16 microseconds. The 5 FPGAs used a combined total of 5,040 digital signal processing units running at 390.625 MHz. Their estimated peak FP32 computing rate was about 1.969 teraflops. For the 1,000 image workload, the network required about 196 million floating point operations. Under perfect utilization, the calculation should have taken approximately 99.6 microseconds. The measured result of 105.16 microseconds means the computing hardware achieved 94.7% utilization. That number may be more significant than the headline speedup. The system did not win because it contained more arithmetic power. It won because almost all of its smaller arithmetic capacity remained busy. The GPU comparison. For comparison, the researchers ran the same workload using 32-bit floating-point precision on a commercial GPU. The paper describes that GPU as containing 3072 CUDA cores operating at 2.76 GHz, with a theoretical FP32 performance of approximately 16.96 teraflops. On paper, the GPU provided more than 8 times the raw computing capacity of the 5 FPGA system, yet it required 15.643 milliseconds to process the images. That made the optical pipeline nearly 149 times faster while using only 11.6% of the GPU's theoretical computing resources. This sounds impossible until we separate peak performance from workload efficiency. The GPU handled the 5 network layers sequentially. After completing one layer, it stored the intermediate feature map in external memory. It then prepared the weights for the next layer, fetched the stored feature map, and resumed calculation. The GPU's thousands of cores were extremely powerful, but this particular workload was too small and too sequential to keep them fully occupied. Launching operations, moving data, changing layers, and accessing memory consumed far more time than the arithmetic itself. The FPGA system was purpose-built for the network. Every layer had dedicated hardware. Data streamed continuously between those layers. The optical pipeline removed much of the waiting. This is a valid comparison for the demonstrated task, but it is not proof that 5 FPGAs will beat every GPU by 149 times on every AI model. A larger GPU batch, a better optimized implementation, a different network, or a heavier workload could produce a very different result. Modern GPUs are designed to handle enormous parallel workloads, and they become more efficient when enough computation is available to fill their cores. The experiment instead reveals how badly a powerful general processor can perform when communication and scheduling dominate a relatively small latency-sensitive task. Why light changes the equation? Light offers several advantages for chip-to-chip communication. Different wavelengths can travel through the same waveguide or fiber simultaneously. This allows wavelength division multiplexing, where several independent data channels share one physical path. Optical signals can also travel across longer distances with lower loss than extremely high-speed electrical signals. They do not create the same electromagnetic interference, and a passive optical switch does not need to inspect, buffer, schedule, and retransmit every packet like a conventional electronic switch. In the Peking University system, the switch acted as a physical routing fabric. The researchers removed much of the overhead associated with a full Ethernet networking stack. They retained essential encoding and error correction functions, but the optical switch itself performed no packet queuing or buffering. That helped keep latency extremely low. However, the system was not completely optical. The FPGAs still calculated electronically. The transceivers still converted between electricity and light. Memory remained electronic. Control logic remained electronic. The correct description is hybrid optoelectronic computing. Light handled high-speed communication, while electronic processors handled the neural network mathematics. This hybrid approach may be more practical than trying to replace every transistor with a photonic device. Why this matters for AI data centers? The AI industry is currently building larger clusters because individual chips cannot contain the largest models or serve every user alone. Thousands of accelerators must communicate during training and inference. The faster processors become, the more damaging communication delays become. A GPU that finishes its work quickly may simply spend more time waiting for another GPU, memory bank, or network switch. This creates a paradox. Companies purchase more computing power, but a growing portion of that power can be lost to coordination. Optical interconnects could help at several levels. The Peking University demonstration focuses on a tightly coordinated group of processing chips executing a pipeline. It shows that co-designing the algorithm and the interconnect can produce far more useful performance from modest hardware. That idea is especially relevant for inference. Many inference applications care about latency more than total throughput. An autonomous vehicle, industrial robot, medical instrument, communication system, or edge device may need an answer immediately. Waiting several milliseconds can matter. A specialized optical pipeline could process a fixed model with very low delay while using less expensive computing hardware. Large cloud systems could also divide frequently used models into permanent pipeline stages, although real commercial workloads are far more complicated than the demonstrated denoising network. What the headline does not mean, the phrase 100 times faster without more GPUs, is accurate only within the context of this experiment. China has not created a universal processor that makes NVIDIA obsolete. The system did not outperform a current flagship accelerator across large language models, generative video, scientific simulation, and model training. It processed a small 5-layer convolutional network on 1032 by 32 images. The comparison used one commercial GPU with 3072 CUDA cores, not an entire modern AI cluster. The model was already trained. The researchers did not publish a complete commercial power comparison showing that the entire optical system used 1/9 of the energy. They reported 1/9 of the theoretical computing resources. The transceivers, optical switch, FPGA boards, control systems, and supporting equipment still consume power. The system also used 5 separate processing boards to defeat one GPU on a workload specifically mapped to those boards. That does not invalidate the result. It defines what the result actually proves. The experiment proves that communication architecture and algorithm mapping can matter more than peak teraflops for some workloads. It proves that an optical network can transmit 400 gigabit data streams without errors while connecting multiple computing nodes. It proves that a carefully designed pipeline can keep modest processors operating near their theoretical limit. And it proves that buying a larger processor is not always the most efficient answer. The scaling challenge. The researchers acknowledge that the demonstration remains small compared with modern AI workloads. 5x5 convolution kernels and a 5-layer network are not comparable to a large transformer containing billions or trillions of parameters. Scaling the architecture would require more processors, more memory, more optical channels, more sophisticated scheduling, and support for many different computational operations. The current system's remaining bottleneck was not the optical transceiver. It was the input and output capability of the FPGAs. The paper notes that the photonic technology can already support 200 gigabits per second on each wavelength and aggregated transceiver capacities up to 1.6 terabits per second. Future processing chips would need more high-speed channels to exploit that bandwidth. The optical switch can theoretically connect 16 processors, but larger AI systems may require hundreds or thousands of nodes. Engineers would need multi-stage optical networks, fault tolerance, calibration, monitoring, and software capable of placing models across changing hardware. Programmability is another challenge. The demonstrated network benefited from a simple model with clear layers. Real AI services run different models, variable input sizes, dynamic workloads, attention mechanisms, sparse operations, and unpredictable user demand. A fixed pipeline may become inefficient when the workload changes. The system must retain enough flexibility to justify its infrastructure. China's strategic advantage. This research fits China's broader effort to improve computing performance despite restrictions on access to the most advanced foreign AI chips and manufacturing equipment. If the best individual processors are difficult to obtain, connecting available processors more efficiently becomes strategically valuable. An architecture that extracts more real work from modest chips can reduce dependence on brute force scaling. China also has growing capabilities in silicon photonics, optical communications, FPGA development, packaging, and data center infrastructure. Combining those fields could create systems that compete at the architectural level, even when individual chips remain behind the leading edge. But this should not be framed as China defeating NVIDIA overnight. NVIDIA's advantage includes hardware, memory systems, networking, software libraries, developer tools, and a massive installed ecosystem. The company is also investing heavily in optical networking and faster interconnects. The global industry already understands that communication is becoming the next major bottleneck. The race is not between China using light and the West ignoring it. The race is about who can turn photonic interconnects into reliable, programmable, manufacturable systems first. My take is that the 149 times result is real, impressive, and easy to misunderstand. The researchers did not build a processor with 149 times more computing power. They built a system that wasted far less of the computing power it already had. That may be the more important achievement. For decades, performance improvements came primarily from faster transistors, more cores, and larger chips. AI is reaching a stage where moving information can cost more time and energy than calculating with it. When that happens, architecture becomes as important as the processor. The Peking University system demonstrates a different philosophy. Divide the model across specialized chips. Keep each stage permanently ready. Stream data directly from one stage to the next. Use light to prevent communication from slowing the pipeline. And design the algorithm, processors, and network as one machine. The experiment is still far from replacing GPU clusters. Its model is small, its hardware is specialized, its commercial energy advantage remains unproven. Its scaling challenges are serious, but the result exposes a weakness in the current AI race. A system with 16.96 teraflops lost badly to a system with 1.969 teraflops because the stronger machine could not use its strength efficiently. That is the warning. The next breakthrough may not come from a GPU with twice as many cores. It may come from a network that keeps every existing core busy. China has shown that optical pipeline parallelism can deliver that advantage on one carefully chosen task. Now researchers must prove that the same principle can scale to larger models, more processors, dynamic workloads, and real products. If they succeed, AI data centers may stop being collections of isolated superchips connected by increasingly desperate wiring. They may become optical computing fabrics where many modest processors operate like one coordinated machine. So what do you think? Is optical interconnection the missing technology that will unlock the next generation of artificial intelligence? Or is this result too specialized to threaten the GPU-centered data center? Let me know your view in the comments, and subscribe to Eastern Engine for more grounded coverage of the chips, factories, and engineering decisions reshaping the global economy. Because China did not make one chip 100 times stronger. It showed that connecting chips with light can make a smaller system behave as if it were. On May 25, 2025, something quietly historic happened that most of the global media barely covered. A freight train pulled out of a station in western China, carrying 32 containers of cargo. 15 days later, that same train arrived in Iran, more than 10,000 kilometers away, having crossed 4 separate countries, 2 major mountain ranges, and some of the harshest desert terrain on the planet, without ever touching an ocean. The journey that train completed in 15 days would have taken between 30 and 40 days by sea. But the duration is not really the story. The story is the route itself. For decades, moving large volumes of goods between Asia and the Middle East has meant one thing: ships, oceans, and a small handful of narrow waterways that determine which cargo arrives where. That arrangement has shaped global trade, global politics, and the balance of economic power for generations. This railway represents something different. It is the first serious attempt in modern history to build a major commercial corridor between 2 continents that bypasses maritime trade routes entirely. And the implications of that, once you sit with them, are genuinely significant. In this video, we are going to walk through how this railway was built, what it means for the countries connected by it, the broader expansion plan that involves 5 additional nations, and the parallel Arctic shipping route that is developing alongside it. The full picture is more strategic and more carefully designed than any single train run can communicate on its own. To understand why this railway exists, you first have to understand a single narrow stretch of water that almost no one outside the shipping industry talks about. It is called the Strait of Malacca, and it sits between Malaysia and Indonesia. Roughly 94,000 ships pass through it every year: oil tankers, container vessels, bulk carriers, and everything in between. It is one of the most heavily trafficked maritime corridors on the planet, and it functions as the primary gateway between the Indian Ocean and the Pacific. For China, this passage is not just useful, it is structural. Approximately 80% of China's oil imports flow through this single waterway. The energy that powers Chinese factories, vehicles, power grids, and consumer products travels through one narrow corridor on its way to refineries and storage facilities across the country. Now consider what that means in practical terms. If the Strait of Malacca were to close for even a short period, the economic effects would compound rapidly. Estimates put the daily cost of a closure in the tens of millions of dollars, and a sustained disruption would begin shutting down industrial activity within weeks. The world's second largest economy depends on a single maritime passage staying open and accessible. This is where geopolitical context enters the picture. Since 2019, the United States has maintained the ability to dock its naval vessels at deepwater facilities in Singapore, which sits at the southern entrance to the Strait of Malacca. In a major conflict scenario, the U.S. Navy has the capability to severely restrict maritime traffic through this corridor on a short timeline. That is not a theoretical concern in Beijing. It is a planning assumption. There are alternative maritime routes that could in theory be used. The Lombok Strait and the Sunda Strait both connect the same broader regions, but neither has the port infrastructure, the depth profile, or the logistical capacity to absorb meaningful volume on short notice. Switching even a portion of China's energy imports to these backup routes would require years of port expansion and supply chain restructuring. The conclusion that Chinese strategic planners reached was straightforward. The vulnerability of relying on a single maritime choke point was unacceptable in the long term, and the solution was to build a way to move energy and goods that did not depend on the ocean at all. The country whose geography made that solution possible was Iran. The route itself is an engineering challenge of a kind that very few projects in modern history have attempted at this scale. Starting in western China, the corridor heads west through Kazakhstan, then south through Uzbekistan and Turkmenistan, and finally crosses into Iran, where it terminates at the Apron dry port near Tehran. 10,400 kilometers of connected railway track, spanning 4 sovereign nations, traversing some of the most punishing terrain on Earth. The terrain alone tells you something about the ambition behind this project. Vast stretches of open desert where shifting sand can bury rail infrastructure between maintenance cycles. Mountain ranges located in seismically active zones where the ground beneath the track is itself unstable. Summer temperatures that warp metal and crack concrete. Winter conditions cold enough to disrupt fuel and lubrication systems. The total cost of the project exceeded $2 billion, financed through a combination of Chinese policy banks, the Asian Infrastructure Investment Bank, and bilateral loan agreements between the participating governments. One of the most technically demanding aspects of the project was solving the rail gauge problem. China and most of Central Asia use different track widths, a legacy of historical infrastructure decisions made over a century ago. Russia and the former Soviet states use a broader gauge than the Chinese network, which historically meant cargo had to be transferred manually between different carriages at each border. That added hours to every shipment and made the route impractical for time-sensitive freight. The engineering response was the construction of automated bogie exchange facilities at the key border crossings. These systems allow the same container, on the same shipping platform, to be transferred between rail systems of different gauges in under 30 minutes. The technology is not new, but its deployment at this scale and across this many borders is unprecedented. There is also a structural detail that speaks to how seriously both sides took this project's strategic importance. Sections of the Iranian portion of the railway were built underground rather than at surface level. Officially, this protects the line from extreme weather. Realistically, it also protects the infrastructure from potential aerial threats. That is not the kind of design decision you make for a routine commercial freight corridor. When the first train completed the full route in May 2025, Chinese state media described the corridor as an energy lifeline between the two countries. That framing was not exaggeration. It was a clear statement of intent. The context for understanding why this railway matters so much to Iran requires looking at the broader economic situation the country has been operating under for years. International sanctions have constrained Iranian access to global financial systems for over a decade. Major banks have been disconnected from international transaction networks. Foreign companies that pursue significant business relationships with Tehran have faced regulatory consequences in Western jurisdictions. Oil buyers have been pressured through secondary sanctions to avoid Iranian crude. The cumulative effect of these measures has been to push Iran toward economic partnerships that operate outside the dollar-denominated global trade system. China made the strategic decision to be that partner. In 2021, the two countries signed a 25-year comprehensive cooperation agreement valued at approximately $400 billion. This was not a routine trade agreement. It was a generational commitment covering energy, infrastructure development, manufacturing partnerships, and technology cooperation. The follow-through has been substantial. In 2024, China purchased the overwhelming majority of Iran's crude oil exports, representing roughly $29 billion in trade. Iran's total oil revenue for the year reached approximately $67 billion, the highest figure the country had recorded in over a decade. The official sanctions remained in place. Their practical impact on Iranian oil exports had diminished significantly. With the railway now operational, those trade flows can move along a corridor that is structurally insulated from external interference. Iranian oil can move onto trains, travel across Central Asian territory, and arrive in China without involving any Western financial institution, insurance provider, or shipping line at any point in the chain. There is also a currency dimension to this arrangement that deserves attention. Since 2012, China has been settling its Iranian oil purchases in yuan rather than US dollars. This sounds like a technical detail. It is actually one of the most quietly consequential elements of the entire relationship. The dollar's role as the default global currency for energy trading is one of the foundations of contemporary American economic influence. Every major oil transaction conducted in an alternative currency reduces that role incrementally. Russia has pursued a parallel strategy with its own energy exports since 2022. The combined volume of energy trade settling outside dollar systems has grown notably over recent years, and this railway adds further infrastructure to that broader shift. Iran's geography also gives it strategic value that extends well beyond its own borders. The country sits directly along the Strait of Hormuz, through which approximately 20% of global oil shipments pass. It also has direct land borders with several Central Asian nations that have historically struggled with limited access to ocean trade routes. For landlocked countries like Tajikistan, Kyrgyzstan, and Afghanistan, a railway network connecting through Iran to Persian Gulf ports represents a fundamental change in their economic options. China gains influence across a region that has traditionally operated within other spheres of geopolitical power. It is a development that benefits multiple parties, which is exactly the kind of arrangement that tends to grow rather than fragment. The China to Iran corridor is the foundation of a larger network that has been under development in parallel. The Five Nations Railway Corridor project connects China, Kyrgyzstan, Tajikistan, Afghanistan, and Iran in a single integrated rail network. The new track required for the project totals around 1,300 kilometers, with the largest single section running through northern Afghanistan. The initial framework agreement was signed in late 2014, and the project has continued advancing through various phases since then. A significant milestone occurred in May 2023, when the first cargo run traveled from Iran into Afghanistan, along the Kaf-Herat segment of the network. That shipment carried 655 tons of railway construction equipment, meaning the network was, in a literal sense, transporting the materials needed for its own expansion. In May 2025, senior officials from Iran, China, Kazakhstan, Uzbekistan, Turkmenistan, and Turkey met in Tehran specifically to discuss the next phase of the transcontinental rail expansion. The momentum behind the project has accelerated rather than slowed. For the landlocked nations involved, the implications are significant. These countries have operated with severe disadvantages in global trade since their independence. Moving goods to or from their territories has always required navigating multiple borders and ultimately depending on ports they did not control. A rail network connecting them to Persian Gulf shipping points changes that situation in fundamental ways. The financing structure supporting all of this is also worth understanding. China's Belt and Road Initiative has committed well over $1 trillion to infrastructure projects globally since its launch in 2013. Central Asia represents one of its most strategically concentrated investment zones. The loan structures attached to these railway projects typically feature extended repayment timelines and resource-backed arrangements, which create durable economic relationships between China and partner countries. While the overland railway is moving freight east-west, China is simultaneously developing a maritime corridor in the opposite direction, one that runs through the Arctic. The Northern Sea Route follows the northern coast of Russia through Arctic waters and represents the most direct shipping path between Asia and Europe. A journey that takes around 45 days via the Suez Canal can be completed in roughly 30 days via the Northern Sea Route. Until recently, the obstacle was simple. Most of the route was locked under ice for most of the year, leaving only a brief 88-day operational window annually. That window is expanding. Climate change has steadily increased the period during which Arctic shipping is viable, and the operational window now extends to around 90 to 100 days per year. In June 2024, Russia and China formally agreed to develop year-round container shipping along this corridor. Russia has been investing in the icebreaker fleet required to make this practical. The latest generation of Russian nuclear-powered icebreakers, including the Arctica and the Sibir, can operate continuously through ice up to several meters thick. The Arctica weighs 33,000 tons, is powered by 2 nuclear reactors, and can operate for 7 years between refueling cycles. The strategic significance of the Arctic route lies in what it bypasses. The Suez Canal, despite being administered by Egypt, operates within a broader Western economic ecosystem. Insurance, financing, and logistics for vessels using it overwhelmingly involve European and American institutions. A functioning Arctic corridor allows trade to flow without any of those touch points. What is taking shape is a pattern. One corridor cutting across Central Asia by land, another opening up through the Arctic by sea, both moving in directions that reduce dependency on the maritime routes and financial infrastructure that have defined global trade for generations. It is worth being honest about the limitations of what this railway can accomplish in the short term. A single oil supertanker carries roughly 2 million barrels of crude oil, the equivalent of hundreds of freight train shipments. Scaling rail transport to fully replace maritime shipping is simply not realistic in any near-term timeframe. The corridor also faces real operational challenges. Multiple border crossings mean coordination overhead. Desert conditions stress rail infrastructure heavily. Fixed rail lines have inherent vulnerabilities that ocean-going vessels do not share. The early operational record reflects some of these realities. Within weeks of the inaugural freight run in May 2025, regional security developments interrupted further commercial services along sections of the corridor. The launch did not progress smoothly into routine operations, but focusing only on the operational hiccups misses what this railway actually represents. It does not need to replace maritime shipping to matter. It needs to exist as a working option that gives all parties involved choices they did not previously have. When China has a functioning land route for at least a portion of its energy imports, the strategic leverage associated with maritime choke points diminishes. When Iran has a major trading partner operating through infrastructure that exists outside the reach of Western financial systems, the practical impact of sanctions weakens. When Central Asian nations have rail access to global markets, they gain leverage in choosing their economic partners. There is also a broader signaling element to consider. Every kilometer of new track in this region sends a quiet message to other countries watching from the sidelines. There are alternatives to the existing global trade and financial architecture, and the alternatives are being built in real time. What I find most interesting about this story is not really the train itself. It is what the project tells us about how infrastructure is being used as long-term strategy rather than short-term capacity. The countries building this railway are not trying to win a single contest with the West. They are constructing an alternative architecture for trade, finance, and energy that can operate in parallel to the existing system. It does not need to replace anything to be effective. It just needs to exist, function reliably, and demonstrate that other options are viable. That is a much harder thing to respond to than a single competitive challenge, because it is not really a confrontation. It is the steady, patient construction of a different way of doing things, one project at a time, across a region that has historically been at the margins of global trade. Whether this approach succeeds at the scale its architects intend will depend on factors that take decades to play out: regional stability, sustained investment, technological developments, and broader geopolitical shifts. But the work being done right now is laying foundations that will shape that future regardless of how individual events unfold. My question for you is this: do you think infrastructure projects like this railway will end up shifting the balance of global trade meaningfully over the next 20 years? Or will the existing maritime system remain dominant despite these alternatives? Drop your honest answer in the comments. I am genuinely curious which way most people are leaning on this one. If this kind of deep dive analysis on global infrastructure and engineering strategy is what you come here for, please subscribe to Eastern Engine and hit the notification bell. We cover the major projects reshaping the global economic landscape with the depth they actually deserve. There is a lot more coming on this topic, and you do not want to fall behind.
Chinese electric vehicles like BYD are flooding the globe, offering sci-fi technology at half the price of Western brands. But everyone is focusing on the wrong thing. The multi-trillion-dollar question is, why did the EV revolution happen in China and not the West? Today, I'm going to break down the greatest industrial master plan of the 21st century. For 100 years, the global automotive hierarchy was built on one thing: the internal combustion engine. China spent decades trying to catch up.
There is a number that automotive engineers have been chasing for over 100 years. Not a speed record, not a horsepower figure, a percentage. A simple, brutal measure of how much energy your engine actually uses versus how much it wastes. For most of automotive history, that number sat stubbornly around 30% for the average production car, meaning 70% of every drop of fuel you ever paid for simply vanished, absorbed into hot metal, pushed out the exhaust pipe, lost to friction before a single wheel ever turned. The industry accepted this. Engineers called it the nature of combustion. Textbooks framed it as a fundamental constraint of physics. Then on April 13, 2026, a company called Geely stood in front of the world, put a single number on a screen, and quietly ended that conversation. 48.41%. Certified. Officially measured. Recognized by Guinness as a world record for a production vehicle engine. That number is not just impressive. It is the kind of number that makes engineers at Toyota, BMW, and Volkswagen go very quiet in meetings. To understand why, you need to understand what it actually took to get there, and why everyone else said it was impossible. Let's go back to basics for a moment, because the context here matters enormously. When a combustion engine burns fuel, it is essentially harnessing a controlled explosion and converting that energy into rotation. Simple in concept, brutally inefficient in practice. The explosion generates enormous heat, and heat is stubborn. It does not wait patiently to be converted into useful work. It spreads
of a car. China succeeded because they built a smartphone on wheels. Reason number 1, overtaking on a curve. China realized an EV is a giant battery driven by software. By abandoning the gas engine entirely, China shifted the battlefield to electrochemistry.
Physics has a name for the theoretical ceiling on how efficient any heat-based engine can ever be: the Carnot limit. Without getting lost in the math, what it essentially says is this: the larger the temperature gap between your combustion event and your exhaust output, the more work you can theoretically extract. But that gap has real-world boundaries on both ends. Push combustion temperatures too high and your engine destroys itself. Keep exhaust temperatures too low and your emission systems stop functioning. Every production engine ever built has been threading that needle. For decades, the practical ceiling for a mass-produced car engine sat at roughly 38 to 40%. Getting past 40 required extraordinary engineering effort. Toyota, one of the most respected powertrain engineering organizations on the planet, spent years and billions of dollars developing their 2.5-liter dynamic force engine. They used a technique called the Atkinson cycle, which slightly extends the intake valve timing to reduce pumping losses and recover a bit more energy from each combustion event. Their result was 41% thermal efficiency. The industry applauded. Engineers wrote papers. The consensus formed that this was, for all practical purposes, the ceiling for production engines at any reasonable cost. The reasoning made sense on paper. The laws of thermodynamics are not negotiable. The materials available for engine construction have hard temperature limits. The fuel being burned has fixed energy content. 41% was framed not as a plateau but as a finish line. What happened next is one of the more interesting stories in modern industrial history. Before Geely's record, another Chinese company had already shaken the assumptions loose. BYD, Build Your Dreams, looked at the hybrid vehicle architecture that the rest of the world had settled on and concluded that the fundamental design was the problem. In a conventional hybrid, the combustion engine drives the wheels directly, with an electric motor assisting during acceleration and recovering energy during braking. It sounds efficient in theory. In practice, it means the engine is constantly changing speeds, revving hard uphill, idling at traffic lights, spinning at a dozen different RPM points throughout a journey. And here is the critical issue. Every combustion engine has one narrow band of RPM where it operates most efficiently. Force it to operate anywhere else and efficiency drops. A conventional hybrid engine spends the majority of its life operating outside that sweet spot. BYD's solution was radical in its simplicity. Remove the engine from the drivetrain entirely for most driving conditions. Let electric motors handle the wheels full-time. Assign the combustion engine exactly one job. Run at its optimal RPM and generate electricity. Nothing more. No gear changes, no speed variations, no compromises. Just one engine, one speed, one purpose. Because the engine was no longer chasing the road, BYD's engineers could tune it obsessively around that single operating point. The result was their 5th-generation DMI platform, delivering 46.06% thermal efficiency, a number that genuinely stunned the global automotive press. To appreciate how significant that jump was, Toyota's journey from roughly 36% to 41% took the better part of 2 decades and required sustained investment most automakers could not match. BYD moved the needle by 5 percentage points in a fraction of that time by simply rethinking the architecture from scratch. Western automakers had a difficult internal conversation. Most of them concluded it was a regional story, a niche, something that mattered in China but would not translate to global markets. They underestimated what was already being built in the background. While the industry was processing BYD's achievement, Geely's engineers had already been working for 2 years on a completely different approach. They were not iterating on existing engine designs. They were not refining valve timing or adjusting compression ratios by small increments. They were asking a more fundamental question: what actually limits combustion efficiency at the most basic physical level, and what would it take to attack those limits directly? The answers they came up with touched every stage of the combustion process, from the moment air enters the engine to the moment power reaches the wheels. Each solution was unconventional. Several of them contradicted standard engineering assumptions. Together, they produced something that sits well outside what anyone projected was achievable. The first major breakthrough addresses something so fundamental it is easy to overlook: what actually happens inside the cylinder when fuel burns. In a standard engine, air and fuel enter the cylinder and mix as best they can in the brief window available before the spark plug fires. The mixing is never perfect. Some areas of the cylinder are fuel-rich. Others are fuel-lean. When ignition happens, the flame front does not detonate simultaneously across the whole chamber. It propagates outward from the spark plug like a slow ripple, combustion spreading unevenly through a non-uniform mixture. That uneven burn has consequences. The first regions to ignite release heat immediately, and that heat starts bleeding into the cylinder walls before the rest of the mixture has even caught. By the time combustion is complete, a meaningful portion of the energy has already transferred into the engine structure, rather than pushing the piston down. It is one of the primary mechanisms driving inefficiency in traditional combustion engines. Geely's engineering team redesigned the intake port geometry and valve angles from the ground up. The result is what they call the Yufeng tornado combustion system. When the intake valve opens, incoming air is not simply drawn into the cylinder passively. The port shape forces it into a high-velocity rotating vortex, a controlled, sustained spin that continues to accelerate as the cylinder fills. By the time the intake valve closes, the air-fuel mixture is spinning rapidly and blending continuously throughout the chamber. When ignition occurs into that spinning mixture, the flame front does not creep. It propagates outward simultaneously in all directions because the fuel is uniformly distributed throughout. The entire charge burns in a fraction of the time a conventional cylinder requires. Less time burning means less time for heat to conduct into the surrounding walls. More energy stays with the expanding gases and pushes down on the piston where it belongs. The efficiency gain from this single change is substantial, but it introduced a new problem. More complete, faster combustion raises cylinder pressure rapidly. Exactly the conditions that cause engine knock, where fuel ignites prematurely before the spark plug fires, causing destructive, uncontrolled detonation. Knock is one of the main reasons engineers have historically been cautious about pushing compression ratios higher. Solving knock without sacrificing the benefits of the tornado combustion system required a second breakthrough, one that looks impossible until you understand how it actually works. Every engineering student learns early that you cannot run a combustion engine extremely hot and extremely cool at the same time. Hot combustion means better efficiency. Cool metal means less knock risk. These goals directly oppose each other, and the standard solution has always been to find a compromise temperature that accepts some loss on both ends. Geely rejected the compromise. Their thermal management system splits the engine into two completely independent cooling zones, with separate coolant circuits, each managed independently by an electronically controlled pump that reads operating conditions many times per second. The cylinder head, the upper section of the engine where combustion actually occurs, is kept aggressively cold. Coolant flows through this zone rapidly, pulling heat away almost as fast as it is generated. Keeping the combustion chamber walls cold means the incoming air charge stays dense right up to the moment of ignition, which dramatically reduces the risk of premature detonation. This allows the engine to operate at a significantly higher compression ratio than would be safe in a conventionally cooled engine. Higher compression extracts more energy from each combustion event. The lower engine block, where the pistons travel up and down in their bores, is kept deliberately warm. Warmer oil is thinner oil. Thinner oil means the pistons experience dramatically less friction as they move. Friction is simply wasted energy converted to heat, so every reduction in friction is efficiency directly recovered. Cold at the top for maximum safe compression. Warm at the bottom for minimum friction losses. Two objectives that traditional design treated as mutually exclusive, running simultaneously in different zones of the same engine. The electronic management system continuously adjusts coolant flow rates based on load, speed, and temperature readings to maintain both conditions simultaneously. The conventional wisdom said this was pointless complexity. The dyno results said otherwise. Even a record-breaking engine is only useful if you can get its output to the wheels without bleeding the gains away in a heavy mechanical transmission. Traditional automatic gearboxes are engineering achievements in their own right, but they are also heavy, complex, and consume a percentage of the power they transmit simply through the friction of their own operation. Geely's solution is their 11-in-1 EHT intelligent drive system. The name refers to how many separate components have been integrated into a single compact housing. The engine, the generator, two electric drive motors, the high-voltage inverters, and the thermal management hardware, all packaged together. Total powertrain weight dropped 13.5% compared to conventional hybrid setups, and the mechanical complexity of a multi-speed gearbox is eliminated entirely. For around 90% of typical driving, the combustion engine has no physical connection to the wheels. It runs at its efficiency sweet spot, drives a generator, and that electricity either charges the battery or powers the motor spinning the wheels directly. From the driver's perspective, the car behaves like a pure electric vehicle, smooth, silent, and immediate in response. Only at sustained highway speeds does the system engage a direct mechanical connection between engine and wheels, because at that specific condition, routing power electrically actually loses more than the direct path gains. An AI power management system oversees all of this, recalculating the optimal energy routing 50 times every second. It reads the navigation map ahead, anticipates gradients and speed changes, and pre-positions the battery's state of charge to be exactly where it needs to be at each stage of your journey. It is not reacting to the road, it is planning ahead of it. The combined result of all four innovations, tornado combustion, split thermal zones, the 11-in-1 integration, and AI routing, is a certified fuel consumption figure of 2.22 liters per 100 kilometers, with a total range exceeding 2,000 kilometers on a full tank. There's an honest conversation worth having about what this technology means beyond the record itself. Pure electric vehicles have real strengths: zero tailpipe emissions, low running costs, exceptional driving refinement. But they also carry genuine practical limitations that hundreds of millions of potential buyers are not yet ready to work around. Battery weight, charging infrastructure gaps, and long refueling times are not hypothetical concerns. They are daily realities in enormous portions of the world. What Geely's iHEV system offers is something different: the driving character of an electric vehicle for everyday use, combined with the refueling simplicity of a conventional car and a range figure that makes long-distance travel completely straightforward. No charging network dependency, no range calculation anxiety. Fill up anywhere on the planet. The vehicle delivering these numbers is not a lightweight city car optimized for fuel economy testing. It is a full-size SUV operating in real-world conditions. For the established automotive industry, this is a genuinely difficult moment. Combustion engine technology, invented in Europe, refined to apparent perfection in Japan, has now reached its highest ever efficiency milestone under a Chinese company that barely existed on the global automotive stage 15 years ago. That kind of lead is not closed quickly. It requires years of engineering work, institutional rethinking, and a willingness to abandon assumptions that have guided the industry for decades. For consumers, the competition this creates is straightforwardly good news. Engineering ambition at this level historically drives prices down and capability up across the entire market. Honestly, what strikes me most about this story is not the 48% figure itself, it is what it represents about where innovation is actually happening right now. The assumption in Western automotive culture has been that the future of the car is fully electric, full stop, and that combustion technology was essentially done evolving. Geely just demonstrated that assumption was wrong in a very public way. I think the most interesting question for the next 5 years is not whether legacy automakers can match this efficiency number. It is whether they can match the pace of development behind it. Geely and BYD are not slowing down. They are not iterating on old platforms. They are building new ones from blank sheets of paper, faster than the traditional industry timeline allows for. What do you think? Does a 2,000-kilometer range hybrid with this kind of efficiency change your mind about electric vehicles? Or are you still holding out for full electric? Drop your answer in the comments below. I read every single one. If you found this breakdown useful, consider subscribing to Eastern Engine. We cover exactly these kinds of engineering stories the moment they break, with the depth they actually deserve. Hit the subscribe button and turn on notifications so you never miss what comes next. The industry is moving fast right now, and the next story is already in the works. A silicon wafer enters a machine. There is no giant projection lens above it. No deep ultraviolet flash sends a pattern through an optical system. Instead, a patterned template moves downward. The chamber is placed under vacuum. Pressure spreads across the wafer. The template touches a thin layer of specially prepared material, and nanoscale structures are copied directly into it, almost like pressing a seal into soft wax, except the details are measured in billionths of a meter. Then the template lifts away. What remains is the pattern for a photonic chip. On June 5th, Chinese nano-imprint equipment company Pre-Nano said it had worked with Shenzhen Litra Technology to validate this process across full 8-inch wafers. The machine is called the PLAS, and according to the companies involved, it can manufacture photonic chip patterns without a conventional DUV lithography step. The cost claim is even more dramatic. Pre-Nano says the relevant manufacturing cost can be reduced to roughly 1/10 of the traditional DUV route. That does not mean every lithography machine has suddenly become unnecessary. It does not mean this process can print the processor inside your phone, and it definitely does not mean every finished chip becomes 90% cheaper. The real story is narrower, but it may also be more believable and more important, because engineers may have found the exact kind of chip where stamping, not projecting, finally makes commercial sense. Modern chips, the pattern is developed, transferred into the layer below, and then the process begins again and again. Different layers build devices, connections, and optical structures. Each new pattern must align with the previous one. A tiny shift can ruin the result. UV lithography achieves extraordinary precision through advanced optics, motion control, materials, and computational correction. The light source must remain stable. The wafer stage must accelerate, stop, and align with almost unnatural accuracy. Temperature, vibration, and contamination must all be controlled. It is astonishing engineering. It is also expensive and complex. Every additional exposure adds tool time, process steps, and another opportunity for variation. Nano-imprint lithography asks a blunt question. What if the pattern did not need to be projected at all? The basic idea is easy to understand. Engineers first create a master template containing the required nanoscale pattern. That template is placed above a wafer coated with imprint resist. Instead of projecting light through a mask, the machine presses the template into the material. The resist flows into the template's tiny grooves. It is hardened, and the template separates from the wafer, leaving behind a physical copy of its surface. Later etching steps transfer that pattern into the material underneath. One master can, in principle, reproduce the same structure many times. Think about the difference between drawing a detailed map repeatedly and using a printing plate. The first plate may be difficult to create, but once it exists, copying becomes far simpler. At nanoscale dimensions, however, simpler is a dangerous word. Prenano says its equipment can reproduce features below 10 nanometers. At that scale, dust is not dust, it is a boulder. A trapped air bubble becomes an empty neighborhood where the pattern never formed. Slightly uneven pressure can change how deeply the resist fills different regions. A warped template can touch the center while missing the edge. During separation, fresh structures can stretch, tear, or cling to the mold. The concept is elegant. The contact is where elegance meets trouble. Nano-imprint has attracted attention for decades because its advantages are difficult to ignore. It can reproduce extremely small structures without an optical system capable of resolving them, and it may copy a large repeated pattern in one operation, yet it never simply replaced optical lithography. The first obstacle was defects. Because the template physically approaches the wafer, a contaminating particle can damage the pattern or the mold itself. A defect on the template can then be printed repeatedly, like a scratch appearing on every copy from a damaged stamp. The second problem was uniformity. The resist remaining below the pattern must be thin and predictable. Too much material in one region and too little in another can make later etching inconsistent. Then comes separation. Pressing down is only half the process. The template must release cleanly without pulling the structures apart. Alignment is another challenge. Most chips require multiple layers, and each new layer must land precisely over the last. The demands become especially severe for dense logic devices. Finally, there is speed. Contact, curing, and separation take time. In a high-volume factory, seconds matter. Nano-imprint could produce impressive demonstrations. The difficult part was producing reliable copies, wafer after wafer. Prenano's latest claim centers on a machine designed for full wafer imprinting. The PLAS is described as a semiconductor-grade vacuum pneumatic nano-imprint system. Rather than pressing one small field, moving and repeating, it is intended to imprint a large wafer area in one operation. Vacuum matters because removing air can reduce bubbles trapped beneath the template. Pneumatic matters because controlled air pressure can distribute force across the wafer more evenly. Imagine pressing a large decal onto a surface using one hard block. Some areas touch first, others receive too much force. Wrinkles appear. A pressure cushion can conform more evenly across the area. Prenano says its face contact method keeps pressure non-uniformity below 0.5%. It also claims residual layer variation below 2 nanometers and resolution below 10 nanometers. Those are company specifications, not a complete independent production report. But they show what the engineers are targeting: equal contact, equal thickness, and repeatable replication across the wafer. The equipment is only one part of the answer. Prenano and Litra also used a customized 2-layer resist system and matching process. That detail is critical. Nano-imprint is not merely a machine pressing downward. It is a relationship between the mold, resist, pressure, curing, release chemistry, and the etching that follows. Change one element and the others may have to change with it. Here is the distinction that makes this story credible. The wafers described in the announcement are for photonic chips, not cutting-edge CPUs or GPUs. Electronic processors manipulate electrical signals. Photonic chips guide and control light. They can contain waveguides that behave like microscopic optical rods, splitters that divide light, gratings that send it in selected directions, resonators that filter wavelengths, and phased arrays that steer beams. These structures can be extremely precise, but many are also repetitive. A grating may contain rows of similar lines. An optical antenna array may repeat one element hundreds or thousands of times. That repetition is where a physical template becomes attractive. A modern logic processor resembles a dense city whose streets and buildings change from block to block. One particle in the wrong place can destroy a critical intersection. A photonic structure can sometimes resemble a carefully arranged field of rails, mirrors, or fence posts. It is still difficult to make, but its geometry may be more compatible with replication. This does not make photonic chips easy. Optical performance is highly sensitive to roughness, width, and dimensional error. A slightly imperfect waveguide can scatter light or shift the device's behavior. But nano-imprint does not need to conquer every semiconductor process to become valuable. It only needs to outperform existing methods where repeated optical structures make stamping practical. The partner in this announcement provides another clue. Shenzhen Litra Technology develops LiDAR systems and optical phased array chips. LiDAR measures distance by sending light into the environment and analyzing what returns. Traditional systems often steer the beam using rotating assemblies or moving mirrors. Those mechanisms can work, but they add size, cost, and wear. An optical phased array attempts to steer light electronically. The principle resembles phased array radar. Instead of rotating one transmitter, the chip controls the phase of many tiny emitters. Their waves reinforce one another in one direction and cancel in others. Change the phase pattern and the beam points somewhere else. No spinning turret is required. To make that practical, a chip may need large arrays of nanoscale optical elements with consistent geometry. That is a natural test case for imprinting. Pranano says the current cooperation focuses on production for Litra's optical phased array devices aimed at vehicle and intelligent terminal applications. Mass production validation is not the same as millions of finished sensors already shipping, but this is more than a generic lab wafer. There is a product direction. There is a customer partner, and there is a reason this manufacturing method could lower cost. If these optical arrays can be copied over full wafers in fewer steps, solid-state LiDAR may become cheaper to build for vehicles, robots, industrial systems, and compact three-dimensional sensors. An 8-inch wafer is approximately 200 millimeters across. Leading processor factories generally use larger 12-inch wafers, but 8 inches remains a genuine industrial format for specialty semiconductors, sensors, and many photonic products. More importantly, covering a complete wafer is very different from printing one small square in a laboratory. A tiny sample is easier to keep flat. Pressure is easier to control. There is less area in which contamination can appear. Across a full wafer, small errors accumulate. The center and edge may behave differently. Resist may flow unevenly. A template may bend by an amount invisible to the eye but damaging to the device. That is why the 8-inch claim deserves attention. It suggests the process has moved from we can reproduce this pattern toward we can reproduce it across a manufacturing-sized surface. But the word suggests matters. The public announcement did not reveal how many wafers were processed, how many chips worked, how consistently the result was repeated, or what defect density was achieved. A full-size wafer is a milestone. Yield decides whether it becomes a business. Pranano says this route can reduce photonic chip manufacturing costs to 1/10 of a traditional DUV-based process. That is the company's estimate for the process it validated. It is not proof that every design, factory, or product will save exactly 90%. And it does not mean a $1,000 LiDAR sensor will suddenly cost $100. Lithography is only one stage. The master template must still be produced with extreme precision. Wafers require preparation and material deposition. Patterns may need etching. Chips must be tested, separated, packaged, and integrated into a final system. Yield matters too. A cheap patterning step that produces many defective chips can still create an expensive finished device. Template lifetime is another unknown. A mold that wears quickly or becomes contaminated can erase the apparent savings through cleaning, inspection, replacement, and downtime. Still, the possible advantage is understandable. The PLAS avoids the projection optics required by DUV equipment. It may replace several exposure or patterning operations with one replication step. A reusable template can spread its creation cost across many wafers. So the accurate interpretation is not, all photonic chips are now 90% cheaper. It is this. For the process Prenano and Litra say they validated, nano imprint reduced manufacturing costs to roughly 10% of the DUV route. That is still a huge claim. Now it needs equally strong evidence. Prenano has disclosed resolution, pressure uniformity, and residual layer control. It has not publicly provided all the figures that determine commercial success. We do not know the demonstrated wafer throughput. We do not know defect density across repeated production lots. We do not know the percentage of functional chips per wafer. We do not know how many imprint cycles one template survives before its performance changes. We do not have detailed independent comparisons showing optical loss, reliability, and lifetime against the same chip produced with DUV lithography. And we do not know every assumption behind the 1/10 cost estimate. That does not prove the announcement is wrong. It means commercial scrutiny is beginning, not ending. The semiconductor industry is unforgiving because a process can be technically brilliant and economically useless at the same time. A machine that creates perfect wafers slowly may lose to a more expensive machine producing acceptable wafers quickly. A cheaper process may lose if templates fail too often. Beautiful resolution means little if alignment and yield are unstable. Factories do not reward elegance. They reward working devices per hour, per tool, and per dollar. That is the scoreboard Prenano must eventually show. Even with those caveats, the strategy is clever. Instead of trying to replace mature logic chip processes immediately, Prenano is aiming at an application where geometry, wafer size, and cost may favor replication. Alternative technologies often enter established industries this way. They do not attack the strongest product first. They find the edge where their unusual combination of strengths and weaknesses becomes useful. For nano imprint, photonics may be that opening. Demand for light-based components is growing. Data centers need faster optical links. Networks need more transceivers. Robots and vehicles need compact sensing. Displays and augmented reality devices depend on precisely shaped optical structures. Not every one of those products will use this process, but they create a wide field of repeated nanoscale patterns, where a physical template can compete. And when a manufacturing platform proves itself in one market, the lessons travel. Better templates, cleaner materials, longer mold life, faster separation, lower defect rates, improved alignment. The first successful product is not the final destination. It is the factory learning how to walk. My view is that this development is interesting precisely because it is not a universal replacement for DUV. A claim that one machine has made optical lithography obsolete would be easy to dismiss. The semiconductor industry is too varied, and different chips require radically different processes. But a machine does not need to replace everything to become disruptive. If the PLAS can reliably manufacture optical phased array chips across full 8-inch wafers, with competitive yield and anything close to the claimed cost reduction, it could change the economics of specific photonic products. The word to watch is reliability. Sub-10 nanometer resolution sounds spectacular. A 90% cost reduction sounds even better. Customers, however, will care about repeatability. The same pattern, the same optical behavior, and the same yield, wafer after wafer. That proof will take time. For now, this is a credible manufacturing direction. A nano imprint equipment company and a LiDAR chip developer say they have placed full wafer stamping into an 8-inch photonic chip production flow. No giant optical projection system, no conventional DUV exposure step, just a master template, controlled pressure, specialized material, and an action that sounds almost primitive until you understand the scale. Stamp the pattern, cure it, lift the mold, repeat. Sometimes the next step in high technology is not a more complicated machine. Sometimes it is a simpler action performed with impossible precision. So what do you think? Is nano imprint the future of lower-cost photonic chips, especially for LiDAR and optical communications? Or will defects, template wear, and factory throughput keep DUV lithography ahead when real production volumes arrive? Let me know your view in the comments. And if you want more grounded stories about the machines, materials, and engineering breakthroughs reshaping technology, subscribe to Eastern Engine. Because the next major chip revolution may not be projected with light. It may be pressed into place. Imagine buying a new stick of Corsair Vengeance memory. The black heat spreader looks familiar. The specifications look ordinary. DDR5, 6,000 megatransfers per second. Support for both Intel and AMD platforms. Nothing on the packaging suggests that this particular module represents a major change inside the global semiconductor industry. But then someone opens the software that identifies the components hidden beneath that heat spreader. The manufacturer listed is not Samsung, it is not Micron, and it is not SK Hynix. Instead, the DRAM chips appear to come from Changxin Memory Technologies, better known as C, a workstation, a laptop, or a server. The memory inside was overwhelmingly likely to originate from the same three companies: Samsung, SK Hynix, Micron. Now, Chinese-made DDR5 has apparently appeared inside a product carrying one of the most recognizable names in enthusiast computing. This does not mean China has suddenly defeated the established memory giants. It does not prove that CXMT has better technology, lower prices, or superior reliability. But it does suggest something more subtle and potentially more disruptive. The door may finally be opening, and once a new supplier enters a market built around only three dominant producers, the first thing that changes is not necessarily technology. It is leverage. People love talking about processors. They compare the number of CPU cores. They debate graphics cards. They analyze clock speeds, cooling systems, and benchmark charts containing more colored bars than most human beings should ever be forced to examine. Memory receives far less attention. RAM usually becomes important only when there is not enough of it. Open too many browser tabs, launch a demanding game, edit a large video, or run an artificial intelligence model locally, and suddenly the computer begins hesitating. Data that should remain immediately available has to be moved elsewhere. Applications stutter. Response times stretch. The CPU may be the worker performing calculations, but RAM is the workbench. A faster worker does not help much if the workbench is too small, too slow, or constantly being cleared. Modern DRAM stores information inside billions of microscopic cells. Each cell represents a bit of data by holding a tiny electrical charge. That charge does not remain indefinitely, so the system must refresh it thousands of times every second. Dynamic random access memory. That is what the D in DRAM means. The process sounds straightforward until you remember the scale. A single memory chip must contain billions of these cells, manufacture them with extremely low defect rates, refresh them reliably, and move enormous quantities of information without corrupting the data. One weak cell can become a problem. One unstable timing margin can produce crashes that appear only under certain temperatures. One manufacturing variation can turn a fast chip into a slower one, or into scrap. Making DRAM is not simply printing a large number of identical switches. It is closer to constructing an apartment tower where every room must repeatedly switch its light on and off in perfect coordination, billions of times, while the entire building is moving. And customers expect it to work for years. That difficulty helps explain why the industry became so concentrated. Today, Samsung, SK Hynix, and Micron dominate conventional DRAM production. They did not reach that position because nobody else ever attempted to compete. The history of memory manufacturing is filled with companies that entered confidently, spent enormous sums, suffered through a downturn, and disappeared. DRAM is brutally cyclical. When demand is high, memory prices rise. Manufacturers earn strong profits and expand production. New capacity arrives, supply increases, prices fall, margins collapse, companies reduce investment or exit the business. Then demand returns. The survivors become stronger. Every cycle acts like an industrial filter, removing manufacturers that lack scale, manufacturing efficiency, or enough cash to survive the bad years. Eventually, only a handful remain. This concentration creates a strange situation. RAM modules are sold under many familiar brands: Corsair, Kingston, G-Skill, Crucial, and others, but the actual silicon beneath the heat spreaders often comes from the same small group of DRAM manufacturers. The module company selects the chips, tests them, places them on a circuit board, programs the operating profiles, adds cooling, and sells the finished product. But the microscopic memory dies themselves are the difficult part. Think of the difference between a bakery and a wheat farm. Many bakeries can package and sell bread under different names, but if almost all of them depend on only 3 farms for wheat, the apparent diversity at the store hides a concentrated foundation. CXMT is attempting to become another farm, and that is why one ordinary-looking Corsair module matters. The module in question appears to be a 16GB Corsair Vengeance DDR5 stick purchased in China. Its reported part number ends with the letters CN, indicating a model intended for the Chinese market. It operates at DDR5 6000 with CL36 timings and a voltage of 1.35 volts. Those numbers are not revolutionary. DDR5 6000 has become a widely used performance point for modern desktop computers. CL36 is respectable, although enthusiasts can purchase lower latency kits. The module is reportedly compatible with both Intel XMP and AMD eExpo memory profiles, allowing systems to apply its rated settings automatically. In other words, this is not an experimental chip sitting beneath laboratory lights. It appears to be ordinary consumer RAM. That may be the most interesting part. Industry changes are not always announced by a dramatic machine, a record-setting benchmark, or an executive standing beneath a giant screen. Sometimes the change is buried beneath a black metal heat spreader, working quietly inside a gaming computer. However, an important qualification is necessary. Corsair has not publicly confirmed the reported CXMT configuration. The evidence comes from photographs and diagnostic information shared online. It appears convincing, and several hardware publications have analyzed it, but it should not be treated as a formal company announcement. That distinction matters. Yet even with that caution, the possibility is significant. A respected international memory brand appears willing to put its name, warranty, and compatibility expectations behind a module using Chinese DRAM. For CXMT, that is more meaningful than another presentation slide. A specification tells people what a company claims it can manufacture. A retail product suggests someone may be willing to depend on it. Changxin Memory Technologies was founded in 2016. That makes it remarkably young compared with the established memory producers. Samsung's semiconductor history stretches back decades. Micron was founded in the late 1970s. SK Hynix traces its origins through a long series of companies, factories, and acquisitions. CXMT entered an industry where its future competitors already possessed enormous factories, experienced engineering teams, established customer relationships, and libraries of manufacturing knowledge built through multiple generations of DRAM. It was not entering at the starting line. It was entering while the race was already moving. CXMT initially focused heavily on domestic customers and more mature forms of memory. That was sensible. A new DRAM manufacturer does not immediately begin by challenging the fastest chips available. It must first learn how to manufacture reliably at scale. Yield is everything. Suppose a factory processes a wafer containing hundreds of memory dies. If most of those dies work, the cost of the wafer can be spread across many sellable products. If a large percentage fails, every surviving chip becomes far more expensive. The drawing may be correct. The transistor may function. The first prototype may impress engineers. But until yields rise, the economics remain broken. This is the invisible mountain every new chip producer must climb. CXMT has apparently climbed far enough to offer a broad DDR5 portfolio. The company officially lists memory dies with capacities of 16 gigabits and 24 gigabits, reaching advertised speeds of up to 8,000 megabits per second. It has also displayed multiple kinds of memory modules for desktops, laptops, workstations, and servers. That does not automatically place CXMT beside the leaders. Published specifications are not the same as independent validation, and maximum speed tells only part of the story. But it shows that the company is no longer confined to yesterday's market. The 24 gigabit figure sounds technical, but it creates a practical advantage. 8 bits make 1 byte. Therefore, a 24 gigabit memory die stores 3 gigabytes of data. Place 8 of those dies on a module, and the result is a 24 gigabyte stick of RAM. That enables unusual but increasingly useful configurations. 2 modules can create a 48 gigabyte kit. 4 modules can create 96 gigabytes. For years, desktop memory capacities usually doubled in a predictable pattern: 8, 16, 32, 64, and then 128 gigabytes. 24 gigabit dies fill the large gaps between those levels. A gamer might not need 64 gigabytes, but could benefit from more than 32. A video editor may find 48 gigabytes ideal. A creator running local AI models might want 96 without paying for 128. This is not a cinematic breakthrough. No glowing reactor activates. No computer becomes 1,000 times faster. But semiconductor industries are often transformed by awkward little improvements that make products fit customers more precisely. A 24 gigabyte module is one of those improvements. Chinese brands such as Gloway and Kingbank have already presented DDR5 products using high-density domestic memory. If CXMT can provide these dies consistently, it gains a way to compete that is not based only on being cheaper. It can compete through configuration. That matters because entering an established market with an identical product is difficult. Entering with a slightly different answer to a real customer problem is easier. Why would a company like Corsair consider another supplier now? The answer may begin far away from gaming computers. Inside AI data centers, advanced accelerators depend on high bandwidth memory, or HBM. Unlike conventional desktop RAM, HBM stacks multiple memory dies vertically and places them extremely close to the processor. This architecture can move huge amounts of data while using less space and energy than a collection of ordinary modules. For artificial intelligence, that bandwidth is critical. An AI accelerator without enough memory bandwidth is like a fire engine connected to a garden hose. The processing units may be extraordinarily powerful, but they cannot remain productive if data arrives too slowly. HBM solves part of that problem. It is also extremely valuable. Memory companies can earn far more from advanced data center products than from ordinary consumer DRAM. Naturally, Samsung, SK hynix, and Micron are investing aggressively in HBM and other premium server products. But factories do not possess unlimited capacity. HBM consumes more wafer resources than conventional DDR5. Micron has explained that producing a given amount of HBM can require roughly 3 times the wafer capacity needed for the same quantity of DDR5 bits, with future generations potentially demanding even more. So the AI boom creates a paradox. The world is producing increasingly sophisticated memory, yet ordinary memory can become tighter and more expensive because manufacturing resources are moving toward the premium end of the market. The penthouse is expanding. The ground floor apartments become harder to find. For a new supplier focused on conventional DDR5, that creates an opening. CXMT does not need to outperform the best memory Samsung has ever built. It does not need to lead HBM technology tomorrow. It does not need to win every benchmark. It needs to become good enough, stable enough, and available enough that module manufacturers consider it a practical alternative. That is a very different target. In established technology markets, customers often remain with the same supplier because changing creates risk. New parts require testing. Firmware may need adjustment. Warranty behavior must be understood. Engineers must confirm that the component performs consistently across different systems and temperatures. Even a cheaper alternative may not be attractive if it introduces unpredictable failures. But shortages change the calculation. When the familiar supplier cannot provide enough chips, or when prices rise sharply, the inconvenience of testing a new source begins to look smaller. Scarcity does not merely increase prices, it lowers the walls surrounding the market. This may be the true opportunity for CXMT. The company is arriving at a moment when conventional DRAM customers are actively looking for more supply, while the established manufacturers are chasing the extraordinary economics of artificial intelligence. It is similar to a busy restaurant focusing almost entirely on expensive private events. The regular customers still need dinner. Eventually, another restaurant opens across the street. At first, people may enter only because the usual place is full. Then some discover that the alternative is acceptable. A few may even prefer it. This is where the story requires restraint. A label showing DDR5 6000 does not reveal long-term reliability. It does not tell us how consistently different modules perform. It does not reveal how much overclocking headroom exists, how the chips behave at elevated temperatures, or how efficiently CXMT can manufacture millions of identical dies. Those questions require independent testing. Memory stability can be deceptive. A system may boot normally, run everyday software, and appear perfect, then produce an error after several hours under a heavy workload. That is why serious qualification takes time. Manufacturers test voltage margins, temperature ranges, signal integrity, compatibility, retention, and repeated stress cycles. Server customers can be even more demanding, because a small failure rate multiplied across thousands of machines becomes a large operational problem. Corsair's involvement, assuming the module is genuine and production-ready, provides some reassurance. A company selling performance memory has a reputation to protect, but the logo on the heat spreader cannot replace comprehensive testing. At present, the most accurate conclusion is not that CXMT has matched Samsung, Micron, or SK hynix. It is that CXMT appears to have reached a level where its DDR5 can be considered for a mainstream branded product. That sentence is less dramatic. It is also more important. The immediate threat is not that millions of customers will suddenly reject Korean and American memory. The immediate threat is bargaining power. When only 3 suppliers can provide a critical component, customers have limited options. If one company reduces output, another encounters production problems, and the third prioritizes higher margin products, buyers must accept the available price. A credible fourth supplier changes those conversations. Corsair does not need to replace every Samsung or Micron chip with CXMT memory. The The mere possibility of shifting part of its, but suddenly every existing operator knows customers have another choice. Prices, service, and availability begin to matter more. CXMT could play that role in conventional DRAM, even if its products remain concentrated in China and selected international markets. The additional capacity may reduce pressure on global supply. It may encourage module brands to diversify. It could also force established producers to think carefully before moving too much manufacturing attention away from ordinary consumer memory. Competition does not require a new company to become number one. Sometimes it only requires the company to become impossible to ignore. There is another reason the Corsair appearance matters. Trust moves through layers. Most consumers have never heard of the company that manufactured the individual DRAM dies inside their memory kit. They trust the brand printed on the outside. Corsair performs the testing, creates the product profile, provides support, and handles the warranty. If the module works, customers rarely investigate further. That allows a relatively unknown semiconductor supplier to enter the market behind a familiar name. This is how industrial acceptance often spreads. First, a component appears in a limited regional product. Then it enters more models. Another brand qualifies it. A laptop manufacturer tests it. Volumes grow. Engineers collect reliability data. Manufacturing improves. Customers become less nervous. Nothing appears to happen, and then the supplier is suddenly part of the normal ecosystem. The hardest step is often not producing the chip. It is persuading the first major customer to take the risk. That is why one Corsair module can mean more than its sales volume suggests. It creates a reference point. Future customers no longer have to ask, "Has anyone used this?" They can ask, "How did it perform?" That is a much easier conversation. Samsung, Micron, and SK Hynix are not standing still. They operate some of the most advanced semiconductor facilities on Earth. They have deep relationships with server companies, computer manufacturers, and smartphone brands. Their technologies have passed years of qualification across enormous product volumes. They also lead in areas where the greatest value is currently being created. HBM is central to AI acceleration. Low-power memory is critical for mobile devices. Advanced server DRAM must combine capacity, efficiency, reliability, and bandwidth at a scale that leaves little room for error. CXMT's presence in DDR5 6000 does not erase those advantages. There is also a difference between demonstrating an 8,000 megabit per second product and shipping it profitably in massive quantities. Yield, cost, consistency, and delivery schedules decide whether a manufacturer becomes a permanent competitor. The established companies have survived multiple market crashes. They understand how to reduce cost from one generation to the next. They can combine technology leadership with enormous purchasing power and global support networks. CXMT therefore faces two races simultaneously. The first is technical, improving density, speed, efficiency, and reliability. The second is economic, producing enough working chips at a low enough cost to earn money throughout the memory cycle. Winning one race does not guarantee victory in the other. Still, the incumbents should not dismiss CXMT because its current products are behind the frontier. Semiconductor progress is cumulative. Every wafer teaches the manufacturer something. Every defective die reveals where the process failed. Every customer qualification exposes another compatibility issue. Every production increase gives engineers more data. A company can purchase equipment, hire experts, and study designs. But manufacturing intuition emerges only through repetition. The first million chips are not merely products, they are lessons. If CXMT begins supplying more module brands, it gains real-world feedback that cannot be replicated inside a laboratory. More shipments reveal failure patterns. More revenue funds better factories. Better yields reduce cost. Lower cost attracts more customers. The loop begins turning. This does not guarantee that CXMT will catch the leaders. Semiconductor history is full of expensive attempts that never closed the gap. But a supplier inside recognized commercial products has crossed a threshold. It is no longer learning only from prototypes. It is learning from the market. Samsung and Micron do not need to fear the exact chip inside today's Corsair module. They need to monitor what the company manufacturing that chip may learn over the next 5 years. Potentially, but not automatically. More supply usually creates downward pressure on prices, particularly for products that can be substituted easily. If module manufacturers can choose between 4 major DRAM sources instead of 3, competition should improve. However, several conditions must be met. CXMT must produce enough volume to influence the market. Its yields must be competitive. Customers must trust the chips. The company must continue manufacturing during downturns rather than disappearing when prices fall. And the savings must reach consumers. A module company can purchase cheaper chips without reducing the retail price. The difference may simply become additional margin. There is also the possibility that new supply is absorbed immediately by growing demand. AI computers, larger software, high-resolution content, and local machine learning workloads are increasing the amount of memory used across many devices. Yesterday, 16 gigabytes felt generous. Today, 32 gigabytes is becoming ordinary for performance systems. Tomorrow, 48 or 64 may feel normal. So CXMT might not make RAM dramatically cheap. It may instead prevent prices from rising even faster. Consumers rarely notice the disaster that did not occur. But economically, avoiding a shortage can be as valuable as creating a discount. For years, the memory industry has resembled a table with 3 chairs. Samsung occupied one, SK Hynix occupied another, Micron occupied the third. Many companies sold memory modules, but nearly all eventually returned to that same table to obtain the underlying chips. CXMT is now pulling another chair toward the room. It has not been invited to the head of the table. It may not yet be trusted with the most demanding dishes. And nobody knows whether the chair will survive the next severe market downturn. But it is visible. That alone changes the atmosphere. The Corsair module is not proof that the old order has ended. It is evidence that another supplier may have reached the beginning of commercial acceptance. And beginnings are easy to underestimate because they look unimpressive. A single module. A regional model. 6,000 megatransfers per second. No world record. No dramatic reveal. Just a computer component performing the ordinary job it was designed to perform. Yet entire industries are often disrupted not when a new technology performs an impossible trick, but when it becomes boring enough to use. My view is that Samsung, Micron, and SK Hynix do not need to panic, but they absolutely need to pay attention. CXMT is not yet an equal competitor across the entire DRAM market. The established manufacturers remain far ahead in advanced memory, especially the HBM products powering the AI boom. They possess enormous technical, financial, and manufacturing advantages. But the Corsair discovery suggests that CXMT may be crossing from technical capability into commercial credibility. That is the transition that matters. A company can remain irrelevant for years while producing impressive prototypes. The moment trusted brands begin placing its components inside normal products, the equation changes. The biggest threat to the established companies may not be that CXMT builds faster memory next year. It may be that CXMT provides adequate memory at the exact moment traditional suppliers are concentrating on more profitable AI products. The leaders are moving upward. CXMT is filling the space they leave behind. And once a new manufacturer establishes volume, customers, and manufacturing experience in the mainstream market, it can begin climbing toward the premium segments later. That journey will be difficult. It could take years. It may encounter technical setbacks, weak yields, or another brutal memory downturn. But for the first time, the possibility no longer looks theoretical. A Chinese DRAM supplier appears to be hiding beneath a Corsair heat spreader. That is small enough to overlook, and perhaps too important to ignore. So what do you think? Would you buy a Corsair memory kit containing CXMT chips if it offered the same warranty and performance at a noticeably lower price? Or would you stay with memory manufactured by Samsung, Micron, or SK Hynix until Chinese DRAM has built a longer record for reliability? Let me know where you stand in the comments. And if you want to see how China's semiconductor industry is moving from laboratory announcements into real products, supply chains, and computers, subscribe to Eastern Engine. Because the next major shift in technology may not arrive inside a futuristic supercomputer. It may already be sitting inside an ordinary stick of RAM. In 1972, an American astronaut climbed back into his lunar module, took one last look at the gray horizon, and left the moon behind. That was the last time any human stood on the surface of another world, 50-some years ago. And ever since, going back has been something the world's biggest space powers have talked about far more than they've actually done. But here's the thing, almost nobody outside the space world is paying attention to. While America's return to the moon keeps slipping, one delay, then another, China has quietly set a date, 2030, and it is hitting its checkpoints one by one, almost exactly on schedule. So the question is no longer whether humans will walk on the moon again. It's who gets there next, and whose flag is planted when they do. Today, let's look at exactly how close China really is, why NASA is genuinely nervous, and whether the country that's never sent a single person to the moon could actually beat the country that's already done it 6 times. Let's start with what China is actually saying, because it would be easy to wave this off as the kind of grand announcement countries love to make and then never follow through on. China's Manned Space Agency has stated, plainly and repeatedly, that it intends to land astronauts on the moon before the year 2030. And recently, officials doubled down, saying the program is on track and that the hardware is, in their words, progressing smoothly. Now, talk is cheap. Plenty of moon promises have come and gone. What makes this one different is that China has spent the last 2 decades building a track record that's almost boringly reliable. They say they'll do a thing, set a date, and then, more often than not, they do it. Consider what they've already pulled off. They've landed robotic missions on the far side of the moon, the side that always faces away from Earth, which no other country had ever soft landed on. They've scooped up lunar soil and flown it back to Earth. They've built and fully staffed their own space station, orbiting right now with crews rotating in and out. This is not a country fumbling towards space. This is a country that has been methodically climbing a ladder, rung by rung, and the top of that ladder is a human footprint on the moon. So what does it actually take to put people on the moon? 3 big pieces of hardware, and China is building all 3 at once. First, the rocket. It's called the Long March 10, a giant 3-stage heavy-lift rocket designed specifically to throw enough mass toward the moon to make a crewed landing possible. Building a rocket this powerful is one of the hardest things any space program can attempt, and only a handful of nations have ever managed it. To put it in perspective, getting a crew to the moon and back isn't like launching a satellite into orbit a few hundred miles up. You have to push a heavy spacecraft nearly 250,000 miles, slow it down, and then have enough power left to bring everyone home. That demands raw muscle that very few rockets in history have ever had, and China is building theirs from the ground up. What's interesting is the approach they've taken. Rather than inventing something wildly experimental, they've scaled up and refined technology they already trust, clustering proven engines together to generate enormous thrust. It's a conservative, methodical design philosophy, and in spaceflight, conservative and methodical is often exactly what gets you to the finish line in one piece. Flashy doesn't matter on the launch pad, reliable does. Second, the crew spacecraft. It's named Mengzhou. Think of it as China's version of the capsule that carries astronauts out to the moon and safely back home. It's built in 2 parts, one section that brings the crew back to Earth, and another that provides power, propulsion, and life support along the way. It's designed to carry a crew of around 6, which is notable on its own, because more seats means more capability, more scientists, more equipment, more ambition per mission. And critically, parts of it are being designed to be reusable, which is a sign China is thinking past a single heroic landing and toward a sustained program of going back again and again. This capsule has to do something genuinely difficult too. Coming home from the moon, a spacecraft slams into Earth's atmosphere far faster than anything returning from low orbit. We're talking a fiery, high-speed re-entry that demands a heat shield and a guidance system that simply cannot fail. The fact that China is already flight testing this hardware, rather than just sketching it on paper, tells you how far along they really are. And third, the lander itself, named Lanyue, which translates beautifully to embracing the moon. This is the vehicle that would actually carry astronauts down to the surface and back up to lunar orbit. It's reportedly capable of bringing along a small rover, so the crew wouldn't just plant a flag and leave. They'd actually drive across the surface and explore. Think about what that signals. A flag and footprints mission is a photo op. A mission that brings a rover is the beginning of real exploration, covering ground, studying the terrain, scouting for resources. China isn't designing a quick visit, they're designing a foothold. Here's the part that should make you sit up. China says testing on the lander began back in 2024. The crew capsule is already going through prototype flights, and they've laid out a clear sequence: robotic test flights first, then uncrewed system tests, then a joint test mission near the end of the decade, with the crewed landing a year after that. Every piece has a slot on the calendar. They've even talked publicly about testing the emergency escape systems, the hardware that would yank a crew to safety if a launch went wrong, which is the kind of unglamorous safety-first detail that serious programs obsess over and pretenders skip. It's a staircase, and so far, they're walking up it on time. Now, let's talk about the other side of this race, because you can't understand why people are nervous without it. America's plan to return to the moon is called Artemis. And to be clear, Artemis is real, it's serious, and it has made genuine progress. NASA has flown crews around the moon for the first time in 50 years. The ambition is enormous, not just to visit, but to build a lasting presence. A stepping stone towards sending humans all the way to Mars. But Artemis has one persistent problem: delays. The timeline has slipped again and again. A mission that was once aimed at 1 year got because it's not simple incompetence. Part of it is that NASA holds itself to an extraordinarily high safety bar. These are human lives, and the agency carries the memory of past tragedies. Part of it is that the program depends on a web of contractors and commercial partners, each with their own timelines and technical hurdles. And part of it is politics. Budgets shift, administrations change, priorities get rewritten every few years. America's space program has to survive a gauntlet that China's, run by a single centralized state, simply doesn't face in the same way. But the reasons for the delays don't change the result of the delays. And this is where the math gets uncomfortable. On paper, America is still aiming to land first. NASA's leadership has said publicly they intend to be on the surface before China is. But on paper is doing a lot of work in that sentence. Because every time Artemis slips, the gap between America's target and China's 2030 deadline gets thinner. A program that's ahead but keeps sliding backward is, at some point, just a program that's running out of cushion. It's like watching two runners. One has a head start and far more experience, but that runner keeps stopping to retie their shoes, while the other is running at a steady, relentless pace and never breaks stride. The runner in front is still in front, for now, but anyone watching can feel which way the momentum is flowing. So why does this rattle people in Washington? Why not just shrug and say, we've been to the moon, we'll get there again? Because in this race, second place has consequences that go way beyond bragging rights. Members of the US Congress have openly warned that the country cannot afford to let China reach the moon first. NASA's own leadership has framed this as a great competition with a rival that has both the will and the means to challenge America in space. Those are not casual words. That's the language of a country that has realized it might actually lose something it assumed it owned. And here's the strategic twist that makes this more than a symbolic contest. Both China and America are aiming for the same destination, the moon's south pole. Why there? Because scientists believe those permanently shadowed craters hold water ice. And water on the moon is everything. You can drink it, you can split it into oxygen to breathe, and into hydrogen for rocket fuel. In other words, whoever establishes a foothold at the lunar South Pole first gets first pick of the most valuable real estate off of planet Earth. This isn't about a flag and a photo. It's about who sets the rules for the next era of space, who builds the first base, who controls the best landing sites, who writes the playbook everyone else has to follow. And there's a deeper layer here that's easy to miss. The first moon race, back in the 1960s, was about proving a point. A contest of ideologies between two superpowers settled the moment a boot hit the dust. This new race is different. It's not about a single symbolic moment, it's about staying. Both sides are talking about permanent bases, long-term presence, and using the moon as a launch pad for going even deeper into space, eventually to Mars. The moon, in this version of the story, isn't the finish line. It's the gas station, the outpost, the high ground. There's also a question of leadership that goes beyond the moon itself. Space achievement has always been a kind of global advertisement, a way of telling the rest of the world, look what our system can do. When a country lands humans on another world, it doesn't just win a scientific prize. It wins prestige, influence, and the ability to pull other nations into its orbit, sometimes literally, by inviting partners onto its missions and into its station. China has been openly courting international partners for its lunar ambitions. Every country that signs on with China is a country not signing on with America, and vice versa. The moon, in that sense, has become a stage where a much larger competition plays out. That's why a country that already won the moon race once is suddenly very, very focused on not coming in second the second time around. Now I want to show you the moment that, to me, really captures how serious China is, and most people scrolled right past it. Recently, China launched a fresh crew to its space station. Routine on the surface, but buried in the details was something remarkable. One of those crew members is expected to stay in orbit for roughly a year, the longest single human spaceflight in China's history. Why does that matter for the moon? Because going to the moon and building a presence there means keeping humans healthy in space for long, grueling stretches. Long-duration missions are how you prove your life support systems, your food, your radiation protection, your crew's bodies can take the punishment. Every long stay in orbit is a rehearsal for something bigger. And it's not just the crewed flights. Look at how often China is launching anything into orbit. They went from around 68 orbital launches in 1 year to more than 90 the next, and they're on track for more than 140 in a single year. That's the tempo of a country that has turned spaceflight into something closer to an assembly line, and a fast-moving one. When a space program is launching that often, testing that aggressively, and keeping people in orbit for a year at a time, it tells you something. They're not hoping to reach the moon. They're training for it. Let me zoom out for a second, because I think the single most important thing to understand about China's space program isn't any one rocket or capsule, it's the pattern. For decades, China's approach to space has followed the same quiet rhythm: announce a clear goal, set a realistic date, build the pieces step by step, and let the results do the talking. No dramatic press conferences promising the impossible. No moonshots in the reckless sense of the word, just a long, patient climb. Look at how the space station came together. They didn't try to build it all at once. They launched a test lab, learned from it, then launched the real modules one at a time, until they had a fully functioning station with crews living aboard. Each step de-risked the next. By the time the hard part arrived, they'd already practiced most of it. The Moon program is following that exact same template. Robotic landings came first, including on the far side, which nobody had ever done. Then sample returns, bringing actual lunar material back to Earth, proving they could get to the moon, operate on it, and come home. Now they're building the crude hardware, testing it piece by piece, with a joint rehearsal planned before the real thing. It's the same staircase, just taller. And this is what makes the 2030 target so credible. It's not a number someone picked out of the air to grab headlines. It sits at the top of a sequence that's already mostly built, with each lower step already proven. When a country tells you it'll do something in 5 years, the right question is, have they been doing the work for the last 15? In China's case, the answer is yes. That doesn't make success guaranteed, but it does mean this deadline deserves to be taken seriously, far more seriously than the West has tended to take it. All right, the big question: can China really beat America back to the moon? Let me be honest with you, because that's the whole point of this channel. Nobody knows for certain, and anyone who tells you they're 100% sure is selling something. China still has enormous work ahead. They've never flown a human anywhere near the moon. Every piece of their lunar hardware, the giant rocket, the deep space capsule, the lander, still has to be tested, flown, and proven, all within a few short years. That is a brutal timeline, and spaceflight has a long history of humbling anyone who gets cocky. One serious failure could push everything back. But, and this is the part that's hard to argue with, America's biggest enemy in this race might not be China at all. It might be America's own delays. If NASA holds its current schedule, it likely still lands first. If. And that little word has been the weak point in the Artemis program from the beginning. So here's the real shape of it. America is ahead, but stumbling. China is behind, but sprinting at a steady, disciplined pace. And when you've got one side losing momentum and the other gaining it, the gap doesn't just shrink, it can close all at once. Here's my honest opinion. For whatever it's worth, I don't think this comes down to who has the better engineers, because both sides are extraordinary at what they do. I think it comes down to consistency. China's superpower in this race isn't a magic piece of technology. It's that they pick a date, build the staircase, and climb it without drama. America has more raw capability and more experience, but it keeps tripping over its own budgets, politics, and shifting priorities. And if I'm being straight with you, I think the safe bet is not that China definitely lands first, but that this race is going to be far, far closer than most people in the West assume. The comfortable belief that America obviously wins because it won before, that assumption is exactly what makes a country slow down, and slowing down in a race this tight is the most dangerous thing you can do. Whoever gets there first, one thing is certain: a new era on the moon is coming this decade. And for the first time since Apollo, it genuinely won't be a one-horse race. So now I want to hear from you. Do you think China actually pulls it off and lands on the moon by 2030? Or does America's experience win out in the end? And honestly, does it even matter to you who gets there first, as long as humanity goes back? Drop your answer in the comments. I read them. And the best takes sometimes become whole videos of their own. And if you want to keep up with this race, and everything else happening in China's technology, economy, and space programs as it unfolds, hit that subscribe button and ring the bell. This is Eastern Engine, where we break down the forces shaping the future, clearly and without the hype. New videos regularly, so you'll never miss what's coming next. Thanks for watching. I'll see you in the next one. For decades, analog computing carried a reputation for being fast but unreliable. Digital computers won because they could repeat the same calculation with predictable precision. Every value became a sequence of zeros and ones. Analog machines worked differently. They represented numbers with continuously changing physical quantities such as voltage, current, pressure, or resistance. That allowed them to solve some equations almost instantly, but tiny errors accumulated. Components drifted. Precision collapsed as problems became larger. Researchers at Peking University now say they have solved much of that problem. Their team built a foundry-made analog matrix solver using resistive random access memory, or RRAM. The system experimentally solved 16 by 16 real-valued matrix inversion problems at 24-bit fixed-point precision, which the researchers describe as comparable to FP32 digital computing. In massive MIMO signal detection, it reached digital-level accuracy after only 3 refinement cycles. And their benchmarking suggests that, with further circuit improvements, this architecture could deliver up to 1,000 times higher throughput and nearly 100 times better energy efficiency than leading digital processors at the same precision. That does not mean this prototype can run every AI model 1,000 times faster than an NVIDIA H100. It cannot replace a general-purpose GPU. The result applies to specialized matrix equation workloads, and the largest advantage is partly projected rather than fully measured in production hardware. Analog computing has always promised extraordinary speed. The missing piece was precision. Why digital computers dominated. A digital computer treats information as discrete values. At the lowest level, a transistor is interpreted as on or off. Software then performs arithmetic through carefully sequenced logic operations. Small electrical fluctuations usually do not change a 0 into a 1. Digital systems can use error correction, repeat operations, and store exact copies of data. Analog systems trade some of that certainty for direct physical computation. Imagine solving a mathematical equation by building an electrical circuit whose voltages naturally settle into the answer. The circuit does not need to execute millions of separate instructions. The physics performs the calculation as the signals move through the hardware. But real components are imperfect. Resistance changes with temperature. Amplifiers introduce noise. Manufacturing creates small differences from one device to another. The answer may be close, but not exact enough for scientific computing, communications, or modern AI. The Peking University team attacked the problem by separating speed from accuracy. One analog circuit produces a fast, approximate answer. A second analog operation measures the remaining error and corrects it. The system repeats this process until the solution reaches the required precision. What RAM actually does. The heart of the design is resistive random access memory. An RRAM cell stores information by changing the electrical resistance of a material between 2 electrodes. A low resistance state may represent one value. A higher resistance state may represent another. In this experiment, each cell supported 8 stable conductance levels, equivalent to 3 bits of information. The researchers used a 1 megabit RRAM chip for high-precision matrix vector multiplication and a smaller 8x8 RRAM array for low-precision matrix inversion. Both were fabricated using a commercial 40-nanometer CMOS platform. This was not a hand-built device assembled from exotic laboratory materials. The chips were produced through a foundry-compatible process using 1 transistor, 1 resistor memory cells. An RRAM array can behave like a physical matrix. Each cell's conductance represents one matrix element. Input voltages represent a vector. When those voltages pass through the array, the resulting currents naturally combine according to Ohm's law and Kirchhoff's current law. The array performs matrix vector multiplication through its physical behavior. A digital processor would normally load data from memory, execute many multiplication and addition instructions, then write the result back. The RRAM array stores the values and performs the calculation in the same location. That reduces data movement and avoids much of the conventional von Neumann bottleneck. The matrix problem. Matrix equations appear almost everywhere in advanced computing. Wireless base stations solve them to separate overlapping signals from many antennas. Some neural network training methods also depend on matrix inversion or related linear system solving. A common form is A times X equals B. The matrix A and vector B are known. Digital methods solve this accurately, but the cost grows quickly as the matrix becomes larger. An analog circuit can produce a solution directly by placing the resistive array inside a closed feedback loop with operational amplifiers. However, the first answer is only approximate. The challenge is improving that result without handing the important calculation back to a digital processor. Earlier hybrid systems often used analog hardware for a rough estimate and digital floating-point hardware for the precise correction. The Chinese team kept both major operations in the analog domain. How the two-stage solver works. The first stage performs low-precision analog inversion. Because the RRAM devices and supporting circuits are not perfectly accurate, the result contains an error. The second stage performed improved by roughly 3 bits during each cycle, reflecting the 3-bit conductance levels in the RRAM cells. A 24-bit 4x4 real-valued matrix reached the maximum target precision after 9 cycles. Larger complex-valued problems generally reach the same precision within about 10 cycles. This is the central idea. The fast analog inversion does not need to be perfect. It only needs to be good enough that repeated analog correction converges toward a precise answer. The design accepts analog error, measures it, and then removes it. That is very different from pretending the hardware is naturally exact. How bit slicing builds precision. One RRAM cell stores only 3 bits, but the complete system reaches 24-bit precision. It does this through bit slicing. A high-precision matrix value is divided into several lower-precision pieces. Each piece represents a different group of bits and is mapped into a separate RRAM array. The arrays perform low-precision calculations in parallel or sequence. Their partial outputs are then shifted according to their significance and added together. It is similar to separating a large decimal number into thousands, hundreds, tens, and units. Each part is easier to represent. Combining the weighted parts reconstructs the original value. Bit slicing was already useful for analog matrix vector multiplication. The harder problem was applying high precision to matrix inversion, where the same simple distributive rules do not transfer cleanly. The researchers solved this by keeping inversion low precision, while using bit-sliced matrix vector multiplication to calculate the correction accurately. Block AMC makes the design scalable. A physical RRAM array cannot grow without limit. Large arrays suffer from wire resistance, routing complexity, stronger currents, parasitic effects, and amplified noise. The team therefore used a block-based algorithm called Block AMC. A larger matrix is divided into smaller submatrices. Different RRAM arrays store different blocks. The system performs a sequence of inversion and multiplication operations on those blocks, then combines the intermediate results. Using this approach, the researchers experimentally solved a 16x16 real-valued matrix inversion problem with 24-bit fixed-point precision. The relative error reached roughly 1 part in 10 million after 10 cycles. 16x16 may sound small compared with giant AI models, but matrix inversion is more difficult to map into analog hardware than ordinary multiplication. The point was to prove that a precise analog solver could scale beyond one tiny hardwired circuit. The block method also allows future systems to use multiple moderate-sized arrays instead of depending on one enormous analog network. The massive MIMO test. The researchers demonstrated the solver on wireless signal detection. Massive MIMO uses many antennas at a base station to communicate with several devices at once. The received signals overlap. The base station must solve matrix equations to separate the different users and recover the transmitted information. The experiment modeled systems using higher-order 256 QAM modulation, which packs 8 bits into each transmitted symbol. That demands far more precision than earlier analog demonstrations limited to simpler modulation. The researchers transmitted a binarized image of the Peking University emblem through the modeled wireless channel. Their analog solver recovered the signal with bit error performance comparable to FP32 digital processing. For a 128x8 system, the detector reached comparable accuracy after only 3 iterative cycles. This matters because it connects the architecture to a real workload rather than only random laboratory matrices. Wireless communication, especially future 5G advanced and 6G systems, may require repeated matrix solving with strict limits on latency and energy. Where the 1000x claim comes from. The 1000 times figure needs careful explanation. The prototype did not directly defeat an NVIDIA H100 by 1000 times in a complete application. The researchers benchmarked their analog architecture against state-of-the-art digital processors at comparable precision. Their model considered matrix size, array dimensions, converter overhead, amplifier speed, and block processing requirements. At moderate array sizes, the analog design already showed advantages for specific matrix solving tasks. For larger optimized arrays and faster operational amplifiers, the projected throughput advantage could approach 3 orders of magnitude. Energy efficiency could improve by nearly 2 orders of magnitude. The paper also notes that Block AMC reduces the advantage as matrices become larger because more stages and intermediate operations are required. Even then, the architecture remained ahead in the researchers' comparisons. The maximum result depends on better supporting circuits and dedicated integration. So the honest statement is that the demonstrated architecture could reach 1000 times higher throughput for precise matrix equation solving. It is not evidence that an analog chip will make every CUDA workload 1000 times faster. Why this could matter for AI? Modern AI depends heavily on matrix operations, but not every matrix operation is the same. Neural network inference is dominated by matrix multiplication. This chip focuses on matrix inversion and solving linear systems. Those operations appear in optimization, scientific machine learning, signal processing, and some second-order training methods. An analog solver could become a specialist accelerator. A conventional CPU or GPU would manage the overall program. When the workload reaches a suitable matrix equation, the system could send that task to the RRAM solver. The analog hardware would produce the answer quickly and efficiently, then return it to the digital processor. This is more realistic than expecting analog computing to replace digital machines completely. Digital hardware remains better for control flow, memory management, software compatibility, and exact general-purpose operations. Analog hardware may win by handling the narrow calculations where physics offers a shortcut. The honest catch: several engineering challenges remain. The low-precision inversion circuit still uses external components, including operational amplifiers, data converters, switches, and a microcontroller. The larger, high-precision RRAM array was integrated, but the complete solver was not one compact commercial chip. Scaling the inversion array beyond the demonstrated size requires dedicated design and fabrication. Larger arrays produce stronger currents and more complicated routing. Noise, wire resistance, device defects, and temperature variation must remain controlled. The system also needs programming and verification procedures to place every RRAM cell into the correct conductance state. Converters and amplifiers consume area and energy, and commercial software would need tools that identify suitable equations and map them efficiently onto the hardware. It does not prove that mass production will be easy. My take is that the breakthrough is not simply bringing analog computing back. It is making analog error part of the algorithm. The first circuit is allowed to be imperfect. The second measures that imperfection. Repeated correction turns a rough physical answer into one approaching digital precision. That is a powerful design philosophy. Future computers may not choose between analog and digital. They may combine both. Digital processors will coordinate the system and preserve programmability. Analog accelerators will solve selected equations using currents, resistance, and feedback, instead of long sequences of instructions. The 1,000 times estimate may shrink once complete commercial overhead is included, or better integration may allow the architecture to approach its projected advantage. Either way, this work moves analog matrix solving from a low-precision curiosity toward a credible specialist technology. So what do you think? Will analog accelerators become essential for AI, science, and 6G? Or will manufacturing variation and software complexity keep GPUs in control? Let me know your view in the comments. And subscribe to Eastern Engine for more grounded coverage of the chips, materials, and engineering breakthroughs reshaping computing. Because China has not built a universal NVIDIA replacement, but it may have solved the precision problem that kept analog computing out of the modern chip era. Picture the emptiest place you can imagine. No buildings, no roads worth mentioning, just cracked earth, howling wind, and a sky that goes on forever. Now drop the single largest wheeled crane ever constructed right in the middle of it. A machine so absurdly oversized that engineers around the world genuinely questioned whether building it was even worth attempting. This is not a concept. This is not a prototype sitting in a lab. This machine was built, transported over 2,000 kilometers, assembled from scratch in the desert, and then put to work doing something no crane had ever done before on wheels. And when the job was finished, the construction industry had to rewrite what it thought was possible. Before we talk about the crane itself, we need to talk about why it exists at all. Because this machine was not built to set records. Records were just a side effect. China has a massive energy challenge. The country needs enormous amounts of electricity, and it has been pushing hard toward wind power as a way to meet that demand without burning more fossil fuels. The Gobi Desert in northwest China turns out to be one of the best wind corridors on the planet. The air moves fast out there, consistently, predictably, across hundreds of kilometers of open terrain. If you can tap into that energy, you can power entire cities. So China has been doing exactly that, building wind farms across the Gobi on a scale that is almost difficult to visualize. Hundreds of turbines, then thousands, more going up every year. But here's the problem that nobody talks about when they show you footage of a wind farm looking serene and picturesque. The turbines keep getting bigger. Engineers discovered that a taller turbine with longer blades catches dramatically more wind than a shorter one. The math is not subtle. Go bigger, generate far more power per structure. So the turbines grew, and then grew some more. The latest generation of turbines being installed in the Gobi now stand over 170 meters tall. That puts them in the same height range as major skyscrapers. At the very top of that tower sits a component called the nacelle, a massive enclosed unit that houses the generator, the gearbox, and the control systems. On these newer models, that nacelle weighs north of 150 tons. And then you have the blades. 3 of them, each stretching 108 meters from root to tip, longer than a regulation American football field, end to end. You have to lift all 3 of them, one at a time, up to the top of a structure taller than most buildings in the world and pin them into place precisely. Regular cranes top out well below this challenge. The best heavy lift cranes used in urban construction can handle around 900 tons. Impressive, until you realize that this operation required something that could manage 4,000 tons, more than 4 times greater, at heights that city cranes never need to reach. That gap between what existed and what was needed is why the Zoomlion Zadat 40000 hour was born. Zoomlion is a heavy machinery company based in Changsha in China's Hunan province. They already had a strong reputation in the crane world. But when the wind energy sector started demanding lifts at heights and weights that no existing equipment could handle, their engineers got to work on something genuinely unprecedented. The Zadat 40000 hour is technically classified as an all-terrain crane, meaning it rides on wheels and can be driven to a job site rather than being built in place. That distinction matters enormously because building a crane that stays in one location permanently is a totally different engineering challenge from building one that has to travel across highways, get disassembled and reassembled, and function reliably in extreme desert conditions. The numbers on this machine are staggering in every direction. Its main lifting boom, once fully assembled, reaches a working height of over 186 meters. That figure alone, roughly 60 stories straight up, would be the headline on almost any other crane. Here it is just the starting point. The counterweight system, which is what keeps a crane from toppling forward when it lifts heavy loads, uses 2 large outrigger arms called superlift wings that spread out behind the crane's body. For the wind turbine installation, the crew loaded 260 tons of counterweight onto those wings. And here is the detail that really lands. That was not even close to the crane's maximum counterweight capacity. It had significant additional headroom for heavier jobs. Individual components of this crane are themselves enormous. The rotating base platform that allows the crane to swing its boom in any direction weighs 65 tons on its own. Each of the 2 main boom base sections weighs 66 tons. The hydraulic cylinders that drive the crane's mechanical systems come in at 32 tons each. When you start adding up all the pieces, the total weight of the assembled crane is simply difficult to hold in your head as a real number. Here is where the story picks up a challenge that the crane's specs alone don't convey. Getting this machine to northwest China was its own logistical operation. The crane does not travel assembled. It travels as hundreds of individual components loaded across a convoy of 28 specialized transport vehicles. When that convoy rolls down the highway, it does not look like a single piece of equipment being delivered. It looks like an entire industrial district changing neighborhoods. The journey from Changsha to the job site in the Gobi covered more than 2,000 kilometers. Route planning for a convoy like this requires months of advance work. Bridge weight limits, tunnel clearances, road curvature, overhead power line heights, every single kilometer has to be assessed in advance. Some sections require escort vehicles. Some require nighttime travel to avoid disrupting daytime traffic. Some require temporary road reinforcements so the heaviest pieces don't crack the pavement. After all of that, the convoy arrived at the desert site and the team immediately began the next challenge, putting the machine together from nothing, outdoors, in one of the most inhospitable environments in China. Assembling the world's largest mobile crane in the middle of the Gobi Desert is not a weekend job. It requires multiple support cranes working in coordination, teams of engineers monitoring every measurement and connection, and the kind of patience that comes with knowing that one misaligned component early in the process can cascade into days of rework. The process started with the slewing platform, that 65-ton rotating ring at the base. Support cranes lifted it into position while the main crane chassis was brought into precise alignment beneath it. The connection requires hydraulic locking pins to seat perfectly. A centimeter of misalignment at this stage affects every lift that follows. Then came the outrigger installation. These are the thick hydraulic legs that extend outward from the crane's body to provide a stable base during lift. Assembly came next. 7 sections, connected in sequence, each one added using hydraulic pin systems, rather than the old-fashioned hammer and brute force method. As each section locked into place, the crew ran alignment measurements from the lifting hook center point all the way back to the crane's rotational axis. That single measurement, accurate to within centimeters, determined whether the machine could operate safely at full capacity. When the superlift wings finally spread open and the full counterweight was loaded, the assembled machine transformed. From a distance, it stops looking like a piece of construction equipment. It looks more like something from a different era of engineering, something built to move a mountain rather than lift a component. The actual turbine installation required 3 cranes working in stages, each one handling the section of the tower within its capacity range before handing the job off to the next. A 900-ton crane started the work, placing the foundation ring and the lower tower sections. A 1,800-ton crane took over for the middle portion of the tower, stacking each heavy segment as the structure climbed. By the time those 2 machines had done their work, the tower was already taller than anything around it for hundreds of kilometers. Then the ZAT 40000 hour took over. The final tower sections went up first, bringing the structure to its full height of over 170 meters. Then came the nacelle lift, 150 tons of machinery swinging at the end of a cable higher above the ground than almost anything in the region. The crew attached guide ropes to all 4 corners of the nacelle before it left the ground. As the crane lifted it skyward, ground teams kept constant tension on those ropes, preventing the wind from catching the nacelle and spinning it into the tower. At that height, an uncontrolled rotation does not result in a minor problem. It results in a catastrophic structural failure. So the teams held on, adjusting and compensating, while the crane lifted steadily upward until the nacelle seated onto the tower and the bolts could be driven home. The nacelle was the heaviest single lift. The blades were the most complicated. Each blade is 108 meters long and weighs 30 tons. Transporting something that size from a manufacturing facility to a desert mountain site is a puzzle with no clean solution. Blade transport vehicles are purpose-built for this job, with extendable frames that can spread the axles far apart to carry the blade in a stable, balanced configuration. On open highway stretches, this works well. But the final approach to the turbine site ran through mountain roads with tight switchbacks and steep grades that an extended transport configuration simply cannot negotiate. So the crew switched to a shorter vehicle configuration for the mountain section. This immediately created a new problem. With the blade hanging off the front of a shorter vehicle, the weight distribution becomes dangerously unbalanced. The rear lifts, the front digs in, and control is compromised. The fix required adding enough total vehicle weight, ballast, equipment, and support machinery to bring the total up to 160 tons, heavy enough to keep the rear wheels planted and the blade level throughout every curve. 3 additional blade-handling vehicles shadowed each transport around the clock, ready to intervene if the load shifted. After all of that, the first blade arrived at the site and could not be installed. Wind. The gusts were too strong. A 108-meter blade in wind behaves like a sail the size of a stadium. The crane cable twists, directional control over the blade disappears, and the risk of impact with the tower becomes unacceptably high. So the team unloaded the blade and waited. They waited through the afternoon, through the evening, through most of the night. Workers sat on the desert floor under a sky full of stars, watching the wind indicators, drinking tea, and waiting for a window. Just before sunrise, the air went calm. The lift began within minutes. By the time dawn broke fully over the Gobi, the first blade was locked into position. The second followed without incident. A convoy of 3 loaders hauled the third blade up the mountain road together, and it went up on the first attempt. The turbine was complete. A 6.25 megawatt wind turbine. Fully assembled, fully installed, 170 meters tall with blades spanning over 200 meters tip to tip, now stands in the Gobi Desert, generating clean electricity. At full output, this single structure produces enough power to supply hundreds of homes every hour. Multiply that across the hundreds of turbines visible from that same hilltop, and across the thousands planned for the broader wind corridor, and the scale of what is being built starts to come into focus. The Zoomlion ZAT 40000 hour made it possible. Not because it is the most automated machine ever designed. The assembly and operation still depend heavily on experienced workers making judgment calls in difficult conditions. Not because it removed the human element. Teams spent a full night on that desert floor waiting for the wind to cooperate. It made it possible because it extended the physical limit of what a wheeled crane can reach and lift, pushing that ceiling high enough to meet the demands of the next generation of wind energy infrastructure. Behind that crane, if you look out across the Gobi horizon, white towers stretch in every direction as far as you can see. Each one was once a pile of components on a truck. Each one now turns wind into electricity for communities hundreds of kilometers away. This machine was not built to sit in a showroom. It was built to go somewhere difficult and do something that had never been done. It did exactly that, on wheels. For the entire history of electrical power, almost every power plant on Earth has worked the same fundamental way. You take a heat source, burning coal, splitting atoms, concentrated sunlight, it doesn't matter which, and you use that heat to boil water. The water turns to steam. The steam, under enormous pressure, blasts through a turbine and spins it. The spinning turbine turns a generator, and the generator produces electricity. Then you cool the steam back into water and do the whole thing over again, millions of times. That cycle is so old, it predates the light bulb. The basic principle of using boiling water and steam to do mechanical work goes all the way back to the steam engines that powered the Industrial Revolution. For more than 2 centuries, through every advance in fuel and engineering and materials science, the working fluid at the heart of nearly every power plant stayed exactly the same. Water in, steam out. Spin the turbine. China just broke that 200-year tradition. In a steel plant tucked into the mountains of southwest China, engineers have switched on a power generator that doesn't use steam at all. Instead, it runs on the one substance the entire world spends enormous effort trying to get rid of. It runs on carbon dioxide, the gas we blame for climate change, the byproduct of every furnace and engine and power station, the thing scientists are racing to capture and bury underground. China has turned it into the beating heart of a power plant. And the headline number is staggering. This system is reportedly around 50% more efficient at squeezing electricity out of waste heat than the steam technology the world has relied on for generations. So how does a power plant run on a pollutant? Why did this take 200 years to figure out? And what does it actually mean for the future of energy? Let's break it all down. Before we go any further, I have to clear something up, because the way this story gets told online is genuinely misleading, and I'd rather give you the honest version. When people hear a power plant that runs on CO2, they immediately picture giant machines sucking carbon dioxide out of the sky, cleaning the atmosphere while generating electricity. A magic device that fixes climate change and powers your home at the same time. That is not what this is. I want to be completely straight with you about that. This technology does not pull CO2 out of the air. It does not reduce the amount of carbon dioxide in the atmosphere. And it does not burn CO2 as a fuel. You can't burn carbon dioxide. It's already been burned, which is what makes it CO2 in the first place. So what is actually happening here? The carbon dioxide isn't the fuel, it's the messenger. In every power plant, you need something to carry heat from your heat source to your turbine. For 200 years, that messenger has been water turned to steam. What China has done is replace the water with carbon dioxide, a fixed amount of it, sealed inside the system, used over and over in a closed loop. The CO2 never escapes. It never gets used up. It just shuttles heat back and forth, endlessly. Why does that matter? Because it turns out carbon dioxide, when you treat it the right way, is a dramatically better messenger than water ever was. And understanding why requires us to look at one of the stranger states that matter can exist in. You already know the 3 everyday states of matter: solid, liquid, gas, ice, water, steam. Carbon dioxide has the same 3 states. Frozen, it's the dry ice that fogs up a concert stage. As a gas, it's the invisible thing you exhale. But there's a 4th condition, and it's the key to this whole story. If you take carbon dioxide and crush it under enormous pressure while also heating it past a certain temperature, something bizarre happens. It stops being clearly a gas and stops being clearly a liquid. It enters a hybrid state that scientists call supercritical. In this state, the CO2 flows freely and fills its container like a gas would, but it's also dense and packed tight, carrying heat the way a liquid does. Think of it as getting the best of both worlds at once. A gas is easy to push around and compress, but it's terrible at holding heat. A liquid is fantastic at holding and moving heat, but it's heavy and hard to pump. Supercritical CO2 behaves like both simultaneously. It moves like a gas and carries heat like a liquid. That combination is exactly what you want in the messenger that carries energy through a power plant. And it gives supercritical CO2 a set of advantages over steam that are honestly difficult to overstate. First, it transfers heat far more efficiently than steam does, which means more of your precious heat energy actually ends up spinning the turbine instead of being lost along the way. Second, and this is the part engineers get genuinely excited about, supercritical CO2 is so dense and energetic that the turbine it spins can be a fraction of the size of a conventional steam turbine for the same power output. We're talking about a turbine you could potentially hold in your arms doing work that would normally require a machine the size of a bus. And third, there's a subtle but enormous efficiency win hiding in the physics. To make steam, you have to boil water, and boiling water requires a huge amount of energy just to force it through that phase change from liquid to vapor. It's a wasteful, energy-hungry step. Turning CO2 into its supercritical state takes far less energy than boiling water into steam. You skip a giant chunk of waste right at the start. Put all of that together and you get a power system that is smaller, more efficient, and able to wring electricity out of heat that older technology would have simply thrown away. Here's the obvious question. If supercritical CO2 is so much better than steam, why has the entire world been boiling water for 2 centuries instead? The answer is that this idea is not new at all. In fact, it's shockingly old. The concept of using a supercritical CO2 cycle to generate power was first seriously explored back in the 1960s. Engineers in Italy and the United States looked at the thermodynamics and realized this approach could, on paper, outperform conventional steam plants. The math worked, the theory was sound, the promise was clear, and then it sat on a shelf for 60 years. Because there was a problem, and it was a brutal one. To make this work, you have to hold carbon dioxide at extreme pressure and extreme temperature, continuously, for years on end, while it surges through your machinery. And the materials available in the 1960s, and for decades afterward, simply could not survive those conditions. The metals would corrode, the seals would fail, the turbine components would degrade under the relentless assault of hot, high-pressure CO2. The fluid that made the system so efficient was also aggressive enough to chew through the equipment meant to contain it. So the idea remained exactly that, an idea. A tantalizing concept that worked beautifully in theory and fell apart the moment you tried to build it and run it for real. For 60 years, supercritical CO2 power was the technology of the future, and it seemed like it always would be. Cracking it required advances in metallurgy, in high-pressure engineering, in turbine design, and in materials that could shrug off conditions that would destroy ordinary steel. It required someone willing to pour money and time into solving a problem the rest of the world had largely given up on. That part of the story should sound familiar if you follow Chinese engineering. It's a pattern we've seen again and again. The project is called Kaitan-1, sometimes referred to as Supercarbon Number 1, and it was developed by the Nuclear Power Institute of China, part of the China National Nuclear Corporation, working alongside industrial partners. It's located inside a working steel plant in Liupan, Shui, a city in mountainous Guizhou province in southwest China. And the choice of location is not random. It's central to the whole point. Steelmaking generates staggering amounts of heat. Furnaces run at blistering temperatures, and a huge portion of that thermal energy normally just escapes into the atmosphere as waste. It does no work. It powers nothing. It simply radiates away, lost forever. Every steel plant on Earth is, in a sense, constantly throwing away energy. Kaitan-1 captures that waste heat, the heat that would otherwise have vanished, and feeds it into the supercritical CO2 system. The hot CO2 expands and drives the compact turbine. The turbine spins the generator. Electricity flows out to the grid, and the CO2 cycles back around to grab more heat and do it all again. Nothing is burned. No new emissions are created. The plant is generating genuinely useful electricity out of energy that was previously garbage. The system was built in 2 units, each producing 15 megawatts. The first unit connected to the grid on December 20, 2025, and ran stably for months. Then, on May 30, 2026, engineers brought the second unit online, bringing the total installed capacity to 30 megawatts. With both units running, China National Nuclear Corporation declared it the world's first full-scale commercial demonstration of supercritical CO2 waste heat power generation, and the largest and most advanced project of its kind anywhere on the planet. And here's where that efficiency figure comes back. According to the teams behind it, the system is roughly 50% more efficient at capturing and converting waste heat from steel production than the steam-based technology that would traditionally do this job. 50% more electricity from the same wasted heat with smaller equipment. Now you'll have noticed this was built by China's Nuclear Corporation at a steel plant, and you might be wondering where exactly the nuclear angle fits. This is where the story gets genuinely forward-looking. The waste heat steel plant is the proving ground. It's the place to demonstrate that supercritical CO2 power works reliably in the real world, in a commercial setting, day after day. But the steel plant isn't the ultimate target. The reason the Nuclear Power Institute developed this technology is that the same supercritical CO2 cycle could one day replace the steam systems inside nuclear reactors themselves. Think about what that would mean. Today's nuclear plants use their reactor heat to boil water and make steam, just like a coal plant does. They just generate the heat in a cleaner way. If you swapped that steam system for a supercritical CO2 system, a nuclear plant could become significantly more efficient and dramatically more compact. The enormous turbine halls that define conventional nuclear stations could shrink. The whole plant could get smaller, cheaper, and more powerful per square meter. And it doesn't stop at large reactors. The engineers behind this project have openly pointed toward a whole family of future uses where compact, efficient power generation matters enormously. Mobile nuclear power sources, reactors small enough to be transported and deployed where they're needed. Concentrated solar power plants, which generate heat from focused sunlight and currently rely on steam. And perhaps most strikingly, space-based power generation, where every kilogram and every cubic meter is precious, and a compact CO2 turbine could be worth its weight in gold. That's the real ambition here. The steel plant is step one. The destination is a fundamentally better way to turn heat into electricity across nuclear power, solar power, mobile generators, and even spacecraft. A 200-year-old bottleneck finally opened. Now, I don't want to oversell this, because part of why you're hopefully here is that I try to give you the real picture rather than pure hype. This is a genuine, significant achievement. The world's first commercial-scale operation of a technology that defeated 60 years of materials problems. That's real, and it deserves recognition. But it's also a demonstration project, and demonstration is not the same as proven at scale. 30 megawatts is meaningful, but it's small in the context of the global power grid. A single large conventional power plant produces dozens of times that. The big open questions now are about durability and cost. Can this equipment survive the relentless assault of high-pressure, high-temperature CO2, not just for months, but for the decades a power plant is expected to operate? Will the maintenance costs stay reasonable? Can it be scaled up and manufactured cheaply enough to compete with the steam technology it's meant to replace? Some energy analysts have raised exactly these concerns, and they're fair ones. A breakthrough that works for a few months in one steel plant still has to prove it can work everywhere, for years, at a price that makes sense. But here's the thing. Every transformative technology starts exactly like this. Small, demonstrated, surrounded by skeptics asking reasonable questions about whether it'll last. The steam turbine itself was once a fragile experiment. The question is never whether the first version is perfect. It's whether the underlying idea is sound, and whether someone is committed to refining it. On both counts, supercritical CO2 looks like the real deal. Step back for a second and consider what this actually represents. Roughly the entire planet's electricity, the power running through the device you're watching this on, is generated by spinning turbines, and the overwhelming majority of those turbines are spun by steam. We have built our entire civilization on top of a 200-year-old method of boiling water. Any improvement to that fundamental process, even a small one, ripples out across literally everything. A technology that's 50% more efficient at recovering waste heat is not a niche curiosity. The world's heavy industries, steel, cement, chemicals, glass, bleed enormous quantities of heat into the atmosphere every single day, heat that represents wasted energy and, indirectly, wasted fuel and extra emissions. If that heat can be efficiently recaptured and turned into electricity, you're getting more power out of the energy you've already spent, without burning anything extra. That's a genuine climate win, even though the system itself isn't pulling carbon from the sky. And if this technology eventually migrates into nuclear reactors, solar plants, and compact mobile power units, the efficiency gains compound across the entire energy landscape. Smaller, cheaper, more powerful generation, everywhere heat needs to become electricity. There's also a bigger pattern worth naming. This is, once again, a case of a technology invented in the West, abandoned as too difficult, and then revived and commercialized by Chinese engineers willing to grind through the hard materials problems that made everyone else give up. The supercritical CO2 cycle was dreamed up in Italian and American labs in the 1960s. The United States has continued researching it, and institutions like the Southwest Research Institute have built their own demonstrators. But it was China that put the first commercial version on the grid. That's becoming a recognizable story in energy and engineering, and it's one worth paying close attention to, regardless of how you feel about it. Here's my honest opinion, for what it's worth. What I find most compelling about this isn't the CO2 angle, even though that's what makes the headline pop. It's the willingness to attack a 200-year-old assumption that nearly everyone else treated as permanent. The entire power industry decided decades ago that steam was simply how you do this, and the supercritical CO2 idea was filed away as too hard. China didn't accept that. They spent more than a decade working the problem until the materials and engineering caught up with the theory. I think the steam plant era is genuinely going to start winding down over the next few decades, and supercritical CO2 is one of the technologies most likely to replace it. Not overnight, the durability and cost questions are real, and the first version will need years of refinement, but the physics is undeniable, and once a better method gets a commercial foothold, the rest of the industry tends to follow whether it wants to or not. The thing that makes me cautious is the same thing that makes every demonstration project uncertain. We won't truly know if this is a revolution or just an impressive experiment until it's run for 10 or 20 years at full scale. But the direction is unmistakable, and the bottleneck that stopped this for 60 years has finally been broken. So here's my question for you. Do you think supercritical CO2 will actually replace steam turbines across the world's power plants in your lifetime? Or do you think steam is too deeply entrenched to ever fully go away? Drop your honest answer in the comments. This is one of those topics where I genuinely want to know which way people are leaning. If you enjoy these deep dives into the engineering breakthroughs quietly reshaping the world, do me a favor and subscribe to Eastern Engine, and tap the notification bell so you don't miss what's next. We break down these stories clearly, without the hype, and there's a lot more coming. Thanks for watching, I'll see you in the next one. For most of recent history, the moon was treated like a chapter humanity had already finished writing. During the 1960s and early 1970s, the Apollo program landed 12 astronauts on the lunar surface. They gathered rocks, planted flags, and proved beyond any doubt that human beings could walk on another world. And then, almost abruptly, it stopped. For nearly half a century, the moon became a place humanity had visited and moved on from, a closed file in the history books. That has changed completely. One country keeps returning. Orbiters, rovers, sample return missions, and now concrete plans to send astronauts. On the surface, it might look like the opening moves of a new space race, but the actual motivation runs far deeper than national competition. China is not simply exploring the moon, it is preparing to use it. Understanding why requires looking at how the whole effort was designed. Because none of this happened by accident or in a hurry. China's return to the moon was built around a carefully structured long-term plan known as the Chinese Lunar Exploration Program. Rather than rushing to put astronauts on the surface, planners laid out a deliberate, sequential roadmap where each phase would build directly on the success of the one before it. The sequence was clear. First, orbit the moon and study it from above. Second, land robotic explorers on the surface. Third, retrieve samples and return them to Earth. And finally, develop the technologies needed for a lasting human presence. No phase could begin until the previous one had succeeded completely. The first mission launched in 2007, Chang'e-1, named for the moon goddess of Chinese mythology. It became China's first lunar orbiter, spending more than a year mapping the surface and producing detailed three-dimensional images of the terrain. 3 years later, in 2010, Chang'e-2 dramatically improved on that work, capturing high-resolution images that allowed scientists to identify promising landing sites across the lunar surface. These early missions never captured public attention the way crewed landings do, but they accomplished something essential. They produced the most detailed geological maps of the moon that China had ever created, helping researchers pinpoint regions that might contain valuable resources. That groundwork would shape everything that followed. The first true breakthrough arrived in 2013, when China achieved its first successful lunar landing with Chang'e-3. For the first time in nearly 4 decades since the Apollo era ended, an active spacecraft was operating on the lunar surface again. Chang'e-3 carried a small robotic rover named U2, meaning Jade Rabbit. Almost immediately, it began transmitting data that caught scientists off guard. As U2 rolled across the surface, its instruments analyzed the composition of nearby rocks and soil. The results were unexpected. Some of the rocks in the region were basalt, volcanic rock formed from ancient lava flows. But these samples did not match the chemical composition of the rocks scientists had studied from the Apollo missions. They were genuinely different. The mineral arrangements and chemical signatures suggested that parts of the moon had formed through volcanic processes unlike anything previously documented. The implication was significant. The moon's geology was far more varied than researchers had assumed. For decades, almost all human understanding of lunar rock came from a small handful of Apollo landing sites, every one of them located on the near side. Chang'e-3 revealed that those samples represented only a fraction of the full picture. Vast stretches of the moon had never been examined directly, and entire regions could still be hiding completely new types of lunar material. But as surprising as that discovery was, it was only a prelude. A few years later, China set out to attempt something no nation had ever managed. In 2019, China launched a mission that many scientists had long considered nearly impossible. Chang'e 4 became the first spacecraft in history to land on the far side of the Moon, the hemisphere that permanently faces away from Earth. Because the Moon is tidally locked, we only ever see one side of it from our planet. The far side stays perpetually hidden, and that creates a serious technical obstacle. The moment a spacecraft lands there, it loses direct line-of-sight communication with Earth entirely. China's solution was elegant. Before the landing, they positioned a relay satellite called Kuiqiao into an orbit beyond the Moon, where it could maintain contact with both the far side and Earth simultaneously. Signals could then bounce between the lander and ground control through this orbiting intermediary. With that communication link established, Chang'e 4 touched down inside the South Pole Aitken Basin, an enormous impact crater stretching more than 2,500 kilometers across, ranking among the largest known impact structures anywhere in the solar system. Scientists believe this basin may have exposed material from deep within the Moon's interior, potentially offering a window into what lies beneath the crust. Then came an even more ambitious milestone. China launched Chang'e 6, designed to do something that had never been accomplished: collect and return samples from the far side of the Moon. The mission successfully gathered roughly 2 kilograms of lunar soil and rock and brought it back to Earth. Early analysis indicated some of the volcanic rock had formed around 2.8 billion years ago. That finding mattered because it challenged long-held assumptions about when lunar volcanic activity ceased. It suggested the Moon may have remained geologically active far longer than scientists previously believed, meaning its history is more complex and more interesting than the textbooks ever recorded. And yet, despite all of these remarkable achievements, the far side is not the ultimate goal of China's lunar program. The real target lies somewhere else entirely. At first glance, the lunar South Pole appears to be one of the most hostile environments imaginable. Towering peaks surround enormous craters that never receive direct sunlight. Because the Moon's axis tilts only slightly, some of these craters have remained in permanent shadow for billions of years. Inside them, temperatures can drop below -200 degrees Celsius, colder than almost anywhere else in the solar system. But those brutal conditions may have produced something extraordinarily valuable. Scientists believe these permanently shadowed craters could hold substantial deposits of frozen water ice. And water on the Moon is far more significant than it might initially sound. Water can be broken down into its two fundamental components: oxygen, which astronauts can breathe, and hydrogen, which happens to be one of the most powerful rocket fuels ever developed. If those resources exist in meaningful quantities, the Moon transforms from a simple destination into something revolutionary, a refueling station in space. Instead of launching every drop of fuel from Earth's surface, future spacecraft could top up on the Moon before continuing deeper into the solar system. That capability would dramatically lower the cost of missions to destinations like Mars. This is precisely why China's upcoming lunar missions are concentrated on the South Pole. But before anyone can use those resources, they first have to confirm the resources are actually there. China's next major step in this search is Chang'e 7, currently planned for launch around 2026. Unlike earlier missions, focused mainly on broad exploration, Chang'e 7 is purpose-built to investigate the Moon's most valuable potential resource: water. To do this, the mission will deploy an entire team of robotic explorers working in coordination. An orbiter will circle the Moon from above, mapping the region and relaying communications. A lander will set down near the South Pole. A rover will then traverse the rugged terrain, studying the surface and analyzing the chemical composition of the soil. But Chang'e 7 also carries something never before used in lunar exploration: a small robotic hopping probe. Rather than driving across the surface like a conventional rover, this probe can leap directly into deep craters that are permanently cut off from sunlight, the exact places where standard solar-powered machines simply cannot operate. Inside those shadowed regions, the probe will hunt for water molecules, hydrogen signatures, and frozen deposits embedded in the soil. If it succeeds, Chang'e 7 could deliver the first direct, on-site confirmation of water ice in these ancient craters. That single discovery would fundamentally reshape how humanity thinks about the Moon, because finding the resources is only the first half of the challenge. The harder part is learning how to actually use them. Launching construction materials from Earth is extraordinarily expensive. Every kilogram delivered to the Moon costs a substantial amount in rocket fuel and engineering. So if humans are ever going to live on the lunar surface for extended periods, they will need to construct habitats from materials that already exist on the moon itself. That is the central purpose of Chang'e 8, planned for around 2028. This mission focuses on a set of technologies known as in situ resource utilization, often abbreviated as ISRU, the practice of using local resources rather than importing everything from home. One experiment will attempt to convert lunar soil into building material. Robotic systems may heat and compress the moon's dusty surface layer, known as regolith, into solid blocks that could be used for roads, landing pads, or protective barriers. Other experiments will explore whether oxygen or water can be extracted directly from lunar minerals. Some proposed designs even involve 3D printing structures from lunar soil, allowing robotic systems to build shelters layer by layer. The vision is that autonomous robots could eventually assemble walls, foundations, and protective domes long before any human crew ever arrives. If these technologies prove themselves in the actual lunar environment, they would demonstrate something genuinely transformative, that humanity does not merely have to visit the moon, but could actually build a lasting presence on it. Once those capabilities are proven, the next phase becomes possible. China's robotic missions are laying the foundation. The phase that follows is human. China is now developing the systems required to send astronauts to the moon, with the stated goal of achieving a crewed lunar landing before the end of the decade. At the heart of this effort is a new launch vehicle called the Long March 10, designed to deliver roughly 27,000 kilograms of payload into lunar orbit, enough to support a crewed landing. The mission architecture is carefully structured and requires two separate launches from Earth. The first rocket carries the crewed spacecraft into lunar orbit. The second launch sends up the lunar lander. Once both vehicles reach the moon, they dock together in orbit. Two astronauts then transfer into the lander and descend to the surface. There, the crew would carry out scientific experiments, collect geological samples, and test new technologies designed for long-term operations. These early missions may last only hours or a few days, similar to the brief surface stays of the Apollo era. But these initial landings are not intended to be the endpoint. China is not setting out to recreate Apollo. It is preparing for something considerably larger. Every piece of this effort, the orbiters, the rovers, the sample returns, the resource experiments, and eventually the astronaut landings, points toward a single ambitious goal: a permanent human presence on the moon. China's long-term project is called the International Lunar Research Station, or ILRS. Formally announced in 2021, it represents one of the most ambitious space infrastructure proposals ever put forward. Its planned location is the lunar South Pole, the same region where scientists believe large frozen water deposits may exist. The station will not materialize all at once. The first phase begins with robotic construction missions. Across the early 2030s, China plans a series of landings designed to gradually assemble the infrastructure needed for a base. Somewhere between roughly 2031 and 2035, multiple missions are expected to deliver the components that will form the station's foundation. These early systems could include communication networks, power generation units, and scientific laboratories. Autonomous robots may handle much of the initial construction, operating on the surface long before any human arrives. Additional systems will focus on resource extraction, experimenting with methods to produce oxygen, water, or fuel from the moon's soil and ice. Initially, the station would function as a robotic research outpost, but over time it is designed to support human crews living and working there for extended stretches. China has also invited international partners to take part, positioning the ILRS as a shared global research platform rather than a purely national venture. If the station becomes operational, it could mark something humanity has never achieved before: a genuine, lasting foothold on another world. This is where the modern era of space exploration enters a new phase. If these plans succeed, the moon could become far more than a target for occasional scientific missions. It could become a foundational piece of a future space economy. The moon offers several advantages that make it uniquely valuable. Its gravity is only about 1/6 that of Earth's, which means spacecraft can launch from its surface using far less fuel. If water ice can be extracted and converted into hydrogen and oxygen, the moon could serve as a refueling depot for deep space missions. Rather than launching enormous, fully fueled rockets directly from Earth, future spacecraft might stop at the moon to refuel before continuing toward Mars or the outer solar system. In effect, the moon could function as a launch platform that dramatically reduces the cost of reaching the rest of the solar system. Beyond transportation, the lunar surface offers something rare for science: Observatories placed on the far side would be shielded from Earth's constant radio noise, creating one of the quietest environments in the solar system for studying the universe. Taken together, these possibilities suggest that whoever establishes the first sustainable infrastructure on the moon may gain a meaningful long-term advantage in space exploration. That helps explain why China is investing so heavily in returning, again and again. When you strip everything down, China's repeated return to the moon comes down to three fundamental motivations. The first is scientific discovery. Even after decades of study, the moon still preserves clues about the earliest history of our solar system. Records that may reveal how planets formed billions of years ago, information largely erased on a geologically active Earth. The second is strategic resources. If water ice exists in large quantities near the lunar poles, it could supply the oxygen and rocket fuel needed to power the next era of space exploration, turning the moon into a stepping stone rather than a final stop. And the third is the largest of all, permanent presence. The moon may become humanity's first long-term settlement beyond Earth, a place where science, industry, and exploration converge on another world. If China succeeds in building that foothold, the next great chapter of human civilization might not begin on Earth at all. It might begin 250,000 miles away, on the surface of the moon. China's largest electric vehicle company has spent years proving that it can build batteries, motors, power electronics, and complete cars at enormous scale. Now BYD is moving deeper into the part of the vehicle that may matter most next decade, the computer that controls intelligent driving. The company has unveiled its Xuanji A3 processor. BYD describes it as China's first domestically designed 4-nanometer chip built specifically for advanced driving systems. One chip delivers around 700 trillion operations per second. A 3-chip configuration exceeds 2,100 TOPS, and BYD says the processor has already entered chip-level mass production. A Chinese automaker is no longer satisfied with buying batteries, sensors, software, and processors from separate suppliers. BYD wants to control the complete stack. But the headline needs an important qualification. The Xuanji A3 has not yet been independently proven to beat NVIDIA's best automotive platform. Mass production of the chip does not mean millions of BYD vehicles are already using it. And a 4-nanometer design does not prove that the processor is fabricated entirely with Chinese manufacturing equipment. Still, BYD is clearly trying to turn the vehicle into a vertically integrated platform, with the processor, software, sensors, battery, motors, and architecture developed around one system. The question is whether BYD can use its scale to make those chips an industry standard. Why BYD built its own car brain? Modern vehicles are becoming computers on wheels. Cameras, radar, LiDAR, ultrasonic sensors, navigation systems, battery controls, entertainment displays, and driver assistance software all generate enormous amounts of data. That information must be processed quickly enough for the vehicle to recognize lanes, detect pedestrians, predict nearby traffic, and decide when to brake or change direction. Traditional vehicles divided these tasks among many separate control units. Advanced driving requires tighter coordination, larger neural networks, millisecond decisions, and safe operation even when one component fails. This is why automotive computing is moving towards centralized platforms. Instead of dozens of isolated control units, more functions are combined inside a smaller number of powerful computers. The Xuanji A3 is designed for that transition. It is the centerpiece of a compact central computing platform, intended to connect intelligent driving, the digital cockpit, and core vehicle control functions. That gives BYD more control over how information moves through the car. It also allows the company to optimize the processor around its own vehicles, instead of adapting every design to a general-purpose chip from another supplier. What 700 TOPS really means. The number attached to the Xuanji A3 is 700 TOPS. TOPS means trillions of operations per second. It is commonly used to describe the peak performance of artificial intelligence accelerators. A higher number can support more camera feeds, larger neural networks, or several models at once. But TOPS should not be treated like horsepower. Two chips with the same advertised number may deliver very different real-world performance. The result depends on numerical precision, memory bandwidth, software efficiency, thermal limits, and how much of the processor can actually be used by the workload. BYD says the Xuanji A3 includes a 16-core CPU and around 273 gigabytes per second of memory bandwidth. One chip provides roughly 700 TOPS, while 3 working together exceed 2,100 TOPS. That is an enormous figure for a passenger vehicle. However, 3 chips do not automatically behave like one perfectly unified processor. The system must distribute work efficiently, move data between chips, avoid duplication, and manage power and heat. The important question is not only how much peak performance exists, it is how much useful performance the software can extract in real traffic. BYD says combining the chip with its own algorithms improves computing utilization. That is one reason vertical integration matters. The company can design models around the exact structure of the processor, then adjust the hardware around the software's needs. Why 3 chips? Most vehicles will not require 2,100 TOPS. A basic assisted driving system can operate with far less. Premium vehicles, however, may run cameras, LiDAR, radar, perception models, parking, driver monitoring, and cockpit intelligence simultaneously. 3 chips give BYD room to divide workloads and create redundancy, with separate processors potentially handling perception, planning, cockpit functions, or backup capacity. Level 3 and Level 4 systems require more than speed. Level 3 automation can allow the vehicle to control itself under limited conditions, but the human driver may still need to take over. Level 4 systems are designed to operate without human control inside defined areas or situations. Supporting those levels requires fail operational design. If one component stops working, the system must remain safe. Extra processors, independent power paths, redundant sensors, and multiple communication networks can all contribute. BYD says the Xuanji A3 is designed to support future Level 3 and Level 4 systems. That does not mean every vehicle carrying the chip will immediately become autonomous. Regulation, software validation, sensors, mapping, and road conditions still determine what the car is legally and technically allowed to do. The NVIDIA comparison. NVIDIA has spent years building one of the strongest automotive computing ecosystems in the world. Its drive platform combines processors, networking, development tools, simulation software, and artificial intelligence models. Automakers do not simply purchase a chip. They purchase access to an established software platform with global engineering support. That is hard to replace. BYD's advantage is different. It does not need to sell the Xuanji A3 to every automaker in the world to make the project successful. BYD can deploy the chip across its own enormous vehicle portfolio. That creates a guaranteed internal customer. Each vehicle can generate data, receive software improvements, and reuse parts of the same architecture. NVIDIA must support many brands, while BYD can optimize around its own sensors, batteries, motors, networks, and factories. This does not prove BYD has beaten NVIDIA. NVIDIA still has deeper experience in AI software, simulation, developer tools, and advanced computing. But BYD may not need to win a direct benchmark battle. It may only need a processor that is powerful, efficient, reliable, and cheap enough for its own cars. The mass production claim. BYD says the Xuanji A3 has entered mass production. That claim must be interpreted carefully. Chip-level mass production means the processor has moved beyond a small laboratory sample. It suggests that the design has completed major validation steps and is being manufactured in meaningful quantities. But it does not necessarily mean the chip is already installed across BYD's current vehicle range. Automotive deployment moves slowly because chips must survive vibration, humidity, voltage changes, extreme temperatures, and long service periods. The full system also needs software validation, sensor integration, cybersecurity testing, and safety approval. Reports indicate that the first major vehicle deployments may arrive later, potentially beginning with premium BYD brands before spreading into higher volume models. So the breakthrough is real, but the rollout should not be exaggerated. The Xuanji A3 is entering the production phase. Its true impact will become visible when BYD reveals which vehicles use it, how many chips are installed, and what driving functions are activated. Who actually manufacturs it? Another major question is fabrication. BYD designed the Xuanji A3, but designing a chip and manufacturing it are different businesses. A 4-nanometer processor requires advanced lithography, materials, process control, packaging, and testing. BYD has extensive semiconductor operations, especially in automotive power electronics and mature node components. But there is no clear evidence that BYD manufactures this particular processor entirely inside its own factories. Chinese automakers and chip designers still depend heavily on outside foundries for leading-edge production, including manufacturers in Taiwan and South Korea. That means the Xuanji A3 is a major step toward design independence, but not necessarily complete supply chain independence. A company can control the architecture, software, and roadmap while still relying on foreign fabrication. That is strategically valuable, but trade restrictions or supply disruptions could still affect production. BYD's long-term challenge is larger than designing one successful chip. It must secure fabrication capacity, advanced packaging, memory when supply chains become unstable. The Xuanji A3 extends that strategy into advanced computing, connecting its batteries, electric drive systems, vehicle platforms, and assisted driving software. The driving system could share information more directly with braking, steering, suspension, battery management, navigation, and the cockpit. That could reduce latency and simplify software updates. It may also lower cost. A processor designed for BYD's exact requirements may avoid features the company does not need. Once production reaches sufficient scale, BYD can spread development costs across a very large number of vehicles. This is where BYD may have an advantage over smaller automakers. Designing an advanced chip costs an enormous amount of money. The investment only makes sense if the company can deploy enough units to recover the expense. BYD has the scale to use the same architecture across several brands, vehicle classes, and price categories. The Chinese chip race. BD is not alone. Chinese automakers are rapidly developing their own intelligent driving processors or working with domestic semiconductor companies. NIO has introduced its own driving chip. XPeng has developed the Turing processor. Li Auto is working on its Mach series hardware. Geely, Huawei, Horizon Robotics, and other companies are also building automotive computing platforms. This competition shows how important the car chip has become. Automakers once differentiated themselves through engines, transmissions, and chassis tuning. In the electric vehicle era, batteries and manufacturing became central. The next competitive layer may be computing. A company that controls the processor can decide how quickly features are added, how data is handled, and how dependent the vehicle remains on suppliers. But fragmentation creates risk. Separate tools and operating systems increase costs and make every platform harder to support. Some automakers may eventually discover that designing chips is too expensive. BYD is better positioned than most because of its scale and its ability to connect the chip directly to its own vehicles. The real economic impact. The biggest opportunity may not be the most expensive autonomous vehicle. It may be bringing advanced computing into affordable cars. BYD has already pushed driver assistance features deeper into mass market segments. If the company controls the processor, it can reduce the amount paid to foreign suppliers and decide how aggressively to spread intelligent driving hardware across its lineup. That could pressure competitors. A feature that begins in a premium vehicle can move into mid-range models once production scales, just as Chinese automakers did with batteries, fast charging, displays, and electric drivetrains. If BYD installs its own chip across hundreds of thousands of vehicles, it gains an enormous data and software advantage. More vehicles create more data, better models, more useful hardware, and a stronger platform. That feedback loop matters far beyond the TOPS number. What remains unproven? Several important questions remain unanswered. We do not yet have independent benchmarks showing how the Xuanji A3 performs against NVIDIA Drive Thor, Huawei's automotive platforms, or rival Chinese chips under identical conditions. We do not know the final production cost, real-world power use, manufacturing yield, or volume of secure foundry capacity available to BYD. And we do not know how quickly the chip will move from premium vehicles into mass-market models. The real test will happen on the road. Can the system recognize unusual objects? Can it handle rain, glare, construction zones, and unpredictable drivers? Can it fail safely? Can BYD maintain the software for years? A large TOPS number cannot answer those questions. My take is that the Xuanji A3 is not important because BYD has already defeated NVIDIA. It is important because BYD is removing another external dependency from the vehicle. The company already controls batteries, motors, power electronics, and much of its manufacturing. Now it is attempting to control the computing architecture that will define intelligent cars. A single chip delivering around 700 TOPS is significant. A 3-chip system exceeding 2,100 TOPS is visually impressive, but the real advantage is integration. BYD can design the processor, algorithms, sensors, vehicle controls, and production process as one system. That is difficult for a traditional automaker coordinating outside suppliers. Limits remain. The chip may rely on foreign fabrication. Mass production does not equal mass deployment. Level 3 and Level 4 support does not mean fully autonomous. BYD cars are already operating everywhere, and NVIDIA remains a much stronger global computing platform. But BYD does not need to replace NVIDIA worldwide. It needs to make outside processors less necessary inside its own vehicles. If it succeeds, the company will not simply be an electric car manufacturer. It will become a large-scale automotive computing company with millions of vehicles serving as the deployment platform. That could reshape global competition. So what do you think? Can BYD turn the Xuanji A3 into a genuine alternative to NVIDIA's automotive processors? Or will manufacturing limits and software complexity prevent the chip from reaching its full potential? Let me know your view in the comments. And subscribe to Eastern Engine for more grounded coverage of the chips, factories, and engineering decisions reshaping the global economy. Because BYD built its rise on batteries, but its next advantage may come from the computer controlling the car. Jensen Huang flew to China. Not once, not twice, at least 3 times in 2026 alone. To Shanghai, to Beijing, to Shenzhen. And each time, industry insiders said the same thing. The CEO of the most powerful chip company on Earth wasn't there to sightsee. He was there because NVIDIA had a problem it couldn't solve at home. A problem so fundamental, so urgent, so deeply embedded in the physics of modern AI chips, that the man who runs a $3 trillion company had to cross the Pacific and walk into a Chinese lab to discuss it face to face. The problem is heat. And the solution, the one thing that can fix it, is the last material anyone expected: diamonds. Not as jewelry, not as decoration, as the beating heart of the next generation of AI chips. China controls more than 50% of global lab-grown diamond production. China holds the key patents. China's researchers published the breakthrough in Nature. And when Jensen Huang sat down in a meeting room with the CEO of a company called Henan Chaoying Diamond Technology, he wasn't browsing. He was there because NVIDIA's next-generation GPUs are already being redesigned around this material. By the end of this video, you'll understand the heat crisis that's quietly throttling artificial intelligence, why silicon can't solve it, why diamond is the answer physics has been sitting on for decades, and why China just positioned itself at the center of the most important material race in modern technology. Let's go. Here's something the AI industry doesn't put in its press releases. Every time a large AI model runs, every time it answers a question, generates an image, writes a line of code, the chips doing that work are fighting a war against heat. A war they are slowly starting to lose. Think about what's inside a modern AI data center. Row after row of server racks, each one packed with processors running at full throttle, around the clock. A single rack can now draw more than 1,000 watts of power. Most of it, somewhere between 30 and 35% of everything flowing into the building, gets consumed, not by the computation itself, but by the cooling systems trying to stop the hardware from melting. You are spending a third of your electricity bill just preventing your computers from destroying themselves. And it's getting worse, not incrementally worse, exponentially worse. Here's the physics that nobody can argue with. Every time chip designers increase transistor density, pack more processing power into the same piece of silicon, the heat generated per square millimeter goes up. There is no version of this math where that doesn't happen. You want more AI power, you need more transistors. More transistors means more heat. More heat means more cooling. More cooling means more power. More power means more heat. The loop closes and it tightens with every new generation of chips. Relevant studies show that for every 18 degrees Celsius rise in a chip's operating temperature, its failure rate increases by 2 to 3 times. That's not a marginal effect. That's a compounding disaster. You push the chip harder, it runs hotter, it fails faster, you spend more on replacements, and every dollar you save on computing gets swallowed by the thermal management problem you created in the process. Jensen Huang knows this intimately. At CES 2026, NVIDIA announced that its next-generation Vera Rubin architecture GPUs would adopt a completely new thermal solution, diamond copper composite cooling, combined with liquid cooling at 45 degrees Celsius. Not water chillers, not fans, diamond. The fact that the world's most advanced chip company just redesigned its flagship product around a material historically used in engagement rings should tell you something. Something big changed. Something broke through a wall that engineers have been staring at for decades. Silicon is remarkable, flexible, abundant, processable, scalable. The entire modern world is built on it. 60 years of Moore's Law didn't happen because silicon was convenient. It happened because silicon is genuinely extraordinary at being turned into transistors. Everything you do online is being watched. Your provider, advertisers, even governments. NordVPN encrypts your connection, hides your location, and unlocks the open internet from anywhere. Grab the deal, link in the description. But silicon has a dirty secret, As a thermal conductor, it's mediocre. Thermal conductivity is the measure of how efficiently a material moves heat away from a source. Silicon sits at about 150 watts per meter Kelvin. For comparison, copper, the metal used in most heat sinks and cooling pipes, sits around 400, 5 times better than silicon at moving heat. Diamond thermal conductivity sits at approximately 2,200 watts per meter Kelvin. That's 5 times better than copper, 14 times better than silicon. When engineers describe diamond as the ultimate semiconductor material, this is the number behind that claim. It's not marketing language, it's physics. Diamond moves heat the way a highway moves cars compared to a dirt road. But here's where the story gets interesting. The industry knew this. Scientists knew this for decades. Diamond's thermal properties have been documented for generations. So why wasn't it already in every chip, in every server rack, in every data center on Earth? Because until very recently, you couldn't make it. Not at scale, not at the quality a semiconductor requires, not at a price that made any commercial sense. That wall just came down. In December 2024, researchers from 3 Chinese institutions, Peking University, the Southern University of Science and Technology, and the University of Hong Kong, published a paper in Nature. The subject was the economical production of ultra-thin smooth diamond films at industrial scale. Read that again. Not diamond synthesis in a lab. Not a proof of concept. Economical. Industrial scale. This was the manufacturing breakthrough that the semiconductor industry had been waiting for without fully admitting it was waiting for it. The method for producing lab-grown diamonds through chemical vapor deposition had existed for years, but it was slow, expensive, and produced material with impurities and surface roughness that semiconductor applications simply couldn't tolerate. Getting a diamond film smooth enough to bond to a chip is a different problem from growing a diamond. A chip's contact surface needs to be flat to tolerances measured in fractions of a nanometer. Rough diamond is useless for this application no matter how good its thermal properties are. The Peking University paper cracked that. And when it landed, the chip industry did not respond quietly. NVIDIA's supply chain team began validation work almost immediately. A Chinese diamond company called Chaoying Diamond confirmed that its diamond copper composite material had passed NVIDIA's supply chain validation for use in high-power density AI chip thermal management. Jensen Huang went to China, met with Henan Chaoying Diamond Technology, and discussed industrialization. This is not a rumor, this is not speculation. The CEO of NVIDIA met with a Chinese diamond chip company because the physics demanded it. Let's be precise here, because this is the part where people misunderstand the technology. And misunderstanding it leads to comments that miss the point. Diamond is not replacing silicon as the material transistors are made from. Not yet. Silicon is still where the transistors live. What diamond is doing is solving the thermal layer, the path that heat takes after it's generated and before it destroys the chip. In the current architecture, heat generated by transistors has to travel through several material layers before reaching the cooling system. Each layer acts as a speed bump. The worse each material's thermal conductivity, the longer heat lingers near the transistors, and the hotter they run. Diamond replaces the worst of those layers. Inserted as a substrate or a heat-spreading layer between the chip and the cooling system, it essentially builds a superhighway for heat to escape. The chip runs cooler. Cooler chips run faster. Faster chips are more efficient. More efficient chips use less cooling. Less cooling means less power. Less power means lower cost. Huawei's engineering team, working with Xiamen University, has already demonstrated the practical results of this in a real system. Using diamond heat dissipation technology integrated with glass interposer chip packaging, they reduced the maximum junction temperature by 24.1 degrees Celsius and cut the chip package's thermal resistance by 28.5%. That's not a marginal improvement. In chip thermal engineering, cutting junction temperature by more than 24 degrees is the difference between running at the edge of safe limits and running with comfortable headroom to push performance higher. Apply that same math to a data center with thousands of chips. Multiply the efficiency gain across millions of server hours. The numbers stop being impressive and start being civilization scale. Here's where the strategic picture snaps into focus, and it's genuinely surprising in a way that the glass substrate story was. China produces more than 50% of the world's lab-grown diamonds, not by a narrow margin, by dominance. The province of Henan is the global epicenter of synthetic diamond production, home to companies like Huanhe Whirlwind, Liliang Diamond, and North Industries Red Arrow. These companies have spent years perfecting the high-temperature, high-pressure, and chemical vapor deposition processes used to grow gem-quality diamonds at scale. That industrial muscle, the accumulated process knowledge, the equipment, the yield management, transfers directly to semiconductor-grade diamond production. It's the BOE story all over again. In the glass substrate videos, we talked about how China's display glass manufacturing infrastructure gave it an unexpected edge in semiconductor glass. The same pattern plays out here, except diamond production is even more concentrated. More than half the world's synthetic diamond capacity sits in Chinese factories that were optimized for jewelry but are now pivoting to chips. And those factories are not starting from scratch on the semiconductor application. The Nature paper gave the industry the roadmap for ultra-smooth, ultra-pure diamond films. Chinese companies are now certifying against NVIDIA's supply chain requirements. Huawei has filed patents combining diamond thermal management with glass substrate packaging, creating a hybrid architecture that is genuinely novel, using two of the most advanced packaging materials simultaneously in a single chip system. Meanwhile, China's diamond stocks on the A-share market surged more than 90% year-to-date. Not because of jewelry demand, because sophisticated investors read the same supply chain signals NVIDIA sent when it redesigned its next-generation GPU around diamond cooling. The market was paying attention. Most of the world's tech press wasn't. Step back, take a breath. Think about what the pattern looks like from altitude. Glass substrate, a material for packaging AI chips that outperforms plastic by a factor of 10. China positioned itself at the manufacturing frontier before most of the industry was paying attention. We covered that. 2 videos, a combined 100,000 views, and the story isn't finished. Diamond, a material for managing AI chip heat that outperforms everything else in existence by a factor of 5. China controls more than half the world's production capacity, holds the key industrial patents, and just cracked the manufacturing problem in a Nature paper. Jensen Huang flew across the Pacific to meet with a Chinese diamond company to discuss it. These are not isolated stories. They are chapters in the same book, and the book is about the layer of the semiconductor industry that nobody was guarding, the packaging and thermal management stack that sits between the raw silicon and the cooling system, the layer that determines whether the most powerful chips in the world run at their potential or throttle themselves to avoid melting. Transistors get all the headlines. This layer is increasingly where AI's actual limits are set. And China, quietly, methodically, and in some cases using manufacturing expertise built for completely unrelated industries, is building a dominant position across it. Glass first, diamond second. The question is, what comes third? Here's my honest view, and I'll make it direct. I've covered glass chips, I've covered the NVIDIA story, I've covered the Huawei Tau scaling law. But this diamond story is the one that genuinely surprised me. Not because the technology is unexpected, but because the convergence is. That kind of accidental advantage is harder to dislodge than a planned one, because it wasn't built to be a competitive weapon. It just became one. And NVIDIA's response, redesigning its flagship GPU around diamond cooling, and sending its CEO to meet with Chinese suppliers to figure out how to get it at scale, is the clearest possible signal about how seriously the world's most advanced chip company takes this material. The AI heat crisis isn't going away. Physics doesn't negotiate. And the country that controls the thermal management stack is going to have a seat at the table every time an AI chip is designed, for the next decade at minimum. That, to me, is the real story here. Here is the question I want you to think about honestly. We are watching China build an advantage in the materials layer of AI chips. First glass, now diamond. Not through copying, but through manufacturing expertise built for completely different industries. Is that a more dangerous kind of lead to compete against than a straightforward technology gap? Or do you think the West's chip designers will just engineer around the thermal problem entirely and make the material irrelevant? Drop your actual opinion in the comments. I genuinely want to know which way people are leaning on this one. If this kind of deep dive, the material, the supply chain, the strategic layer most coverage misses completely, is why you come here, subscribe to Eastern Engine and turn on notifications. We cover the breakthroughs that matter before they become obvious. Glass chips, diamond chips, whatever comes next in this stack, you'll see it here first. Thanks for watching. I'll see you in the next one. On March 27, 1989, a room full of Soviet engineers on the Crimean Peninsula sat waiting for a signal that was already overdue. 400 million kilometers away, in orbit around Mars, their spacecraft had just performed what should have been a routine maneuver. It rotated to photograph one of Mars's 2 small moons. To aim its cameras, it had to swing its main antenna away from Earth and fall silent for a few minutes. The engineers expected that. They knew almost to the minute when the signal should return. The minute came. The signal did not. About 4 hours later, something finally arrived. But it was wrong. It was the garbled, broken kind of pulse a spacecraft sends when it is no longer pointed at anything at all, when it is tumbling helplessly through space. That faint, distorted transmission was the last thing anyone on Earth ever received from the probe. It had crossed the entire solar system to reach Mars and to slip closer to one of its moons than any machine before it. And in its final minutes, circling the red planet, it captured a photograph. What that photograph showed, and what made the spacecraft fall silent at the exact moment it turned to look, became one of the strangest and most disputed episodes in the history of spaceflight. Let's find out what was actually out there. The spacecraft was called Phobos 2, and it carries a distinction most people don't know about. It was the final interplanetary probe the Soviet Union ever designed. To understand why that matters, you have to understand how long the Soviets had been away from Mars. After a string of disappointing Mars probes in the early 1970s, the political leadership had largely lost patience with the red planet. The results weren't impressive enough to justify the enormous cost, and the funding dried up. But the scientists never stopped thinking about it. At the Space Research Institute in Moscow, known by its Russian initials IKI, a group of researchers kept turning the problem over. They knew that to return to Mars, they needed an idea compelling enough to change the leadership's mind. By the end of the 1970s, they had one. The idea was this: don't go to Mars itself, go to its moons. Mars has two, and they are tiny. The larger is called Phobos, the smaller Deimos. What made Phobos so attractive wasn't only the science, it was the orbit. Phobos circles Mars on a path a chemically powered spacecraft could actually reach without too much difficulty. It was, in a sense, the easy door into the Martian system. And targeting a moon instead of the planet carried one more advantage that mattered enormously in 1980s geopolitics. It let the Soviets do something the Americans hadn't done, rather than repeating something they already had. In early 1985, the government approved the mission, with public announcements following that March. Here is where the human story begins, and it explains everything that follows. The man running the Space Research Institute at the time was a physicist named Roald Sagdiv. His institute had just pulled off the Vega missions, an international effort that had sent Soviet probes past Venus and on toward Halley's Comet in 1986. It was a triumph, and it had placed Sagdiv and his scientists firmly in the spotlight. According to Sagdiv himself, that spotlight created a problem. The leadership of the Soviet rocket industry resented the attention the scientists were receiving. So when the Phobos project was organized, overall control was handed not to the scientists who had conceived it, but to the ministry responsible for building the rockets. In practice, the manufacturer got to dictate terms to the customer. The people who would fly the mission no longer fully controlled how it was built, and there was one more pressure, the one that would haunt the entire story. By the Institute's own estimate, a project this complex needed 6 or 7 years to do properly. They were given 3.5. Remember that number, because it comes back. Yet, for all the rush and rivalry, this was also a hopeful project. It arrived precisely as the Soviet Union was beginning to open to the world, and it became one of the largest international science efforts the Soviets had ever attempted. Scientists from 14 countries contributed, from both sides of the Iron Curtain: Austria, Bulgaria, Hungary, Finland, France, Sweden, the United States, both German states, and institutions of the European Space Agency among them. That openness went remarkably far. In 1987, before either probe had launched, the Soviets displayed full-scale models of the Phobos spacecraft at an air and space show in France. In the final days before launch, Western visitors were invited to tour the Baikonur Cosmodrome itself, including an Apollo astronaut and a delegation from the US Air Force. The old reflexes hadn't entirely vanished. Rank-and-file soldiers were still ordered to swap their uniforms for civilian clothes when foreigners visited, to disguise the military nature of the site. But the direction was unmistakable. This was the Soviet space program trying to step into the light, which is part of what makes everything that came next so painful. Phobos 2 did not fly alone. It had a twin. The plan called for 2 identical probes, Phobos 1 and Phobos 2, launched a few days apart in July 1988, both bound for Mars. The logic was redundancy. If one failed, the other would carry the mission. 2 spacecraft, 2 chances. Phobos 1 lifted off first, on July 7th. For the first weeks, it behaved beautifully. It made its course correction, switched on an X-ray telescope, and photographed the sun, capturing well over 100 images of the solar corona and even catching a solar flare in the act. Then, on September 2nd, during a routine communication session, Phobos 1 simply didn't answer. Here's what happened, and it is one of the most quietly devastating facts in the history of spaceflight. A controller on the ground had sent the spacecraft a long string of commands, a routine package meant to keep the probe stable during an upcoming gap in communications. Somewhere in that string of code, a single character was wrong. One missing digit. Let that sit for a second. Not a hardware fault, not a collision, not a cosmic ray frying a circuit, a typo. That missing digit changed the meaning of the command. Instead of doing what it was supposed to, the code reached into the spacecraft's memory and triggered an old test program. A routine written to check the attitude control system on the ground, which, because there hadn't been enough time before launch, had never been erased from the spacecraft's memory. The test program ran, and the very last thing it did by design was switch off the attitude control system. So that is exactly what Phobos 1 did. 11 million kilometers from home, it shut off the system that kept it oriented. With nothing holding it steady, the spacecraft drifted, slowly nudged off axis by the faint constant pressure of the solar wind. Its solar panels turned away from the sun. The power faded, the batteries emptied. After weeks of trying to revive it, the Soviets declared Phobos 1 lost in early November. The mission had lost half its fleet before reaching Mars. Everything now rested on the second probe. Phobos 2 was built on a brand new platform, a full generation's leap beyond the old Venus probes. At its heart sat a ring-shaped instrument compartment, atop a powerful propulsion unit fed by 8 fuel tanks. That propulsion design was so good, it would later live on as a rocket stage called Fregat, which still flies today. But the most important part of Phobos 2 for our story isn't the engine, it's the brain. The spacecraft was controlled by 3 identical onboard computers, working on a principle that sounds almost democratic. For any decision, the 3 computers would effectively vote, and the spacecraft would do whatever at least 2 of the 3 agreed on. The logic was sound. If a stray cosmic ray flipped a bit and made one computer briefly malfunction, the other 2 would outvote it. 3 brains, majority rules, no single point of failure. Hold on to that idea. The mission plan was extraordinary. Phobos 2 would enter a wide orbit around Mars, then gradually tighten it until it circled in step with the moon Phobos itself, eventually flying in formation just 35 kilometers above the surface. Then came the part that made this mission unlike anything before it. Once it had mapped the moon, Phobos 2 was supposed to descend until it hovered just 50 meters above the surface. Not landing, hovering. Landing on Phobos is nearly impossible because the moon's gravity is so feeble that a hard touchdown would simply send a craft bouncing back into space. While hovering, it would fire a laser at the surface, vaporizing a tiny puff of soil into a glowing cloud, then read the light from that cloud to determine exactly what the moon was made of, a way to taste a world without ever touching it. Finally, it would release landers. One designed to hop across the surface on spring-loaded legs, another built to fire a small harpoon into the ground to anchor itself to a moon that barely wanted to hold anything at all. To point its cameras at Phobos, the spacecraft had to turn its body, and turning its body meant swinging its main antenna away from Earth. Every close look at the moon required the probe to stop looking at home. It had done this before, more than once, without trouble. Just file that away. Phobos 2 launched on July 12, 1988. 5 days behind its doomed twin. Almost immediately, it began to show the strain of the rush it had been built in. Remember the 3.5 years versus the 6 or 7 the scientists said they needed. This is where that shortfall started to bite. During the long cruise to Mars, things began to fail. By the time Phobos 2 reached Martian orbit, its 3-computer brain had quietly become a crisis. One of the 3 computers was completely dead. A second was beginning to fail. Now go back to the voting rule. The spacecraft does whatever 2 of 3 computers agree on, with 1 healthy computer and 2 failing ones. The single working computer was outnumbered. It could be entirely correct, and it wouldn't matter, because the system was built to trust the majority, and the majority was now the failures. A safeguard designed to protect against a single failure had, through sheer attrition, turned into a trap. And it wasn't only the computers. The high-speed transmitter meant to pour data back to Earth had developed its own problems, forcing the probe to trickle its findings home at a fraction of the intended rate. The spacecraft had crossed the entire inner solar system and arrived at Mars already wounded, already dying by degrees. And yet, remarkably, it kept working. It entered orbit around Mars on January 29, 1989. It built a thermal map of the surface, photographed the planet in visible and infrared light, and studied the atmosphere. Its science kept flowing slowly through a half-broken transmitter controlled by a brain one bad day away from being unable to vote itself out of disaster. By early 1989, a crippled spacecraft, the last hope of an entire program, was circling Mars and slowly closing in on a tiny moon. Its handlers knew it was failing. They knew the clock was against them. They decided to push forward anyway, because the alternative was to have come all that way for nothing. The final close approach was scheduled for April 7th. The probe just had to survive a few more weeks. So it began photographing the moon in stages, like a camera slowly pulling focus. On February 21st, it imaged Phobos from roughly 1,000 kilometers away. A week later, from 300 to 400 kilometers. On March 25th, from less than 300. Each pass closer, each image sharper, a potato-shaped little world resolving out of the dark, scarred with craters and strange parallel grooves, swelling larger in the frame. In total, across its short life at Mars, the probe sent home fewer than 40 images of Phobos, some resolving features just tens of meters across. For a dying spacecraft trickling data through a damaged transmitter, that was a genuine scientific haul. Then came March 27th. Phobos 2 was scheduled to make another imaging run, to turn and face the moon for a fresh series of pictures. To do that, exactly as before, it had to point its body at Phobos, swinging its antenna away from Earth. You already know what happened. The spacecraft went quiet for the imaging session as planned. The session ended, and the probe never cleanly returned. 4 hours later came that faint, garbled, indecipherable signal, the signature of a spacecraft tumbling out of control, unable to hold itself steady or aim its antenna home. A tumbling spacecraft can't keep its solar panels in sunlight. By early April, the temperature inside would fall to freezing. By mid-month, it would be too cold for anything to function. On April 14, 1989, with the probe surely frozen in orbit around Mars, the Soviets declared the mission over. Here is the strange part, the part that turned an engineering tragedy into a legend that refuses to die. When investigators later tried to explain the loss, they could agree on what the spacecraft did. It tumbled, lost power, and froze. What they could not fully explain was why it started tumbling in the first place. That initial push, during the few minutes the probe had turned away from Earth, remained. In the words of one detailed account, a mystery. Officially, blame settled on human error somewhere on the ground, as it had with Phobos 1. Other explanations circulated. A failure of the attitude control system, a loss of the transmitter, or a final breakdown of that ailing flight computer, which had been showing signs of trouble for months. That last explanation is generally considered most likely. But notice the word likely. There has never been a single definitive public failure report that closes the case. Into that open question, the stories came rushing in, and here we have to be careful and honest about what is fact and what is not. The most famous claim came from a remarkable woman named Marina Popovich. She was a Soviet test pilot, one of the best the country ever produced. They called her Madame MiG. In 1964, she became the first Soviet woman to break the sound barrier, and over her career, she set more than 100 aviation world records. After the Soviet Union collapsed, she became one of the most prominent voices in the Russian UFO movement. At her public appearances, she would display a photograph she said was the last image taken by Phobos 2, claiming it showed an unexplained, elongated cylindrical shape near the spacecraft just before the transmission stopped. So what do we actually have? We have a heroic but controversial figure, presenting an image and a story. We have a spacecraft that really did die suddenly, never fully explained, while turning to photograph a moon. And we have a public hungry to connect those two facts. Let's separate the threads. The spacecraft really did photograph something. It photographed Phobos, a real, moving, dark little world crossing in front of Mars. The probe's final frame really was an image of Phobos taken from less than 200 kilometers away. That part is completely true. The claim that the image showed an artificial object, however, is attached to one person with no confirmation behind it. And the claim that Moscow deliberately cut the transmission to hide a discovery runs straight into the most boring and most likely explanation of all. A spacecraft built in half the time it needed, flying on a brain that could no longer outvote its own failures, finally losing its grip during a routine turn. But there is a grain of truth buried in the conspiracy. Moscow did not cut the transmission. The spacecraft died on its own. What Moscow did was something quieter and, in its way, more revealing. When the failures were discussed in May 1989, the head of the team that built the spacecraft tried to blame the loss on outside forces, the kind of bad luck no engineer could be held responsible for. According to those present, his arguments were met with open ridicule by the Institute's own scientists, while the foreign partners watched the Soviets argue among themselves. The old guard wanted to keep systemic problems in-house and pin any failure on meteoroids or radiation. The scientists who had flown the mission wanted an honest public investigation because they believed the real problems had to be admitted before they could ever be fixed. So when people say Moscow covered something up, they are half right and half wrong. There was no hidden photograph of anything unexplained. But there was a deep instinct in the system to reach for an external villain rather than confront a failure of its own making. The thing being concealed wasn't a secret in the sky, it was a flaw on the ground. There is, however, one genuinely strange detail in this story, and it has nothing to do with the supernatural. It's about the moon itself. Phobos is barely like a moon at all. It's small, only about 22 kilometers across on average, and lumpy, irregular, shaped like a potato. Its gravity is so weak, less than 1,000th of Earth's, that it never pulled itself into a sphere. It races around Mars in roughly 7 hours, so fast that from the Martian surface it crosses the sky in the wrong direction. Its dominant feature is a vast crater called Stickney, about 9 kilometers wide, taking up nearly half of one face. Whatever carved out Stickney very nearly shattered the moon. Back in the 1960s, a brilliant Soviet astrophysicist named Iosif Shklovsky looked at Phobos and noticed something that bothered him. For its size, the moon seemed too light. Its density seemed too low. Shklovsky floated a startling thought in the popular press. What if Phobos was so light because it was partly hollow? And if hollow, perhaps even artificial? It was a wild idea, but it came from a serious scientist, and it stuck. For decades, the notion drifted through the culture. So by the time Phobos 2 fell silent while staring at the moon, the cultural ground was already prepared for a mysterious interpretation. There's even a real object on Phobos that keeps the story alive: the Phobos monolith. A single large boulder roughly 85 meters across near the edge of Stickney crater, casting a long, sharp shadow. In low-resolution images, it looks oddly upright and out of place. But science has a calm answer. When something smashed into Phobos hard enough to blast out Stickney, it would have flung enormous boulders across the surface. The monolith is almost certainly one of them, a chunk of debris frozen in place on a low-gravity world. It looks strange mostly because our cameras can't quite resolve it, and a blurry rock often reads to the human eye as something too regular to be natural. But here is the honest twist that survives all the debunking. Shklovsky was wrong about why Phobos is light, but he wasn't wrong that it is light. Modern measurements confirm Phobos really is less dense than solid rock should be, most likely because it isn't fully solid at all, but a loose, porous pile of rubble full of empty space. And we still cannot say for certain where it came from. Some scientists think Phobos and Deimos are captured asteroids. Others think they formed from debris blasted off Mars in a colossal ancient impact. After all these years, we still don't know what the moons of Mars actually are. As a final footnote, the instruments on Phobos 2 searched the moon for any sign of water before the end. They found none. Phobos 2 was the last interplanetary probe the Soviet Union ever designed, and the system that built it didn't outlast it by much. Within 2 years, the Soviet Union collapsed, and planetary exploration funding collapsed with it. A later attempt to fly a similar design, Mars 96, failed when its rocket fell back to Earth. Russia tried once more, decades later, with a probe called Phobos Grunt, aimed at the very same moon. And it failed too, stranded in Earth orbit in 2011. Add it all up, and you reach a sentence that sounds almost impossible. To this day, there has never been a fully successful mission to Phobos. We have flown past it, photographed it, mapped its craters, even filmed it from the Martian surface drifting across the sun. But we have never landed on it. We have never held a piece of it. The story, though, isn't quite finished. Right now, a spacecraft is being readied by Japan with help from agencies in the United States, France, Germany, and Europe. Its mission is the one the Soviets dreamed of and never completed: to fly to Phobos, land on it, scrape up a few grams of that ancient surface, and carry them home. If everything holds, sometime in the next several years, a small capsule will fall through Earth's atmosphere, carrying the first piece of Phobos human hands have ever touched. Then perhaps, we'll finally learn whether it's a captured asteroid, the shattered child of Mars, or something we haven't imagined yet. Until then, the moon keeps its secret. It keeps racing around Mars every 7 hours, casting its long shadow, falling imperceptibly toward the planet that will one day end it. And somewhere up there, frozen and silent for over 3 decades, is a small Soviet machine that crossed an entire solar system to look at it, and got close enough, in the very last moment, to see the grooves on its surface before it turned away from us for good. We built the probe. We aimed it across 400 million kilometers of empty space. We watched it reach the one small strange world it was sent to find. And then, at the exact instant it turned to look, we lost it. And the dark closed back over the moon, leaving us exactly where we have always been. Standing on one planet, staring at another, holding a blurry photograph, and realizing how little we truly know about the small worlds right next door. For nearly 50 years, there was a number that every fusion scientist on Earth treated as a law of nature. It wasn't written into the universe like gravity or the speed of light. It was a wall discovered by experiment, a hard ceiling that showed up again and again, in reactor after reactor, country after country. Push your fusion fuel past this particular density, and the whole thing falls apart. The superheated plasma, the star stuff you're trying to control, destabilizes, tears itself apart, and the reaction collapses. Every time. Scientists gave it a name, the green-walled limit, and it was one of the great frustrating barriers standing between humanity and the dream of limitless clean energy. Because to make fusion actually produce more power than it consumes, you need that fuel, dense and hot and stable all at once, and the green-walled limit said you couldn't have all three. Then, on the first day of 2026, a team of Chinese scientists running a reactor they nicknamed the Artificial Sun did something the textbooks said shouldn't be possible. They blew straight past that limit, not by a little, but by as much as 65%. And the plasma didn't collapse. It stayed stable. It held. A wall that stood for nearly half a century just developed a door. Now, and you know this is coming if you watch this channel, there is crucial context here, and I'm going to give you all of it, honestly, including why this is not the free energy by next year miracle some headlines are selling. But the real story, the true one, is arguably more important than the hype. By the end of this video, you'll understand what fusion actually is, why this specific limit terrified scientists for 50 years, exactly how China broke it, and what it really means for the future of energy on this planet. Let's get into it. Let's start with the basics, because the nickname is doing a lot of work, and it's worth understanding why it's earned. Look up at the sun. Every bit of warmth and light pouring off it comes from one process: fusion. Deep in the sun's core, under crushing pressure and unimaginable heat, hydrogen atoms are smashed together so hard that they merge, they fuse into helium. And every time they do, a tiny bit of mass gets converted into an enormous burst of energy. That's it. That's what powers every star in the sky. It is, quite literally, the engine of the universe. Now imagine bottling that. Imagine building a machine on Earth that recreates the heart of a star, that fuses atoms the same way the sun does, and harnesses the energy that pours out. That's the dream of fusion power, and the prize is almost too good to believe. The fuel is essentially a form of hydrogen you can pull from seawater. It produces no carbon emissions. It can't melt down like a conventional nuclear plant. It generates only tiny amounts of short-lived waste compared to the fission reactors we use today. A single glass of fusion fuel could, in theory, hold the energy of barrels and barrels of oil. Clean, safe, and very nearly limitless. That's why nations have poured tens of billions of dollars into chasing it for over half a century. It's arguably the most valuable engineering goal in human history. The machine China uses to chase it is called EAST, the Experimental Advanced Superconducting Tokamak, located in Hefei. A tokamak is a specific design, a giant donut-shaped chamber wrapped in incredibly powerful magnets. Here's the central problem it solves. To make atoms fuse on Earth, you have to heat your hydrogen fuel to insane temperature. It uses a cage made of pure magnetic force, suspending that star-hot plasma in midair so it never touches the walls. That is the artificial sun, a man-made knot of magnetic fields holding a sliver of star, glowing at 100 million degrees in the middle of a steel donut in eastern China. And the limit they just broke is all about how much fuel you're allowed to pack into that magnetic cage. Here's where we get to the heart of it. The green-walled limit, and why it haunted fusion for so long. To get useful power out of fusion, three things have to be true at once. Your fuel has to be hot enough, it has to be held together long enough, and it has to be dense enough, meaning you've packed enough fuel particles into the space for them to actually collide and fuse in large numbers. Temperature, time, and density. Crank up all three together, and you approach the holy grail. Ignition, the point where the reaction produces more energy than you put in and becomes self-sustaining, like a fire that keeps itself burning. The problem was density. Back in the 1980s, a physicist named Martin Greenwald noticed a stubborn pattern across fusion experiments. Every tokamak seemed to hit a density ceiling, try to pack in more fuel beyond a certain point, and the plasma would suddenly become violently unstable. It would develop disruptions, lose its confinement, and the reaction would crash. It happened so consistently that it became an empirical law of the field. The Greenwald limit, a line you simply did not cross, and it was a genuine roadblock to the entire dream. Because if you can't increase density past this line, you're capped on how much fusion power a reactor of a given size can produce. It forced designs to be bigger, more expensive, more conservative. For decades, fusion scientists essentially had to build around this wall, accepting it as a fixed fact of nature. Here's the part that makes the new result so striking. For nearly 50 years, most people assumed the Greenwald limit was something close to fundamental, a hard rule baked into how plasmas behave. But a newer theory suggested something more hopeful, that the limit wasn't a law of physics at all. It was a consequence, a side effect of how the plasma interacts with the walls of the reactor as it forms. And if that was true, then in principle, with exactly the right conditions, you might be able to sidestep it entirely. That theory had a name: plasma wall self-organization. It was elegant, it was promising, and for years, nobody had ever proven it actually worked in a real reactor. It was a beautiful idea waiting for evidence. China's artificial sun just provided that evidence. So how do you walk through a wall that stopped everyone for 50 years? The answer is surprisingly subtle and genuinely clever. The Chinese team, led by Professor Ping Zhu and Associate Professor Ning Yan, didn't break the limit with brute force, not by simply building bigger magnets or cranking up the power. They broke it by carefully choreographing the very beginning of the reaction, the startup phase, the first moments when the plasma is being born. Here's the core idea, simplified. Normally, as you cram more fuel into the plasma, the edge of that plasma, where it meets the reactor, gets cold and dirty. Impurities build up, energy leaks away, and that cascade is what triggers the instability that crashes the whole thing at the Greenwald limit. The wall and the plasma get into a destructive relationship. The Chinese team's insight was to manage that relationship from the very first instant. They precisely controlled two things: the amount of fuel gas they started with, and a special type of heating called electron-cyclotron resonance heating, essentially using carefully tuned microwaves to energize the electrons in the plasma at exactly the right moment. By dialing in those startup conditions just so, they got the plasma and the reactor walls to settle into a balanced, self-regulating relationship, the self-organization the theory predicted. In that balanced state, something remarkable happens. The plasma stops fighting to high density. Instead of becoming unstable as you pack more fuel in, it stays calm and confined. The team sustained stable plasma at densities between 1.3 and 1.65 times the Greenwald limit. That's 30 to 65% past the line that crashed reactors for half a century, with no disruptions. And critically, this was the first time anyone had ever experimentally confirmed that the self-organization theory actually works in a real tokamak. They didn't just break a record, they proved a theory that could reshape how every future reactor is designed. It's the difference between forcing a locked door and discovering it was never truly locked. You just had to turn the handle the right way. That's what makes this more than a number. It's a new understanding of how the rules actually work. Now here's where I have to be completely straight with you, because this is exactly the kind of story that gets wildly overhyped, and I'd rather you trust this channel than mislead you. This breakthrough does not mean fusion power is arriving next year, or even this decade. It does not mean your electricity bill is about to vanish, and here are the honest reasons why. First, and most important, no fusion reactor on Earth, including East, currently produces net positive energy when you account for the entire system. Right now, these machines still consume more energy to run than they generate. Breaking the density limit is a crucial ingredient toward changing that, but it is not the same as achieving it. East is an experiment, not a power plant. It will never put a single watt into anyone's home. Second, fusion still faces brutal engineering challenges that have nothing to do with this particular limit. Building materials that can survive years of relentless neutron bombardment and star-level heat. Sustaining the reaction not for seconds or minutes, but indefinitely. Turning the heat into electricity efficiently and affordably. These are enormous, unsolved problems, and progress on the materials side has actually been slower than progress on the plasma physics side. And third, even the scientists involved are careful here. As one expert put it, this breakthrough improves confidence in future reactor designs rather than accelerating timelines. It doesn't suddenly make commercial fusion arrive sooner. It makes the eventual reactors potentially smaller, cheaper, and easier to design, because they may not need to be as enormous or as conservative about density as everyone assumed. So the honest framing is this: China did not just solve fusion. What China did is remove one of the longest-standing roadblocks on the path, and prove that a barrier everyone treated as nearly fundamental was actually beatable. That's not the finish line, but it's a genuine, verified, peer-reviewed step toward it, published in the journal Science Advances, and it matters for every fusion project on Earth. not just China's. Here's the part that makes this bigger than a single experiment in Hefei. This discovery doesn't just help China. Because it's a fundamental insight into how plasma behaves, it potentially helps everyone chasing fusion. The world's largest fusion project, ITER, a massive international collaboration in France involving dozens of countries, could potentially use this density-free regime to reach its own goals more easily. The same is true for the wave of private fusion startups that have collectively attracted billions of dollars in investment. A barrier that constrained all of their designs may have just been loosened for all of them at once. There's even a fascinating bonus buried in the data. For years, there's been a rivalry between two reactor shapes, the donut-shaped tokamaks and a twisted design called a stellarator. Each had different strengths around density. The EAST results suggest tokamaks can now operate in a high-density regime that was previously thought to be a stellarator's advantage, effectively giving the most common reactor design a new superpower it wasn't supposed to have. And then there's the strategic picture, which is impossible to ignore. China has now formally written controllable nuclear fusion into its national 5-year plan as a major strategic priority, with a roadmap targeting a pilot reactor around 2035 and a demonstration reactor by roughly 2045. While much of the world has treated fusion as a someday maybe science project, China is treating it as a national industrial goal with a timeline and serious funding behind it. EAST breaking the Greenwald limit isn't an isolated lab result. It's one milestone in a deliberate, long-term national march toward being the country that figures out how to put a star in a bottle first. And whoever does that first, whoever cracks practical, commercial fusion, doesn't just win a scientific prize. They potentially gain control over the cheapest, cleanest, most abundant energy source in human history. The country that masters fusion could reshape the entire global balance of power, because energy underlies everything. Every factory, every data center, every economy. This isn't only about science, it's about who powers the next century. Here's my honest opinion. I think the right way to hold this is to resist both of the easy reactions. The breathless headlines screaming "China just solved fusion, unlimited energy is here," are flatly wrong. We're still decades from a commercial reactor, no machine yet produces net energy, and the hardest engineering problems remain unsolved. Anyone promising you a fusion-powered home by 2030 is selling fantasy. But the cynics who shrug and say fusion is always 30 years away, ignore it, are making a subtler mistake. Because the nature of the progress is changing. For 50 years, the Greenwald limit was treated as a near-permanent wall. China just demonstrated, with peer-reviewed evidence, that it was never a wall at all, just a problem waiting for the right understanding. That's not 30 years away, that's a barrier falling in real time. When the supposedly impossible limits start breaking one by one, the old joke about fusion being perpetually distant stops being quite so funny. What strikes me most is the shift in posture. Fusion used to be a graveyard of broken promises that no one wanted to bet on. Now, there's billions in private money flowing in, nations writing it into industrial plans, and reactors breaking limits that stood since the 1980s. The momentum is real, even if the finish line is still far off. And the fact that one of the biggest recent breakthroughs came out of an artificial sun in eastern China tells you something about who's taking this prize most seriously right now. So here's my question for you, and I genuinely want your honest answer. Do you think we'll see practical, commercial fusion power in our lifetimes? Or is it still the technology that's always 30 years away, no matter how many limits get broken? Are you a fusion optimist or a fusion skeptic? Drop your real take in the comments. I read everyone, and I have a feeling this splits people right down the middle. If you want to keep following this, the breakthroughs, the broken limits, the race to power the future before the rest of the world catches on, subscribe to Eastern Engine and hit the notification bell. Energy, chips, the foundations of the modern world are being rewritten right now, and we break it all down clearly and honestly. Thanks for watching. I'll see you in the next one. Artificial intelligence has a networking problem. The world is building larger GPU clusters, larger data centers, and increasingly powerful computing systems. But all of those processors must constantly exchange enormous amounts of data. If the network connecting them is too slow, expensive, or power-hungry, even the most advanced AI chips can spend valuable time waiting. Now, China says it has completed a major test of a technology designed to attack that bottleneck. Yangtze Optical Fiber and Cable, better known as YOFC, worked with China Telecom and optical equipment company Decoli to transmit 51.3 terabits of data per second across 206.5 kilometers, or roughly 128 miles. The system reached as much as 1.2 terabits per second on a single wavelength, and it completed the entire distance without electronically regenerating the signal or using remotely pumped amplifiers along the route. But the most unusual part was the cable. Instead of sending light through a conventional solid glass core, the system used hollow core fiber. Most of the light traveled through an air-filled channel surrounded by a carefully designed glass structure. That allows optical signals to move faster and experience far less interaction with the glass itself. YAVC says its technology can reduce latency by approximately 31%, increase optical propagation speed by around 47%, and sharply reduce nonlinear distortion. The question is whether this is simply another impressive telecommunications demonstration, or whether air-filled fiber could become a critical part of the infrastructure connecting the world's largest AI systems. Why normal fiber uses glass? Modern communications depend on fiber optic cables. Internet traffic, cloud services, financial transactions, video streaming, mobile networks, and data center connections all rely on pulses of light traveling through extremely thin strands of glass. Traditional optical fiber contains a solid core made primarily from silica. That core is surrounded by another layer of glass with different optical properties. The structure keeps light confined inside the cable as it travels across long distances. This technology transformed global communications because fiber can carry vastly more information than copper while losing relatively little signal strength. But conventional fiber still has physical limitations. Light does not travel through glass at the same speed that it travels through a vacuum or through air. The refractive properties of silica slow the signal down. In ordinary fiber, optical propagation is typically around 2/3 of the speed of light in a vacuum. That delay may sound insignificant, but over hundreds or thousands of kilometers, microseconds accumulate. For ordinary video streaming, the difference may not matter. For distributed artificial intelligence clusters, financial trading, cloud infrastructure, or scientific computing, small delays can affect performance. Glass also interacts with intense optical signals. As more power and more data channels are pushed through the same fiber, nonlinear effects can distort the signal and limit how much information can be transmitted reliably. Hollow core fiber attempts to avoid those problems by moving most of the light away from solid glass. How hollow core fiber works. The name can be misleading. Hollow core fiber is not simply an empty plastic tube. It is still an advanced glass structure, manufactured with extremely precise geometry. Around the air-filled center are thin glass membranes or tubes arranged to keep light trapped inside the hollow region. The structure reflects and guides the optical signal through the air-filled core, while allowing only a small portion of the light to interact with the surrounding material. Because the light travels primarily through air, it can move significantly faster than it does through solid silica. The lower interaction with glass also reduces several types of distortion. This can allow engineers to send stronger optical signals, use more advanced modulation, and potentially increase the distance between major network equipment. The concept is not completely new. Researchers have studied hollow core fiber. YOFC says its latest fiber has achieved loss as low as 0.04 decibels per kilometer under reported test conditions. That is a critical milestone because low latency only matters commercially if the signal can also survive a useful distance. What China's trial achieved. The new Chinese trial combined high capacity, long distance, and a real cable deployment. The system transmitted an aggregate 51.3 terabits per second across a 206.5 kilometer hollow core fiber span. Aggregate capacity means the total data rate across multiple wavelengths. It does not mean one optical channel carried all 51.3 terabits. The maximum reported rate for an individual wavelength was 1.2 terabits per second. Different colors, or wavelengths of light, can travel through the same fiber simultaneously. This technique is called wavelength division multiplexing. Each wavelength carries its own stream of information. When many channels are combined, the fiber can transport an enormous total volume of data. The companies used a self-developed optimization system to adjust the data rate and optical power of individual wavelengths. That matters because not every channel experiences exactly the same conditions. Rather than forcing every wavelength to operate at one fixed setting, the system could allocate resources more efficiently. The result was a very high total capacity across a long hollow core span. What without repeaters really means, some headlines have suggested that the trial required no signal boosting. That is not completely accurate. The system used conventional erbium-doped fiber amplifiers, commonly called EDFAs. These devices amplify optical signals without first converting the information into an electronic form. What the system avoided was signal regeneration along the 206.5-kilometer span. A regenerator receives a weakened optical signal, converts it into electrical data, cleans and retimes that data, and then creates a new optical signal for the next section of the journey. Regeneration can extend network reach, but it adds equipment, power consumption, cost, latency, and potential failure points. The trial also avoided remotely pumped amplifiers placed at difficult locations along the cable route. So the achievement is not that the light traveled completely unassisted. The achievement is that the companies maintained a 51.3 terabit per second connection across the full span, using optical amplification without needing intermediate electronic regeneration. That makes the result far more relevant to real long-distance networks. Why this matters for AI? An AI cluster is not just a room full of processors. It is a networked system. During model training, thousands of accelerators repeatedly exchange gradients, parameters, activations, and other information. The processors must remain synchronized. If communication takes too long, expensive hardware can sit idle while waiting for data from another machine. Inside one server, this problem is addressed through extremely fast chip-to-chip connections. Inside one rack, specialized networking connects multiple systems. But the AI industry is increasingly moving beyond individual racks and even beyond individual buildings. Power availability may force companies to divide computing infrastructure across several data centers. One location may not have enough electricity, cooling capacity, or physical space to contain an entire cluster. Distributed AI infrastructure therefore needs high-capacity connections between separate buildings or regions. This is where hollow core fiber may become valuable. Lower propagation latency could help distant data centers behave more like one coordinated computing system. Lower optical nonlinearity could allow stronger signals and more data channels. Longer spans without electronic regeneration could reduce network complexity and energy use. Hollow core fiber will not make a slow network switch faster or improve poorly designed software, but it could improve the physical layer carrying information between major computing facilities. The energy question. AI data centers are already placing enormous pressure on electrical grids. The processors consume power. Cooling systems consume power. Memory and storage consume power. And the networking equipment connecting everything also consumes power. Long-distance optical systems require amplifiers, transponders, switches, and sometimes regenerators. If hollow core fiber allows longer distances between regeneration points, operators may be able to remove some equipment from a network route. That could reduce power consumption, maintenance requirements, and physical infrastructure. However, the total savings will depend on the complete network. A faster fiber does not automatically make every attached device more efficient. Transceivers still consume energy. Switches still process traffic. Cooling is still required. Installation costs may also remain high. The strongest case for hollow core fiber may initially appear in networks where latency and capacity are more valuable than the lowest possible cable price. The global race. China is not developing hollow core fiber alone. Microsoft acquired British hollow core specialist Luminicity and has been deploying the technology in parts of its Azure infrastructure. Microsoft has also worked with manufacturing partners to expand production. Researchers associated with Luminicity and the University of Southampton have demonstrated hollow core designs with losses below some long-standing solid core fiber benchmarks. Amazon and other major cloud companies have also examined advanced fiber technologies as data center networks expand. This means the Chinese trial should not be interpreted as proof that China invented the entire field or has permanently defeated Western competitors. It shows that China is building its own manufacturing, deployment, and optical equipment ecosystem around the technology. YOFC says it has established an integrated production chain covering preform manufacturing, fiber drawing, coating, cabling, and testing. The company has also produced a continuous hollow core fiber length exceeding 90 kilometers and participated in multiple pilot or commercial projects. That manufacturing capability may become as important as laboratory performance. A fiber technology cannot transform global networks if it can only be produced in short, fragile pieces. The manufacturing challenge. Conventional fiber has decades of industrial experience behind it. Manufacturers can produce enormous quantities at low cost. Telecommunications companies understand how to install it, splice it, test it, and repair it. The supporting standards and equipment are mature. Hollow core fiber must compete with that entire ecosystem. Its internal geometry is far more complex. Small manufacturing defects can increase optical loss. Joining two hollow core sections can be difficult because the air-filled structures must remain precisely aligned. Connections with conventional fiber can also introduce additional loss. Bending, cabling, environmental stress, and long-term reliability must be carefully tested. A record achieved on one route does not prove the same performance can be reproduced cheaply across millions of kilometers. Operators also need compatible amplifiers, transceivers, connectors, monitoring equipment, and installation procedures. This is why hollow core fiber is unlikely to replace all conventional fiber in the near future. Traditional silica fiber is already extremely effective for most communications. It is inexpensive, reliable, and widely available. Hollow core technology will probably enter the market first where its unique advantages justify the added cost. Where it could be used first. The most obvious early applications are financial networks, major cloud regions, AI data center links, scientific facilities, and telecommunications backbones. High-frequency trading companies pay large amounts of money to reduce network latency by tiny fractions of a second. Cloud providers may value faster communication between separate data centers. AI companies may need to connect clusters located near different power sources. Scientific institutions may use the fiber to transfer enormous datasets or synchronize precision instruments. Military and government networks could also value lower latency and reduced signal distortion. Consumer broadband will probably not be the first major market. Replacing the fiber entering individual homes would be expensive, and most household internet connections are limited by service plans, routers, Wi-Fi, and network congestion rather than the propagation speed of the glass itself. The technology makes more sense in the backbone of the network, where enormous quantities of data travel across long distances. My take is that this trial is important, but not because conventional fiber is suddenly obsolete. Solid core silica fiber will remain the foundation of global communications for many years. It is proven, inexpensive, and good enough for an enormous range of applications. The breakthrough is that hollow core fiber is moving out of small laboratory experiments and into longer commercial-scale links. China's 51.3 terabit per second trial demonstrates that an air-filled core can support high-capacity transmission across more than 200 kilometers without electronic regeneration along the span. That is a meaningful engineering result. The technology still faces manufacturing costs, splicing challenges, standardization questions, and competition from improving conventional fiber. But AI is changing the value of network performance. When companies spend billions of dollars on processors, memory, and data centers, the cost of a better cable becomes easier to justify if that cable keeps the entire computing system operating more efficiently. The next AI bottleneck may not be the chip. It may be the connection between the chips. And China has just demonstrated a fiber designed to move that data through air instead of solid glass. So what do you think? Could hollow core fiber become the next major upgrade to global AI infrastructure? Or will manufacturing complexity keep it limited to specialized networks? Let me know your view in the comments. And subscribe to Eastern Engine for more grounded coverage of the chips, factories, and engineering decisions reshaping the global economy. Because the future of computing will not depend only on how fast processors can calculate. It will also depend on how quickly information can move between them. Silicon has been the foundation of the modern world for more than half a century. Every smartphone, every gaming PC, every AI server, every data center, every satellite, every electric vehicle, and nearly every advanced electronic system relies on one material more than any other. Silicon quietly became the invisible backbone of civilization. It powered the internet, fueled the smartphone revolution, and now drives the AI race that has reshaped the global economy. For decades, the assumption seemed impossible to challenge. If you wanted faster chips, you improved silicon. If you wanted smarter AI, you built more silicon. If you wanted more computing power, you invested billions into making silicon smaller, faster, and more efficient. But what if the entire industry has been chasing the wrong answer? Because while much of the world continues investing hundreds of billions of dollars into squeezing another few percentage points out of silicon, researchers in China have been quietly pursuing something far more ambitious. Instead of asking how to improve silicon, they asked a completely different question: what comes after it? That question has suddenly become one of the biggest discussions inside the semiconductor industry. Not because silicon is disappearing tomorrow, but because the physical limits that engineers have warned about for years are becoming increasingly difficult to ignore. As transistors shrink toward atomic dimensions, every new manufacturing generation becomes exponentially more expensive, more complicated, and more difficult to produce. the roadmap that carried computing for decades is beginning to slow down. And whenever one era starts slowing, another usually begins. Across China, universities, research institutes, advanced laboratories, photonics companies, material scientists, and semiconductor manufacturers are all exploring technologies that could fundamentally change how information moves through computers. Some projects focus on light instead of electricity. Others replace traditional semiconductor materials with entirely different compounds. Some abandon conventional transistor designs altogether. Individually, many of these breakthroughs seem incremental. Together, they begin to paint a picture of where computing may be heading next. That possibility is making investors, governments, and technology companies pay very close attention. Because replacing silicon wouldn't simply create another faster processor. It could reshape AI infrastructure, data centers, telecommunications, cloud computing, autonomous vehicles, defense technologies, and countless industries built on digital hardware. And unlike previous generations of chip improvements, this transition may not simply be about making today's computers faster. It could redefine what computers actually are. The reason this matters now is because artificial intelligence has changed the rules. Modern AI models require staggering amounts of computational power. Companies are building data centers consuming gigawatts of electricity. GPU clusters now contain tens of thousands of processors, communicating simultaneously. Memory systems struggle to keep pace. Heat generation continues increasing. Power consumption rises year after year. Ironically, many of today's biggest AI limitations are no longer caused by software. They're caused by physics. Moving electrical signals through microscopic copper wiring generates resistance, heat, latency, and energy loss. Shrinking transistors further introduces quantum effects that engineers spent decades trying to avoid. Every new manufacturing node requires increasingly expensive lithography equipment and unprecedented engineering precision. Silicon hasn't stopped working. It's simply becoming much harder to improve. That reality has pushed scientists around the world to search for alternatives that were once considered experimental. Photonic computing, advanced glass materials, optical interconnects, wide bandgap semiconductors, two-dimensional materials, and entirely new computing architectures have all moved from academic research into serious engineering programs. China has invested heavily across nearly all of these fields. Some of those investments are beginning to produce results that have attracted attention well beyond China's borders. The conversation is no longer whether alternative technologies will exist. The real question has become which country commercializes them first, because history shows something remarkably consistent. The companies that dominate one generation of computing rarely dominate the next without adapting. Mainframes gave way to personal computers. Desktop computing gave way to smartphones. Traditional CPUs were joined by GPUs. AI accelerators emerged alongside them. Every technological transition created new leaders, while forcing established giants to reinvent themselves. Doesn't mean silicon suddenly disappears. Far from it. Silicon will almost certainly remain essential for years, perhaps decades. But the industry's focus may gradually move toward hybrid systems where silicon works alongside entirely new technologies rather than carrying the entire workload alone. And that's where China's latest research becomes especially interesting. Because instead of trying to replace every silicon chip overnight, many of its projects focus on replacing only the components where silicon performs worst. Communication between chips, high-speed data transfer, AI memory bottlenecks, heat generation, optical computing, advanced materials, one breakthrough at a time. Individually, none of these developments may seem revolutionary. Combined, they could represent the early stages of something much bigger. A transition away from an era that has defined computing for more than 50 years. And if that transition accelerates faster than expected, the biggest question won't simply be whether silicon has reached its limits. It will be who built what comes next. To understand why researchers are searching beyond silicon, you first have to understand how extraordinary its success has been. Silicon didn't become the world's dominant semiconductor by accident. It offered an almost perfect combination of affordability, stability, electrical performance, and manufacturability. As fabrication techniques improved, engineers discovered they could place more transistors onto a single chip while reducing cost per calculation. That simple trend became the engine behind modern computing for decades. Every 2 or 3 years, processors became faster, smartphones became smarter, video games became more realistic, cloud computing became practical. Artificial intelligence evolved from science fiction into everyday reality. Silicon made all of it possible. But every technology eventually reaches a point where improvement becomes increasingly difficult. For silicon, that challenge arrives at the atomic scale. Modern transistors are now measured in just a few nanometers. At these dimensions, engineers aren't simply designing electronic circuits anymore. They're designing around the strange behavior of quantum mechanics. Electrons begin leaking through barriers they were never supposed to cross. Heat becomes increasingly difficult to remove. Manufacturing tolerances shrink to astonishing levels. A tiny defect invisible to the human eye can ruin an entire wafer worth millions of dollars. This is one reason semiconductor fabrication has become one of the most expensive industries on Earth. Building a leading-edge fabrication plant now costs tens of billions of dollars. Every new manufacturing generation requires increasingly sophisticated equipment. Extreme ultraviolet lithography, atomic layer deposition, advanced packaging, high-precision metrology. Each improvement demands more investment while delivering smaller performance gains. Engineers sometimes describe this as the easy progress coming to an end. For decades, shrinking transistors solved nearly every problem. Today, shrinking them further solves fewer problems while creating entirely new ones. Artificial intelligence has made those limitations impossible to ignore. Modern AI models no longer rely on a single processor performing calculations independently. Instead, thousands of processors work together simultaneously. Each processor constantly exchanges enormous amounts of information with every other processor. That communication consumes time. It consumes electricity. It generates heat. And increasingly, it limits overall system performance. Ironically, some of the world's most powerful AI processors now spend part of their time waiting. Not because they're too slow, because information can't reach them quickly enough. That's a remarkable reversal. For years, processors represented the bottleneck. Now the bottleneck often exists between the processors. Moving data has become almost as important as processing data. This shift explains why researchers are exploring technologies that don't simply improve silicon. They're trying to redesign the entire architecture surrounding it. China has become particularly active in this area. Over the past several years, we've seen Chinese researchers publish advances involving photonic chips capable of transmitting information using light rather than electrical signals. Glass-based packaging technologies designed to improve chip communication. Air-filled optical fibers capable of transmitting enormous amounts of data across impressive distances. Novel semiconductor materials intended to reduce energy loss. Optical interconnects designed specifically for AI infrastructure. Advanced chip packaging that shortens communication pathways. Viewed separately, each breakthrough appears highly specialized. Viewed together, they reveal a consistent strategy. Instead of asking how to build a slightly faster processor, researchers are asking how to eliminate the limitations surrounding today's processors altogether. That's an important difference. Imagine upgrading the engine inside a race car while leaving narrow tires, weak brakes, and poor suspension unchanged. The engine becomes more powerful. The car doesn't necessarily become much faster. Modern AI faces a similar challenge. Processors have advanced rapidly. Memory has improved. Storage has become dramatically faster. But communication between all those components hasn't improved at the same pace. That imbalance has created entirely new engineering priorities. This helps explain why many semiconductor conferences today focus as much on packaging, networking, photonics, and material science as they do on transistor density. The future isn't being defined by one component. It's being defined by how every component works together. China's semiconductor strategy appears increasingly aligned with that philosophy. Rather than concentrating every investment on traditional silicon scaling, the country has expanded research across multiple complementary fields. Advanced materials, optical communication, AI networking, memory technology, chip packaging, photonics, integrated manufacturing. Each area addresses a different weakness inside conventional computing. Individually, none replaces silicon. Collectively, they reduce dependence on silicon doing everything alone. That's why the title of this video isn't suggesting silicon suddenly disappears tomorrow. It suggests something arguably more significant. Silicon may no longer be the only foundation capable of supporting next-generation computing. Future AI systems may rely on entirely new combinations of technologies working alongside traditional semiconductor designs. Processors optimized for specific workloads, photonic communication replacing electrical signaling, advanced packaging reducing communication distances, novel materials handling specialized calculations, silicon remaining where it performs best. This hybrid approach could extend computing far beyond what conventional transistor scaling alone can achieve. Some researchers even argue that the future of computing won't belong to a single revolutionary material. Instead, it will belong to ecosystems capable of combining multiple technologies into one highly efficient platform. That possibility is attracting enormous investment worldwide, because whoever successfully builds that platform may define the next era of computing, not by making silicon slightly better, but by making the entire system fundamentally smarter. If silicon is approaching practical limits, the obvious question becomes surprisingly simple. What exactly replaces it? The answer is more complicated than many headlines suggest. There probably won't be a single material that suddenly takes over the semiconductor industry overnight. Instead, engineers increasingly believe the next generation of computing will emerge from several technologies working together, each solving a different problem that silicon struggles to handle. In many ways, the future of computing may look less like a replacement and more like an evolution. That's where China's recent research becomes particularly interesting. Rather than betting everything on one breakthrough, Chinese laboratories have been exploring multiple paths simultaneously. One of the most promising involves photonic computing. Traditional processors move information using electrons flowing through microscopic circuits. Photonic systems replace some of those electrical signals with light. At first glance, that may not sound revolutionary, but light behaves very differently from electricity. Photons travel at incredible speeds. They generate far less heat while transmitting information. They experience minimal electrical interference. And perhaps most importantly, they can carry enormous amounts of data simultaneously through optical pathways. These advantages become especially valuable inside artificial intelligence infrastructure. Modern AI isn't limited by mathematical calculations alone. It's limited by communication. Thousands of processors constantly exchange data. Memory modules feed enormous datasets into GPU clusters. Networking hardware moves information between racks. Storage systems continuously deliver new training data. Every delay reduces efficiency. If light can move that information faster than electricity, AI systems become more productive without necessarily building faster processors. That's one reason photonic technologies have become one of the semiconductor industry's hottest research areas. China isn't alone in pursuing this vision. Companies and research institutions across the United States, Europe, Japan, South Korea, and Taiwan are investing heavily in optical computing as well. But China's pace of announcements has accelerated noticeably over the past few years. We've covered breakthroughs involving photonic processors, glass-based chip packaging, air-filled fiber capable of record-breaking transmission speeds, optical interconnects, integrated AI networking. Each project addresses a different communication challenge. Together, they point toward a future where electrical signaling no longer carries every piece of information inside advanced computers. Another promising direction involves entirely new semiconductor materials. For decades, silicon dominated because it balanced cost, reliability, and manufacturing simplicity. But other materials possess electrical properties that outperform silicon in specific applications. Gallium nitride allows higher power efficiency. Silicon carbide excels in electric vehicles and industrial power electronics. Two-dimensional materials measured only atoms thick are being explored for future transistor designs. Researchers are investigating carbon-based structures with remarkable electrical behavior. None of these materials completely replaces silicon today. Instead, each one solves particular problems where silicon reaches its limits. That's an important distinction. The semiconductor industry rarely abandons successful technology immediately. It gradually introduces specialized alternatives where the benefits justify the cost. We've already seen this happen in memory. Traditional hard drives still exist. Solid-state storage expanded alongside them. Cloud storage joined both. Each technology found its own role. The same pattern may emerge with computing materials. Silicon remains excellent for general-purpose processing. Photonics may dominate communication. Wide bandgap materials may power electric infrastructure. Advanced packaging may reduce communication delays. Novel memory technologies may eliminate existing bottlenecks. Instead of replacing silicon entirely, future computers may simply rely on silicon much less than they do today. That shift could prove just as significant. China's strategy appears designed around exactly this kind of diversification. Rather than concentrating every research dollar on one revolutionary invention, investments span nearly every layer of modern computing. Semiconductor manufacturing, memory technology, advanced packaging, optical communication, artificial intelligence hardware, materials science, telecommunications, industrial automation. This creates something more valuable than isolated breakthroughs. It creates an ecosystem where improvements in one field immediately benefit another. Faster networking improves AI clusters. Better packaging enhances processor performance. Advanced materials reduce energy consumption. Optical communication eliminates bottlenecks. Each improvement strengthens the others. That's why many analysts increasingly evaluate semiconductor competition differently than they did 10 years ago. The question isn't simply who builds the fastest chip, it's who builds the strongest ecosystem around that chip. Because artificial intelligence has fundamentally changed what high-performance computing requires. Success no longer depends on processor speed alone. It depends on communication, power efficiency, heat management, memory bandwidth, packaging technology, networking architecture, manufacturing capability, software optimization, supply chains. The winners of tomorrow's computing industry will likely master all of them. That's why replacing silicon isn't really about one material defeating another. It's about building an entirely new generation of computing infrastructure. And if China's current strategy succeeds, the biggest breakthrough may not be a single revolutionary processor. It may be something much larger, a computing platform where silicon is no longer the star of the show. Instead, it becomes just one component inside a far more advanced technological ecosystem. Whether silicon is truly nearing the end of its dominance remains an open question. Predicting the future of technology has never been easy, especially in an industry that has repeatedly surprised even its own experts. Every few years, a breakthrough emerges that changes expectations, reshapes investment, and forces companies to rethink their long-term strategies. What's different today is the scale of that transformation. Artificial intelligence has accelerated demand for computing faster than almost anyone anticipated. Data centers continue growing larger. AI models require exponentially more processing power. Energy consumption keeps climbing. At the same time, the physical limits of traditional chip design are becoming increasingly difficult and expensive to overcome. That reality is pushing the entire industry to think differently. Instead of relying on one material to solve every problem, researchers are building systems where multiple technologies work together. Silicon may continue handling general-purpose computing, while photonics speeds up communication. Advanced materials improve efficiency, and new packaging techniques reduce delays between components. In many ways, the future may not belong to a single revolutionary invention. It may belong to whoever integrates these technologies into one seamless platform first. China appears determined to compete in exactly that race. Over the past several years, we've seen growing investment across semiconductor manufacturing, AI hardware, optical networking, advanced materials, memory technologies, and chip packaging. Each announcement on its own may seem incremental, but together they suggest a broader strategy, one focused on shaping the next era of computing rather than simply catching up to the last one. Of course, none of this means silicon suddenly becomes obsolete tomorrow. Billions of devices around the world will continue relying on silicon for many years to come. The semiconductor industry doesn't replace foundational technology overnight. It evolves step by step, generation by generation. But history shows that every technological era eventually reaches a turning point. Vacuum tubes gave way to transistors. Mainframes gave way to personal computers. CPUs were joined by GPUs. Now, the industry is searching for what comes after today's AI hardware. Whether the next breakthrough comes from photonics, new semiconductor materials, hybrid architectures, or an approach nobody has imagined yet, one thing is becoming increasingly clear. The future of computing will likely look very different from the systems we've relied on for the past 50 years. And if that future arrives sooner than expected, today's biggest advantage may not belong to the company with the fastest silicon chip. It may belong to the country that successfully builds what comes next. If you enjoyed this video, don't forget to like, subscribe, and turn on notifications so you never miss our latest deep dives into AI, semiconductors, and the technologies shaping the future. Thanks for watching, and I'll see you in the next one. For more than 50 years, nearly every major advance in computing has followed the same basic strategy. Make silicon transistors smaller, place more of them on one chip, then use those extra transistors to increase performance, reduce power consumption, and add new capabilities. That formula transformed computers that once filled entire rooms into processors small enough to fit inside phones, watches, and medical sensors. But silicon cannot shrink forever. As transistor channels become extremely thin, electrical current becomes harder to control. Leakage increases. Heat becomes more difficult to manage. And the material begins behaving in ways that make conventional scaling less effective. Researchers around the world are therefore searching for something that could eventually work alongside silicon. or possibly replace it in specific parts of future chips. A team at Fudan University in China has now demonstrated one of the most advanced alternatives yet. They built a functioning 32-bit RISC-V processor using 5,931 transistors made from molybdenum disulfide. The active semiconductor inside each transistor consists of one layer of molybdenum atoms placed between two layers of sulfur atoms, 3 atomic planes in total. The processor is called RV32WUGI. It can execute standard 32-bit instructions, perform arithmetic, and operate as a programmable microprocessor rather than a single isolated laboratory transistor. It is not fast. It runs at approximately 1 kHz, millions of times slower than a modern desktop or smartphone processor. Its 5,931 transistors are almost nothing compared with the billions found in commercial chips. But speed was not the purpose of this experiment. The breakthrough was proving that thousands of atomically thin transistors could be manufactured consistently, connected into reusable logic cells, and assembled into a complete processor architecture. Researchers did not simply create one transistor that worked under perfect laboratory conditions. They created a system. And that may be the step two-dimensional semiconductor technology needed most. Why silicon becomes difficult to shrink. A transistor is essentially a tiny electrical switch. One terminal controls whether current can travel through a semiconductor channel between two other terminals. When the switch is on, current flows. When it is off, the channel should block that current. Billions of these switches combine to create logic gates, registers, memory interfaces, and processor cores. For decades, reducing transistor dimensions improved nearly everything. Smaller transistors switched faster, they required less energy, and manufacturers could place more computing power inside the same area. But when a conventional semiconductor channel becomes extremely thin, the electric field controlling it can lose authority over the charge inside. Current may leak even when the transistor is supposed to be off. Interfaces between the semiconductor and surrounding materials can interfere with electron movement. The difference between the transistor's on and off states can become less distinct. Engineers have extended silicon scaling through advanced structures such as FinFETs and gate-all-around transistors. Instead of controlling the channel from only one side, the gate wraps around more of it. That improves electrostatic control. But even these designs face limits. The thinner the silicon becomes, the more its electrical properties can degrade. This is why two-dimensional semiconductors are so interesting. They are naturally atomically thin. Researchers do not need to carve a thick block of material down until only a fragile channel remains. The crystal itself is built in layers. What molybdenum disulfide actually is, molybdenum disulfide, usually written as MoS2, is made from molybdenum and sulfur. In its single-layer form, one sheet of molybdenum atoms sits between two sheets of sulfur atoms. This structure is extremely thin, but it still behaves as a semiconductor. That distinction matters. Graphene is probably the most famous two-dimensional material. It is strong, thin, and highly conductive. But ordinary graphene lacks a natural band gap. That makes it difficult to switch completely off, which is a serious problem for digital logic. A processor needs a clear difference between 0 and 1. MoS2 has a band gap, allowing a transistor to control current much more effectively. Its atomically thin body also gives the transistor gate strong electrical control over the complete channel. In theory, that could help engineers continue shrinking devices after conventional silicon becomes increasingly difficult. But producing one excellent MoS2 transistor is not the same as building a processor. A transistor may work beautifully when a researcher selects one perfect location on a small sample. A processor requires thousands, millions, or eventually billions of devices to behave predictably at the same time. A small variation that seems unimportant in one transistor can ruin an entire logic circuit when repeated across a wafer. That is the challenge the Fudan team tried to solve. From one transistor to 5,931. Before RV32WUGI, researchers had created many promising two-dimensional transistors. They had also built small logic circuits, but integration remained limited to only a few hundred devices. UGI increased that complexity dramatically. The finished processor contained exactly 5,931 months two transistors on a die measuring approximately 6 mm by 6 mm. Researchers fabricated multiple dies on a 4-inch sapphire wafer. Sapphire was used as an insulating base that helped electrically isolate the devices. The important achievement was not density. A 6 mm modern silicon chip could hold millions or even billions of transistors, depending on the manufacturing process. WUGI's devices were physically large. Their transistor channels were approximately 3 micrometers long. That is thousands of times larger than the smallest features inside advanced commercial processors. But the researchers were working with university-level fabrication equipment rather than one of the world's most advanced semiconductor factories. They prioritized reliability over density. Before shrinking the system, they needed to prove that the material could support a complete processing architecture. Building a library of logic processor designers do not normally draw every transistor individually. They use collections of verified building blocks called standard cells. A standard cell library may include inverters, AND gates, OR gates, multiplexers, registers, and more complex combinations. Design software connects these cells to create larger circuits. The Fudan team developed a complete library containing 25 types of logic units made from its two-dimensional transistor technology. This was essential. A single transistor is only a switch. Useful computation begins when switches are combined into logic. An inverter changes a 1 into a 0 or a 0 into a 1. An AND gate produces an output only when multiple conditions are true. Registers store temporary values. Adders combine binary numbers. Once these blocks behave consistently, engineers can reuse them throughout the processor. This is where WUGI moved beyond many earlier demonstrations. The project was not only material science. It combined material growth, transistor fabrication, circuit design, standard cell development, and processor architecture. The team co-optimized the manufacturing process and the chip design. Instead of assuming that tools created for mature silicon would transfer perfectly to MIOS-2, researchers adjusted both sides together. The circuits were designed around what the new devices could manufacture reliably. The manufacturing process was improved according to what the processor needed. Why machine learning was used? Wafer-scale two-dimensional materials contain many possible sources of variation. The film may not grow identically across every location. Contacts between metal and the semiconductor can vary. Residue defects and microscopic contamination can affect device behavior. Threshold voltage may shift from one transistor to another. When thousands of devices are connected, these small variations can accumulate. The researchers used machine learning methods to help optimize fabrication steps and improve consistency. This does not mean artificial intelligence designed the complete processor by itself. Machine learning helped researchers analyze manufacturing data, identify relationships between process conditions and device performance, and refine the production flow. The team reported a manufacturing yield of approximately 99.77%. That level of consistency was critical. A processor containing almost 6,000 transistors cannot function if large numbers of devices fail randomly. High yield allowed the team to move from individual test structures to a complete programmable circuit. Why they chose RISC-V? The processor uses the RISC-V instruction set architecture. An instruction set defines the commands a processor understands. Instructions may tell it to add numbers, move data, compare values, or jump to another part of a program. RISC-V is open and modular. Companies and researchers can design processors around it without paying for a proprietary instruction set license. That makes it especially useful for experimental hardware. The researchers did not need to create an entirely new software language simply because they were using a new semiconductor. They could implement a recognized 32-bit architecture and test whether the MIOS-2 processor executed standard instructions correctly. UGI demonstrated arithmetic, including addition and subtraction, as well as movement of data through its registers and control logic. That may sound basic, but basic arithmetic is built from multiple coordinated steps. Inputs must enter the processor. Control logic must decode the instruction. Registers must hold values. The arithmetic unit must produce the correct result. The output must then be stored or transmitted. Completing that sequence proves that the devices are operating as an organized computer. The performance reality. WUGI runs at approximately 1 kHz. That means around 1,000 clock cycles per second. A modern processor may operate at several gigahertz, or several billion cycles per second. The comparison is not close. WUGI also contains fewer than 6,000 transistors, while advanced commercial chips contain tens of billions. During arithmetic operation, the prototype consumed approximately 0.43 milliwatts. That sounds impressive, but it would be misleading to compare the number directly with a high-performance laptop processor. UGI is performing far less computation. Its low total power partly reflects its limited size and very low speed. The researchers are not claiming that this prototype can replace an Intel, AMD, Apple, or Qualcomm processor. The accurate comparison is with previous two-dimensional circuits. From that perspective, UGI represents a major jump from small collections of laboratory devices towards system-level integration. The Wright brothers' first aircraft was not useful as a modern passenger jet. Its importance was proving controlled powered flight. UGI plays a similar role for atomically thin logic. It proves the material can do more than switch one signal in a laboratory. It can form a programmable processing system. Why atomic thickness could matter later. One possible advantage of two-dimensional materials is better control at extremely small dimensions. Another is vertical integration. Modern chips are increasingly stacking components. Memory dies are stacked to create high-bandwidth memory. Chiplets are combined inside advanced packages. Manufacturers are exploring ways to place logic layers above other circuits. The problem is temperature. Traditional transistor fabrication often involves processes hot enough to damage circuitry already built underneath. Some two-dimensional materials may be deposited or integrated at lower temperatures. That could eventually allow engineers to add new logic or sensing layers above completed silicon circuits. A future chip might use silicon for high-performance processor cores, while atomically thin devices handle sensors, local processing, or additional logic in layers above them. Two-dimensional semiconductors may therefore complement silicon before they replace it. They could also be useful in low-power edge devices. A smart sensor may not need billions of transistors or gigahertz performance. It may need a small amount of computation close to where information is collected. Thin materials could potentially combine sensing and processing in compact devices with unusual shapes or strict power limits. What still has to be solved? The road from Wuji to commercial production remains long. The transistor channels must become much shorter. The researchers' current 3 micrometer devices are enormous by modern standards. Better lithography could increase density and improve speed. Contacts between metal and METS2 must also become more reliable and lower in resistance. Manufacturing must scale from small research wafers to large industrial wafers with consistent material quality. The design will need complementary transistor types comparable to the efficient CMOS logic used in modern silicon chips. Packaging, long-term reliability, temperature stability, and manufacturing cost must all be tested. And every improvement must occur without destroying the properties that make the material attractive. A working prototype is evidence of possibility. It is not evidence that mass production will be easy. Shanghai has announced an engineering demonstration line intended to move related two-dimensional chip technology beyond the university laboratory. But ambitious production targets should remain separate from what has already been scientifically demonstrated. The verified achievement today is the processor itself. My take is that the 3-atom headline is impressive, but the most important number is 5,931. Researchers have produced atomically thin transistors for years. The problem was making thousands of them behave consistently enough to create a processor. Wujuji demonstrates that the challenge is no longer limited to proving the material can switch current. The conversation can now move toward design library bit RISC-V system, 25 types of logic cells, and nearly 6,000 MOS2 transistors. The processor is slow, it is physically large, and it remains a laboratory prototype. But every semiconductor platform begins with devices that look uncompetitive next to the mature technology they hope to challenge. Silicon has received decades of investment, factory development, and design optimization. Two-dimensional semiconductors are only beginning to build that ecosystem. So what do you think? Will atomically thin materials eventually become a serious successor to silicon, or will they remain specialized layers used only in sensors and low-power edge devices? Let me know your view in the comments. And subscribe to Eastern Engine for more grounded coverage of the chips, materials, and manufacturing breakthroughs shaping the future of computing. Because China has not built a 3-atom thick replacement for today's fastest processors. But it has proved that transistors only 3 atomic planes thick can work together as a real programmable CPU. And that is where a laboratory material begins becoming a computing technology. Most countries announce a big project, spend a decade building it, and then hold a press conference. China announces a big project, builds it in 2 years, and by the time the press conference happens, they are already halfway through the next one. What is happening in China right now is not one mega project, it is dozens of them, running simultaneously, across industries that have nothing to do with each other, all moving at a pace that is genuinely difficult to process when you lay them out side by side. Delivery infrastructure, transportation, automotive engineering, construction, healthcare, agriculture, biometric systems, humanoid robotics. Each one of these sectors is being rebuilt from the ground up, and most of the world is only paying attention to 1 or 2 of them at a time. This video is about what it looks like when you zoom out and see all of it at once. Let's start somewhere familiar. food delivery, because it is a useful anchor for understanding the broader pace of change. In most countries, food delivery means a person on a motorbike navigating traffic, finding your address and knocking on your door. It works. It is slow. It has not changed much in 30 years. China's Meituan has been deploying autonomous delivery drones across urban areas, already completing hundreds of thousands of successful deliveries. The drones operate on fixed aerial corridors, deposit packages at designated collection points, and achieve delivery windows measured in minutes, rather than the half-hour guesses most people are used to. In rural areas, the challenge is different. Many villages in China sit beyond road infrastructure that supports normal logistics networks. JD.com has been addressing this with heavy-lift cargo drones capable of carrying loads up to 30 kilograms, effectively extending supply chain reach into communities that previously had no access to rapid delivery at all. Remote does not mean disconnected anymore. It just means the drone route is longer. The infrastructure being built around this is not experimental. These are operational networks with real volumes, and they are expanding. China's automotive sector is currently doing something that deserves more sustained attention than it receives in Western media. The scale of autonomous and semi-autonomous capability being deployed into consumer vehicles is genuinely without parallel anywhere else in the world. 2 out of every 3 new vehicles being sold in China this year are equipped with some level of autonomous driving hardware. That is not a projection, it is a current production reality. The number of test vehicles operating on designated autonomous driving corridors across Chinese cities now runs into the tens of thousands, spread across nearly 20 major urban areas. One vehicle that captures where this technology is heading is the Z01. It runs on a dual-chip AI computing platform, delivering over 500 trillion operations per second, feeding data from 11 high-definition cameras, 12 ultrasonic sensors, and 5 radar systems simultaneously. The vehicle's AI assistant can receive voice commands from outside the car and drive itself to the owner's location from up to 2 kilometers away. That is not a demonstration model. That is the production specification. BYD's engineering decisions in this era deserve attention on their own. Their Yangwang U8 SUV uses 4 fully independent electric motors, 1 per wheel, which enables movement modes that are simply impossible in a conventional drivetrain. The vehicle can rotate in place by running opposite wheels in opposing directions. It can move laterally by running all wheels in the same sideways direction. In flood conditions, it can enter water nearly 1.5 meters deep, remain buoyant, and propel itself by wheel spin for up to 30 minutes. This is not a limited production novelty. It is available to buy. At the performance end of BYD's lineup sits the Yangwang U9, a supercar that recently recorded a top speed of just under 500 kilometers per hour, putting it among the fastest production vehicles ever documented. Its active suspension system can raise and lower individual wheels by 75 millimeters in 40 milliseconds, giving the car the ability to absorb obstacles, adjust its stance dynamically at speed, and even execute coordinated movements that look choreographed when demonstrated at low speed. The same company building a car that can boat through floods is also building one of the fastest production vehicles on the planet. Both are electric. Both are available now. One of the persistent objections to electric vehicle adoption has been charging time. Even fast chargers at current standards require meaningful waiting, long enough to matter on a road trip, long enough to be genuinely inconvenient in daily life. BYD's latest battery and charging platform has moved the technical argument to a different place entirely. Their current generation system supports charging at 1 megawatt, 1,000 kilowatts, which delivers approximately 400 kilometers of driving range in 5 minutes of charging. That number reframes the comparison. A 5-minute stop to gain 400 kilometers of range is shorter than the average petrol station visit when you factor in paying, waiting, and moving. The argument that electric vehicles are fundamentally slower to refuel than combustion vehicles no longer holds at this charging rate. The infrastructure to support this is being built out alongside the vehicle capability. The two are developing in parallel, which is how you actually change a market rather than just announcing intentions to change it. The construction sector in China has been quietly undergoing a transformation that rarely gets the attention it deserves. A project in western China recently completed a highway section using a fleet of 100 autonomous haul trucks, each capable of carrying 85 tons of material. The trucks operated continuously, including in temperatures reaching -40 degrees Celsius, without human operators. They were supported by autonomous road rollers and automated paving equipment, guided by GPS and real-time terrain mapping. The outcome of that combination, autonomous excavation, autonomous haulage, autonomous compaction, automated paving, is a highway construction process that runs around the clock regardless of weather or shift schedules, with consistent output that does not degrade with fatigue. China's stated goal is to have several thousand autonomous haul trucks operating across major construction projects by the end of this year. Given the rate at which the pilot deployments have scaled, there is no particular reason to be skeptical of that timeline. There is something worth pausing on here. These machines are building the roads that autonomous vehicles will eventually use. The infrastructure for a robotic future is being constructed by robots. China's maglev train program has been advancing in two parallel tracks: commercial deployment and speed research, and both are producing numbers that are difficult to contextualize against anything in the existing transport landscape. Commercial maglev lines in operation currently achieve speeds well above 400 kilometers per hour, roughly comparable to the fastest conventional high-speed rail. But the research program has been testing at significantly higher velocities. Experimental runs have recorded speeds exceeding 600 kilometers per hour in controlled conditions. At those speeds, the geography of China changes. A journey between Beijing and Shanghai, currently around 5.5 hours by high-speed rail, drops below 3 hours. Distances that currently require domestic flights become competitive with ground transport for the first time. The technology eliminates rail contact entirely. No friction between wheel and track means no track degradation at high speeds, no wheel wear, and a noise profile fundamentally different from conventional rail. The engineering challenges are enormous, but China is further along in addressing them practically, as opposed to theoretically, than any other country. At more than 60 major airports across China, passengers move through security, check-in, baggage drop, and boarding gates using only their face. No ticket printed, no identification card presented, no interaction with staff required, unless the passenger initiates it. The processing speed at optimized checkpoints is approximately 12 seconds per passenger from entry to clearance. Beijing's main international airport has over 600 biometric verification points integrated across its facilities. Shanghai Hongqiao's system handles the complete journey from terminal entrance to aircraft boarding without a single document exchange. The broader facial recognition infrastructure extends beyond transport. More than 200 million cameras are currently installed across China, feeding into systems that identify individuals in real time, flag regulatory violations, and assist law enforcement in tracking specific individuals through public spaces. This is the part of China's technological development that generates the most complex conversation in the West, and understandably so. The capability is extraordinary. The applications raise questions about civil liberties, state surveillance, and the appropriate limits of biometric data collection that have no easy answers. China has moved faster on deployment than on the policy frameworks that would govern its use, which is a tension that will intensify as the technology spreads globally. WeChat Pay's palm recognition payment system is now operational in over 1,500 retail locations across China. Users register their palm, the system maps both surface lines and subcutaneous vein patterns, and then pay by holding their hand above a scanner. The registration takes seconds. The payment takes less than one. The security architecture is more robust than fingerprint recognition, primarily because vein patterns are internal and cannot be lifted from surfaces the user has touched. The error rate is below 1 in a million transactions. Students at universities, commuters on transit systems, and shoppers in regular retail stores are all using it as a primary payment method. The trajectory is toward a payment infrastructure that requires the user to carry nothing at all: no card, no phone, no physical token of any kind. China's robotics industry has moved past the industrial automation phase and into territory that is harder to categorize neatly. Unitree Robotics produces a humanoid robot designated the G1, standing just over 1.30 m, weighing 35 kilograms, with 23 articulated joints. It walks with a gait that closely mimics natural human movement, responds to voice commands, can carry objects, and can perform physical tasks in environments designed for humans rather than machines. The price point sits at $16,000, a figure that, compared to humanoid robots developed elsewhere in the world, is dramatically lower. Their quadruped robot series, four-legged machines roughly the size of a medium dog, has been deployed in actual working environments, including sporting events, police operations, and industrial inspection. The machines navigate autonomously, respond to voice commands, and carry payloads at running speeds. They were used at the Asian Games in Hangzhou to retrieve equipment on the field during competition, operating in front of large crowds without incident. XP Robots in Dalian is doing something more unsettling. They build humanoid robots designed to be visually indistinguishable from humans at conversational distance. Each unit takes approximately 1 month to produce, involves over 140 degrees of motion freedom in the face and body, and achieves a level of realism in skin texture, eye movement, and facial expression that makes extended observation increasingly uncomfortable. They are currently producing over 500 units per year, deployed in museums, hotels, educational institutions, and government facilities. Several units have been built as replicas of historical scientific figures, rendered as functioning, conversational robots that can discuss the subject's life and work. Chinese hospitals have been deploying automation across multiple points in the patient care pathway. Robotic systems now handle blood draws in some facilities, using vein mapping technology to locate and access veins with a precision rate that reduces failed attempts compared to manual techniques. Automated medication dispensing and delivery robots move pharmaceutical orders from pharmacy to ward without human handling. More significantly, telesurgery systems have been used to perform procedures on patients in remote locations with the surgeon operating from a different city. The latency requirements for surgical precision over long-distance connections are extremely demanding, and the fact that this has moved from research to clinical practice is a notable threshold. The AI diagnostic systems being piloted in some facilities are achieving accuracy rates on specific diagnostic tasks that compare favorably with specialist physicians. This is not a replacement argument. It is a capability argument. The availability of diagnostic support that performs at specialist level, in settings where specialists are not geographically accessible, changes what rural and underserved healthcare can look like. Agricultural automation in China has moved well past GPS-guided tractors. Crop spraying drones capable of carrying 100 kilograms of material cover fields at speeds and consistency that manual application cannot match, operating at night and in conditions that restrict human workers. Automated transplanting equipment covers multiple hectares of planting per day with GPS precision that eliminates the spacing inconsistencies inherent in manual planting. Specialized robotic systems for cotton cultivation can cover dozens of hectares daily at a rate many times faster than field workers performing the equivalent task. The economic logic is straightforward. Labor-intensive agricultural tasks are being transferred to machines that operate continuously, do not require rest, and maintain consistent output across an entire working day. The food supply chain that feeds 1.4 billion people is being restructured around this automation at a speed that has significant implications for agricultural labor markets across the region. What strikes me most about laying all of this out in one place is how different it looks from the way it is usually presented. Individual stories about a fast-charging battery or a robot dog are easy to absorb as novelties. The aggregate picture is something different, not a collection of cool gadgets. That is an attempt to rebuild the operating layer of a civilization. Whether every piece of it works as described, whether the social trade-offs involved are ones other societies would accept, and whether the pace is sustainable, those are all legitimate questions. But the ambition and the execution speed are real, and they deserve to be understood clearly rather than dismissed or exaggerated. My question for you is this: which one of these technologies do you think will reach your country first? The ultra-fast EV charging, the autonomous vehicles, or the humanoid robots? Tell me in the comments. I genuinely want to know what people in different parts of the world think the timeline looks like from where they are sitting. If this kind of deep dive breakdown is what you come here for, make sure you are subscribed to Eastern Engine. Hit the subscribe button and turn on notifications. We cover the engineering and technology stories that are reshaping the world, and there is a lot more coming. The pace of development right now means there is a new story worth telling almost every week. Don't miss it. A data center can contain the fastest AI chips ever built. Thousands of GPUs, hundreds of billions of transistors, cooling systems powerful enough to remove the heat generated by a small industrial facility. And yet the entire machine can still be slowed down by something that looks almost ordinary. A strand of glass, not a silicon wafer, not high bandwidth memory, not another advanced processor, glass. Inside modern AI data centers, microscopic pulses of light travel through optical fiber, carrying information between servers, switches, buildings, and entire campuses. These fibers have become the nervous system connecting the chips together, and demand is now increasing so quickly that some of China's largest optical fiber manufacturers reportedly have production lines operating near full capacity, with order schedules extending into early 2027. One industry executive estimates that AI-focused data centers may require approximately 36 times more fiber than traditional CPU-based racks. Corning says individual 72 GPU systems, including designs based around NVIDIA's Blackwell platform, can already need 16 times more fiber than conventional cloud switching racks. That helps explain why NVIDIA recently entered a long-term partnership with Corning to expand American optical connectivity manufacturing capacity tenfold. It also helps explain why NVIDIA committed $2 billion to optical specialist Coherent, while Meta agreed to purchase as much as $6 billion of fiber, cable, and connectivity equipment from Corning. The next AI bottleneck may not be the ability to manufacture more GPUs. It may be the ability to connect them, because an isolated AI chip is not an AI factory. It is simply a very expensive calculator waiting for data, the component hiding in plain sight. When most people picture artificial intelligence, they imagine processors, large black packages, glowing server racks, silicon wafers moving through advanced factories. Optical fiber rarely receives the same attention because the technology appears passive. A fiber does not calculate. It does not train a model. It does not store billions of parameters. It simply carries information. But that simple job has become one of the hardest problems in modern computing. Large AI models are not usually trained on one processor. The work is divided across hundreds, thousands, or even tens of thousands of accelerators. Every accelerator calculates only one part of the result. Then the machines must exchange what they learned again, and again, and again. The processors are constantly talking. If that communication slows, the expensive computing hardware waits. Imagine hiring 10,000 brilliant engineers to build one aircraft, then giving them a single narrow hallway through which every drawing, component, and instruction must pass. The engineers may be fast. The hallway determines how quickly the aircraft is completed. Optical fiber is the hallway, and AI has turned that hallway into a traffic jam. Why AI needs so much more fiber? Traditional data centers mainly handle requests moving between users and servers. Someone loads a website. A company accesses a database. A video is streamed. Information generally enters the data center, reaches the correct machine, and leaves again. AI clusters generate a different kind of traffic. Most of the communication happens inside the facility. GPU to GPU, rack to rack, switch to switch, building to building. This is called east-west traffic. During AI training, thousands of accelerators repeatedly exchange model updates. If one part of the cluster finishes its calculation early, it may still have to wait for the others before the next step begins. The network, therefore, cannot merely be fast on average. It must be consistently fast. One congested connection can hold back an entire group of processors. This is why AI networks are built with enormous numbers of redundant links. Engineers try to ensure that any GPU can communicate with many others without all the traffic being forced through one narrow route. The network begins to resemble a giant web. More processors create more possible connections. More connections require more ports. More ports require more transceivers, switches, connectors, and fibers. The growth is not always linear. Double the number of accelerators, and the communication problem may increase by far more than 2 times. That is how a data center filled with GPUs can consume dozens of times more optical fiber than a traditional server installation. Why copper cannot handle everything? Copper still plays an important role inside computing systems. It is inexpensive, it is familiar, and over short distances it can move data extremely quickly. But copper has limits. As transmission speeds increase, electrical signals weaken, interference becomes harder to control, power consumption rises because the system must work harder to preserve signal quality. A short connection inside one server can remain electrical. A connection running across a row of racks becomes more difficult. A link crossing a large building becomes harder again. At 800 gigabits per second, and especially as networks move toward 1.6 terabits, distance becomes expensive. Copper cables can also become thick and heavy. A rack containing hundreds of high-speed connections can begin to resemble a mechanical sculpture made from cables. Fiber changes the equation. Instead of pushing electrons through metal, the system converts data into pulses of light. Those pulses travel through an extremely pure glass core, surrounded by material with a slightly different optical property. Light reflects internally and remains trapped inside the fiber, traveling long distances with far less signal loss than an equivalent electrical connection. The strand can be thinner than a human hair, yet it may carry extraordinary amounts of data. That is why AI infrastructure is gradually shifting from copper toward optics. Not everywhere, not all at once, but closer and closer to the processor. The light is moving toward the chip. Traditional optical networks use pluggable transceivers. A cable reaches the front of a network switch. An optical module converts the incoming light into an electrical signal. The electrical data then travels across the circuit board to the switching chip. That arrangement has worked well. But as bandwidth rises, the electrical path between the optical module and the chip begins consuming more power. It also creates heat. NVIDIA's answer is co-packaged optics. Instead of keeping optical components at the outer edge of the switch, the optical engines move much closer to the networking silicon. The electrical path becomes shorter. More of the journey happens as light. NVIDIA says its photonics-based networking systems can improve power efficiency, while allowing AI clusters to scale to much larger numbers of GPUs. But this transition does not reduce the importance of glass. It increases it. More optical engines create more optical connections. More connections require more fibers, connectors, splitters, and precision components. The light may move closer to the chip. The glass follows it. This is why NVIDIA's partnerships with Corning and Coherent matter. The company is not merely buying cable. It is helping expand the manufacturing base for the optical architecture its future AI systems will depend on. What sold out until 2027 really means. The phrase sounds absolute. It is not. China has not run out of every spool of fiber. Homes will not suddenly lose internet access because AI consumed the world's glass. The real situation is more specific. Industry reports indicate that large Chinese manufacturers such as Hengtong and FiberHome are operating at high utilization, while delivery schedules for some optical products now extend into early 2027. Other Chinese suppliers have reported overseas orders booked into the first quarter of next year. That means much of the available manufacturing capacity has already been committed. A new customer can still place an order. The customer may simply have to wait much longer than before, and the shortage is not equal across every product. Basic telecom fiber is different from the bend-resistant, high-density and low-loss fiber required inside advanced data centers. AI installations often need specialized products capable of being packed tightly into limited spaces while maintaining signal quality. Those are precisely the products experiencing the greatest pressure, so sold out is useful shorthand. The more accurate description is this: the production calendar is filling faster than factories can expand it. The demand curve turned vertical. In 2025, global demand for optical fiber and cable used in data centers reportedly increased by almost 76%. The total reached nearly 70 million core kilometers. 1 core kilometer represents one fiber core extending for 1 kilometer. A cable containing hundreds or thousands of individual cores therefore adds up quickly. Industry forecasts suggest demand could exceed 100 million core kilometers in 2026. That is not normal growth. That is the shape of a market being reorganized. For years, optical fiber demand was driven mainly by telecom networks, broadband expansion, and mobile infrastructure. Fiber traveled toward homes. Now, increasingly, it travels toward GPUs. One Chinese industry expert summarized the transformation clearly. Optical fiber used to be installed near households. Now it is installed beside every accelerator. The destination changed. The volumes changed with it. And manufacturers that survived years of weak pricing suddenly find themselves facing more demand than they prepared for. Why factories cannot simply make more optical fiber look simple after it is finished? The manufacturing process is not. It begins with a preform. A preform is a large, extremely pure cylinder of specially engineered glass. It contains the same basic optical structure that will exist inside the final fiber, but at a much larger scale. The center becomes the fiber core. The surrounding glass becomes the cladding. To create the preform, manufacturers deposit carefully controlled layers of glass material while adjusting chemical composition and refractive properties. Impurities must be minimized. A tiny contamination can scatter light. A slight variation can change how the signal travels. Once the preform is completed, it is placed inside a tall drawing tower. The bottom is heated until the glass softens. Gravity and precise mechanical control pull a thin strand downward. A cylinder weighing hundreds of kilograms can become thousands of kilometers of optical fiber. The strand must maintain an almost perfectly consistent diameter. Protective coatings are applied immediately. The fiber is tested, bundled, and later assembled into cables. Expanding this process is not as simple as buying another machine and turning it on. Preform factories require specialized equipment, skilled engineers, clean production environments, and significant capital. New capacity can take 18 months to 2 years to become operational. That delay explains the current mismatch. AI demand changes in months. Glass capacity changes in years. The preform is the real bottleneck. The preform is often the most valuable part of the optical fiber supply chain. It determines the quality and performance of the final strand. Manufacturers can sometimes expand cable assembly capacity relatively quickly. Producing much more high-quality preform is harder. That is where technical knowledge becomes important. The glass must be pure enough that light can travel through kilometers of fiber while losing only a small fraction of its power. The composition must remain stable from the center of the preform to its outer edge. The material must draw smoothly without creating microscopic defects. Think of stretching a highly detailed image painted on a thick cylinder until the cylinder becomes a thread. Every internal proportion must remain correct. China's major fiber companies have invested heavily in this upstream capability. FiberHome recently displayed what it describes as the world's largest optical fiber preform, reflecting the industry's effort to extract more finished fiber from each manufacturing cycle. But even larger preforms do not instantly solve the shortage. They must be manufactured consistently. They must meet the correct specifications, and the rest of the production system must be able to draw, coat, test, and cable the resulting fiber. The chain is only as fast as its slowest operation. Why China matters? China built enormous optical fiber capacity during the expansion of broadband, mobile networks, and national communications infrastructure. That scale once contributed to oversupply and weak pricing. Factories competed aggressively. Margins narrowed. Some smaller producers left the market. Larger manufacturers became cautious about adding even more capacity. Then AI arrived. The same industry that had spent years worrying about too much fiber suddenly faced the opposite problem. Chinese manufacturers now supply domestic computing projects while receiving rising orders from overseas customers. First quarter overseas sales across parts of the Chinese fiber industry reportedly increased by more than 55% compared with the previous year. The advantage is not only low manufacturing cost, it is scale. Large preform capacity, existing draw towers, cable factories, experienced engineering teams, and supply networks already capable of delivering enormous quantities. The AI boom did not create this industrial base, it revealed how valuable it had become. The price of specialized glass is rising. Not every fiber price has moved equally, but certain high-performance categories have increased sharply. One specialized bend-resistant product used in dense installations reportedly rose from around 32 yuan to as much as 240 yuan per core kilometer over roughly 1 year. That represents an increase of several 100%. Why would bend resistance matter? Because AI data centers are crowded. Cables must turn around tight corners. They pass through racks, trays, and densely packed connection panels. A normal fiber bent too sharply can leak light and weaken the signal. Bend-resistant fiber maintains performance in tighter spaces. That becomes valuable when thousands of connections must be installed inside a limited area. The data center does not merely need more glass. It needs better glass, and better glass is harder to produce quickly. NVIDIA's response is not small. In May 2026, NVIDIA and Corning announced a multi-year partnership to expand optical connectivity manufacturing in the United States. Corning plans to increase its American optical connectivity capacity tenfold. It also plans to raise American fiber production capacity by more than 50% and construct 3 new manufacturing facilities. That is not the response of a company expecting demand to return to normal next quarter. NVIDIA separately announced a $2 billion investment in Coherent, alongside purchase commitments and access to future optical capacity. Coherent manufactures lasers, optical components, and networking products needed to convert electrical information into light and move it through AI systems. Meta has reached its own agreement with Corning worth as much as $6 billion. The pattern is clear. Large technology companies are no longer treating fiber as a generic product they can purchase whenever needed. They are securing manufacturing capacity years in advance. They are funding expansion. They are reserving supply. That usually happens when a component moves from being a commodity to being strategically important. Can a glass shortage actually delay AI? Potentially. A company can purchase GPUs and still be unable to deploy them immediately if the rest of the infrastructure is missing. Servers need power, cooling, switches, memory, buildings, transformers, and connectivity. An AI cluster cannot simply place thousands of accelerators in one room and expect them to cooperate. The network must be installed, tested, and synchronized. If optical cables arrive late, the entire facility may open late. If only part of the network is available, expensive processors may remain underused. This does not mean fiber will stop the AI industry. Manufacturers are expanding. Customers can redesign networks. Some short connections can continue using copper. Engineers can reduce fiber counts through more efficient architectures, higher capacity strands, or multi-core designs. But each workaround has limits. At some point, physical data must move. The processors cannot calculate information they have not received. The honest catch: the 36 times figure should not be treated as a universal law. Different data centers use different architectures. A small inference facility may not resemble an enormous training cluster. Some systems use more copper, others move rapidly toward optics. The number of fibers depends on rack design, GPU count, redundancy, network topology, and transmission speed. Corning's estimate of 16 times more fiber for certain 72 GPU nodes may be more relevant to specific modern systems. The 36 times estimate describes the broader intensity of AI-focused facilities compared with traditional CPU racks. Both numbers communicate the same direction. AI networking is far more fiber-intensive than conventional computing. The exact multiplier changes. The demand problem remains. My take: my view is that this story reveals something important about every major technology boom. The public focuses on the glamorous component, the GPU, the model, the benchmark, but the limitation often appears somewhere less exciting. A transformer, a cooling pipe, a memory package, a cable. In this case, a strand of purified glass. NVIDIA can design a faster accelerator, but if thousands of those accelerators cannot exchange data quickly enough, much of the additional computing power is wasted. That is why optical fiber has moved from the background to the center of AI infrastructure planning. The most interesting part is not simply that China has large fiber factories. It is that those factories were built for one technological era and have suddenly become critical to another. Infrastructure created for telecom networks is now being redirected toward AI. Manufacturing capacity that once looked excessive now looks scarce, and the industry cannot expand quickly because the true bottleneck begins with a highly specialized cylinder of glass that may take years of factory investment to produce at a larger scale. No glass, no connection, no AI factory. So what do you think? Will optical fiber become one of the biggest hidden constraints on artificial intelligence over the next several years? Or will new networking designs, multi-core fiber, and co-packaged optics allow manufacturers to stay ahead of demand? Let me know your view in the comments. And if you want more grounded stories about the materials, machines, and overlooked components shaping the future of computing, subscribe to Eastern Engine. Because the next limit on artificial intelligence may not be hiding inside the chip. It may be the glass connecting one chip to another. A laboratory in Oregon takes one of Huawei's newest smartphone processors and begins removing it layer by layer. The package comes apart. The memory is separated. The silicon is polished until structures invisible to the human eye become visible under powerful microscopes. And deep inside the chip, researchers find a number that appears to break the normal hierarchy of semiconductor manufacturing: 32.5 nanometers. That is the measured pitch of the lowest local metal layer inside Huawei's Kirin 9030 processor, manufactured by China's SEMIC using its N+3 process. Now compare that with Intel's newest commercial manufacturing technology. Inside Panther Lake processors built on Intel 18A, the equivalent layer is reportedly spaced at 36 nanometers. On that one measurement, China's 7-nanometer class process went smaller than the layer shipping inside Intel 18A. And it did so without EUV lithography. That sounds like SMIC somehow jumped beyond Intel. It did not. Intel's overall process remains denser, more efficient, and considerably more advanced. Intel 18A can also support a tighter metal pitch than the version used in Panther Lake. But the measurement is still remarkable because it reveals how aggressively SMIC has stretched older lithography equipment. The company did not overcome the problem with one secret machine. It attacked the chip from several directions at once. Quadruple patterning, narrower cells, fewer transistor fins, contacts placed in tighter positions, and a metal network compressed almost to the practical edge of DUV manufacturing. The result is not a clean victory, it is an engineering trade. SMIC gained density, but it paid for that density with additional masks, extra processing, tighter alignment tolerances, and greater manufacturing complexity. And that trade may tell us more about the future of Chinese chipmaking than a simple benchmark ever could. Modern semiconductor names are misleading. 7 nanometers, 5 nanometers, 3 nanometers, 18 angstroms. These labels sound like direct physical measurements, as though every important feature inside a 7-nanometer chip must be 7 nanometers wide. That has not been true for years. Process names have become generational labels. They describe a package of manufacturing improvements rather than one universal dimension. Intel 18A does not mean every structure measures 18 angstroms. SMIC N+3 does not mean every feature measures 7 nanometers. Two companies can use completely different names while producing structures that overlap in certain dimensions. That is why comparing 7 nanometer with 18A by name alone creates the wrong picture. A chip contains many different measurements. There is gate pitch, fin pitch, cell height, transistor density, metal pitch, SRAM density, and the spacing between contacts and wires. Each reveals one part of the process. The new teardown focused attention on M0, the first local metal layer sitting just above the transistor structures. Think of the transistors as tiny buildings. The metal layers are the roads connecting them. M0 handles extremely short local connections inside the smallest logic cells. Higher layers gradually become wider roads carrying signals across larger regions of the chip. A tighter M0 pitch allows more local wiring to fit into a smaller area. But one narrow street does not automatically mean the whole city is better. The city also needs highways, power delivery, intersections, and enough space for traffic to move. That is where the comparison becomes complicated. The chip examined was Huawei's Kirin 9030 Pro, part of the processor family used in the Mate 80 series. It is manufactured using SMIC's third-generation 7nm class process, known as N+3. Researchers measured the M0 pitch at approximately 32.5 nanometers. That is around 10% tighter than the 36nm M0 configuration found in Intel's Panther Lake processors. SMIC's M1 layer measured approximately 38 nanometers, while M2 measured around 40. These dimensions show that SMIC compressed the lowest wiring layers aggressively, but the larger picture is different. The teardown estimated SMIC N+3 at roughly 113 million transistors per square millimeter using a normalized logic density metric. That places it around the level of TSMC's older N6 process. Intel 18A's high-density library remains approximately 38% denser. So how can one local layer be tighter while the overall process remains far behind? Because density is not controlled by one dimension. SMIC squeezed M0 partly because it needed to. Intel could leave more space there because it had already removed one of the largest sources of congestion: power. Traditional chips deliver both data signals and electrical power through metal layers above the transistors. Imagine trying to build a city where delivery vans, commuter traffic, power cables, and water pipes all compete for the same narrow streets. The result is congestion. Intel's Power Via technology changes that arrangement. Instead of routing power through the front-side metal stack, Intel brings power through the back of the silicon. Signals remain on one side. Power arrives from the other. This frees valuable routing space above the transistors and reduces resistance in the power network. With less front-side congestion, Intel does not always need to compress every local wire to the smallest possible pitch. Panther Lake uses a 36nm M0 pitch, but Intel 18A reportedly supports a 32nm option. Intel chose the looser configuration partly because Panther Lake relies heavily on higher performance cell libraries and because Power Via gives designers more routing freedom. That is why the headline needs the phrase "in one critical layer." SMIC produced a tighter M0 pitch in this shipping Huawei chip. But Intel's process is not limited to 36 nanometers, and a wider M0 layer does not automatically represent weaker technology. Sometimes additional space is not a failure to shrink. It is a choice enabled by a better architecture. The most impressive part of SMIC N+3 is not that the company found a magical replacement for EUV. It is that engineers extracted more resolution from DUV lithography through repetition. The key method is called self-aligned quadruple patterning, or SAQP. The concept sounds almost like a geometric trick. A DUV lithography system first prints a relatively wide guide pattern called a mandrel. A thin spacer material is deposited along the sides of that guide. The original guide is removed, leaving the spacers behind. Those spacers then become guides for another deposition and removal cycle. One original line effectively becomes 4 narrower lines. Imagine drawing one thick stripe on a road. You place barriers along both edges, then remove the original stripe. Next, place smaller barriers around the barriers that remain. After several carefully controlled steps, one broad pattern has been multiplied into several narrow, evenly spaced features. The lithography machine did not directly resolve every final line. The process created them through deposition and etching. That is how SMIC could form a roughly 32nm grid using DUV equipment. But every added operation creates risk. The spacers must have nearly identical thickness. The etch must remove exactly the intended material. The new lines must remain aligned with contacts and structures created in other steps. If one stage shifts slightly, the error can propagate through the entire pattern. EUV can print finer features with fewer pattern-splitting steps. DUV can reach similar dimensions in selected layers, but the path is longer. SMIC replaced machine simplicity with process complexity. Quadruple patterning sounds clever because it is clever. It is also expensive. Each additional deposition, etch, cleaning, and inspection step consumes factory time. More steps require more equipment. More equipment means more maintenance. More masks increase cost before the first commercial wafer is even produced. Alignment becomes increasingly difficult because patterns created in separate operations must meet with extraordinary precision. A small overlay error can place one metal line too close to another, creating electrical leakage or a short circuit. Place it too far away, and the intended connection may fail. Then there is variation. If one spacer is slightly thicker than another, the final lines will not be identical. Resistance changes, timing changes. One region of the chip may behave differently from another. The teardown reportedly found that the tight M0 trenches had a more difficult profile than the looser metal layers above them. That does not mean the chip is defective. It means the manufacturing cost is visible in the structure. SMIC successfully created the feature, but the feature carries evidence of how hard it was to create. This is the central paradox of DUV scaling. The machine itself is older. The process surrounding it becomes more complicated. The metal layer was only part of the story. SMIC also used several design and manufacturing techniques to reduce the area of the basic logic cells. The first was fin depopulation. The Kirin 9030 uses FinFET transistors. In a FinFET, current flows through vertical silicon fins surrounded by the gate. More fins can provide stronger electrical drive, but more fins also consume space. SMIC N+3 uses 2 NMOS fins and 2 PMOS fins in its measured logic cells. Reducing the fin count allows cells to become narrower, but it can also limit drive strength. It is similar to replacing a wide multi-lane tunnel with a narrower one. The tunnel occupies less land. It may not move the same amount of traffic. The second technique is contact over active gate. Normally, the electrical contact connected to a gate may sit beside the active region, consuming additional space. Place that contact directly over the active gate, and the cell becomes shorter. Simple in a diagram. Difficult in production. The contact must land accurately without damaging or interfering with the transistor below it. The third technique is the single diffusion break. Logic cells need isolation between neighboring transistor regions. Older layouts often used a wider double break. A single diffusion break saves space, but it increases sensitivity to local manufacturing variations. Again, density improves. Margin becomes smaller. None of these ideas is unique to SMIC. Major foundries use similar density-enhancing techniques. What stands out is how aggressively SMIC combined them in one process generation. This is where the story moves beyond lithography. A foundry cannot simply shrink every shape to support the new layouts. The result is a feedback loop. Suppose a transistor loses one fin to save area. The circuit may now switch more slowly. Designers compensate by changing the cell, adjusting the signal path, or using a stronger cell elsewhere. Suppose a metal layer becomes tighter but gains resistance. Engineers may shorten important routes or move selected connections to a higher layer. The process is no longer simply about drawing smaller transistors. It becomes a puzzle involving density, power, performance, heat, and manufacturability. SMIC N+3 appears to be a product of that puzzle. Its density did not come from one enormous leap in lithography. It came from dozens of smaller compromises that reinforce one another. Huawei used the denser N+3 process to fit more capability into a chip with a die area similar to its predecessor. The Kirin 9030 reportedly adds another middle CPU core, expands several caches, and increases GPU and neural processing resources. Individual CPU cores also became smaller. The prime core shrank despite receiving a larger private cache. The middle cores became significantly more compact. GPU compute units became smaller, allowing Huawei to increase the number of units while keeping the full graphics section within a manageable area. That is what process scaling is supposed to accomplish. The goal is not merely creating a beautiful cross-section under a microscope. The goal is using less area for existing functions, then spending the saved area on more capability. Huawei appears to have done that successfully, but performance reveals the limitation. The Kirin 9030 improved significantly over the previous generation, especially in graphics. It still trails current flagship processors from the leading mobile chip companies. Its CPU architecture and manufacturing efficiency remain behind the newest designs. The chip can contain more hardware than its predecessor. It cannot operate that hardware with the same power efficiency as a processor manufactured on a leading 3nm class process. Density matters. the voltage and frequency curve matters more. A smaller structure does not automatically switch faster. Narrower metal wires have greater electrical resistance. Smaller transistors can suffer from leakage and variability. More patterning can introduce dimensional differences across the wafer. A process must balance density with the ability to operate at useful voltage and frequency. This is where SMIC's disadvantage becomes clear. The Kirin 9030 is a credible modern smartphone processor, but it is not equal to the latest Apple, Qualcomm, or MediaTek flagship chips. Its strongest CPU core reportedly performs more like an older high-end design. Its GPU made a major generational jump, yet remains far behind current top-tier alternatives. Efficiency is the greater challenge. A processor can reach competitive performance by consuming more power, but a smartphone has strict thermal limits. The device cannot use a large cooling system. The battery must last. The surface cannot become uncomfortably hot. That means performance per watt determines how much of the chip's theoretical capability can be used continuously. SMIC compressed the layout. It has not yet matched the manufacturing characteristics of the most advanced nodes. In M0 pitch inside these two shipping products, yes, the Kirin 9030's measured 32.5 nanometer pitch is tighter than Panther Lake's 36 nanometer implementation. Across the entire manufacturing process, no. Intel 18 amps uses gate-all-around ribbon FET transistors, rather than conventional FinFETs. It includes backside power delivery. It offers substantially greater normalized logic density, and it provides a more advanced platform for performance and efficiency. Even the narrow M0 victory needs context because Intel 18A supports a tighter 32 nanometer version that was not used in Panther Lake. So the correct interpretation is not that SMIC's 7 nanometer process is better than Intel 18A. It is that process node names hide enormous complexity. A company working with older lithography can produce one dimension that looks more advanced than a dimension inside a newer process. But it may need more steps, more masks, and more compromise to get there. The number is real. The meaning is conditional. The significance lies in what SMIC proved can still be extracted from DUV. Many observers assumed that without EUV, advanced logic manufacturing would quickly reach a hard wall. The Kirin 9030 suggests the wall is not perfectly vertical. It is more like a steep mountain. Progress remains possible, but every meter becomes harder than the last. SMIC has tightened local metals, reduced cell dimensions, and incorporated multiple density boosters. It has reached roughly TSM6 class logic density, while using a more complicated manufacturing route. That is not parity with the leading edge. It is evidence of continued movement, and commercial shipment matters. This is not a research wafer designed only to demonstrate one small test structure. The process is manufacturing a complete smartphone system on chip containing CPU cores, graphics, AI processing, memory controllers, image processing, and communication hardware. Every one of those blocks must work together. A laboratory can optimize one line. A consumer processor must survive millions of interacting lines. That makes the result harder to dismiss. SMIC may still have additional scaling options. Cell height could be reduced again. Some local metal layers could be pushed into even more aggressive patterning. Gate pitch may shrink slightly. Future designs could use backside contacts or advanced three-dimensional stacking. But each option becomes more difficult. If another routing layer requires quadruple patterning, mask count rises again. If cells become shorter, designers lose wiring tracks. If contacts move to the backside, manufacturing requires wafer thinning, backside alignment, and new integration steps. None of these is impossible. Together, they become unforgiving. The danger is not that one individual step cannot work. The danger is that the combined process becomes too expensive, too slow, or too sensitive to variation. A foundry does not win by producing the world's most impressive cross-section. It wins by producing large numbers of functional chips at a competitive cost. That is why EUV remains so valuable. It does not perform magic. It reduces the number of tricks required. If shrinking the chip in 2 dimensions becomes increasingly expensive, the next option is to build upward. Huawei has discussed an approach called logic folding, which would divide parts of a logic block across multiple active silicon layers. Instead of placing every transistor beside the others on one flat surface, some functions could sit above or below their neighbors. Short vertical connections could replace longer horizontal wires. This could improve density per package area and reduce the time required for signals to travel across large blocks. The approach has its own difficulties. Stacked active logic creates heat. Bonding must be extremely precise. Testing becomes more complicated. The density comparison also changes. because adding another layer increases transistors per package footprint without improving the transistor process itself. Still, the direction is logical. When the map cannot become much smaller, fold the map. SMIC N+3 may therefore represent both progress and a warning. It demonstrates how far planar DUV scaling can be pushed. It also demonstrates why the industry is looking beyond planar scaling. My view is that the 32.5 nanometer result is more interesting than the phrase "China beat Intel" suggests. A simple victory would almost be less revealing. SMIC did not create a universally superior process. It created an unusually aggressive one. The company used quadruple patterning, tighter local wiring, and several layout optimizations to achieve a dimension that looks extraordinary beside Intel's shipping configuration. But Intel's wider M0 layer exists partly because PowerVia removed power congestion from the front side. Intel could afford not to squeeze that layer as hard. One company compressed the road because space was scarce. The other redesigned the city so the road did not need to carry everything. Both are engineering achievements. The difference is cost and headroom. SMIC's approach demonstrates ingenuity, but each additional shrink will demand more complexity. Intel's architecture gives it more room for future optimization. So no, the Kirin 9030 does not prove that China has overtaken Intel. It proves something narrower, and still significant. A 7nm class chip, manufactured without EUV, can contain one local wiring layer tighter than the configuration used inside a commercial Intel 18A processor. That should not be exaggerated. It should not be ignored either, because technological progress does not always arrive as a clean leap from one machine generation to another. Sometimes it comes from taking an old tool, surrounding it with new processes, and forcing it to perform one more task that looked unreasonable. The final product may cost more. It may consume more power. It may remain behind the leader overall, but it works. And once something works in a commercial chip, the question changes. It is no longer, can this be done? It becomes, how far can they push it next? So what do you think? Is SMIC's 32.5 nanometer metal pitch evidence that DUV lithography still has meaningful life left? Or does the added cost and complexity prove that this approach is approaching its practical limit? Let me know your position in the comments. And if you want more grounded breakdowns of the machines, materials, and hidden engineering choices shaping the semiconductor industry, subscribe to Eastern Engine, because sometimes the most important part of a processor is not the feature advertised on the box. It is the wire buried at the very bottom of the chip. For years, whenever people talked about the global chip race, the conversation almost always started with NVIDIA. Everyone wanted the fastest AI processors. Everyone wanted the most powerful GPUs. And for a while, it seemed like whoever controlled AI chips would control the future. But something unexpected happened. The biggest bottleneck wasn't the processor anymore. It was memory. Every AI model, every data center, every cloud server, and every supercomputer depends on enormous amounts of DRAM memory just to keep information flowing fast enough. Without it, even the world's most advanced AI chips spend valuable time waiting for data instead of processing it. In other words, the world's most expensive AI chips become dramatically less useful if they don't have enough memory beside them. And that's exactly why one Chinese company has suddenly become one of the most closely watched semiconductor companies on Earth. Its name is Changshin Memory Technologies, better known as CXMT. Until recently, most people outside China had never even heard of it. Now investors are preparing for what could become Asia's biggest IPO of 2026, raising at least 57.9 billion yuan, or roughly $8.6 billion, with the amount potentially climbing to more than 66 billion yuan if additional shares are sold. The company has already become the world's fourth largest DRAM manufacturer, reaching roughly 7.7% global market share in 2025, and plans to use the new capital to expand production and upgrade its technology. That's a remarkable rise for a company that, just a few years ago, barely registered on the global semiconductor map. Even more surprising, this isn't happening during a weak market. It's happening while demand for memory is exploding. Artificial intelligence is changing everything. Training larger AI models requires enormous amounts of memory. Running AI assistants, cloud platforms, recommendation systems, autonomous vehicles, and enterprise software requires even more. Every new AI server installed around the world needs massive quantities of DRAM, turning memory chips into one of the hottest commodities in the semiconductor industry. That surge in demand has pushed memory prices higher and created an opportunity that companies around the world are racing to capture. For decades, the global DRAM market has been controlled by just 3 companies: Samsung, SK Hynix, and Micron. Together, they built an industry that many believed would remain almost impossible for newcomers to enter. The costs are enormous, the technology is incredibly complex, and catching up can take years. Yet somehow, CXMT has managed to grow from a domestic Chinese project into a company that investors now believe could become one of the semiconductor industry's biggest long-term challengers. That doesn't mean it's already ahead of Samsung or Micron. It still trails the leaders in the most advanced memory technologies, particularly high-bandwidth memory used in cutting-edge AI systems. But its growth has been rapid enough that the established leaders are paying close attention. So, how did a company that almost nobody talked about become one of the biggest stories in the semiconductor world? And why are investors suddenly treating memory chips as one of the most important technologies in the entire AI revolution? Because this story isn't really about one IPO, it's about the next battlefield in the global AI race. To understand why CXMT is suddenly making headlines around the world, you first have to understand something that most people never think about. Memory isn't storage. A lot of people confuse DRAM with SSDs or hard drives, but they're completely different. Storage is where your files stay after you turn your computer off. Memory is where everything happens while your computer is actually working. Think of it like this. If your processor is the brain, then memory is the desk. The larger and faster the desk is, the more information the brain can access instantly. If the desk is too small, the brain spends most of its time reaching into filing cabinets instead of actually working. That's exactly what happens inside AI systems. When ChatGPT answers a question, when an AI generates an image, when a self-driving car recognizes a pedestrian, or when a cloud server handles millions of users, every calculation depends on enormous amounts of memory moving data back and forth at incredible speeds. In fact, today's AI servers don't just use one memory chip. They use dozens, sometimes hundreds. Without enough DRAM, even the most powerful AI processor becomes a bottleneck because it spends too much time waiting for information instead of processing it. That's why companies building AI infrastructure aren't just buying GPUs anymore. They're buying memory as fast as manufacturers can produce it. And demand has become so intense that analysts now describe memory as one of the biggest constraints on AI expansion. Prices have risen sharply, manufacturers are expanding capacity, and AI servers are consuming a growing share of global DRAM production. For decades, this wasn't much of a competition. 3 companies controlled almost everything: Samsung, SK Hynix, and Micron. Together, they built an industry so advanced that many believed nobody else could realistically catch them. Building a modern memory company isn't like opening another electronics factory. It requires billions of dollars, years of research, extremely complex manufacturing. Technology companies suddenly needed more memory. Cloud providers expanded their data centers. Governments invested in AI infrastructure. Tech giants raced to build larger and larger models. And something unexpected happened. Instead of having too much memory on the market, the world suddenly didn't have enough. Rather than flooding the market with cheap chips, manufacturers found themselves trying to keep up with orders. Analysts now expect AI demand to keep memory markets tight well into the coming years, especially for server applications. That's where China saw an opportunity. For years, Beijing invested heavily in building a domestic semiconductor industry. The goal wasn't simply to manufacture more chips, it was to reduce dependence on foreign suppliers. Processors, memory, manufacturing equipment. Every part of the supply chain became a strategic priority. Most of those investments happened quietly. While headlines focused on Nvidia, Apple, TSMC, or Samsung, Chinese companies kept expanding behind the scenes. One of them was CXMT. At first, almost nobody outside China paid much attention. It wasn't competing for the world's fastest AI chips. It wasn't making flashy announcements. It was focused on something much less glamorous: DRAM. But as AI transformed the semiconductor industry, that quiet strategy suddenly became incredibly valuable. Because in the AI era, it's no longer enough to build the fastest processor. You also need enough memory to feed it, and that's exactly where China's biggest memory company found its opening. In just a few years, CXMT went from being a relatively unknown domestic manufacturer to becoming the world's 4th largest DRAM supplier, a rise that surprised much of the industry and set the stage for one of the biggest technology IPOs of the year. So how does a company go from being virtually unknown to becoming one of the biggest stories in the semiconductor industry? The answer wasn't one revolutionary invention, it was years of steady expansion. CXMT was founded in 2016 with a simple but ambitious mission: build a domestic DRAM industry in China. At the time, that goal sounded almost impossible. The memory market had already been dominated for decades by Samsung, SK Hynix, and Micron. These companies had spent billions refining their manufacturing processes, shrinking transistors, improving yields, and scaling production to levels few competitors could match. Breaking into that club wasn't supposed to happen. Yet while much of the world's attention remained focused on AI processors, CXMT quietly concentrated on manufacturing. It expanded fabrication plants, hired engineers, improved production yields, introduced newer generations of DRAM, and perhaps most importantly, it kept increasing capacity. That steady approach is exactly why the company now finds itself in a position few people expected. According to Reuters, CXMT has already grown into the world's fourth largest DRAM manufacturer, holding roughly 7.7% of the global market by the end of 2025. That's still well behind the industry's biggest players, but it's a remarkable leap in less than a decade. Now the company is preparing for another massive step. Its upcoming IPO isn't just about raising money, it's about accelerating growth. Reports indicate the listing could raise around 58 billion yuan, with the potential to reach more than 66 billion yuan if additional shares are sold. That would make it one of Asia's largest technology offerings this year. The funds are expected to support new production lines, manufacturing upgrades, and continued research into more advanced memory technologies. And that's happening at almost the perfect time, because the memory industry itself is changing. For years, memory chips followed a familiar cycle. Demand would rise, companies would expand production. Eventually, the market would become oversupplied. Prices would collapse. Manufacturers would cut output. Then the cycle would repeat. But AI is changing that pattern. Today's data centers consume vastly more memory than traditional servers ever did. A single modern AI server can require many times more DRAM than previous generations because it has to feed enormous AI accelerators with a constant stream of data. That means demand isn't coming from one company. It's coming from nearly everyone. Microsoft, Amazon, Google, Meta, Alibaba, Tencent, countless cloud providers and enterprise customers are all investing heavily in AI infrastructure. And every one of those systems needs memory, lots of it. That's one reason analysts expect DRAM demand to remain unusually strong, even as manufacturers continue expanding production. AI has become one of the industry's biggest growth drivers. But here's where the story gets even more interesting. Despite its rapid growth, CXMT isn't yet competing head-to-head with Samsung or SK Hynix in the most advanced AI memory. The highest-end AI systems rely heavily on HBM, or high-bandwidth memory. That's the ultra-fast memory sitting next to AI processors like NVIDIA's latest accelerators. HBM is one of the most difficult semiconductor products in the world to manufacture. Samsung, SK Hynix, and Micron still lead that market. CXMT's strength today is mainly in conventional DRAM, not cutting-edge HBM. So why is everyone paying attention? Because history has shown that once a semiconductor company masters one generation of technology, the next generation becomes much easier to pursue. Today's mainstream DRAM can become tomorrow's advanced memory. And if CXMT continues expanding at its current pace, the gap separating it from the industry's established leaders could become much smaller than many people expected. That possibility, not an overnight takeover, is what has investors, competitors, and governments watching so closely. But here's the question everyone is asking. If CXMT is growing this fast, should Samsung and Micron actually be worried? The answer is both yes and no. Let's start with the obvious. No company becomes the world's fourth largest DRAM manufacturer by accident. That alone is enough to make competitors pay attention. CXMT has already proven it can manufacture memory chips at scale, expand production quickly, and win customers inside one of the world's largest technology markets. And that market just happens to be China. Think about that for a moment. China isn't just building more AI. It isn't just building more data centers. It also happens to be one of the world's biggest consumers of semiconductors. Every smartphone, every laptop, every server, every electric vehicle, every AI data center, every industrial robot, they all need memory. If more of that demand can be supplied by a domestic manufacturer, that's a significant shift in itself. Instead of importing every memory chip from overseas, Chinese technology companies now have another supplier growing right at home. That doesn't mean foreign companies disappear overnight. Samsung, SK Hynix, and Micron remain among the most advanced memory manufacturers in the world. But every percentage point of market share matters in an industry worth tens of billions of dollars. Losing even a small portion of future demand can have a noticeable impact over time. And that's exactly why investors are paying so much attention to CXMT's expansion. This isn't just another semiconductor company opening another factory. It's a company increasing production during one of the strongest memory markets in years. Analysts expect AI infrastructure spending to continue driving DRAM demand, with cloud providers investing billions into larger AI clusters and new data centers. That means manufacturers capable of increasing output could benefit from sustained demand rather than a short-lived boom. But there is another reason this story matters. Competition changes everything. For years, the memory market was controlled by only a handful of companies. That limited competition, limited supply, and sometimes contributed to higher prices. If another major manufacturer continues growing, the entire industry becomes more competitive. Customers gain another option. Supply chains become more diversified. Pricing dynamics begin to change. That's why this story reaches far beyond China. It's about how the global semiconductor market itself could evolve. Of course, there are still major challenges ahead. The most profitable part of the AI memory market isn't standard DRAM. It's high bandwidth memory, or HBM. HBM is the specialized memory used alongside the world's most powerful AI accelerators. Manufacturing it requires extremely advanced packaging technologies, precise engineering, and years of experience. That's where Samsung, SK Hynix, and Micron still hold a significant advantage. In fact, SK Hynix remains the dominant supplier of HBM for many of NVIDIA's flagship AI systems, while Samsung and Micron are also investing heavily to expand their next-generation memory production. So despite all the excitement surrounding CXMT, the company still has important technological milestones to reach before it can compete across every segment of the memory industry. But history shows that semiconductor industries rarely stand still. World's biggest memory companies aren't ignoring CXMT anymore. Because whether it takes 5 years, GPU, who could build the biggest AI model? Who would dominate artificial intelligence? But today, the conversation is much bigger. Because AI isn't powered by processors alone. It needs memory, massive amounts of it. And as AI systems become larger and more powerful, memory is becoming just as important as the chips doing the calculations. That's exactly why companies like CXMT are suddenly attracting so much attention. The company hasn't replaced Samsung, it hasn't overtaken Micron, and it certainly hasn't won the memory race. But it has done something almost as important. It has proven that China is no longer just trying to participate in the global memory industry. It's becoming one of its biggest players, with billions of dollars expected from its IPO, rapidly expanding production, and demand fueled by the AI boom. CXMT is entering the next stage of its growth, at a time when the world needs more memory than ever before. Whether it eventually catches today's industry leaders remains to be seen. Samsung, SK Hynix, and Micron still have enormous technological advantages, especially in the most advanced AI memory, but competition is increasing. And history has shown that industries can change much faster than people expect. Just a decade ago, few believed Chinese electric vehicle companies would challenge the world's biggest automakers. Today, they're competing across global markets. Now, many analysts are wondering whether the memory industry could follow a similar path. One thing is already clear: the next battle in the AI revolution won't be fought only with faster processors. It will also be fought with faster, larger, and more efficient memory. And if current trends continue, CXMT may become one of the companies helping shape that future. The AI race is no longer just about who builds the smartest chip. It's also about who can keep that chip fed with enough memory to unlock its full potential. And that may end up changing the semiconductor industry in ways very few people expected. If you enjoyed this video, don't forget to like, subscribe, and let us know in the comments. Do you think China can eventually challenge Samsung and Micron in the global memory market, or will the current leaders stay on top?
Okay, so let me ask you, you said something recently that was quite provocative. You said that China was winning the AI race, the AI competition. I know that you've got a powerful, competitor in Huawei, and Huawei has a lot of advantages you don't have. Why don't you describe this?
In March 2026, an engineer walked onto a stage in Shenzhen and held up a single card, small enough to fit in one hand. Then he said the number out loud: 1.56 petaflops. If that means nothing to you, here's the translation. That is roughly 1.5 quadrillion AI calculations every second, about the muscle of 150 high-end laptops, compressed into a slab of hardware the size of a paperback book. And according to Huawei, that single card is close to 3 times more powerful than the best AI chip the company was previously able to get its hands on for the Chinese market. But the performance number, as wild as it sounds, is not actually the story.
Competition. Are we really losing?
It was a very good headline.
It was a great headline, yeah.
And it apparently caught a lot of attention. As you know, with headlines, the disclaimer part, the foundation part, was left out of the headline.
The story is what's hiding underneath that chip, and why it just exposed a weakness in the most dominant company in artificial intelligence that almost nobody was talking about out loud. Because for years, one company has effectively owned AI. Not most of it, almost all of it. And the assumption everyone made was that its position was untouchable, that there was simply no way around it. This chip is the first real crack in that assumption. By the end of this video, you'll understand exactly what it does, how it was built when every rule said it couldn't be, and why the part that should make NVIDIA nervous isn't the speed at all. Let's get into it. To understand why this matters, you first have to understand the chip this thing was designed to kill. When export restrictions tightened on advanced semiconductors heading into China, NVIDIA, the company that supplies the overwhelming majority of the world's AI chips, was put in an awkward position. It couldn't sell its best hardware into one of its biggest markets, so it built a special, deliberately weakened version specifically for China, a chip known as the H20. The whole point of the H20 was to be a ceiling, powerful enough for everyday tasks, but intentionally held back so it couldn't be used to train the largest, most ambitious AI models. It was a compromise, enough to keep selling into China, but not enough to let Chinese companies reach the frontier. And the expectation was that this ceiling would hold for years. Huawei's new chip didn't just bump against that ceiling. According to the specs Huawei presented, it blew straight through it. The company claims its single card delivers nearly 3 times the throughput of that limited H20, carries a massive pool of high-speed memory, and, here's the part that made executives sit up, sits at roughly the same price point Chinese companies were already budgeting for the American chip it's now meant to replace. Same price, far more power, no restrictions. You can already guess what happened next. Within weeks, China's biggest technology companies, the Alibabas, Tencents, and ByteDances of the world, reportedly started placing bulk orders. Huawei's AI chip business, which was already growing fast, is now projected to balloon further in 2026. That alone would be a big story, a new challenger, undercutting the dominant player in its own backyard. But it's not the story, because the truly remarkable thing isn't how fast this chip is. It's that by every conventional rule of how advanced chips get made, it should not exist at all. Here's something most people never think about when they hear the word chip. A modern AI accelerator isn't made by one company in one place. It's the end product of a global supply chain so specialized that only a tiny handful of companies on Earth can even participate in it. Picture an assembly line that stretches across multiple continents. The most advanced processors are manufactured in Taiwan, using almost unimaginably complex machines built by a single company in the Netherlands. Machines that cost hundreds of millions of dollars each and that nobody else on the planet knows how to build. The ultra-fast memory that feeds those chips comes from 2 companies in South Korea. Pull out any single link in that chain, and the conventional wisdom has always been simple. You cannot build a competitive AI chip without it. China was cut off from essentially all of those links at once. No access to the most advanced manufacturing machines. So Huawei's manufacturing partner had to use older equipment, a generation behind, with lower yields and bigger chips for the same performance. By every spreadsheet in every Western tech company, the conclusion was identical and confident. You cannot get there from here. And then Huawei did something that genuinely wasn't supposed to be on the table. They didn't just work around the manufacturing problem, they tackled the memory problem too, by building their own from scratch. This is the detail that deserves a second of your attention. That fast memory I mentioned, the kind that comes from those 2 South Korean companies, Huawei says it developed its own version, in-house from the ground up. Not licensed, not borrowed, not a copy of someone else's design. A proprietary memory standard, engineered inside China, tuned specifically for the messy, irregular data patterns that large AI models throw at hardware. Think about what that means. Practically every AI chip, in practically every data center, in practically every country, relies on memory from those same 2 suppliers. According to Huawei, this one doesn't. The processor, the memory, the connective fabric that ties it all together. For the first time, the whole thing is sourced domestically. The closest comparison I can think of is this. Imagine someone confiscates every machine shop, every specialized supplier, and every blueprint you'd need to build a jet engine. And then you build the jet engine anyway, out of parts you had to invent yourself, and it actually flies. That's roughly the scale of what's being claimed here. But even the hardware isn't the most important part of this story. The thing that should genuinely worry NVIDIA is something you can't hold in your hand at all. Here's what most people get completely wrong about NVIDIA's dominance. They think it's about the chips. It isn't, or at least not only. NVIDIA's deepest, strongest, most defensible advantage is something called CUDA. Let me explain why that's the real story, because this is the actual weakness in the title, and it cuts both ways. CUDA is NVIDIA's software layer. It's the bridge that sits between the physical chip and the AI models that run on top of it. And over more than a decade, virtually every major AI model in existence, the famous chatbots and assistants you've heard of, was written to run on CUDA. The entire ecosystem of AI development grew up speaking CUDA's language. That's NVIDIA's true moat. It was never just that the chips were fast. It was that switching away from them was almost unthinkable. Moving your AI work off CUDA isn't like swapping out a part. It's like deciding to rewire an entire building while people are still working inside it. The cost, the risk, the time. For years, that was enough to keep everyone locked in. Most analysts assumed that lock would hold China back on the software side for years, even if the hardware caught up. This is the weakness the title is talking about. NVIDIA's greatest strength, that everything depends on its software, is also its single biggest vulnerability. Because a dependency that's strong is exactly the kind of thing a determined competitor will spend everything to break. And in 2026, someone tried. A Chinese AI company released a new frontier-class model and made a striking claim about it, that it was built with no NVIDIA dependency anywhere in its stack, not trained on NVIDIA chips, not optimized for CUDA. Instead, its engineers reportedly spent months rewriting the deepest, most technical layers of their software to run natively on Huawei's hardware, using Huawei's own alternative to CUDA. If that holds up the way it's described, it's genuinely significant, because it means the unthinkable rewiring job, the one everyone assumed was too painful to ever attempt, somebody just attempted it. And the building still had the lights on at the end. Now step back and look at the whole picture, because this is where it stops being about a single product. Stack it up. The chip is domestically made. The memory is domestically developed. The software framework that runs it is domestically built. And now a frontier AI model has reportedly been trained and deployed on top of all of it. For the first time, you have a complete AI system, from the raw silicon all the way up to the finished model, built without relying on the usual handful of irreplaceable suppliers. That's the thing that's actually new here. Not a chip, a whole parallel ecosystem. And the numbers around NVIDIA's position in China tell the other half of the story. The company's chief executive himself has acknowledged that its sales into China effectively collapsed, going from dominating the market to almost nothing in a remarkably short window. That's not a rumor or a projection. That's the company's own leadership, describing a market worth tens of billions of dollars largely slipping away, and being candid that it may not come back. Here's the irony at the center of all this, and it's worth sitting with. The restrictions were designed to do one specific thing: slow China's AI progress by cutting off the tools, the memory, and the chips. The logic seemed airtight: no advanced hardware, no advanced AI. What appears to have happened is closer to the opposite. In a span of roughly 18 months, the world's largest AI chip market went from near total reliance on NVIDIA to building a homegrown alternative across the entire stack. Not because any restriction was lifted, but precisely because it wasn't. Every barrier that was meant to be a wall ended up functioning more like a blueprint. It told Chinese companies exactly which capabilities they had to develop themselves, and gave them an enormous guaranteed domestic market to sell into once they did. That's a pattern worth recognizing, because it shows up again and again in the history of technology. When you cut a determined, well-funded player off from something, you don't always stop them. Sometimes you just force them to build their own version, and once they do, they never need yours again. Now, I want to be straight with you here, because I'd rather give you the real picture than pure hype. And there's a temptation with a story like this to overstate it. This does not mean NVIDIA has been beaten. It hasn't. Globally, NVIDIA is still the dominant force in AI by an enormous margin, and its newest chips are still, by most measures, ahead of what Huawei can currently produce. Huawei's approach involves real trade-offs. Older manufacturing means bigger, hotter, less efficient chips and lower production yields, which makes scaling up genuinely hard. Many of the most eye-popping specifications here come from Huawei's own announcements, not from independent testing. So a healthy amount of "let's see it proven at scale" is warranted. So the accurate framing isn't "China crushed Nvidia." It's something more interesting and, honestly, more important. China demonstrated that Nvidia's position is not unbreakable. The moat everyone assumed was permanent turned out to have a crossing point. That's the weakness that got exposed. Not that Nvidia is weak today, but that its single greatest advantage, total dependency, can be escaped if someone wants it badly enough and is willing to spend years and billions to do it. And that's a different world than the one we were in 2 years ago. 2 years ago, there was one AI hardware ecosystem, and everyone lived in it. Now there appear to be two, one centered on Nvidia, one centered on Huawei, developing in parallel on opposite sides of the Pacific. And the gap between them, which was supposed to be widening, looks like it might actually be narrowing. Zoom all the way out, and here's why this matters beyond the corporate scoreboard. AI is rapidly becoming the foundation that everything else runs on. The models behind search, software, medicine, science, defense, and the tools millions of people now use every day. And the hardware those models run on is the foundation beneath that foundation. Whoever controls the chips and the software ecosystem effectively sets the terms for the entire industry built on top. For the last decade, that control was concentrated in one place, with one company. A single ecosystem, a single set of rules, a single point of dependency for the whole world. What this chip represents, whatever you think of the politics around it, is the emergence of a genuine second option. And in technology, a second option changes everything. It drives competition. It pushes prices down. It forces the incumbent to move faster. And it means no single company gets to dictate the future entirely on its own terms. That's the real headline. Not that one chip is fast, but that the most locked-in, most dependent corner of the entire tech world just proved it has an exit, and somebody walked through it. Here's my honest opinion, for what it's worth. What I find most fascinating about this isn't the hardware specs, which we'll all be debating for months as real-world tests roll in. It's the strategic lesson buried inside it. The whole effort to contain China's AI ambitions rested on one assumption: that certain pieces of technology were simply too hard to replicate, that the supply chain was too specialized to ever be rebuilt from scratch. This chip is a direct challenge to that assumption, and whether or not every claim about it holds up perfectly, the bigger trend is undeniable. A second, fully independent AI ecosystem is taking shape, and that genuinely reshapes the next decade of computing. I think the people who dismiss this as just propaganda and the people who treat it as Nvidia is finished are both wrong. The truth is in the uncomfortable middle. Nvidia is still ahead, but its position is no longer guaranteed, and that single fact changes the entire game. Here's the question I genuinely want your take on, and be honest, because people get heated about this one. Is it a good thing that the AI world is splitting into two competing ecosystems, because competition makes everyone build better and cheaper? Or is it dangerous to have the most powerful technology on Earth fragmenting into two separate camps that don't depend on each other at all? There are real arguments on both sides. Where do you land? Drop it in the comments. If you enjoy these deep dives that get underneath the headlines and explain what's really happening before the rest of the world catches on, subscribe to Eastern Engine and turn on notifications. We break down the chips, the breakthroughs, and the strategic moves that decide who leads the next decade of technology. And there's a lot more coming. Thanks for watching. I'll see you in the next one. For decades, 3 companies have controlled almost the entire global market for computer memory: Samsung, SK Hynix, and Micron. Their chips sit inside smartphones, laptops, gaming computers, servers, and artificial intelligence data centers. Now, a Chinese manufacturer founded only 10 years ago is preparing an expansion that could change that balance. Changxin Memory Technologies, better known as CXMT, is expected to add roughly 85,000 wafer starts per month of new DRAM manufacturing capacity during 2026. Samsung is expected to add around 15,000. That means CXMT could install more than 5 times as much new wafer capacity as Samsung this year, not 5 times as much total production. Samsung remains far larger, but in terms of new capacity being added during 2026, China's leading DRAM producer is moving faster, and CXMT is preparing to raise another 29.5 billion yuan, approximately $4.3 billion, through one of the largest technology IPOs ever attempted on Shanghai's star market. The money is expected to support production expansion, research, and the development of more advanced DRAM, including memory designed for artificial intelligence. This is arriving at an extraordinary moment. AI data centers are consuming memory faster than manufacturers can comfortably supply it. Memory prices have risen. Samsung, SK Hynix, and Micron are earning enormous profits. And CXMT's revenue reportedly increased more than sevenfold in the first quarter of 2026. But rapid expansion does not automatically make CXMT a technological equal to Samsung. The Chinese company is still behind in advanced high-bandwidth memory. Its manufacturing efficiency, product mix, and total output remain smaller. And increasing wafer capacity during a memory shortage can be highly profitable, or extremely dangerous if demand weakens before the new factories are ready. So is CXMT becoming a genuine fourth global memory giant, or is it expanding at the most expensive point in a historically unstable industry? Why memory has become the new AI bottleneck? When people discuss artificial intelligence, most attention goes to processors. NVIDIA GPUs, custom accelerators, massive clusters filled with computing power. But a processor is useful only when it can receive data quickly enough. Every AI accelerator needs memory to hold model weights, temporary calculations, instructions, and the information moving between layers of a neural network. If memory cannot deliver that data fast enough, the expensive processor waits. That waiting time is one reason memory bandwidth has become so important. Traditional DRAM serves as the working memory inside computers. It stores information that processors need immediately. Unlike an SSD, DRAM is extremely fast, but it loses its contents when power is removed. A modern server may contain hundreds of gigabytes or several terabytes of DRAM. An AI cluster can contain thousands of servers. Multiply that memory across an entire data center, and demand becomes enormous. AI is also increasing demand for a specialized form of DRAM called high bandwidth memory, or HBM. HBM stacks multiple memory dies vertically and places them close to an AI processor. Thousands of tiny connections move data between the layers and the processor at extremely high speed. But HBM is difficult to manufacture. It requires advanced DRAM dies, precise stacking, specialized packaging, and strong control over heat and yield. Producing more HBM can also consume manufacturing capacity that could otherwise make conventional server, smartphone, or computer memory. This creates pressure across the entire market. As the established manufacturers redirect advanced production toward profitable AI products, supplies of standard DRAM can tighten. That is the opening CXMT is trying to exploit. The Chinese company that appeared almost from nowhere. CXMT was established in 2016. That makes it extremely young compared with its major competitors. Samsung has manufactured semiconductors for decades. SK Hynix traces its history through several older Korean memory companies. Micron was founded in the 1970s. DRAM is one of the hardest semiconductor markets to enter. Each memory cell must store a reliable electrical charge while occupying as little silicon as possible. Factories must produce enormous volumes, because memory is usually sold as a standardized product. A small difference in manufacturing yield can determine whether a company makes money or loses billions. CXMT initially focused on providing China with a domestic source of conventional DRAM. Its early products trailed the leading manufacturers in density, power efficiency, and process technology. But the company continued expanding. It introduced newer generations of DDR memory for computers and servers. It moved into low-power LPDD, our products used in mobile devices. And it gradually increased production inside large 300mm wafer fabrication plants. By the fourth quarter of 2025, estimates placed CXMT at nearly 8% of global DRAM revenue. In the first quarter of 2026, Counterpoint estimated its share at approximately 8%. Samsung remained the leader with around 38%. SK Hynix held close to 29%, while Micron remained another major supplier. CXMT was still far behind the top three, but it had clearly separated itself from the industry's smaller manufacturers and established itself as the world's fourth largest DRAM supplier. The gap remains large. The direction is what matters. What 85,000 wafers per month really means. Semiconductor manufacturing capacity is often measured in wafer starts per month. A wafer start occurs when a blank silicon wafer begins its journey through the fabrication process. Each wafer passes through hundreds or sometimes thousands of manufacturing steps. Thin films are deposited, patterns are printed, materials are etched away, ions are implanted, connections are formed, the wafer is cleaned, measured, and inspected repeatedly. Depending on the chip and process, completing one wafer can take several months. After fabrication, the wafer contains many individual dies. Those dies are tested, cut apart, and packaged into usable memory chips. When analysts say CXMT may add approximately 85,000 wafer starts per month during 2026, they do not mean the company will manufacture only 85,000 wafers during the year. They mean its factories may gain the ability to begin processing roughly 85,000 additional wafers every month once that capacity is operational. That could represent hundreds of millions of additional memory dies over time, depending on die size, process technology, and manufacturing yield. Samsung's estimated addition of around 15,000 wafer starts per month is much smaller, but the comparison needs context. Samsung already operates an enormous installed manufacturing base. It does not need to add as much conventional DRAM capacity to remain larger than CXMT. Samsung is also spending heavily on process upgrades, HBM, advanced packaging, and new facilities whose full capacity may arrive in later years. A company can increase memory output without adding an equal number of wafers. Moving to a more advanced process can place more memory bits on each wafer. Improving yield allows more usable chips to leave the same production line. Changing the product mix can also dramatically alter revenue. So CXMT's 85,000 versus 15,000 comparison is powerful, but it is not a complete measurement of who will produce the most memory. It shows aggression, it does not yet show leadership. Why CXMT is expanding right now? Memory manufacturers have lived through repeated cycles of shortage and oversupply. When demand rises, prices increase. Manufacturers earn large profits and build new capacity. But semiconductor factories take years to construct and equip. By the time production begins, demand may have weakened. Several manufacturers can then bring new supply online at the same time. Prices collapse, profits disappear, investment slows. Then demand eventually recovers and the cycle begins again. AI is making the current cycle unusual. Memory suppliers believe demand from data centers may remain strong for longer than previous consumer electronics booms. Large cloud companies are building enormous AI clusters. Each new generation of accelerator uses more memory. Models are becoming larger. Inference workloads are spreading into more services. Micron has said it expects tight memory supplies to continue through at least 2027. Major manufacturers are signing longer-term agreements with customers that include deposits, minimum purchases, and pricing protections. CXMT is entering this market while prices are high and supply is limited. Its first quarter 2026 revenue reached approximately 50.8 billion yuan, representing a year-over-year increase of more than 700%. The company moved from losses into substantial profitability. Part of that improvement came from increased shipments, part came from better products, but a major factor was the sharp rise in global memory prices. That financial improvement makes an IPO much easier to sell. Investors are no longer being asked to fund only a long-term semiconductor ambition. They are being shown a company generating large revenue during one of the strongest memory markets in history. What the $4.3 billion IPO could fund CXMT plans to raise 29.5 billion yuan through its Shanghai listing. That equals roughly $4.3 billion. The offering would be the largest mainland Chinese IPO of 2026 and the second largest listing in the history of Shanghai's technology-focused star market. For a semiconductor company, $4.3 billion is significant, but it is not unlimited. A modern memory fabrication plant can cost tens of billions of dollars when buildings, cleanrooms, lithography systems, deposition tools, etching equipment, testing systems, and supporting infrastructure are included. CXMT is therefore not building its entire expansion with IPO money alone. The company already has factories, investors, financing, and other sources of capital. The IPO adds another pool of funding. According to its listing plans, the proceeds are intended for manufacturing upgrades, research and development, process improvement, and product expansion. That last category may be the most important. Standard DDR and LPDDR products helped CXMT establish volume. HBM could determine whether it becomes strategically important to the AI market. The HBM gap CXMT's biggest weakness is not basic DRAM capacity. It is advanced memory. Samsung, SK Hynix, and Micron are already producing high-bandwidth memory for leading AI accelerators. SK Hynix became especially successful by investing early in HBM and building a strong relationship with NVIDIA. HBM carries higher margins than ordinary memory, but it also demands better technology. The DRAM dies must be manufactured efficiently. The dies must be thinned. Tiny vertical connections called through-silicon vias must pass signals through the stack. Multiple dies must be aligned and bonded. The final package must remain reliable while transferring enormous amounts of data and operating beside a hot AI processor. One defective die can damage the value of an entire stack. CXMT is investing in an HBM packaging facility in Shanghai and has targeted production by the end of 2026. But starting production is not the same as reaching high-volume manufacturing. It must demonstrate acceptable yields. It must qualify its products with accelerator designers. It must prove long-term reliability. And it must catch competitors that are already moving toward newer HBM generations. This means CXMT's immediate expansion will probably have a larger impact on standard DRAM than on the most advanced AI memory. It may pressure prices in consumer, mobile, and server memory before it seriously threatens SK Hynix in premium HBM. Could CXMT actually hurt Samsung? Samsung is not facing an immediate collapse. It remains the largest DRAM supplier by revenue. It has far more manufacturing experience. It operates advanced process technology, major research facilities, and a global customer network. It also produces NAND flash, processors, image sensors, displays, and complete electronic products. CXMT is much more concentrated, but that concentration can become an advantage. CXMT can focus capital and engineering effort on DRAM. It can compete aggressively in the Chinese market. And it can supply domestic computer, smartphone, server, and accelerator manufacturers that want alternatives to foreign memory. CXMT does not need to defeat Samsung worldwide to create pressure. It only needs to capture enough volume to affect industry supply. Memory products are highly sensitive to small differences between demand and production. If the world needs 100 units of DRAM and manufacturers produce 98, prices can rise quickly. If they produce 105, prices can collapse. An extra few percentage points of supply can change profitability for every company in the market. Semi-analysis expects the DRAM market to remain undersupplied even after accounting for CXMT's expansion. But the expected shortage does not last forever. Capacity being installed now may influence prices in 2027 and 2028. If AI demand continues rising, the new supply could be absorbed. If AI investment slows, CXMT's expansion could arrive just as the market becomes oversupplied. What this could mean for consumers. For buyers of computers, servers, and smartphones, more competition is generally positive. Additional supply can reduce shortages. It can provide device manufacturers with more negotiating power. It may eventually lower the price of DDR5 modules, laptop memory, and server DRAM. CXMT manufactured chips have already appeared in memory products sold under recognizable international brands. That does not necessarily mean those brands have committed to CXMT for every model or every market. Memory module manufacturers frequently source chips from different suppliers depending on price, availability, and qualification. But it shows that CXMT is no longer restricted to experimental or purely domestic products. Its chips can enter commercial supply chains when they meet the required specifications. The question is whether the company can maintain performance and reliability while rapidly increasing output. Expanding too quickly can create yield problems. New production lines require trained workers. Equipment must be calibrated. Processes must remain consistent across multiple factories. A chip that works in one small production run must continue working when millions are produced every week. Scale exposes weaknesses that laboratory demonstrations can hide. The biggest risks. CXMT faces three major risks. The first is technology. Adding wafer capacity is valuable only if the products are competitive. A less advanced process may produce fewer memory bits per wafer and consume more power. That can make apparently large manufacturing capacity less productive than a smaller but more advanced factory. The second risk is the market cycle. CXMT is investing during a period of exceptional memory prices. Those prices helped create its recent profits. If supply catches demand and pricing falls, the financial picture could change rapidly. The third risk is execution. Semiconductor expansion is not simply a construction project. Factories need complex tools, materials, software, replacement parts, and skilled engineers. Any bottleneck can delay production, and advanced DRAM requires constant process improvement. Samsung, SK Hynix, and Micron will not remain still while CXMT expands. They are investing in denser DRAM, more efficient manufacturing, and newer generations of HBM. CXMT is chasing moving targets. My take is that the 5x number is not proof that CXMT has overtaken Samsung, but it may be evidence of something more important. China is no longer treating domestic DRAM as a small backup industry. It is building for global scale. CXMT already holds a meaningful share of the market. Its revenue has accelerated. Its factories are expanding. Its IPO could provide another $4.3 billion for manufacturing and research, and it is beginning the difficult move from conventional memory toward HBM. Samsung remains larger. SK Hynix remains stronger in high-end AI memory. Micron remains deeply connected to major American technology companies, but the memory industry may no longer be a permanent three-company market. CXMT is becoming a fourth participant capable of influencing supply, prices, and investment decisions. The most important test will not be how much money the IPO raises. It will be what comes out of the factories afterward. Can CXMT convert 85,000 additional monthly wafer starts into reliable competitive memory? Can it improve yields while increasing volume? Can it manufacture HBM at scale? And can it remain profitable when today's memory shortage eventually ends? If the answers are yes, Samsung, SK Hynix, and Micron will face a competitor with domestic scale, strong financial backing, and one of the fastest capacity expansions in the industry. If the answers are no, CXMT could discover the same lesson that has punished memory manufacturers for decades. Building capacity is easy compared with filling it profitably. So what do you think? Is CXMT on its way to becoming the world's fourth true memory giant? Or is it expanding too aggressively during a temporary AI-driven shortage? Let me know your view in the comments, and subscribe to Eastern Engine for more grounded coverage of the chips, factories, and engineering breakthroughs changing the technology industry. Because China is not adding 5 times Samsung's total memory production, but it may be adding more than 5 times as much new wafer capacity this year. And in an industry where a small shift in supply can move the entire market, that difference could matter far more than it first appears. It is the largest power station ever built, a wall of concrete stretching more than 2 kilometers across the Yangtze River, holding back a reservoir that runs for hundreds of kilometers behind it. It can generate more electricity than any other single structure on Earth, and its construction required relocating well over 1 million people. The Three Gorges Dam is, by almost any measure, one of the most ambitious engineering projects in human history. But for years, it has also been the subject of persistent questions about the quality of its construction, about its effect on the region's environment, about sediment piling up behind it, and about whether the enormous benefits it provides come with risks that have never been fully accounted for. Critics have even given it a nickname that is stuck: a tofu dread project, a Chinese phrase used for construction work that looks solid on the surface but is allegedly poorly built underneath. So how much of this is genuine concern, and how much is exaggeration? Today we are going to walk through the real debate around the Three Gorges Dam, the documented concerns, the official responses, what has been verified, and what hasn't. Because the truth here is more complicated and more interesting than either side usually admits. Let's start with the scale of what we're actually talking about. The Three Gorges Dam sits on the Yangtze, China's longest river and one of the largest in the world. Construction officially began in 1994, and the project came online in stages over the following years, with full power generation reached around 2012. The total cost is generally estimated in the range of tens of billions of dollars, with figures around the 28 to 32 billion mark commonly cited. The dam was built with 3 primary goals. The first was flood control. The Yangtze has a long and devastating history of flooding, with major floods in the 20th century alone killing enormous numbers of people. The dam's reservoir was designed to absorb floodwaters and release them in a controlled way, protecting cities downstream. The second goal was power generation. The dam's turbines produce a massive amount of clean electricity, displacing what would otherwise be generated by burning coal. And the third was improved navigation, allowing larger ships to travel further up the river through a system of locks. On those headline goals, the dam has delivered real results. It generates an enormous quantity of carbon-free electricity every year, and it has been credited with moderating several flood events on the Yangtze. These are genuine achievements that any fair assessment has to acknowledge. But the scale that makes the dam impressive is also exactly what makes its critics nervous. When a structure is this large and holds back this much water, the consequences of anything going wrong are correspondingly enormous. And that is where the controversy begins. The most attention-grabbing criticism of the dam concerns the quality of its concrete. During construction, the project poured concrete at a record-setting pace. In one peak year around 2000, the volume of concrete placed was several times what the famous Hoover Dam required across its entire construction. Pouring concrete that fast creates a genuine engineering challenge, because as concrete cures, it generates heat, and if that heat isn't managed carefully, the material can develop internal stresses, cracks, or voids as it expands and contracts. The Hoover Dam famously solved this problem by mixing its concrete with chilled water and running cooling pipes through the structure to control the temperature as it set. Critics of the Three Gorges project have alleged that, in the rush to set records and meet deadlines, similar temperature control measures were not applied as rigorously as they should have been, and that this led to cracking and voids in parts of the structure. These concerns are not purely the invention of outside critics. Some of the people involved in the project's own quality inspection process raised flags during construction. There are documented references to inspection teams finding surface defects, cracks, and seepage in certain areas, particularly around the ship lock system, where teams reportedly found voids in the concrete during the early 2000s. Internal correspondence from quality reviewers described the overall quality at the time using cautious, hedged language rather than glowing approval. Here's the crucial context that often gets left out, though. According to the same engineering records, those defects were identified and then remediated. Reports document that water-seeping cracks in the lock system, totaling thousands of meters in length across hundreds of instances based on mid-2000s surveys, were subsequently repaired to meet design requirements. In other words, the concerns were real, but they were also addressed through ongoing maintenance and repair, which is, to be fair, a normal part of operating any massive piece of infrastructure. So the honest picture is this. There were genuine quality concerns during construction, some raised by insiders, and there has been ongoing repair work since. Whether that represents a structure that is fundamentally sound but high maintenance, or one with deeper problems, is the heart of the dispute, and reasonable engineers have landed on different sides of it. In July 2019, a story exploded across the internet. Someone posted satellite images appearing to show the dam visibly warping and bending out of shape, sparking a wave of panic that the structure was deforming and at risk of failure. This is worth examining closely, because it became one of the most widely shared claims about the dam, and it turned out to be misleading. The apparent warping in those images was not real structural deformation. It was an artifact of how certain satellite mapping services process images, automatically stretching and distorting flat imagery to drape it over three-dimensional terrain models. When you look at a long, straight structure laid over uneven terrain in those systems, it can appear to curve even when it is perfectly straight in reality. Other satellite images of the same dam, processed differently, showed no such bending. Chinese authorities responded by stating the dam was operating normally and within its safety parameters, and independent observers who examined the imagery agreed that the viral deformation was an image processing illusion rather than evidence of a failing structure. This episode is important for two reasons. First, it shows how quickly alarming claims about the dam can spread regardless of whether they hold up. And second, it's a useful reminder to treat dramatic claims in either direction with some caution. The dam has genuine, documented issues worth discussing. The 2019 It's Bending panic was not one of them. Beyond the structure itself, some of the most substantial debate concerns the dam's effect on the surrounding environment. And here, the science is genuinely complex and still debated. One area of concern is local climate. After the reservoir filled, the surface area of standing water in the region expanded enormously, by some estimates more than doubling, some in areas that had historically been prone to drought. A NASA-affiliated study using satellite data did examine the reservoir's potential influence on regional precipitation and surface temperatures, and found measurable effects on rainfall in certain areas near the reservoir. However, it's important to be precise here. Attributing specific weather disasters to the dam is scientifically difficult. The same years saw broader climate variability across China and the wider world, and separating the dam's local influence from larger regional and global climate trends is genuinely hard. So while the idea that a reservoir of this size affects its immediate microclimate is plausible and supported by some research, sweeping claims that the dam caused every flood or heat wave in the broader region go well beyond what the evidence can support. Other documented environmental concerns are more clear-cut. Sediment management is a real and ongoing engineering challenge. The Yangtze carries a heavy load of silt, and dams interrupt that natural flow, causing sediment to build up in the reservoir over time. Water quality changes in slow-moving reservoir water are a recognized issue, and there are well-studied concerns about reservoir-induced geological activity, where the immense weight of stored water and fluctuating water levels can increase the frequency of small landslides and seismic events near large reservoirs. These are not unique to the Three Gorges Dam. They are known challenges for major dams worldwide, but the sheer scale here amplifies them. One of the more thought-provoking concerns raised by critics involves not the Three Gorges Dam alone, but the entire system of dams now operating on the Upper Yangtze and its tributaries. Over the years, China has built a series of additional large hydropower stations upstream on the Jinsha River, which feeds into the Yangtze. On one level, this makes engineering sense. Upstream dams can hold back floodwater and trap sediment before it reaches the Three Gorges Reservoir, easing pressure on the main dam. But critics point out a less comfortable implication. Stringing many massive dams along the same river system creates a chain. The concern is that if any single dam in that chain were to fail catastrophically, the sudden release of its stored water could threaten the dams downstream of it in a cascading sequence. It's a low probability but high consequence scenario, and it's the kind of systemic risk that's genuinely worth engineers thinking carefully about. Not because failure is likely, but because the stakes are so high. It's worth stressing that this is a hypothetical risk, not a prediction. Modern dams are built with significant safety margins, and a cascading failure would require an extraordinary chain of events. But the more dams you build on one system, the more the individual structures become interdependent, and that interdependence is a legitimate subject for ongoing safety analysis. Part of what fuels skepticism about the dam is the series of expensive follow-on projects that have been built around it over the years. Projects that critics argue exist partly to manage problems the dam itself created. One example is the bypass system for shipping. Because traffic through the dam's locks can back up significantly, with ships sometimes waiting days to pass, authorities built an over-dam transport route. Goods are unloaded from ships on one side, trucked overland along a dedicated highway, and reloaded onto ships on the other side, bypassing the lock bottleneck. The highway portion alone reportedly cost hundreds of millions of dollars, and that's before adding the upstream and downstream port facilities. Another major project is a large water diversion tunnel, begun in 2022, designed to carry water from the Three Gorges Reservoir area through a nearly 200-kilometer tunnel to the Han River. Officially, this is framed as a follow-up to China's broader water diversion programs, aimed at maintaining water levels downstream. But analysts have noted it also serves another function, giving the dam an additional channel to discharge water during flood conditions, helping relieve the difficult balancing act the dam operators face. When a major flood hits, releasing too much water risks flooding cities downstream, while holding too much back risks flooding cities upstream. An extra outlet gives operators more flexibility in that trade-off. Supporters would frame all of this as sensible infrastructure that maximizes the value of a major asset. Critics frame it as evidence that the original project created cascading problems requiring ever more expensive fixes. Both interpretations describe the same facts, which is often how these debates work. Underlying all of these specific concerns is a deeper debate that goes back to before the dam was ever built. During the project's planning and evaluation in the late 20th century, it was not universally supported, even within China's own expert community. The environmental impact assessment process was genuinely contentious. Some experts argued that the ecological and environmental downsides of the project were serious enough to warrant reconsidering whether it should proceed at all. And there were disagreements about how the official conclusions were ultimately framed. This internal debate is part of the historical record, and it reflects something true about megaprojects everywhere. Enormous infrastructure decisions involve real trade-offs, and reasonable experts can disagree about whether the benefits justify the costs. That tension has never fully gone away. Supporters point to the clean electricity, the flood control, and the navigation improvements as transformative benefits for a country of over 1 billion people. Critics point to the displaced communities, the environmental disruption, the sediment and water quality challenges, and the ongoing maintenance burden, and argue the full costs were understated from the beginning. The most honest assessment is probably that both things are true at once. The Three Gorges Dam is a genuine engineering achievement that delivers real, measurable benefits. It is also a project with real, documented downsides and ongoing challenges that its operators have to manage continuously. Whether the balance comes out positive or negative depends heavily on which costs and benefits you weigh most heavily, and that's ultimately a question of values as much as engineering. Let's come back to the question in the title. Is the Three Gorges Dam facing a new crisis? The responsible answer is, not in the dramatic, imminent collapse sense that sometimes circulates online. The dam has now operated for roughly 2 decades. It has weathered major floods. The viral claims about it physically bending were debunked. There is no credible evidence that the structure is on the verge of failure. What the dam does face is a set of ongoing chronic challenges that don't make for dramatic headlines, but are genuinely significant. Sediment accumulation that worsens over time, environmental effects on the surrounding region, the maintenance burden of a structure built at record-breaking speed, and the systemic questions raised by an entire chain of dams on one river system. These are real engineering and environmental issues that will require attention for as long as the dam exists. So rather than a single sudden crisis, the more accurate picture is a massive piece of infrastructure that delivers enormous benefits while carrying a long tail of complicated, slow-moving problems. Exactly the kind of trade-off that comes with building at this scale. What do you think? Do the flood control and clean energy benefits justify the environmental and engineering trade-offs? Or do you think projects on this scale create more problems than they solve? Let me know your honest take in the comments. This is one of those topics where thoughtful people genuinely land on different sides. And if you found this balanced breakdown useful, consider subscribing so you don't miss the next deep dive into the engineering megaprojects shaping our world. Here's something that sounds completely made up. Over the past few years, China has quietly poured more than $1 billion into glass. Not oil, not rare earth metals, not the next generation of computer chips themselves, glass. And because of that bet, some of the most powerful technology companies on the planet are now scrambling to catch up in a race many of them barely noticed had started. Now, before you assume this is about windows or phone screens, stay with me, because the glass at the center of this story is nothing like anything you've ever held. It's engineered to a level of precision that would have looked like pure science fiction 20 years ago. It's thinner than a human hair, flatter than anything that occurs in nature, and it may turn out to be the single most important material in deciding who controls the next decade of computing power. And here's the strange part. This didn't sneak up on the industry because it was secret. The factories, the patent filings, the investment funds, all of it was public. It just wasn't being watched, because for years, almost everyone obsessed with the global chip race was staring at the exact same thing: transistors. Who could make them smaller? Who could print more of them? Who could reach the next generation first? While that loud, expensive conversation dominated every headline, a much quieter conversation was happening about the layer underneath the chip, the part that holds everything together. And it turns out that layer is now one of the most important battlegrounds in the entire industry. Let's get into why. To understand why glass suddenly matters so much, you first need to understand what it's replacing. Picture a modern city: skyscrapers, subway tunnels, power grids, fiber optic cables threading under every street. You can admire all of it: the architecture, the engineering, the sheer scale. But none of it functions if the ground beneath it shifts. The moment the foundation moves, everything built on top is compromised, no matter how brilliant the design above ground is. A shaky foundation is a problem that no amount of clever work upstairs can ever fully fix. Computer chips have a foundation too. It's called the substrate, the base layer the chip sits on. It holds everything in place, routes electrical signals between components, and helps manage the heat the chip generates while running. For roughly 50 years, these substrates have been made from engineered plastics and resins, layers of synthetic material bonded together into something that, if you could hold it, would resemble a very sophisticated, very thin piece of laminate. Not glamorous. Nobody makes a marketing campaign about it. But it's essential in the same way concrete footings are essential to a building. For most of chip history, plastic was perfectly adequate. Early chips were small, the demands were modest, and the substrate did its job without complaint. The trouble only started when chips became dramatically more complex, and the thing that made them so complex was artificial intelligence. The chips powering today's most advanced AI systems aren't single chips anymore. They're clusters of smaller chips, called chiplets, bundled together into one enormous, densely interconnected package. Engineers build them this way because it lets them combine different types of chips: memory, processing, communication, each optimized for its specific job, into a single unified system that performs far beyond what any one chip could manage alone. It's genuinely brilliant engineering, but it created a problem that gets worse as the systems grow. Some of these chiplet packages now stretch beyond 8,000 square millimeters. Sit with that for a second. That's roughly the size of your phone screen. Now imagine that entire surface packed with billions of microscopic connections, all exchanging data at the same time, at speeds measured in hundreds of gigabytes per second, while throwing off enough heat to shut down a laptop in seconds. At that scale, the substrate underneath stops being a passive holder and becomes one of the most critical performance variables in the whole system. Here's exactly where the trouble shows up. Plastic warps. When a plastic substrate heats up during operation, it expands a little. When the chip powers down and cools, it contracts. That cycle repeats thousands of times over the life of a chip. Each individual movement is almost impossibly small, shifts measured in fractions of a millimeter. But at the scale of a modern AI package, where the connections are so fine they'd make a strand of DNA look like a thick rope, those tiny shifts accumulate into a serious problem. Connections that were perfectly aligned during manufacturing begin to drift. Signals that should travel cleanly start to distort. Performance degrades in ways that are inconsistent and maddening to diagnose. And in the worst cases, connections break entirely and the chip simply fails. The most frustrating part is that you can't see any of it happening. There's no visible crack, no obvious moment of failure. The damage stays invisible right up until the instant it isn't. Engineers fought this for years with clever design tricks, tighter manufacturing tolerances, and ever more sophisticated quality control. Those approaches held up fine while chip packages stayed small and demands stayed low. But the next generation of AI chips is pushing into territory where those patches simply cannot hold anymore. The substrate material itself had to change. And the answer the industry landed on, after years of materials research, failed experiments, and manufacturing breakthroughs, still catches people off guard when they hear it. Glass is such a counterintuitive answer that it's worth pausing on how strange it sounds. Engineers are talking about building the foundation for the world's most powerful AI systems, machines running at extreme speeds, under extreme heat, handling workloads worth billions of dollars, and the solution they're pointing to is, in essence, the same material that gets swept up after a kitchen accident. Except it really truly is not the same material at all. The glass used in next-generation chip substrates is a precisely engineered product developed specifically for semiconductor packaging. It shares the same basic chemistry as window glass, the way a Formula One car shares the same basic idea as a bicycle. Technically related, practically a completely different thing. Here's the clearest way to understand what makes it special. Think about how plastic behaves under heat. It acts like a rubber band. Stretch it, heat it, cool it, and over time it loses its shape and fatigues. It becomes less predictable with every cycle. At small chip sizes, that's manageable. Engineers can design around it. Glass under the same conditions behaves more like a steel rod. You can heat it, cool it, run it through thousands of thermal cycles, load it with mechanical stress, and it barely moves. Its dimensional stability is dramatically better than any plastic currently used in chip packaging. And that stability has a direct, measurable payoff. Because the foundation doesn't drift, engineers can place electrical connections far closer together without worrying they'll fall out of alignment over the chip's lifetime. Here's the number that stops people cold. Glass substrates can support up to 10 times the interconnect density of today's best plastic substrates. Not 10% more, 10 times more. That isn't an upgrade. 10 times more connections in the same physical space means chips that can move data faster, with less energy lost in transit, across greater distances within the package, with cleaner signal quality than anything plastic can offer. And this matters more than it might seem, because the performance of an AI chip isn't determined only by the transistors inside it. It's also determined by how efficiently data moves between the components. If the connections between chiplets are slow, lossy, or limited, the chip underperforms no matter how advanced the transistors are. The substrate is the communication backbone of the entire package. Improve it dramatically, and you improve the whole system dramatically, without ever touching a single transistor. The thermal story reinforces this. Glass distributes heat in ways that make cooling easier as packages grow. Heat is one of the primary limits on any chip. Push it too hard, generate too much heat, and the chip throttles itself to avoid damage. Better heat management means running chips at peak performance for longer. And on signal quality, electrical signals traveling through glass face less interference and less loss than signals through plastic, a difference that compounds into real performance gaps at the data rates these chips run. So why didn't the industry switch to glass a decade ago? Because making it is extraordinarily hard. The glass has to be flat to tolerances invisible to any instrument outside a specialized lab. The holes drilled through it to create electrical pathways, called through-glass vias, are thinner than a human hair and must be placed with perfect precision. Drilling those holes without introducing microscopic cracks that could spread and cause a failure weeks later is a manufacturing challenge that has taken years of dedicated engineering just to approach. That difficulty isn't a footnote. It's the entire reason this story matters, because whoever solves the manufacturing problem at scale controls the next layer of the semiconductor supply chain. For most of the last decade, the dominant story in the global chip race came down to a single machine, the extreme ultraviolet lithography machine, made by a Dutch company called ASML. It's the only machine on Earth capable of printing transistors at the most advanced scales. Without it, you can't make a leading-edge chip. A whole system of export controls was constructed around keeping these machines out of certain countries. The logic seemed airtight. No advanced lithography machine, no advanced chips. What that framing missed is that it was optimized for one specific path to more powerful computing. And that path is not the only path. Advanced packaging, and the substrate layer specifically, is a completely different route. And it doesn't require an ASML machine. It requires materials, science, precision manufacturing, process engineering, capital, and patience. All things that can be developed independently without access to any export-controlled equipment. Seen that way, the decision to pour serious money into glass substrate technology isn't just a technical choice. It's a strategic repositioning toward a part of the supply chain where the rules of the game are fundamentally different. The investment has been substantial. China's national semiconductor funds have been steering capital toward advanced packaging since around 2023. Multiple companies, multiple programs, all targeting glass substrates, the total crossing $1 billion across factories, equipment, patents, and talent. None of it secret. All of it publicly registered. It just didn't generate much Western coverage, because the coverage was fixated on lithography and transistor nodes. The company that brings this strategy into sharpest focus is BOE. BOE is one of the world's largest makers of display technology. The precision glass panels inside hundreds of millions of smartphones, TVs, and monitors every year. Running that business requires large-scale precision glass infrastructure, specialized equipment, deep process knowledge, and engineering talent built up over decades. And here's what makes BOE's move into semiconductor-grade glass so logical. That infrastructure overlaps significantly with what substrate production requires. The equipment is related. The process knowledge transfers. The supply chains are already in place. For BOE, this isn't a reinvention. It's an extension of a capability they already built at massive scale for a different purpose. Their program targets production-capable output running into 2026 and accelerating from there. What makes this approach so effective is the timing. The transition from plastic to glass hasn't happened yet at volume. It's coming. The industry broadly agrees it's coming, but the factories producing glass substrates at scale for major AI chip customers don't fully exist yet. Whoever builds those factories first, solves the yield problems first, and qualifies with the major customers first will gain the kind of first-mover advantage that's almost impossible to dislodge in capital-intensive precision manufacturing. It's the same dynamic that made TSMC the dominant force in chip manufacturing for 2 decades. When TSMC built its lead in the 1990s, it looked incremental. By the time the world realized how dominant it had become, the lead had compounded into something structural. Glass substrates are sitting at an earlier point on that very same curve right now. When a shift this significant gains momentum, the rest of the industry does not stay still, and the response from the United States, South Korea, and Japan has been more serious than most outsiders realize. Intel has the longest track record in glass substrates of anyone in the world. Their program goes back over a decade, which in semiconductor terms is an eternity. In that time, they've built one of the deepest patent portfolios in the field and worked through manufacturing challenges most competitors haven't even hit yet. More recently, Intel has shifted toward licensing, sharing its technology with manufacturing partners rather than trying to control production directly, positioning itself as the intellectual property backbone of the emerging glass ecosystem. Even if others run the lines, Intel captures value from every line built on its technology. It's a bet on being the foundation of the foundation. Samsung is further along in production readiness than most observers appreciate. The company is running an active pilot line at its Sejong facility, not a research project, an actual pilot staffed with engineers hired specifically for glass substrate expertise. In late 2025, Samsung's components arm signed a materials partnership with a major Japanese specialty chemical company to secure the specialized glass the process requires. Their internal roadmap targets commercial-scale production around 2028, which would make Samsung one of the first volume suppliers to major AI chip customers. TSMC controls roughly 90% of the world's advanced AI chip packaging capacity today, a level of dominance that's genuinely hard to overstate. But TSMC understands better than anyone that dominance in this industry is never permanent. In 2024, it revived its glass substrate research program, a clear signal that this technology had graduated from interesting experiment to genuine strategic priority. When TSMC treats something as a priority, the whole industry takes notice. And Corning plays a different but equally important role. Most people know Corning from the protective glass on their phones, but its real expertise is specialty glass across fiber optics, pharmaceuticals, aerospace, and scientific instruments. That depth positions Corning as a potentially critical upstream supplier, the company producing the raw semiconductor-grade glass that substrate makers then process. Its involvement signals that the supply chain needed to support large-scale glass manufacturing is starting to form. And that matters enormously, because a production ecosystem is only as strong as its weakest link. What it all adds up to is a race that is genuinely undecided. No single company or country has locked up the glass substrate market. The infrastructure is being built simultaneously across multiple continents right now. But the window for establishing leadership isn't unlimited. Here's a pattern that shows up again and again in technology history. The most consequential shifts almost never look consequential while they're happening. They look small. They look technical. They look like something that belongs in a trade journal rather than a front-page story. And then, years later, everyone who missed it looks back and sees clearly what they were looking at. They just didn't recognize it at the time. The transition to glass substrates has exactly that quality. The chip race has been fought loudly and publicly for years. Export restrictions, government subsidies, front-page stories about transistor sizes and fab capacity. All of that is real and all of it matters. But it also created a kind of tunnel vision, an intense focus on one layer of the chip that made it easy to overlook what was happening in the layer just below. The substrate is being reinvented right now, and the consequences will ripple through everything that runs on advanced chips. AI training is the most immediate. The models behind today's AI tools are trained on enormous clusters of chips, running for weeks at a time, burning vast amounts of power. Better substrates let those clusters exchange data faster with less energy wasted, which means training runs finish sooner, model development accelerates, and more experiments happen per year. Data centers feel it too. If better substrates let them pack more computing power into the same floor space and run it more efficiently, the economics of AI deployment shift, costs come down, and the technology reaches further into more industries faster. And the cascade goes wider than AI. Drug discovery, climate modeling, materials research, scientific computing across every discipline, all of it runs faster when the foundation improves. These aren't hypothetical benefits. They follow mechanically from the performance gains glass unlocks. Here's the economic reality that makes this window so hard to recover from if you miss it. A single glass substrate production line costs somewhere between $500 million and $1 billion to build, and it takes years to qualify with customers, because chip designers have to validate that the substrate performs reliably at scale before committing their products to it. Whoever reaches volume production first enters that qualification process first. Whoever qualifies first gets the design wins. Whoever gets the design wins accumulates the production experience that pushes yields up and costs down. And there it is again, that compounding loop. Higher yields mean lower cost per unit, which means more competitive pricing, which means more market share, which means more volume, which means more experience, which means higher yields. The loop tightens with every year of production, and companies outside it don't just stay behind, they fall further behind every quarter. It's the exact dynamic that turned TSMC from a scrappy contract manufacturer in the 1980s into the irreplaceable backbone of the global chip industry by the 2000s. Not through any single dramatic breakthrough, but through consistent early investment in a capability that compounded relentlessly until no competitor could replicate it. The Silicon Era, 50 years of progress driven by shrinking transistors, isn't ending, but it's being joined by something new. A second axis of improvement that doesn't depend on making transistors smaller at all. It depends on making the foundation underneath them dramatically better. And the material making that possible is one that's been around for thousands of years. Flat, precise, stable under heat, and invisible to the conversation until, suddenly, it wasn't. The AI era may well be built on glass, and the race to own that foundation is being decided in the years between now and 2028. Not in some distant policy debate, but right now, in factories being built, supply agreements being signed, and patent portfolios most people have never heard of. Here's my honest opinion, for what it's worth. What strikes me most about this story isn't the glass itself. It's how easily the most important shift in an industry can hide in plain sight while everyone argues about something else. The entire world fixated on lithography machines and transistor nodes, built an enormous policy apparatus around controlling them, and meanwhile a parallel path to more powerful computing was quietly being developed in a completely different part of the supply chain, requiring none of the equipment everyone was watching. That's a genuinely fascinating lesson about how technological competition actually works. the decisive move is rarely the one everyone is staring at. I think the next few years are going to reshuffle the hierarchy of the chip industry more than most people expect, and glass substrates are a big reason why. The lead that exists today is real, but it is not locked in. This is still anyone's race, and the companies and countries that take it seriously now are the ones that will shape how it plays out. Here's the question I genuinely want your take on, and be honest, because people get heated about this one. Is it a good thing when one country pulls ahead in a technology this foundational? Or does the world actually work better when no single nation controls the infrastructure everything else depends on? There are real arguments on both sides. Competition drives faster innovation, but concentration creates dependence. Where do you land? Tell me in the comments. If you like these deep dives that get underneath the headlines and explain what's actually happening before the rest of the world catches on, subscribe to Eastern Engine and turn on notifications. We cover the materials, supply chains, and strategic moves that decide who leads the next decade of technology, and there's a lot more coming. Thanks for watching. I'll see you in the next one.
The semiconductor industry is truly the engine room of the global economy. Chips go into everything from your smartphone to your car to massive data centers. And the web of global connections is enormous. ASML in the Netherlands producing the lithography machines that are shipped to TSMC here in Taiwan that manufactures the actual chips using designs from ARM in the UK, Nvidia and Apple. China, the biggest consumer of semiconductors.
Right now, TSMC, Samsung, and Intel are focused on something unexpected, not just smaller transistors or global trade limits, but glass. A super thin sheet of engineered glass is becoming one of the biggest changes the chip industry has seen in years. China has already invested more than $1 billion into this technology as companies race to shape the future of advanced chips. It may sound strange at first. Glass is everywhere, from phone screens to windows, but this new type of glass could completely change how powerful chips are built. That is why major tech companies and governments are paying close attention and investing heavily in it. For decades, the tech world followed one simple rule: make transistors smaller, and devices become faster and smarter. That idea helped create smartphones, cloud computing, AI systems, and modern technology as we know it. But now, in 2026, the industry is running into new limits. Today's advanced AI chips use so much power that even the best current designs are struggling to keep up. Engineers have started running into a major problem, and surprisingly, the issue is not inside the chip itself, it is underneath it. That is where advanced glass technology comes in, and once you see why companies are focusing on it so early, the whole situation makes a lot more sense. Think about a skyscraper. No matter how impressive the design looks, everything depends on the foundation underneath. If the base is weak, the entire building can run into problems. Computer chips work the same way. Every chip sits on something called a substrate, which acts like the foundation that supports everything above it.
On the planet. Just think of all the electronics that China produces, and a country that's also trying to build out its own chip industry, so it's less reliant on the West. And that has put the broader industry in the crosshairs of Washington. They have imposed export controls and tariffs to try to contain China's chip industry. They've also spent heavily to try to ensure there's production and more of it on US soil. Tariffs can only go so far. No company builds chips from the start to finish.
For years, these substrates were made from special plastic and resin materials that help move electrical signals and control heat. They have done the job well for decades, but today's powerful AI chips are pushing those older materials close to their limits. That is why companies are now turning to ultra-thin glass as a possible next step in chip design. Older substrate materials worked well when computer chips were smaller and less demanding, but today's AI processors are far more advanced. Modern AI systems now combine multiple smaller chips called chiplets into one powerful package that handles memory, processing, and communication all at the same time. This design helps companies push performance even further, but it also creates new engineering challenges. These chip packages are becoming much larger and more complex, with billions of tiny connections working at extremely high speeds while producing a huge amount of heat. That is where the substrate becomes a major factor. Traditional organic materials can bend and expand as temperatures rise during operation. As AI systems grow more powerful, keeping everything stable and efficient is becoming much harder, which is why advanced glass substrates are getting so much attention right now. As chips heat up and cool down over time, traditional substrate materials can slightly expand and shrink. These tiny changes may not seem important, but in advanced AI systems, even small shifts can affect performance. Connections can slowly move out of alignment, signals may become less efficient, and reliability can suffer over time. Engineers have spent years trying to reduce these problems with smarter designs and tighter manufacturing controls. But as AI chips become more powerful and complex, older materials are reaching their limits. That is why the industry started searching for a completely different solution, something more stable, precise, and reliable under extreme conditions. The surprising answer turned out to be advanced glass substrates. Unlike older materials, glass can stay much more stable during temperature changes, making it a strong candidate for the next generation of high-performance AI chips. At first, glass sounded like a strange choice for advanced computer chips. Many engineers thought it would be too fragile, too expensive, and too difficult to manufacture at scale. But the glass used in next-generation chip packaging is very different from everyday glass. It is a specially engineered material designed for the extreme demands of modern computing. Traditional substrate materials react to heat by expanding and shrinking over time, which can make large AI chip systems harder to keep stable. That was manageable with smaller chips, but today's powerful AI processors need much higher precision. Advanced glass substrates offer a big advantage because they stay far more stable under changing temperatures. That stability helps engineers maintain better performance, reliability, and efficiency as AI chip designs continue to grow larger and more complex. Advanced glass substrates can handle heat and mechanical stress with far greater stability than traditional materials. Even during constant heating and cooling cycles, they keep their shape with impressive precision. That allows engineers to place electrical connections much closer together without worrying about long-term alignment issues. The improvement is huge. Glass substrates may support far higher connection density than current organic materials, creating faster communication between chip components while using energy more efficiently. For AI systems, that could mean major performance gains without relying only on smaller transistors. Glass also helps with heat management, which is one of the biggest challenges in modern computing. Better cooling and thermal control allow powerful AI processors to run more efficiently for longer periods, especially inside massive data centers, where performance and energy use are critical factors. Glass substrates could help future AI chips run at higher performance levels for longer periods, without slowing down from heat buildup. They also improve signal quality, allowing data to move with less interference compared to traditional materials. At the extreme speeds modern AI systems operate, those improvements can make a major difference in overall performance. But there is a challenge. Manufacturing these advanced glass substrates is incredibly difficult. The material must be perfectly flat, and tiny pathways inside the glass have to be created with extreme precision. Even microscopic imperfections can affect reliability. Producing this technology at large scale requires years of advanced engineering and highly specialized equipment. That difficulty is one of the biggest reasons only a small number of companies are capable of competing in this space right now. That manufacturing barrier is exactly why the recent moves by China, Intel, Samsung, and TSMC are getting so much attention. While most headlines focused on advanced lithography machines, another major technology race was quietly building in the background. For years, many experts believed the future of powerful chips depended mostly on access to cutting-edge lithography systems. The idea was simple: control the most advanced manufacturing tools, and you control the future of chip production. But China and several major tech companies also focused heavily on another strategy: advanced chip packaging and substrate technology. Instead of relying only on smaller transistors, companies began investing in new ways to connect chip components together more efficiently. That includes advanced glass substrates, precision manufacturing, and material science breakthroughs that can improve performance without depending entirely on next-generation lithography tools. China has spent years investing heavily in these areas, building factories, research programs, and supply chains focused on advanced packaging technology. Now, as AI systems demand more power and efficiency, those investments are starting to attract serious global attention. BOE is one of the clearest examples of why China's strategy around glass substrates makes sense. The company is already one of the world's biggest makers of display technology, producing precision glass for smartphones, TVs, and monitors on a massive scale every year. That experience gives BOE a strong advantage, because many of the same skills used in display glass manufacturing also apply to advanced semiconductor glass substrates. The equipment, engineering knowledge, and supply chains are closely connected, making the move into chip packaging technology a natural expansion rather than a completely new business. Other Chinese companies have also been investing heavily in solving one of the toughest challenges in this field: creating tiny electrical pathways inside the glass with extremely high precision. Over the past few years, research programs, patent activity, and production plans have all shown growing momentum in this area. Several companies are now aiming for larger-scale glass substrate production between 2026 and 2027 as demand for advanced AI chip packaging continues to rise worldwide. What connects all of these efforts is the massive level of investment going into advanced chip packaging technology. Since 2023, China has directed major funding toward factories, research programs, equipment, patents, and engineering talent focused on next-generation semiconductor packaging. Much of this activity received less global attention because most headlines were centered on the race for smaller transistors and advanced lithography systems. Meanwhile, companies and government-backed programs were steadily building capabilities in packaging technology, especially around advanced glass substrates and precision manufacturing. One reason this strategy stands out is that it builds on skills China already developed through industries like display manufacturing and materials engineering. With long-term investment and large-scale production experience, the country positioned itself to compete strongly in a growing part of the semiconductor supply chain. Now, as demand for powerful AI systems keeps rising, companies in the United States, Taiwan, South Korea, and Europe are accelerating their own investments in advanced packaging and glass substrate technology to stay competitive in the next phase of the chip industry. Intel, Samsung, TSMC, and several major American materials companies have all increased their focus on glass substrate technology over the past few years. The decisions being made now could shape the future of the global semiconductor supply chain for years to come. Intel has one of the longest histories in this area, spending more than a decade researching and developing advanced glass substrate solutions. During that time, the company built a large patent portfolio and gained valuable manufacturing experience that gives it a strong position in the industry. Intel has also started working closely with partners and suppliers to expand the overall ecosystem around this technology. Samsung is also moving quickly. The company has been developing pilot production lines and investing heavily in engineers with expertise in advanced packaging and glass materials. It has also formed partnerships with materials suppliers to help secure the specialized components needed for future production. As AI systems continue growing more powerful, major semiconductor companies are racing to improve packaging technology, and glass substrates are becoming one of the most important areas of competition. Samsung's long-term plans reportedly aim for large-scale glass substrate production around 2028, which could make the company one of the first major suppliers for advanced AI chip systems. Because Samsung already plays a huge role in the global tech supply chain, its progress in this area is getting a lot of industry attention. TSMC has also increased its focus on glass substrate research in recent years. As one of the biggest leaders in advanced AI chip packaging, the company understands that future performance gains may depend just as much on packaging technology as on transistor design itself. Expanding its work on glass substrates helps TSMC stay competitive as the industry evolves. Corning is another important player in the space. The company has decades of experience producing highly specialized glass for telecommunications, displays, and scientific applications. That expertise could make Corning a key supplier as demand for advanced semiconductor glass materials continues to grow worldwide. Investments in semiconductor-grade glass production show that the supply chain for advanced glass substrates is starting to grow in the United States. That is important because future chip manufacturing depends not only on technology, but also on having strong materials suppliers and production networks in place. Right now, the race for leadership in glass substrate technology is wide open. Companies across the United States, Asia, and Europe are investing heavily as they compete to build the next generation of AI chip packaging. Over the next few years, major AI chip designers and large cloud computing companies are expected to begin selecting long-term suppliers, which could shape the market for years to come. Big technology shifts often seem small at first. They usually begin with highly technical changes that receive little public attention, then later become recognized as major turning points for an entire industry. Many experts believe advanced glass substrates could become one of those key moments for the future of computing. Of course, that was the moment everything changed. Honestly, glass substrates are starting to feel exactly like that kind of turning point. While most people focused on export rules, advanced chips, and transistor technology, a quieter race has been happening underneath it all, the race to reinvent chip packaging. The companies and countries leading this shift are not just developing a new material. They are building the foundation that could power the next generation of AI systems. Faster AI training, more efficient data centers, and stronger computing performance could all come from improvements in this hidden layer of technology. The stakes are massive because building advanced glass substrate production lines can cost hundreds of millions, sometimes even billions of dollars. The companies that scale production first could gain a huge long-term advantage through better manufacturing experience, lower costs, and stronger partnerships. In my opinion, this may end up being one of the biggest technology shifts people overlooked at first. The transistor race still matters, but the future of AI could depend just as much on packaging and materials innovation as raw chip power itself. What do you think? Will glass substrates become the next major breakthrough in AI computing, or is the industry moving too fast to predict? Drop your thoughts in the comments. And if you enjoyed this breakdown and want more deep dives into the future of AI and technology, make sure to subscribe to the channel and turn on notifications so you do not miss the next video. Imagine you go to sleep on a Monday night and there is an empty plot of land outside your window. Cleared ground, maybe some foundation work, nothing else. You wake up Friday morning and there is a 16-story residential building standing there. 150 fully finished apartments, tiles on every floor, toilets installed, lights working, hot water running, move-in ready. That sentence does not describe a hypothetical. It describes something that physically happened in Abu Dhabi in late 2025. A building called Earth Tower went from first crane lift to completed structure in 96 hours. And the company that built it is not a startup with a flashy pitch deck. It is a Chinese manufacturer that has been quietly perfecting this process for 15 years while the rest of the construction world told them it could not be done at scale. The company is called Broad Group, and what they have built is not just a faster way to construct apartments. It is a fundamental reimagining of what construction actually is. To understand where Broad is today, you need to go back to where they started. Because the gap between then and now tells you everything about how seriously to take what they are doing. In 2011, Broad assembled a 30-story hotel in 15 days. The building went up in Changsha, in central China, using prefabricated sections that were manufactured off-site, transported to the location, and bolted together with a precision that looked, on video, like someone had hit fast forward on the whole process. The interior was not a shell waiting to be fitted out. Insulation was already in the walls. Plumbing was already run. Air conditioning was already installed. The finishing work had been done in the factory, not on the site. The global construction industry watched the time-lapse footage and reached for familiar responses. It was called a publicity stunt. Questions were raised about structural integrity. People argued that speed and quality were fundamentally incompatible in construction, that cutting timelines that dramatically meant cutting corners somewhere. Broad kept building. 3 years after the 30-story hotel, they completed Mini Sky City, a 57-story tower standing over 200 meters tall, assembled in 19 days at a rate of roughly 3 floors per day, 800 apartments. Working space for several thousand people, the same modular system, simply applied at greater height. At that point, the conversation shifted from whether the buildings could go up quickly to whether they were actually safe to live in. Broad had anticipated this. Their structural system uses a steel frame architecture with a tolerance for seismic activity that meets and in some specifications exceeds conventional high-rise construction standards. The speed was not achieved by weakening the structure. It was achieved by moving as much work as possible off the construction site and into a controlled factory environment where consistency is higher and quality control is easier to maintain. Then came the number that started to genuinely unsettle people. A 10-story apartment building, assembled in 28 hours and 45 minutes, not days, hours, 3 cranes, 1 continuous working period, and a building that would have occupied a conventional construction crew for 6 to 8 months was standing before the second day was done. The industry did not really have a framework for processing that figure. It sat outside the range of what the existing mental model of construction could accommodate. Here is the thing that most coverage of Broad gets wrong by omission. The speed you see on the construction site is not where the innovation lives. The construction site is almost beside the point. The actual work happens in Broad's manufacturing facility in central China, and it operates nothing like a construction company. It operates like a car factory. Each module that goes into a Broad building is produced on a robotic assembly line. The module itself is roughly the dimensions of a standard shipping container, a self-contained segment of a finished apartment. By the time it reaches the end of the production line, it is approximately 90% complete. The floor tiles are laid, the bathroom fixtures are installed, the electrical wiring is run through conduits, the plumbing connections are made, the insulation is fitted, the walls are painted, the windows are in. Everything that takes months on a conventional construction site has already been completed in the factory under controlled conditions, with robotic systems maintaining tolerances that human workers in outdoor environments cannot consistently match. When those modules arrive at a construction site, the process that follows is not construction in any traditional sense. It is assembly. Cranes lift each module into its designated position. Workers make the structural connections between modules, bolting the steel frame elements together according to specifications. Crews connect the interface points where plumbing, electrical, and mechanical systems from adjacent modules meet. Then the next module goes up. The construction site becomes a logistics operation rather than a manufacturing operation. And logistics can be optimized for speed in ways that on-site construction fundamentally cannot. Broad's factory currently produces an output equivalent to roughly 84,000 housing units per year, a single facility. That figure is not about individual impressive projects. It is about what happens when you treat housing the way the automotive industry treats vehicles. You design a system, build a factory around the system, and the output scales with production capacity rather than with the availability of skilled construction labor at a specific location. Everything Broad had demonstrated in China up to 2024 could be, and was, filed away by much of the international construction industry as locally specific. A Chinese company doing impressive things in China, within Chinese regulatory frameworks, using Chinese labor, for Chinese clients. Interesting. Not necessarily transferable. Earth Tower ended that argument. Eagle Hills, a property development company connected to Emaar, the group responsible for building the Burj Khalifa, sent executives to Broad's factory in central China. They walked the production floor. They watched the robotic assembly lines produce finished apartment modules. They reviewed the structural specifications. Then they placed a commercial order for 259 modules, comprising 150 residential units across multiple apartment configurations. This was not a pilot program or a research collaboration. It was a transaction. One of the most credentialed property development organizations in the world, with the technical knowledge to evaluate what they were looking at, decided the technology was ready for the Gulf market and wrote a purchase order. The modules were manufactured in September 2025. Broad's production team completed the entire order in 30 days. The units were loaded onto cargo ships in October and transported 6,000 kilometers across the ocean to the UAE. They arrived in Abu Dhabi later that month. From the moment the first crane lifted the first module on site, the clock ran for 96 hours. When it stopped, Earth Tower was standing. 16 stories, 150 apartments, 168,000 square feet of residential space. Every unit finished and operational. The project carried a value of 125 million RMB and became the first Chinese prefabricated residential building delivered into the Middle Eastern market. At CES 2026, it received the Speed Award for Smart Living, a prize that had never previously gone to a construction project, because construction projects had never previously moved at a pace that warranted the category. That last detail is worth sitting with. An industry award typically given to consumer electronics went to a building. The implication is that what Broad is doing has more in common with product manufacturing than with construction as the industry has historically understood it. Broad's next move is more significant than any single building they have assembled. The company is working toward establishing full manufacturing facilities in the UAE, not shipping modules from China, but replicating the production system itself on the ground in the Middle East. The distinction matters enormously. Shipping finished modules across oceans works, as Earth Tower demonstrated, but it adds freight cost and transit time that a local production facility eliminates entirely. If you can manufacture the modules where the demand is, you remove the ocean from the equation and the economics improve substantially. Broad's stated production target is 70 manufacturing facilities operating globally by 2030, with a combined annual output of 200 million square meters of buildings. That number is not presented as aspiration, it is presented as the production plan. The Abu Dhabi project was not the destination, it was the proof of concept that unlocks the expansion. Broad is not operating in isolation. The broader signal from the Chinese construction sector is consistent and pointed in the same direction. CSCEC, the China State Construction Engineering Corporation, currently the largest construction company on Earth by annual revenue, has received initial regulatory approval in Dubai for its modular construction division, operating under the brand name Homagic. The approval covers low-rise and mid-rise residential construction, and the company has set a target of 50,000 housing units per year specifically for markets connected to the Belt and Road Initiative. 50,000 units per year from a single company's modular division. Deployed into markets that have been struggling to build housing fast enough using conventional methods for years. Dubai's approval of CSCEC's approach is a regulatory signal. When governments begin formally approving the framework conditions for modular construction from Chinese providers, the barrier shifts from technical capability to market access. And market access, once the regulatory pathway exists, tends to open quickly. The numbers confirm the trajectory. In 2025, China exported the equivalent of $4.34 billion worth of prefabricated building structures internationally. That figure represents a 42% increase in exports to Gulf markets compared to the previous year. The growth rate is not slowing. Both the supply side and the demand side are accelerating simultaneously. Construction has been, for most of human history, a craft industry. Buildings were made by skilled workers assembling materials on site, in variable weather, with variable quality outcomes, at timelines that have not fundamentally changed in decades, despite improvements in equipment and materials. Every other major manufacturing sector has already undergone the transition from craft production to industrial production. Automobiles made the shift over a century ago. Consumer electronics made it 50 years ago. Clothing, furniture, appliances, all of them moved from hand-built to factory-built at some point in the 20th century. And in each case, the result was the same. Output increased dramatically, costs fell, and access expanded to populations that previously could not afford the product. Housing has resisted this shift longer than any other sector, partly because of the regulatory complexity of building codes, partly because of the deeply local nature of construction labor markets, and partly because the industry's culture has been slow to accept that a building can be treated as a manufactured product. Broad and CSCEC are not arguing this point anymore. They are simply doing it, at scale, in markets far outside China, with commercial clients who have evaluated the technology and decided it is ready. The 30-story hotel in 2011 was version 1 of a system that is now on perhaps version 8 or 9, deployed internationally, validated by credentialed buyers, and backed by a production infrastructure that treats housing the way Toyota treats the Corolla. What I find genuinely fascinating about this story is not the 96 hours. The headline number is striking, but the deeper point is about what happens to housing affordability when you apply industrial production logic to residential construction. If a factory can produce 84,000 housing units a year, and the economics of modular construction continue to improve as the system scales, the cost floor for residential construction drops in a way that nothing else currently on the horizon can match. That has implications for housing markets in the Gulf, in Southeast Asia, in Africa, and eventually in Western cities where construction costs have made affordable housing effectively impossible to deliver at the required pace. The construction industry has had a century of warning that this transition was coming. It is here now, and the company leading it is operating out of central China, not out of London or New York or Tokyo. Here is my question for you. If a broad-built apartment was available in your city, fully finished, structurally certified, assembled in under a week, would you buy or rent one? Or does the speed of construction make you nervous regardless of what the data says about quality? Drop your honest answer in the comments. I think the responses are going to split pretty sharply, and I want to see where people land. If you want to keep following stories like this, technology and engineering developments that are reshaping industries most people are not paying close enough attention to, subscribe to Eastern Engine and turn on notifications. We cover these shifts as they happen, with the depth they deserve. There is a lot more coming, and you do not want to be catching up later. For the last 3 years, one company has held the entire world of artificial intelligence in the palm of its hand. Not Google, not OpenAI, not Microsoft. A chip company, NVIDIA. Because every major AI model you've ever heard of, every chatbot, every image generator, every breakthrough that made headlines, was trained and run on NVIDIA's chips. The company became so essential, so unavoidable, that it briefly became the most valuable company on planet Earth. If you wanted to build serious AI, you went through NVIDIA. There was no other door. And it wasn't just the chips. NVIDIA's real fortress was something most people have never heard of. A piece of software called CUDA, the invisible layer that every AI developer on Earth has been building on for over a decade. People in the industry have a name for this trap. They call it the CUDA moat. A castle wall so wide and so deep that even if a rival built a faster chip tomorrow, no one could use it, because the entire world's AI software was written for NVIDIA and NVIDIA alone. That was the situation. That was the lock on the door. And a few weeks ago, a Chinese AI company called DeepSeek did something that was supposed to be nearly impossible. It built a brand new frontier-class AI model that runs from top to bottom without a single piece of NVIDIA software anywhere in its stack. No CUDA, running instead on chips made by Huawei, a company the United States sanctioned years ago specifically to keep it away from this exact moment. Now, and you know this is coming, there's crucial nuance here, and parts of this story cut against the hype in ways that are genuinely fascinating. I'm going to give you all of it, honestly. But by the end of this video, you'll understand what just happened, why NVIDIA's own CEO publicly admitted he's losing China, why the CUDA moat suddenly looks less like a wall and more like a dam with a crack in it, and why this might be remembered as one of the most important moments in the AI race. Let's get into it. To understand why this is such a big deal, you have to understand how complete NVIDIA's grip really was. And it came down to two things working together. The first is the chips themselves. Training a modern AI model requires a staggering amount of raw mathematical horsepower, and NVIDIA's chips, originally designed to render video game graphics, turned out to be almost perfectly suited to the kind of massively parallel math that AI demands. For years, they were simply the best on Earth at it, by a wide margin. If you wanted to train a serious model, you needed NVIDIA silicon. Full stop. But the chips were only half the fortress. The other half, the part that really locked everyone in, was the software. CUDA is NVIDIA's programming platform, the bridge that lets AI code actually talk to the chips. And here's the thing, the entire global AI community has been building on CUDA for more than a decade. Every framework, every tool, every tutorial, every trick built for CUDA. An entire generation of engineers grew up speaking it. That's the moat. Imagine a country where every road, every gas station, every mechanic, and every driving school was built for exactly one brand of car. Even if a competitor released a better vehicle, who would buy it? You couldn't fuel it, fix it, or find anyone trained to drive it. That's what NVIDIA built. Not just a better car, but the entire road system everyone else was forced to drive on. Switching away wasn't just hard. For most companies, it was unthinkable because it meant abandoning every tool and rebuilding from scratch. So when the United States wanted to slow China's AI progress, the strategy seemed obvious and airtight. Cut China off from NVIDIA's most powerful chips. No advanced NVIDIA silicon, no frontier AI. The leash was the chip, and the lock was the software. And for a while, that logic held, until a cornered company decided the only way out was to build its own road system from scratch. The company at the center of this is DeepSeek, a Chinese AI lab that already shocked the world once. Back in early 2025, when its earlier model launched, it was so unexpectedly capable and so cheap to run that it wiped out hundreds of billions of dollars from NVIDIA's market value in a single day. Investors suddenly panicking that maybe the future of AI wouldn't need quite so many expensive NVIDIA chips after all. Now DeepSeek is back with its new generation, V4, a genuinely frontier-class model, a colossal system with 1.6 trillion parameters, competitive on serious benchmarks with the best models from American labs. On certain coding and reasoning tests, it ranks at or near the very top, trading blows with the flagship models from the biggest names in Western AI. But the benchmarks aren't the real story. The real story is what's underneath. According to multiple reports, V4 is the first DeepSeek model with no NVIDIA CUDA dependency anywhere in its core stack. Instead, it was natively built to run on Huawei's Ascend chips, using Huawei's own software framework, called CNN, as the replacement for CUDA. Think of CNN as Huawei's homegrown version of that road system, its own bridge between AI code and its own chips. And the engineering effort this took is staggering, which is actually why V4 was so delayed. For months, the model kept slipping past its expected release dates, and there was a single reason. Migrating a system this enormous off of CUDA and onto Huawei's completely different software framework, essentially from scratch, is brutally hard. There's even a detail that perfectly captures the difficulty. The team developed its own specialized programming language, called Tilelang, so the model's core operations wouldn't be permanently chained to any one company's chips. Months of delay weren't a failure, they were the price of independence. Here's the detail that drives the point home like nothing else. DeepSeek reportedly gave Huawei weeks of exclusive early access to optimize the model for its chips, a courtesy it pointedly refused to give NVIDIA and AMD. The Chinese company put its own domestic chip maker first and made the American giants wait. A few years ago, that would have been unthinkable. If you want a single piece of evidence for how serious this is, you don't have to take China's word for it. You can take NVIDIA's. NVIDIA's CEO, Jensen Huang, one of the most powerful figures in all of technology, publicly admitted that his company has largely conceded China's advanced AI chip market to Huawei. Let that sink in. The head of the most dominant chip company on Earth, openly acknowledging that in the world's second-largest economy, he's handing the field to his Chinese rival. CEOs do not say things like that lightly. That is not spin. That is a man reading the board and admitting he's losing a piece of it. And the market is moving on exactly that belief. Reports indicate that China's three internet giants, Alibaba, ByteDance, and Tencent, have collectively pre-ordered hundreds of thousands of Huawei's new AI chips, positioning themselves to run models like V4 at massive scale. Pre-orders on that scale don't happen on a hunch. They happen when the biggest players in a market have decided which way the wind is blowing. Huawei is now bracing for something like $12 billion in AI chip revenue, with reports that Chinese fabs can barely keep up with demand, while NVIDIA's share of that same market quietly craters. The picture is unmistakable. A model the world's developers actually want to use, running on Chinese chips, bought in enormous volume by China's biggest companies, with NVIDIA's own CEO conceding the territory. The lock on the door didn't just loosen. Someone built an entirely new door. But, and this is where I have to be honest with you, because the truth here is more interesting than the clean headline. The door isn't quite as wide open as it first appears. Here's the nuance that separates this channel from the breathless headlines. Because there are three big caveats, and you deserve every one of them. First, and most important, V4 was still trained mostly on NVIDIA. Building an AI model has two phases: training, the immensely expensive process of creating the model's intelligence, and inference, the cheaper process of actually running it for users. The NVIDIA free achievement is strongest on the inference side. For the hardest part, frontier training, Chinese firms, including DeepSeek, have still largely leaned on NVIDIA hardware because Huawei's chips and software aren't yet reliable enough for that brutal workload. In fact, DeepSeek reportedly couldn't complete a clean training run for an earlier model on Huawei chips even with Huawei's own engineers on site. So cut NVIDIA out completely is true for running the model, but the deepest, hardest layer of AI still has NVIDIA footprint. Second, DeepSeek deliberately kept V4 compatible with NVIDIA too. Buried in the technical details, V4 was validated on both Huawei and NVIDIA platforms. Why? Because if the model only ran on Huawei chips, the global community of developers, who overwhelmingly own NVIDIA hardware, couldn't use it. And an open-source model that nobody outside China can run is just a political statement, not a living technology. So DeepSeek is playing a clever double game. Prove independence is possible, while keeping global compatibility so the model stays relevant everywhere. That's not weakness, it's strategy. But it means the total break is more nuanced than it sounds. Third, Huawei's KNA software still trails NVIDIA's CUDA by a wide margin, by something like an order of magnitude in ecosystem maturity. A decade of global development doesn't get matched in a year. KN works because DeepSeek controls its own full stack and tuned everything by hand. For the average developer worldwide, CUDA is still the default and will be for a long time. So here's the fair summary, the one the hype skips. China has not matched NVIDIA. Huawei has not caught up. KN has not equaled CUDA. What actually happened is subtler and honestly more important than any of those simple claims. For the first time, a frontier-class AI model exists that was built from chip to model, with no American software at its core. Proving the thing everyone said was years away is possible right now. The wall isn't gone, but everyone just watched someone climb over it. So if China hasn't fully caught up, why is this such a big deal? Because of what it starts, not what it finishes. The real significance is something experts call a learning loop, and it's the thing NVIDIA should actually fear. Here's how it works. DeepSeek optimizes its model for Huawei's chips. Huawei gets a serious, real-world, world-class workload to learn from. Its canned software gets battle-tested and improves. Cloud providers gain experience running it. Other Chinese AI labs see it working and start building for Huawei too. And the next model becomes easier to run on Chinese chips than the last one. Round and round, each loop making the domestic alternative a little stronger. That's how an ecosystem is born. Not in one dramatic leap, but through exactly this kind of repeated, workload-driven improvement. NVIDIA's moat was never really just the chips. It was the ecosystem, the decade of everyone building on CUDA. And the only way to challenge an ecosystem is to start a rival one and let it compound. V4 is the starting gun for precisely that. It gives the Chinese stack its first true frontier-class workload to organize around. And the strategic ripple effects are already spreading. Because V4 is open source and dramatically cheaper to run than Western alternatives, reportedly by a huge margin, it becomes attractive far beyond China. Governments and institutions in countries that can't or won't rely on American cloud infrastructure can now run a top-tier AI model entirely on a non-American stack. That's a genuinely new option in the world, and it didn't exist a year ago. Step back and the pattern is the one we keep seeing on this channel. A restriction was designed to lock China out. Instead, it forced China to build the one thing the restriction was meant to prevent: a complete, independent, domestic alternative. The export controls didn't stop the parallel ecosystem. They may have been the very thing that created it. Cut off from the road system everyone else uses, China started paving its own. Here's my honest opinion. I think the two loudest reactions to this are both wrong, and the truth is more interesting than either. The people shouting China just destroyed NVIDIA and won the AI war are flatly ahead of the facts. Frontier training still leans on NVIDIA, Cana still trails CUDA badly, and DeepSeek itself kept NVIDIA compatibility on purpose. Anyone selling you NVIDIA is finished is selling a fantasy. But the people waving this away, it's nothing, they still need NVIDIA, ignore it, are making the bigger mistake, the same one that's been made at every stage of this story, because they're fixated on the fact that the wall still stands, and missing that someone just proved it can be climbed. The single most important word in this entire story is not chip or model, it's possible. For 3 years, the iron assumption was that you simply could not build frontier AI without the American stack. That assumption is now dead. Not weakened, dead. And once something is proven possible, it almost always gets better, cheaper, and more common from there. What strikes me most is that NVIDIA's own CEO seems to understand this better than the cheerleaders on either side. He didn't dismiss it, he conceded ground. That tells you the person with the most to lose and the best view of the board is taking it seriously. Maybe the rest of us should too. The CUDA moat was the widest, deepest competitive wall in modern technology. It still stands, but for the first time, there's a crack in the dam, and water has a way of finding every crack and slowly, relentlessly making it bigger. So here's my question for you, and I genuinely want your honest answer. Did the chip restrictions backfire? By forcing China to build a complete, independent AI ecosystem it might never have bothered to build otherwise, or were they still worth it, because they've kept China a step behind and burning enormous resources to catch up? Did cutting the cord set China free, or just slow it down? Drop your real take in the comments. I read every single one, and this is exactly the debate I love seeing down there. If you want to keep following this, the breakthroughs, the workarounds, the shifts the rest of the world keeps underestimating until they can't, subscribe to Eastern Engine and hit the notification bell. Chips, AI, computing, the entire foundation of the modern world is being rewritten right now, and we break it all down clearly and honestly before the mainstream catches on. Thanks for watching. I'll see you in the next one. For years, the world's fastest supercomputers have followed one dominant formula. Start with powerful central processors. Add enormous numbers of specialized GPU accelerators. Connect everything with an ultra-fast network. Then, use those GPUs to perform the mathematical work that would overwhelm ordinary CPUs. America's El Capitan follows that model. It combines AMD server processors with AMD Instinct MI300A accelerators and delivers more than 1 quintillion calculations every second. It held the official title of the world's fastest publicly ranked supercomputer. Until now, a previously unlisted Chinese machine called Lineshine has entered the official TOP 500 ranking at number 1. Its verified performance is 2.198 exaflops. America's El Capitan recorded 1.809 exaflops. That places the Chinese system approximately 21.5% ahead on the benchmark used to determine the global ranking. But the most surprising part is not simply that China moved into first place, it is how Lineshine got there. The machine reached more than 2 exaflops of sustained double precision computing without dedicated GPU accelerators. No NVIDIA GPUs. No AMD Instinct accelerators. No Intel data center GPUs. Instead, Lineshine uses millions of custom Chinese CPU cores, a proprietary interconnection network, and a domestic software stack. It is the first publicly ranked supercomputer to sustain more than 2 exaflops using CPUs alone. That does not automatically make it the best AI computer in the world. It does not mean GPUs are suddenly obsolete. and one benchmark can never describe every workload a machine may encounter. But this result is official. China has taken the #1 position on the TOP 500 for the first time since 2017, and it did so by rejecting the architecture used by almost every other leading exascale machine. What officially #1 actually means. The top 500 list has ranked the world's most powerful publicly disclosed supercomputers since 1993. It is updated twice each year. To determine the ranking, systems run a benchmark known as High Performance LinPack, or HPL. HPL asks the computer to solve an enormous system of dense linear equations using high-precision, 64-bit floating-point mathematics. This kind of calculation appears in scientific simulation, engineering, and numerical analysis. The benchmark measures how many floating-point operations the machine can sustain each second while solving the problem. A petaflop is 1 quadrillion operations per second. An exaflop is 1 quintillion. Lineshine sustained 2.198 exaflops. Written out, that is roughly 2.198 quintillion floating-point operations every second during the benchmark. The number is not a theoretical marketing figure. Lineshine's theoretical peak is higher, at approximately 2.736 exaflops. But theoretical peak assumes every component operates perfectly. Every cycle is fully utilized and no time is lost to communication, memory access, or software overhead. Real machines never maintain theoretical peak continuously. Lineshine converted slightly more than 80% of its theoretical capability into measured HPL performance. That is one of the most important details in this story. Building millions of processor cores is difficult. Keeping them busy at the same time is much harder. A supercomputer does not become fast merely because it contains many processors. The processors must communicate, share data, synchronize, and divide a single enormous problem without spending most of their time waiting. Lineshine's 80% result suggests that its architecture is not simply large, it is highly coordinated, inside the CPU-only machine. Lineshine is installed at the National Supercomputing Center in Shenzhen. The machine was built by the Shenzhen Cloud Computing Center and is based on a custom platform called Lingkun. At its core is a Chinese processor known as the LX2. Each LX2 contains 304 CPU cores running at 1.55 GHz. The complete system contains 13,789,440 cores. Divide that total by 304, and the architecture appears to use roughly 45,360 of these processors. That is not 45,000 individual desktop computers. These processors are installed in densely packed computing nodes, surrounded by memory, cooling equipment, power distribution systems, and the network required to connect the entire machine. A modern GPU may contain thousands of smaller parallel computing units. Lineshine instead spreads its work across a vast population of general-purpose CPU cores. The individual clock frequency of 1.55 GHz may sound modest compared with a consumer desktop processor that can exceed 5 GHz. But supercomputers are not built to make one core run as fast as possible. They are designed to make millions of cores work together. A higher clock frequency increases power consumption and heat. At this scale, efficiency, parallelism, and communication matter more than winning a single core benchmark. Imagine trying to move a mountain. One extremely strong worker cannot do it. 45,000 organized teams might, but only if every team knows exactly which section to move, where to place it, and when to act. Without coordination, adding more workers can make the project slower. That is why the processor count is only half the story. The hidden weapon is the network. Every processor inside a supercomputer needs data. A calculation performed on one node may depend on a result produced somewhere else. If those results move slowly, the processors sit idle. At exascale, even tiny communication delays become enormous when repeated trillions of times. Lineshine connects a second benchmark called HPCG. HPCG stands for High Performance Conjugate Gradients. Unlike HPL, it places greater pressure on memory access, communication, and irregular data movement. These are the parts of supercomputing that often prevent theoretical performance from becoming useful performance. Lineshine achieved approximately 22 petaflops on HPCG. El Capitan achieved around 17.4 petaflops. That places Lineshine roughly 26% ahead on this second measurement. This result is important because it weakens the simplest criticism. The machine did not merely win one highly optimized matrix calculation while collapsing on a more communication-intensive workload. It also led the benchmark intended to represent patterns found in real scientific applications more closely. HPCG is still only a benchmark. No single test can reproduce climate modeling, fluid dynamics, molecular simulation, seismic analysis, and every other scientific workload. But finishing first on both HPL and HPCG suggests that Lineshine's interconnect and memory system are not afterthoughts. The architecture appears balanced enough to keep millions of CPU cores supplied with data. Why build a supercomputer without GPUs? The obvious question is why anyone would avoid accelerators. GPUs became dominant in supercomputing for a reason. A CPU is designed to handle a broad range of instructions. It is flexible. It can manage operating systems, complicated decision-making, serial code, and workloads with unpredictable branches. A GPU is narrower but massively parallel. It excels when the same mathematical operation must be applied across enormous arrays of data. Scientific simulations and neural networks are filled with those operations. That is why America's leading machines use accelerators. El Capitan combines AMD EPYC processors with MI300A accelerated processing units. Frontier uses AMD MI250X accelerators. Aurora uses Intel GPU Max accelerators. Europe's Jupiter Booster uses NVIDIA Grace Hopper superchips. Against that field, Lineshine looks almost deliberately unconventional. One possible advantage is programming simplicity. Accelerated systems divide applications between CPUs and GPUs. Developers must decide which code runs where, move data between different memory spaces, and optimize software for specialized hardware. A CPU-heavy machine can provide a more uniform programming environment. The same processor type handles more of the workload. That does not make programming easy, especially across nearly 14 million cores, but it can reduce the architectural divide between a host processor and an accelerator. CPU-based systems may also perform well on workloads that contain complex control logic, irregular memory access, or sections that do not map cleanly onto GPUs. The disadvantage is efficiency. GPUs can perform far more parallel arithmetic per watt on suitable workloads. To compete without them, Lineshine must deploy an enormous number of CPU cores and keep those cores highly utilized. The machine is not proving that accelerators were a mistake. It is proving that accelerator-free exascale computing remains possible when processors, memory, software, and networking are designed as one system. An entirely custom computing stack. Lineshine is not only unusual because it avoids GPUs, its major layers are Chinese-developed. The processors are custom LX2 chips. The computing platform is called Ling Kun. The interconnect is Ling Qi. The operating system is Qilin. The benchmark submission also lists a customized compiler and locally adapted mathematical software. This matters because supercomputer performance depends on more than silicon. A powerful processor running poorly optimized code can waste most of its theoretical capability. The compiler must translate software into instructions that exploit the processor's architecture. The mathematical libraries must perform common operations efficiently. The operating system must coordinate resources across thousands of nodes. The communication software must move messages across the network without creating unnecessary delays. When a system achieves 80% of its theoretical peak on HPL, that usually means multiple layers have been optimized together. The hardware team cannot work in isolation. Neither can the software team. The machine behaves less like a collection of separate products and more like one enormous engineered instrument. This full-stack approach may be the real achievement. China did not simply build a processor and insert it into an existing American or European supercomputer design. It submitted a complete domestic platform capable of taking first place on two major rankings. The power bill behind the performance. There is a cost. Lineshine draws approximately 42.2 megawatts while delivering its submitted performance. That is industrial-scale power consumption. At that rate, operating continuously for 24 hours would require more than 1,000 megawatt-hours of electricity. Cooling the hardware adds another major engineering challenge. Every watt entering a processor eventually becomes heat. Thousands of high-density computing nodes must be cooled continuously, because overheating can reduce performance or damage components. Lineshine achieves an energy efficiency of approximately 52.07 gigaflops per watt. El Capitan records around 60.94 gigaflops per watt. That makes the American system roughly 17% more efficient on the reported metric. This is where the accelerator advantage becomes visible. Lineshine wins the raw HPL ranking. El Capitan produces more computation from each watt. Neither result cancels the other. The Chinese system was designed to maximize sustained high-precision CPU performance. The American system combines CPUs and specialized accelerators to improve performance across traditional simulation and mixed precision workloads. Two different architectural philosophies produce different strengths. In an era when electricity and cooling are becoming limits on both supercomputers and AI data centers, energy efficiency cannot be ignored. Winning the performance crown is impressive. Operating the machine economically for years is a separate challenge. The AI benchmark changes the story. This is the most important caveat. Lineshine is officially number 1 on HPL. It is also number 1 on HPCG. But when the benchmark shifts toward lower precision mathematics used heavily in artificial intelligence, the ranking changes. The HPL MXP benchmark measures mixed precision performance. Traditional scientific calculations often use 64-bit precision because tiny errors can accumulate and affect the final result. Many AI workloads can use 32-bit, 16-bit, 8-bit, or even lower precision numbers. Specialized accelerators are extremely fast at these operations. On HPL MXP, Lineshine achieved approximately 7.92 exaflops and ranked 4th. El Capitan achieved 16.7 exaflops and remained number 1. That means El Capitan delivered more than twice Lineshine's mixed precision result. This is why the phrase "world's fastest supercomputer" needs context. Lineshine is the fastest system on the official benchmark used to rank the top 500. That benchmark measures sustained double precision performance. It does not prove that Lineshine will train the largest AI model faster than El Capitan. It does not prove that it will outperform GPU systems on every application. For AI-style low-precision mathematics, El Capitan's accelerators provide a major advantage. The two machines are like different vehicles. Lineshine is an enormous high-precision freight engine capable of moving a massive scientific workload. El Capitan is a hybrid machine with specialized engines for different terrain. On the official straight-line test, Lineshine wins. On the mixed precision AI test, El Capitan pulls far ahead. Does no GPU mean the return of the CPU? Not exactly. GPUs are not disappearing from supercomputing. In fact, accelerator adoption continues to grow across the TOP 500. AI demand is making specialized low-precision computing more important, not less. Lineshine demonstrates a different point. There is no single correct architecture for every supercomputer. The best design depends on the workload. If a research center prioritizes high-precision scientific simulation, CPU flexibility, and a uniform programming environment, a massive CPU-based design may remain competitive. If the goal is training neural networks or running mixed precision mathematics, specialized accelerators are difficult to beat. Future systems may become even more heterogeneous. They may combine CPUs, GPUs, AI accelerators, photonic processors, and custom chips, assigning each task to the hardware that performs it most efficiently. Lineshine stands out because it moves in the opposite direction. Instead of adding more types of processors, it scales one processor architecture to an extraordinary level. That simplicity at the component level creates extreme complexity at the system level. Nearly 14 million cores must operate as one computer. The fact that they do so efficiently enough to reach 2.198 exaflops is the central engineering story. What will China use it for? The public top 500 entry identifies Lineshine as a research system at the National Supercomputing Center in Shenzhen. Supercomputers at this level can support many categories of scientific work. Possible workloads include weather forecasting, materials discovery, fluid dynamics, engineering simulation, molecular modeling, and large-scale numerical research. However, the precise workload mix and access policies for Lineshine have not been fully disclosed publicly. That lack of detail matters. Benchmark numbers tell us what the machine achieved during controlled tests. They do not tell us how much useful scientific work it completes each week, how easy it is to program, or how reliably it operates under sustained demand. A supercomputer becomes valuable when researchers can use it efficiently. Applications must be rewritten or optimized for the architecture. Scientific teams need access. Storage systems must feed enormous data sets into the machine. The system must remain stable, while millions of components operate simultaneously. China has demonstrated the hardware platform. The next evidence will come from published scientific results produced using it. Why this changes the global supercomputing picture. Before Lineshine entered the ranking, the top positions were dominated by American accelerated systems. El Capitan was first, Frontier was second, Aurora was third. The United States had established a clear lead in publicly ranked exascale computing. Lineshine did not slowly climb from 10th place to 5th and eventually first. It appeared directly at the top. That creates two important changes. First, the official performance lead has moved back to China for the first time since 2017. Second, the machine expands the definition of what an exascale system can look like. The industry had been moving toward the belief that accelerators were practically mandatory at this scale. Lineshine proves that a CPU-only approach can still win the traditional performance crown. Whether that approach becomes widely copied is another question. The power demand is substantial. Its AI performance is weaker than El Capitan's, and the public technical details are not yet deep enough for outside experts to evaluate every design decision. But the result cannot simply be dismissed. Top 500 accepted the submission. The measured numbers place Lineshine first, and its HPCG result strengthens the claim that this is more than a narrowly optimized demonstration. The honest catch. There are 4 major caveats. First, Lineshine is number 1 on specific benchmarks, not automatically on every real application. Second, its lack of dedicated, low-precision accelerators limits its advantage in modern AI computing. Third, it consumes more power per unit of reported performance than El Capitan. Fourth, many architectural details remain proprietary or publicly unexplained. We know the processor core count, clock frequency, system platform, interconnect, operating system, and benchmark results. We know much less about the internal design of the LX2 core, its memory hierarchy, vector capabilities, manufacturing process, packaging, and the exact topology of the Lingqi network. Those details would help explain how China reached this level without GPUs. Until more information or scientific performance results appear, some questions must remain open. But uncertainty around the details does not erase the verified result. Lineshine sustained more than 2 exaflops of high-precision performance and displaced El Capitan from the top of the official list. My take is that the number 1 ranking is important, but the architectural divergence is even more important. China did not win by building a slightly larger copy of El Capitan. It chose a different route. America concentrated enormous parallel performance inside advanced accelerators. China distributed the work across nearly 14 million custom CPU cores and built a network powerful enough to keep them synchronized. The American design is more efficient and much stronger on mixed precision AI mathematics. The Chinese design is now faster on the traditional HPL benchmark and also leads HPCG. This is not a simple story of one country possessing better technology in every category. It is a story of 2 systems optimized around different strengths. Lineshine shows what can happen when processor design, networking, software, and system architecture are developed together around one objective. It also shows that mature technologies can still produce surprising results. The CPU was supposed to become a supporting actor in the exascale era. Lineshine put millions of CPUs at the center of the machine and reached number 1. The question now is whether this is a one-time engineering achievement or the beginning of a broader CPU-first supercomputing strategy. Will China continue scaling the Lincoln platform? Will future LX processors improve energy efficiency and mixed precision performance? Will Lineshine produce scientific results that justify its enormous size and power demand? And will American laboratories respond with even larger accelerated systems? The supercomputer race has not ended. It has become more interesting because the leading machines are no longer following the same blueprint. So what matters more to you? Should Lineshine be considered the world's most powerful supercomputer because it officially ranks first on HPL and HPCG? Or does El Capitan's stronger efficiency and AI-oriented performance make it the more capable overall machine? Let me know your view in the comments. And subscribe to Eastern Engine for more grounded coverage of the chips, materials, and computing systems changing the global technology industry. Because China did not take the supercomputer crown by copying the dominant design. It took the crown by proving there was another road to exascale. In December 2023, something Samsung, TSMC, and the entire semiconductor world had been circling for years without solving. And at CES 2026, Intel made it official. The first commercial processor in history built on a glass foundation shipped to real customers. A 10-year head start turned into a finished product. The glass age of computing, as one analyst put it, had officially begun, and Intel was standing at the front of the line. There was just one problem. While Intel spent a decade perfecting glass chips in the lab, a Chinese company that had never made a single semiconductor was quietly building the exact factories needed to mass produce them. And it was doing it in a fraction of the time. Not 10 years, months. This is the story of how the company that invented the future of chips may have just handed the lead to someone else. And the reason it happened has almost nothing to do with chips at all. Let's get into it. To understand what just happened, you need to understand why glass chips matter in the first place. and why Intel's decade of work was such a big deal. If you've watched my earlier videos on this, you know the short version. The most powerful AI chips today aren't single chips anymore. They're clusters of smaller chips, called chiplets, all mounted on a shared foundation called a substrate. And that foundation for the last 20 years has been made of an organic material, essentially a very advanced plastic. That plastic foundation has hit a wall. Literally, the industry calls it the war page wall. As AI chips get bigger and hotter, the plastic underneath them expands and contracts unevenly, warping just enough to break the microscopic connections holding everything together. The plastic that served the industry for 2 decades simply can't handle the size and heat of modern AI hardware. Glass solves this. It barely expands under heat. It stays flat. It carries far more connections and cleaner signals than plastic ever could. Intel, to its credit, saw this coming earlier than almost anyone. They started working on glass substrates more than 10 years ago, when AI chips were nowhere near the monsters they are today. They bet correctly on a problem that didn't fully exist yet, and here's where the assumption everyone made comes in. The entire industry believed that whoever solved the science of glass first would win. Intel solved the science. Intel shipped first, so Intel should win, right? That assumption turned out to be wrong, because solving the science and winning the race are 2 completely different things, and the gap between them is exactly where China walked in. Let me show you just how hard the thing Intel accomplished actually was, because it makes what happened next even more surprising. Building a glass substrate is brutal. I covered the manufacturing nightmare in detail in earlier videos, but here's the essence. You have to drill thousands of microscopic holes, each thinner than a human hair, straight through a sheet of glass thinner than a fingernail, without cracking it. Then you have to fill those holes with metal that expands at a different rate than glass without the 2 separating under heat. Then you have to keep the entire surface flat to within a fraction of a hair's width across the whole panel. Glass is rigid, brittle, and unforgiving. It punishes the smallest mistake with invisible cracks that don't show up until months later, when the finished chip suddenly fails. For years, the percentage of glass substrates that survived manufacturing without a defect was so low that producing them commercially made no financial sense at all. This is what took Intel 10 years. Not because Intel was slow, because the problem was genuinely that hard. They had to invent the processes, the tools, the inspection methods, the entire approach, mostly from scratch. By the time they shipped Clearwater Forest in early 2026, they had earned every bit of their first-mover advantage. Intel's launch marked the world's first successful high-volume implementation of glass core substrates in a commercial CPU, signaling the beginning of what engineers called the glass age of computing. So how does a company with 0 semiconductor history come along and threaten that 10-year lead in a matter of months? The answer is the most surprising part of this entire story. Here's the twist almost nobody outside the industry understands. The hardest part of making glass substrates isn't the chip science, it's the glass handling. Cutting enormous sheets of ultra-thin glass with perfect precision, keeping them flat, inspecting them for microscopic flaws, moving them through a factory without shattering them, running all of this at massive scale every single day with the yield high enough to make money. Now, what other industry on Earth has spent the last 20 years mastering exactly that? Precision handling of giant, ultra-thin sheets of flawless glass at enormous scale? Display manufacturing, the screens in your TV, your monitor, your phone. And the largest display glass manufacturer on the planet is a Chinese company called BOE. BOE has never made a semiconductor, but it has spent 2 decades perfecting the single hardest physical skill that glass substrates require, handling big, thin, perfect glass without breaking it, at industrial scale, profitably. The factories are already built, the expertise already exists, the equipment is already humming. China's ability to repurpose existing LCD and OLED production lines for semiconductor glass has given it an unexpected speed advantage over global giants like Intel and Samsung, who have been researching glass substrates for years. Everything you do online is being watched. Your provider, advertisers, even governments. NordVPN encrypts your connection, hides your location, and unlocks the open internet from anywhere. Grab the deal, link in the description. Think about what that means. Intel had to learn glass from a chip maker's starting point. BOE is approaching it from a glass maker's starting point, and it turns out the glass was always the hard part. Intel spent 10 years learning to handle a material China had already mastered for a completely different reason. That's the 10 years versus 10 months. It's not that China is smarter or working harder. It's that China was already standing at the finish line of the hardest part of the race, holding skills it built for televisions, while everyone else was still figuring out how to run. This isn't theory, it's happening right now, and the pace is genuinely startling. By January 2026, BOE had already transitioned from small pilot lines to full-scale panel production, leveraging its expertise in ultra-thin glass to produce substrates with ultra-low warpage. Mass production is being targeted on a timeline that the rest of the industry simply isn't matching. And it's not just BOE. The entire Chinese supply chain is mobilizing at once. Visionox, one of China's leading display manufacturers, is investing 5 billion RMB into a new project that accelerates its glass substrate work. On the equipment side, Chinese manufacturers such as Hans Laser have begun delivering domestically produced laser drilling equipment for the through-glass via process, addressing one of the key bottlenecks in glass substrate manufacturing. And packaging companies, including Tongfu Microelectronics, have already developed the through-glass via packaging capability, with product-level applications expected between 2026 and 2027. Here's the strategic detail that matters most. According to industry sources, Chinese suppliers are deliberately trying to stand up entire manufacturing flows all at once to shorten time to market, rather than scaling up incrementally the way the rest of the industry does. That's the difference in philosophy in a single sentence. Intel built glass chips the careful way, one validated step at a time, over a decade. China is building the whole chain simultaneously, in parallel, racing to volume. One approach is methodical, the other is explosive. And in a market where being first to high volume is everything, explosive tends to win. Here's the part that should make Intel nervous, and it's a lesson that shows up again and again in the chip industry. Inventing a technology first does not mean you win the market. What wins the market is reaching high-volume production first, and then accumulating the manufacturing knowledge that only comes from running millions of real units through real factories. Every substrate that runs through a production line teaches the factory something. Every defect solved becomes knowledge that can't be bought or copied. The company that reaches true mass production first starts climbing that learning curve first, and the customers who design their chips around that supplier's specifications don't switch easily, because re-qualifying a new supplier costs years and enormous risk. This is the exact dynamic that made TSMC nearly untouchable. TSMC didn't win because it permanently had better technology than everyone else. It won because it reached massive volume first, learned faster than anyone could catch up, and locked in customers whose own roadmaps became dependent on it. Intel, ironically, has spent years on the painful end of that exact lesson, being technologically capable but behind on volume manufacturing. Now the same pattern may be repeating, except this time Intel is the one holding the early invention while someone else races toward the volume. Intel invented the glass chip, but if BOE reaches reliable mass production first, using its 2-decade head start in glass handling, then the manufacturing knowledge, the customer relationships, and the cost advantages could accumulate on China's side of the board. And those advantages, once they compound, are extraordinarily hard to reverse. Being first to invent gets you a headline. Being first to volume gets you the industry. Now let me be straight with you, because I don't want to overstate this and have you call me out in the comments. China has not won the glass chip race, not even close to over. Intel genuinely shipped first, and that real, commercial first-mover advantage matters enormously. Intel currently holds the first-mover advantage, and Samsung is targeting mass production in the second half of 2026, with a pilot line already producing samples. This is a four-way race between Intel, Samsung, TSMC, and China's manufacturers, not a finished story. And there's a real catch on China's side too. Glass is famously fragile. Industry analysts caution that the mass production timelines being touted across the board are overly optimistic, because glass substrates are extremely fragile. Microscopic impacts during cleanroom transport can shatter an entire panel, and the adhesion issues between smooth glass and metal routing aren't fully solved. Some analysts think large-scale commercial penetration won't really arrive until 2028 for anyone, China included. So the honest framing isn't China crushed Intel. It's something more interesting. Intel spent a decade earning a lead that China's display industry may be able to erase in a fraction of the time. Not because China out-invented anyone, but because the hardest part of this particular race happened to be something China had already mastered for televisions. That's a genuinely different kind of competition than the chip world is used to. And it's why this race is suddenly wide open when everyone assumed Intel had it locked. Here's my honest opinion. What fascinates me about this story is that it completely upends how we usually think about technology leadership. We assume the company that invents something first and works on it longest deserves to win. And usually, we assume they will. Intel did everything right. They saw the future early. They invested for a decade. They shipped first. By every traditional measure, they earned the lead. And it still might not be enough, because the decisive advantage in this race didn't come from the lab. It came from a factory floor in China that was built to make TV screens. The skill that took Intel 10 painful years to develop was something BOE had been quietly perfecting the whole time for a completely unrelated product. Sometimes the most important advantage in a technology race isn't the technology at all. It's the boring industrial capability sitting in an adjacent industry that nobody thought to connect. I think the next 2 years of this race are going to surprise a lot of people who assumed the inventor automatically wins. The lead Intel built is real, but it is absolutely not safe. Here's my question for you, and I really want your honest take. Does the company that invents a technology deserve to win the market? Or is it fair game for whoever can manufacture it best, even if they showed up years later with skills borrowed from a totally different industry? Is that brilliant strategy, or is it unfair? Drop your real opinion in the comments. I read them all, and this one's going to divide people. If you want to keep following this race, and all the others where the expected winner suddenly isn't, subscribe to Eastern Engine and turn on notifications. Glass, diamond, silicon, the entire foundation of modern computing is being rebuilt right now, and the story is moving faster than almost anyone realizes. Thanks for watching. I'll see you in the next one. What if I told you the chip everyone's been fighting over, the one NVIDIA built an empire on, the one entire nations are trying to control, the one the whole AI boom runs on, might be the wrong technology entirely? Not slower, not weaker, wrong. As in, based on a fundamental approach that a team of Chinese researchers just sidestepped completely. Because while the world has been obsessed with electrons, pushing tiny electrical charges through smaller and smaller transistors, a lab in Shanghai built a chip that doesn't really use electricity to compute at all. It uses light, actual beams of light, photons, doing the calculations. And they're claiming this light-powered chip can perform certain AI tasks up to 1,000 times faster than NVIDIA's best graphics chips, while using a fraction of the power and generating almost none of the heat. 1,000 times, not 1,000%, 1,000 times. Now, before you get swept away, that number comes with serious fine print, and I'm going to give you all of it, honestly, because the real story here is more interesting than the hype. By the end of this video, you'll understand exactly how a chip can compute with light, why that's such a big deal for AI, where the 1000X claim is real, and where it falls apart, and why this might be one of the most important shifts in computing in decades, happening, once again, in a place the rest of the world wasn't watching closely enough. Let's get into it. To understand why a light-based chip matters, you first have to understand the wall that every electronic chip on Earth is slamming into. Every computer you've ever used works by moving electrons. Tiny electrical charges flow through microscopic switches called transistors, flipping on and off billions of times a second. And that dance of electricity is what we call computing. It's worked beautifully for 70 years. But it has two problems that are getting worse every single year. And no amount of clever engineering fully solves them. The first is heat. When you push electricity through a material, that material resists, and resistance creates heat. The more powerful the chip, the more electrons you're shoving through it, the hotter it gets. Modern AI data centers now spend an enormous share of their entire electricity bill not on computing, but on cooling, just trying to stop the chips from cooking themselves to death. We've covered this on the channel before, just to feed their data centers. That is not a metaphor. That is a real plan, because electrons are hungry. So here's the question a handful of scientists started asking years ago. What if we stopped using electrons to compute? What if we used something that doesn't resist, doesn't heat up the same way, and moves at the fastest speed the universe allows? What if we computed with light? This is the part that sounds like science fiction, so let me make it concrete, because the core idea is genuinely elegant. Think about the last time light passed through a glass of water and bent, or split into a rainbow, or two ripples on a pond crossed and combined into a bigger ripple. Light naturally interacts. It bends, it combines. It interferes with itself in precise, predictable, mathematical ways. And here's the insight that took decades to turn into hardware. Those natural interactions are math. When two beams of light combine, the universe is, in a sense, performing a calculation, instantly, at the speed of light, using no transistors at all. A photonic chip is built to harness exactly that. Instead of wires carrying electrons, it has microscopic channels, waveguides, that carry beams of light. By splitting those beams, shifting them, and recombining them in carefully designed patterns, the chip performs the kind of mathematical operations that sit at the absolute heart of artificial intelligence. The multiplication of huge grids of numbers over and over, that's most of what training and running an AI actually is. And it turns out light is astonishingly good at doing that specific kind of math. Here's the analogy I find most useful. Traditional computing with electrons is like sending thousands of messengers through a crowded subway system. They bump into each other, they generate heat, they wait in line, they burn energy at every step. Photonic computing is like sending those same messages as laser beams through open air. No traffic, no friction, no heat from resistance. Just information moving at the one speed nothing in the universe can beat. That's the dream that's been chased for decades. The reason it stayed a dream so long isn't the physics, it's the manufacturing. And that's exactly the wall a Chinese institute just claims to have broken through. The chip at the center of this story comes from an institute called ChipX, working with a company called Turing Quantum, based in Shanghai. And what makes their announcement different from 20 years of photonic computing promises isn't a lab demo. It's a factory. Here's what they built. A 6-inch wafer made of a material called thin-film lithium niobate. And that material choice is the whole key, so hang on to it. Onto that wafer, they packed more than 1,000 optical components, the tiny light splitters, shifters, and channels that do the computing. Over 1,000 of them, integrated onto a single chip, all working together with light. Why does lithium niobate matter so much? Because it has an almost magical property. When light passes through it, you can precisely control that light, its phase, its intensity, its timing, and you can do it incredibly fast, with very little of the light lost along the way. It's stable at room temperature, which means no exotic, expensive cooling. For controlling light on a chip, it's close to an ideal material. The problem was always that working with it at scale, building real wafers full of these delicate structures without defects, was brutally hard. Many labs could make one. Almost nobody could make them reliably, in volume. ChipX says it cracked exactly that. In June, the institute launched what it describes as China's first pilot production line for these thin-film lithium niobate photonic wafers, with a capacity of around 12,000 6-inch wafers a year, each wafer yielding roughly 350 chips. Now, in raw numbers, 12,000 wafers is tiny compared to a giant silicon fab that pumps out hundreds of thousands. But for this specific cutting-edge type of photonic chip, it's a genuine industrial foothold, the difference between a science project and the early days of a real supply chain. And the developers claim these chips are already being used in the real world, in fields like aerospace and finance. So what about that headline number? Everything you do online is being watched. Your provider, advertisers, even governments. NordVPN encrypts your connection, hides your location, and unlocks the open internet from anywhere. Grab the deal, link in the description. The one, 000X. Here's where I have to be completely straight with you, because this is exactly the kind of claim that gets channels in trouble when they don't read the fine print. The 1,000 times faster than NVIDIA figure is real in the sense that it was genuinely claimed by the developers and reported by serious outlets like the South China Morning Post. But it comes with 3 critical pieces of fine print that the breathless headlines leave out. And you deserve all 3. First, and most important, that speed is for specific, narrow tasks, not general computing. A photonic chip is not a drop-in replacement for your computer's processor, and it's not a drop-in replacement for an NVIDIA GPU across the board. It's spectacularly fast at one particular kind of math, the optical interference calculations it's physically built for. For those specific workloads, the speedup is real and enormous. Ask it to do something outside that narrow lane, and the advantage vanishes. As one set of researchers put it, these chips can outperform GPUs by orders of magnitude, but only in tightly constrained domains. To use an analogy, it's like comparing a drag racing car to a regular sedan. On a perfectly straight quarter-mile track, the dragster is unbelievably, jaw-droppingly faster. But you can't drive it to the grocery store, you can't take it on the highway, and it can't turn corners. The 1000X is a drag strip number. NVIDIA's chips are the sedan you can drive anywhere. Both facts are true at once. Second, there's a separate but related breakthrough worth knowing, because it makes the story stronger, not weaker. Researchers at Shanghai Jiaotong University and Tsinghua University, in a paper published in the prestigious journal Science, demonstrated a fully optical chip called LightGen, built with over 2 million photonic neurons, that ran image and video generation tasks more than 100 times faster and more efficiently than a leading NVIDIA GPU. So this isn't a single lab making a wild claim. Multiple serious Chinese research teams are independently showing that light-based chips can crush GPUs at narrow AI tasks. The pattern is real even where any single number is debatable. Third, the honest caveats. The technology still faces real challenges. Yields are low, the long-term stability of these chips under sustained heavy use isn't fully proven, and exactly how that 1000X was measured remains a little murky. This is early-stage, frontier technology. It is not about to replace every NVIDIA chip in every data center next year. So here's the fair summary, the one you won't get from the hype videos or the dismissive ones. China has not made NVIDIA obsolete, but it has demonstrated in real silicon coming off a real pilot line that for the specific math that AI leans on most heavily, there is a fundamentally different and dramatically more efficient way to compute, and China is currently the one scaling it toward production. Here's the part of this story that I find genuinely fascinating, and it ties back to everything else happening in this race. When the world's biggest tech players thought about the future of radical new computing, most of them, especially in the West, bet heavily on a different approach: superconducting quantum computers. Incredibly powerful in theory, but with a brutal catch. They have to be cooled to nearly absolute zero, colder than deep space, inside giant, fragile, fantastically expensive refrigeration systems. It's a moonshot that requires extraordinary infrastructure. China made a different bet. It poured serious effort into room temperature photonic computing, chips that use light and work at normal temperatures, no exotic cooling required. And here's why that bet is so clever and so consistent with the pattern we keep seeing. Photonic chips, unlike the most advanced electronic chips, can be manufactured using older, more mature fabrication processes, the kind that don't require the single most advanced, most restricted chip-making machines on Earth. Do you see the move? Just like the GPU-free supercomputer, just like the new approach to chip design we covered recently, being blocked from the cutting edge of electronic chip-making, pushed China to invest heavily in a different kind of computing entirely, one where the restrictions matter far less. Light doesn't need a 2-nanometer transistor. Photonic computing is a lane where the export controls lose much of their grip. The wall once again didn't stop the water. It just changed the direction it flowed. And this time, it flowed toward light. Let me zoom out, because it's easy to lose the forest for the trees here. Nobody serious is claiming silicon is dead or that NVIDIA is finished. Electronic chips are flexible, mature, and woven into everything. They are not going anywhere for a very long time. The realistic future isn't light replacing electronics, it's light joining them. Imagine a data center where the flexible, general-purpose work runs on traditional chips, but the specific, brutal, repetitive math at the heart of AI gets handed off to photonic chips that do it 100 or 1,000 times more efficiently. A hybrid, the best of both worlds. And that future matters enormously for one reason above all: energy. If even a portion of the world's exploding AI workload can be shifted onto chips that compute with light, generating less heat, sipping a fraction of the power, it could meaningfully bend the curve on AI's terrifying energy appetite. That's not just a speed story, it's a sustainability story. It might be the difference between an AI future that's possible and one that's strangled by its own power bills. And the strategic dimension is just as large. For years, the entire framework of this technology race assumed the battlefield was electronic chips. Who can make the smallest transistor? Who controls the best lithography machine? Photonic computing potentially reframes the whole contest. It's a different battlefield, with different rules, and China has quietly built one of the strongest early positions on it. Whether or not any single 1000X headline holds up, that is the development the rest of the world should be paying attention to. Here's my honest opinion. I think the smartest way to hold this story is with two ideas at the same time, refusing to collapse into either easy version. On one hand, the people shouting China just made NVIDIA obsolete with a magic light chip are running way past the evidence. The 1000X is a narrow drag strip number, the yields are low, and this is early technology with real unanswered questions. Anyone selling you that is selling hype. But on the other hand, the people rolling their eyes and saying it's just a niche lab toy, ignore it, are making the bigger mistake, and it's the same mistake people keep making in this race. Because underneath the inflated headline is something genuinely real. Multiple serious Chinese teams, publishing in journals like Science, building actual chips on an actual pilot production line, proving that light-based computing can demolish the world's best GPUs at exactly the kind of math AI needs most. That's not nothing. That's the early shape of a different future. What strikes me most is how familiar the pattern has become. Cut off from the most advanced electronic chip making, China didn't just try harder to catch up on the same road, it invested in a road that goes around the roadblock entirely. Light instead of electrons, room temperature instead of near absolute zero, older fabs instead of forbidden machines. Over and over, the constraint becomes the catalyst. I genuinely don't think that's luck anymore. I think it's the defining strategy of this entire era, and we're watching it play out in real time. So here's my question for you, and I really want your honest answer. Do you think the future of AI computing belongs to light, these photonic chips that sip power and run cool? Or will electronic chips like NVIDIA's stay on top because they can do everything, even if they run hot and hungry? Is light the real future, or just a brilliant specialist that'll never leave its narrow lane? Drop your honest take in the comments. I read every single one, and I have a feeling this one's going to spark a real debate. If you want to keep following this, the breakthroughs, the workarounds, the technologies the rest of the world underestimates until they suddenly can't, subscribe to Eastern Engine and hit the notification bell. Chips, light, energy, supercomputers, the entire foundation of modern technology is being rewritten right now, and we break it all down before the mainstream catches up. Thanks for watching. I'll see you in the next one.
So Apple looking for relief from the chip crunch behind this week's Mac and iPad price hikes. And I'm told by a person briefed on the discussions, that includes asking the administration for more flexibility to work with Chinese memory suppliers. And of course follows CEO Tim Cook telling the Journal just last week that all vendor options are back on the table. Now the two key names in question are YMTC and CXMT, China's heavily state-backed domestic memory players. YMTC makes NAND flash storage, CXMT makes DRAM, the working memory.
China's largest memory chip maker has reportedly secured a deal worth nearly $3 billion from Tencent, one of the biggest technology companies in the country. Just days after reports said Apple was asking Washington for political clearance to buy memory from the same Chinese supplier, Changshin Memory Technologies, better known as CXMT, has landed what may be the strongest commercial endorsement in its history. The reported agreement covers more than 20 billion yuan, or roughly $2.94 billion in DRAM chips for Tencent servers over several years. That memory will support cloud computing, databases, and artificial intelligence workloads. CXMT is no longer being treated only as a protected domestic challenger. It is becoming a supplier that major Chinese technology companies may be willing to depend on at enormous scale. If Tencent is prepared to commit billions of dollars to CXMT, could Apple be next? It is a story about how the global memory shortage, the AI infrastructure boom, and political pressure are rewriting the semiconductor supply chain. For decades, the DRAM market has been dominated by three companies. Samsung Electronics, SK Hynix, and Micron control most global production. That concentration gave them enormous influence over pricing, technology, and supply. When demand rises faster than new factories can respond, there are very few alternative suppliers capable of filling the gap. AI data centers are consuming huge amounts of advanced memory. Large models need memory close to processors so data can move quickly enough to keep expensive computing systems busy. Cloud companies also require conventional server DRAM for databases, virtualization, storage systems, and general computing. High-bandwidth memory receives most of the attention because it sits beside advanced AI accelerators. And when the biggest technology companies build infrastructure at the same time, demand spreads across the entire market. According to the latest reporting, DRAM contract prices rose roughly 95% quarter over quarter during the first quarter of 2026.
Used in iPhones, PCs, and servers. Both are young companies compared with Samsung, SK Hynix, and Micron, which built their businesses decades ago. But they are gaining share quickly. Counterpoint says YMTC now has 13% of the global NAND market, while CXMT has 8% of DRAM. CXMT also gaining ground fast, preparing for what could be mainland China's largest IPO in years. And Counterpoint is hearing from stakeholders in the supply chain that these Chinese memory names can
Large cloud companies do not want to enter every quarter uncertain about price, availability, or delivery. And in some cases, they are willing to provide prepayments or commit years in advance to secure supply. The reported CXMT agreement may run for 3 years, while another source suggested it could extend as long as 5. That means Tencent is not simply making a spot purchase to cover a temporary shortage. DRAM is one of the most difficult semiconductor businesses to enter. The product may look simple compared with a central processor or graphics chip, but manufacturing it profitably requires extraordinary precision. A memory producer must create billions of microscopic cells that store data reliably. Those cells must work at high speed, consume little power, survive repeated use, and maintain consistency across huge production volumes. That increases cost and makes it difficult to compete with established companies that have spent decades refining their processes. Its early products were aimed mainly at China's domestic market, and many international customers had little reason to take the company seriously. A company does not need to be the global technology leader to become strategically important. It only needs to offer acceptable products, meaningful capacity, and a willingness to sign contracts when other suppliers are constrained. The company reportedly held about 7.7% of the global DRAM market in 2025, making it the fourth largest producer. In a tight market, even a single-digit share can influence prices and customer negotiations. It currently operates major 12-inch DRAM fabrication plants in Hefei and Beijing, with combined output estimated at around 300,000 wafers per month. New facilities and additional expansion could eventually double that figure to approximately 600,000 wafers per month. The company is also developing operations in Shanghai, including DRAM production and high-bandwidth memory packaging. But Tencent's reported commitment gives CXMT something extremely valuable: demand visibility. It can help a manufacturer plan equipment purchases, staffing, material supply, and future process development. CXMT received approval in May for an initial public offering on Shanghai's Star Market. The company reportedly aims to raise 29.5 billion yuan. Investors want proof that growth is not based only on policy support or optimistic forecasts, and they want evidence that the company's products are important enough for large buyers to sign long-term commitments. Major Chinese technology companies are trying to reduce their exposure to foreign supply restrictions. Tencent, Alibaba, ByteDance, Lenovo, Xiaomi, and other firms all depend on semiconductors produced or controlled by companies outside mainland China. Export controls have already restricted China's access to advanced AI accelerators and semiconductor manufacturing equipment.
Undercut incumbent suppliers by up to 30% depending on the contract. Now, Apple, it's been here before. 4 years ago, the company explored using YMTC chips in China-sold iPhones, then retreated under pressure from Washington. But the shortage is more severe now, and Apple has a lot less leverage with its traditional suppliers. That's why more tech companies are looking for alternatives. HP and Lenovo are both reportedly pursuing Chinese memory as a way to diversify supply. But this is not a quick swap.
A cloud company cannot expand infrastructure if it cannot secure enough components. So Chinese technology firms have strong reasons to support a domestic supplier, even if that supplier remains behind the global leaders. This does not mean they will accept any product at any price. Large data center operators care about performance, failure rates, power consumption, compatibility, and total operating cost. Server memory must run continuously under heavy workloads. A defective module can create outages, corrupted data, or expensive maintenance. Tencent therefore has to believe that CXMT can meet a meaningful standard. That is why the reported agreement is more important than a symbolic government order. Tencent is not buying memory for a demonstration project. It needs chips for real servers supporting real customers. The contract could therefore become one of the strongest tests of CXMT's manufacturing discipline. Success would generate more than revenue. It would create operational data. Every shipment provides information about defect rates, system compatibility, thermal behavior, and long-term reliability. That feedback can help CXMT improve future products. Higher production volumes also allow engineers to identify recurring process problems and improve yield. Semiconductor manufacturing becomes more competitive through repetition. The more wafers a company processes, the more opportunities it has to learn. This is one reason large customers can accelerate a supplier's development. Tencent may be buying memory because it needs supply today, but the partnership could help create a stronger competitor tomorrow. That is where Samsung, SK Hynix, and Micron should pay attention. CXMT is not about to replace them. The established leaders remain ahead in manufacturing technology, scale, customer trust, and advanced products. They also dominate high-bandwidth memory, which currently delivers some of the strongest margins in the industry. CXMT still faces serious challenges. One reported problem is low yield on next-generation DDR5 products. That matters because DDR5 is increasingly important for modern servers and personal computers. A company can announce impressive specifications, but customers ultimately care about how many reliable chips can be produced at acceptable cost. If yield remains weak, expansion alone will not solve the problem. More factory capacity can simply produce more expensive defective wafers. CXMT must therefore improve technology while expanding volume. That is difficult, but the Tencent deal provides time and money. And if CXMT can use this period of high prices to improve yield, the competitive landscape could change. The memory industry is cyclical. Shortages produce high prices and heavy investment. High prices encourage companies to build more capacity. Eventually, supply catches up. Prices fall. Weak producers then struggle because memory becomes a commodity again. CXMT's challenge is to use the current upcycle to become efficient before the market turns. The company's recent financial performance shows how powerful the upcycle has been. Its first quarter revenue reportedly reached 50.8 billion yuan, an increase of about 700% from a year earlier. It also recorded a net profit of 25 billion yuan after reporting a loss in the previous year. Those numbers are extraordinary, but they should be interpreted carefully. A booming memory market can make almost every producer look stronger. The real test comes when prices normalize. Can CXMT still compete when buyers have more options? Can it maintain margins? Can it continue investing? And can it keep customers when Samsung, SK hynix, and Micron have available capacity again? Tencent's long-term agreement may protect CXMT from some of that uncertainty. Now we come to Apple. Reports say Apple has been lobbying the United States government for clearance to purchase memory chips from CXMT. The request does not mean a contract has been signed. It does not mean CXMT memory is already inside MacBooks or iPads. And it does not mean Apple plans to abandon its current suppliers. Apple still depends on Samsung, SK hynix, and Micron. But the company recently raised prices on several Mac and iPad models after memory and storage costs rose sharply.
Qualifying a new supplier can take months to as long as 2 years with device testing, reliability checks, factory audits, and technical sharing. And it's especially complicated with YMTC. It's been on the Commerce Entity List since 2022, meaning that U.S. companies need approval to share their blueprints and other proprietary details with them.
That makes another supplier extremely attractive. Apple does not need CXMT to replace the market leaders. It only needs CXMT to provide qualified products at meaningful volume. Even a limited supply agreement could strengthen Apple's negotiating position. It could reduce dependence on 3 dominant producers. And it could help Apple avoid even larger price increases if the shortage continues. The Tencent agreement may make CXMT easier for Apple to evaluate. A multi-billion-dollar server contract gives the company commercial credibility. It shows that another major technology buyer is willing to make a long-term commitment. But Apple's standards are different. For laptops and tablets, power consumption is critical. Memory affects battery life, heat, system stability, and product reliability. Apple also demands consistency across millions of devices. A supplier must deliver the same quality from one production batch to the next. It must support product launches, regional demand changes, and strict delivery schedules. So Tencent's approval would not automatically lead to Apple qualification. Server DRAM and low-power mobile memory serve different needs. Apple would still need extensive testing, audits, traceability, and supply guarantees. The political barrier may be even harder. CXMT is included on a Pentagon list of companies alleged to have links to China's military. That listing does not create a simple universal ban on every commercial transaction, but it creates serious political and reputational risk. American lawmakers may argue that allowing Apple to purchase from CXMT would strengthen a strategic Chinese semiconductor producer. They may also warn that Apple could become dependent on a supplier that Washington later restricts. Apple wants confidence before spending months qualifying products and redesigning logistics. A deal that is legal today could become impossible tomorrow. That uncertainty explains why Apple reportedly approached the government before moving forward. The White House has not publicly approved the request. Apple has not announced a supply agreement. And CXMT has not confirmed that it will supply Apple. So the title, Apple may be next, must remain a possibility, not a conclusion. Still, the Tencent deal changes the context. Before this agreement, CXMT could be described as a rising Chinese memory producer, seeking credibility. After a $3 billion commitment, it begins to look like a strategic supplier with major customers, rapid growth, expanding capacity, and access to capital. That does not guarantee Apple will follow, but it makes the possibility more believable. My take is that the most important part of this story is not the dollar amount. It is the speed at which CXMT's position is changing. A global shortage has turned capacity into leverage. AI demand has pushed memory from a commodity component into a strategic resource. Chinese technology companies are locking in domestic supply, and Apple is reportedly considering a supplier that would have seemed politically unrealistic only a short time ago. The old memory market was built around 3 dominant companies, and predictable customer relationships. The new market is becoming more fragmented, more political, and more expensive. Tencent wants supply security. CXMT wants scale and validation. China wants semiconductor independence. Apple wants lower costs and another negotiating option. Washington wants to limit the growth of strategic Chinese technology. Those goals are now colliding inside one of the most basic components in modern computing. A small memory chip has become part of a much larger contest over AI, industrial power, and national security. The Tencent contract may prove that CXMT can serve China's largest technology companies. The Apple decision could determine whether it can cross into the supply chain of one of America's most influential corporations. So what do you think? Should Apple be allowed to buy MT did not just win a $3 billion order. It may have won the credibility needed to compete for something even bigger. There's a material so pure that, until a few days ago, only a tiny handful of places on the planet could make it. Not a handful of countries, a handful of facilities. It was one of those quiet, invisible bottlenecks that the rest of the world barely thinks about, yet it sits underneath one of the most important technologies of the next century. China just started mass producing it. The material is called silicon-28, and calling it pure doesn't quite capture it. It's purified to better than 99.99%, which earns it a nickname scientists actually use, the purest silicon on Earth. On June 15, 2026, China's National Nuclear Corporation announced it had achieved independent, large-scale production of this material for the first time. No headlines about a flashy new gadget, no glowing phone chip to hold up on a stage, just a slab of the quietest, cleanest silicon humanity knows how to make. And here's why that matters more than almost any product launch. This specific material is the foundation that one of the most promising paths to a working quantum computer is built on. Without it, an entire approach to quantum computing essentially can't scale. With a domestic, mass-produced supply of it, a door that was previously held shut by a few foreign suppliers just swung open for China. Now, like every story on this channel, there's important nuance here, and I'll give you all of it honestly, including why this is a foundation stone and not a finished building. But by the end of this video, you'll understand what makes this silicon so special, why noise is the great enemy of quantum computing, why only a few places on Earth could make this stuff, and why a quiet materials announcement might matter more than the loudest chip launch of the year. Let's get into it. Start with the basics, because silicon is one of those words everyone half knows. Silicon is the bedrock of the modern world. It's the second most abundant element in the Earth's crust. It's literally in sand. Purify it, slice it into wafers, etch tiny circuits onto it, and you get the chips that run your phone, your laptop, every device you own. The entire digital age is built on refined sand. We've been making ordinary electronics-grade silicon at massive scale for over half a century. That part is not new and not hard for anyone anymore. But here's the thing most people never learn. Not all silicon atoms are identical. Silicon comes in slightly different versions of itself, called isotopes, atoms with the same chemical identity, but slightly different weights. Natural silicon is a blend of three: silicon-28, which makes up about 92%, silicon-29 at roughly 5%, and silicon-30 making up the rest. For normal electronics, this blend is completely fine. Your phone's processor does not care which silicon isotopes it's made of. For 70 years, nobody needed to separate them. The mixture worked perfectly. But quantum computing is not normal electronics. And in the quantum world, that small, harmless-seeming 5% of silicon-29 turns out to be a saboteur. It's the difference between silicon that's good enough to run a supercomputer and silicon that's good enough to run a quantum computer, and those are two completely different bars. To understand why that tiny fraction matters so enormously, you have to understand the single greatest enemy of quantum computing. And that enemy has a name: noise. Here's the heart of it, and I'll keep it concrete. A regular computer thinks in bits, switches that are either on or off, 1 or 0. Rock solid, dependable, binary. A quantum computer uses something far stranger and far more powerful: the qubit. A qubit can exist in a delicate blend of both states at once, and it's this fragile in-between condition that gives quantum computers their almost magical potential to solve problems that would take a normal supercomputer billions of years. But that power comes with a curse. Qubits are unbelievably fragile. They hold their delicate quantum state for only a fleeting moment before the outside world disturbs them, and the information collapses into useless randomness. Scientists call this collapse decoherence, and it is the central villain of the entire field. The whole game of building a quantum computer is, in large part, a desperate fight to keep qubits in their delicate state for as long as possible. Every extra fraction of a second of stability is hard-won. So what disturbs them? Noise. Not sound, environmental interference. Heat, stray electromagnetic fields, vibration, and, crucially, magnetic disturbance from the very material the qubit is sitting inside. This is where that 5% of silicon-29 becomes a wrecking ball. Here's the key piece of physics. Silicon-28 has a property called zero nuclear spin. In plain terms, its atomic nucleus is magnetically silent. It sits there perfectly still and quiet, generating no magnetic disturbance whatsoever. But silicon-29 is different. Its nucleus does have a spin. It acts like a tiny restless magnet, constantly flickering and wobbling. Scientists have a wonderfully descriptive name for the havoc this causes. They call it nuclear flip-flopping. Imagine you're trying to keep a single feather perfectly still and balanced on your fingertip. That's the qubit. Now imagine the room is full of tiny invisible fans randomly puffing air at it from every direction. Those puffs are the silicon-29 atoms magnetically jostling your qubit, knocking it off balance, destroying the delicate state you fought so hard to create. The more silicon-29 around your qubit, the more puffs of disturbance, and the faster your quantum information falls apart. Now the solution becomes obvious. If silicon-29 is the source of the noise, get rid of it. Strip it out. Engineer silicon that is almost pure silicon-28, magnetically silent, a calm and quiet home where a qubit can hold its delicate state in peace. Do that, and you've built what researchers describe as a solid-state vacuum, an environment so quiet the qubit can survive dramatically longer. That is exactly what the purest silicon on Earth is. And it changes everything about how stable a silicon qubit can be. So if everyone knows silicon-28 is the answer, why isn't every quantum lab swimming in it? Why was this announcement a genuine breakthrough rather than a routine purchase order? Because separating isotopes is one of the hardest things in all of industrial science. Remember, silicon-28, silicon-29, and silicon-30 are chemically identical. They behave the same in every chemical reaction. You cannot separate them with chemistry. There's no reaction that grabs one and leaves the others. The only thing that distinguishes them is a minuscule difference in weight, because each has a slightly different number of neutrons. So to purify silicon-28, you have to sort atoms by weight, one tiny mass difference at a time, until you've stripped out almost every last silicon-29 and silicon-30 atom from the mix. This is brutally difficult. It typically involves converting the silicon into a gas, then spinning that gas in sophisticated centrifuges, or using other exotic enrichment techniques to gradually concentrate the lighter silicon-28, repeating the process over and over to inch the purity higher and higher. Pushing past 99.99% purity at any meaningful quantity demands enormous technical mastery and expensive specialized infrastructure. It's closer to the world of nuclear-grade isotope enrichment than to ordinary chip making, which is precisely why China's nuclear corporation, not a traditional chip maker, is the one that cracked it. And here's the part that gives this story its strategic weight. Until now, the ability to produce ultra-pure silicon-28 at scale was concentrated in a very small group of overseas players, facilities tied to Russia, to Europe, and to US-linked supply chains. If you were a Chinese quantum lab and you needed this material, you were dependent on importing it from a handful of foreign sources. That's a choke point, a quiet, invisible one, not a banned machine or a blocked chip, but a raw material that a few outside suppliers controlled. This is the pattern that should feel familiar by now if you watch this channel. The most powerful restrictions aren't always the loud, obvious ones. Sometimes the real leverage is buried in an unglamorous material that nobody outside the field even knows exists. And China just removed that particular piece of leverage from the board by moving silicon-28 from imported from a few foreign suppliers to mass-produced at home. The achievement isn't a finished quantum computer. It's something quieter and in the long run, possibly more important. Supply chain independence in a material the future may be built on. Now, you might be wondering, there are several different ways people are trying to build quantum computers. Why does this particular path, the silicon one, matter so much that purifying its core material is a national-level achievement? Because silicon has one colossal advantage no other approach can match. The entire planet already knows how to manufacture it. Think about it. For decades, the world has poured trillions of dollars and unfathomable engineering effort into building silicon chips with billions of features etched at near-atomic precision. There are vast factories, refined techniques, and deep institutional knowledge dedicated to manipulating silicon better than any other material in human history. If you can build a quantum computer out of silicon, you can potentially tap into all of that existing manufacturing muscle to scale it up, instead of inventing an entirely new industry from scratch. That's the dream of silicon quantum computing. Other leading approaches, like the superconducting chips and trapped ion machines you may have heard of, are powerful, but require building exotic infrastructure largely from the ground up. Silicon qubits promise something seductive: the quantum future, manufactured on a foundation the world has already spent 70 years mastering. And critically, because silicon qubits can be incredibly small, this approach holds the promise of one day fitting thousands of qubits on a single chip, and potentially millions on one device, exactly the kind of scaling you'd need for a quantum computer that can actually change the world. But, and this is the catch, that entire vision rests on having silicon quiet enough to keep the qubits stable. The dream is only as good as the purity of the material underneath it, which is exactly why mass-producing the purest silicon on Earth isn't a footnote. It's the literal foundation the whole silicon quantum dream stands on. Remove the supply problem for that material, and you've cleared one of the biggest roadblocks standing between China and a scalable silicon quantum computer. Now let me be completely straight with you, because I'd rather you trust this channel than oversell you a story. Mass-producing silicon-28 does not mean China has built a working quantum computer. It does not mean the quantum era arrived last week. What it means is that China has secured a critical ingredient, and ingredients, however essential, are not finished meals. There are real, hard problems still standing between this material and a useful quantum machine. Silicon qubits, across the whole field worldwide, are still at an early stage. Researchers have coherently controlled only a handful at a time, somewhere in the range of a few to a dozen qubits, with recent demonstrations reaching around 11. That's a long, long way from the thousands or millions you'd need for a quantum computer that can crack hard real-world problems. Getting from a dozen qubits to a million is a staggering engineering climb, and pure silicon alone does not get you there. You still need precise qubit control, error correction, packaging, wiring, and a dozen other unsolved challenges. So the honest framing is this: China has not won quantum computing. No one has. What China has done is eliminate a specific supply chain vulnerability and secure domestic control over a foundational material that its silicon quantum ambitions absolutely depend on. It's a step that's necessary but not sufficient, a cleared roadblock, not a crossed finish line. The headlines calling this the breakthrough that gives China quantum supremacy are getting ahead of reality, but the cynics waving it away as just some pure silicon, who cares, are missing the strategic point entirely. In a field where the whole game is fighting noise, controlling the quietest material on Earth is exactly the kind of unglamorous advantage that compounds over years. And there's a strategic dimension that makes this bigger than quantum computing alone. The same institute announced it has now mastered the production of 26 stable isotopes across 12 elements, materials with uses stretching into nuclear medicine, aerospace, particle physics, and deep space exploration. Silicon-28 is the headline, but the real story may be that China has built an entire domestic isotope enrichment industry, turning a whole category of materials it once imported into things it now makes itself. Step back, and you'll notice this is the same shape as story after story we've covered. It's almost never the loud, obvious component that becomes the decisive battleground. It's the quiet foundational layer underneath, the substrate beneath the chip, the memory beside the processor, the cooling material that keeps it from melting, and now the ultra-pure raw silicon beneath the qubit. Over and over, the real leverage in a technology race lives in the parts most people never see, and the country that secures those invisible foundations quietly buys itself a future the headlines won't notice until much later. And the response to restriction keeps rhyming too. Faced with dependence on a handful of foreign suppliers for a critical material, China didn't shrug. It built its own production from scratch, using expertise borrowed from its nuclear industry, and removed the dependency entirely. Whether it's lithography, memory, or now isotope enrichment, the pattern holds. A choke point identified becomes a choke point engineered around. I genuinely don't think it's a coincidence anymore. It's a deliberate, systematic march to control every foundational layer of the technologies that will define the rest of this century. This particular announcement won't trend the way a flashy gadget does. There's no screen to admire, no benchmark to gawk at. But years from now, when silicon quantum computers are real and scaling, the quiet ability to manufacture the purest silicon on Earth may turn out to have been one of the foundation stones the whole thing was built on. Here's my honest opinion. I find these boring material stories more revealing than the splashy ones, precisely because almost nobody pays attention to them. It's easy to get excited about a chip you can hold up on a stage. It's much harder to get excited about a slab of ultra-pure silicon, and that's exactly why this kind of move is so telling. The companies and countries that win technology races are usually the ones quietly locking down the unglamorous foundations, while everyone else is dazzled by the product launches. Silicon 28 is the definition of an unglamorous foundation, and China just made sure it owns its supply of it. Do I think this means China is about to leap ahead in quantum computing? No, the field is too young, the qubit count's too small, the road too long for any single material to decide it. But do I think it's a meaningful, deliberate piece of a much larger strategy that's easy to underestimate? Absolutely. The whole point of this kind of move is that it doesn't look like much until, one day, it suddenly looks like everything. The quietest silicon on Earth, made to silence the noise that kills qubits, secured at home instead of bought abroad. It's a small story that's secretly a big one. And those, in my experience, are usually the ones worth paying attention to. So here's my question for you, and I genuinely want your honest take. Do you think quantum computing is going to arrive sooner than we expect and quietly transform everything? Or is it overhyped, perpetually almost here, and decades further away than the headlines suggest? Are you a quantum optimist or a quantum skeptic? Drop your real opinion in the comments. I read every single one. If you want to keep following this, the breakthroughs, the invisible foundations, the quiet moves that matter long before the world notices, subscribe to Eastern Engine and hit the notification bell. Chips, materials, quantum, the entire foundation of modern technology is being rebuilt right now, and we break it all down clearly and honestly before the mainstream catches on. Thanks for watching. I'll see you in the next one. Here's something that should bother you. Right now, somewhere in the Gobi Desert, a machine is releasing air that was frozen solid last Tuesday, and that release is powering a city through the night. In Shanghai, a factory is pulling carbon dioxide out of the sky, combining it with hydrogen split from seawater, and producing jet fuel molecule for molecule identical to what comes out of an oil well. In Shanxi province, an ammonia plant is running on nothing but nitrogen from the air and sunlight. No natural gas, no extreme heat, no fossil fuels, and it hasn't stopped for 50 days straight. 6 breakthroughs, all running right now. Not in labs, in the real world, on factory floors, with real investors writing real checks. And almost none of it is in the news. That's not an accident. The story underneath all of it is so large and so structurally threatening to how the world currently works that it's easier to report each piece individually as a curiosity than to report them all together as what they actually are: a coordinated dismantling of the energy architecture the entire modern world was built on. This is that story. And by the end, you'll understand why a Chinese oil refinery voluntarily spending 800 million yuan to stop being an oil refinery is actually the most important data point in all of it. The choke point everyone ignores. To understand why these breakthroughs matter, you need to understand what they're solving for. China manufactures more physical goods than any economy on Earth. Pick up a random product in any store in any country. There's a high probability that something inside it, a component, a material, a subassembly, started as energy consumed inside a Chinese factory. That scale of production is staggering, and it has a single, brutal vulnerability almost nobody outside military planning circles talks about. More than 70% of China's oil comes from abroad. That alone is manageable. What isn't manageable is the geography of how it arrives. Almost every drop travels by ship through the Strait of Malacca, a stretch of water between Malaysia and Indonesia that, at its narrowest point, is under 3 kilometers wide. 1 in 4 barrels of oil traded on the entire planet squeezes through that gap. Military strategists have a name for the anxiety this creates: the Malacca dilemma. At its core, it's simple. If that passage gets blocked, by conflict, by political decision, by anything, Chinese factories don't slow down. They stop. Not in weeks, days. China has spent decades trying to route around it. Pipelines through Central Asia, deepwater ports in Pakistan, underground emergency reserves. None of it solves the root problem because the oil still has to cross the ocean first. The pipeline from Pakistan helps until the oil reaching Pakistan is cut off upstream. The only solution that actually works is making the energy locally, from materials that are everywhere, that nobody can blockade. That's what these 6 breakthroughs are. Not energy innovation for its own sake. A systematic, deliberate disassembly of the Malacca dilemma, one technology at a time. Fuel made from nothing. The first piece is almost offensive in its simplicity once you understand it. A facility in Shanghai, opened January 2026, built by a company called Carbonology, is producing jet fuel from carbon dioxide and water. Not biofuel, not almost jet fuel, actual aviation fuel, chemically identical to what refineries pump out of crude oil. A plane engine cannot tell the difference. A pilot cannot tell the difference. The only way you'd know is if someone told you. The process. Machines pull CO2 from the atmosphere. Solar-powered electrolyzers split water into oxygen and hydrogen. The CO2 and hydrogen combine under controlled heat and pressure. The result is a liquid hydrocarbon, the same molecule, built from scratch, from ingredients that exist literally everywhere on Earth. Current output is 100 tons per year. A proof of concept scale. But the roadmap goes 1,000 tons, then 5,000, then a commercial facility targeting 100,000 tons annually by 2027. Sequoia China has already written a check. And here's the detail that tells you this isn't vaporware. European aviation law already mandates a minimum percentage of sustainable fuel in aircraft, growing to a much larger share by 2050. The buyers were legally required to exist before the factories finished building. That almost never happens. It means the market was created by regulation before supply could catch up, the most favorable commercial position possible. This solves the where does the fuel come from problem. But fuel requires power to produce, and power has its own problem, the night problem, solved with frozen air. Solar and wind have a flaw so obvious it almost goes unexamined. They stop when conditions change. The sun goes down. The wind dies. Even the largest battery installations in the world typically bridge gaps of 4 to 5 hours. That's enough to cover a residential suburb. It is not enough to run a continuous industrial operation through a cloudy week. In the Gobi Desert, engineers tried something so straightforward it sounds like it shouldn't work. They froze air. Take normal atmospheric air, the mixture you're breathing right now, and cool it to minus 194 degrees Celsius. At that temperature, it becomes a liquid you can pump into tanks and store like diesel. When you need the energy back, you let the liquid air warm up and expand. It expands 700 times. That expansion spins turbines. The turbines generate electricity. The facility next to a 250 megawatt solar farm uses daytime surplus power, energy that would otherwise be wasted, to freeze air instead. At night, that stored air powers a city for 10 hours, double the duration of the best battery systems available, using no lithium, no cobalt, no rare earth minerals requiring international supply chains, just air and industrial equipment that can be manufactured anywhere. The plant has been running since late 2025, not a prototype, a working facility producing roughly 180 gigawatt hours of energy per year. The night problem is solved. But there's a separate category of machine, ships, heavy industrial equipment, long-haul freight that can't run on stored electricity. Those need actual fuel, and the answer to that comes from a molecule most people associate with cleaning products. The boring chemical that could end oil shipping. Ammonia, industrial solvent, fertilizer precursor, the smell from a horse stable. Also, the most promising carrier for clean hydrogen that humanity currently has. Here's the problem ammonia solves. Hydrogen is a spectacular clean fuel. Burn it, and the only byproduct is water. But hydrogen is also the lightest element in existence, which means storing and shipping it requires either extreme compression or extreme cooling. Expensive, technically demanding, and logistically difficult at ocean freight scale. You can't casually ship hydrogen across the Pacific the way you ship crude oil. Ammonia solves this by acting as a container. Pack hydrogen into ammonia molecules, ship the ammonia as a liquid at normal industrial temperatures, unpack the hydrogen at the destination. It's a lunchbox for energy that happens to use chemistry instead of plastic. The traditional ammonia production process, Haber-Bosch, invented in 1909, requires massive heat, enormous pressure, and enormous quantities of natural gas. It also feeds roughly half the world's population through fertilizer. Stopping it isn't an option. In Shanxi province, a facility is now making ammonia at room temperature. No natural gas, no extreme pressure, nitrogen pulled from air, hydrogen made from water via solar power, combined without the energy-intensive conditions the century-old process requires. It has operated continuously for over 50 days at more than 90% efficiency. Japan and South Korea are already running ammonia-powered cargo ships on live ocean routes with real freight. If bulk shipping, which moves 90% of everything traded globally, migrates to ammonia, oil's role in maritime fuel doesn't get smaller. It becomes optional. That word, optional, is the one that should give you pause. An optional commodity is a different kind of commodity than a necessary one. The thread connecting all of it. Every technology described so far needs hydrogen. The synthetic jet fuel factory needs hydrogen to build the fuel molecule. The ammonia plant needs hydrogen as its core ingredient. The electrolyzers powering the frozen air facility run on clean electricity. Electricity that's increasingly used to produce hydrogen as an intermediate step. This isn't coincidence. Hydrogen is the connective tissue of the entire system, so the relevant question becomes, how much can one country produce? In 2019, China's clean hydrogen output was roughly 23,000 tons annually. By 2024, it was 125,000 tons. Nearly a six-fold increase in 5 years, still accelerating. One province, Guangdong, is building an offshore wind installation specifically to power water-splitting electrolyzers, targeting 80,000 tons of hydrogen per year from a single project. The more significant number, China currently manufactures approximately 65% of the world's electrolyzers, the machines that split water into hydrogen. This is the detail most coverage of this space completely ignores. It doesn't matter how much hydrogen a country wants to produce if it needs to import the machine that makes it. Whoever builds the electrolyzer controls the pace of the entire transition, not just domestically, but for every nation purchasing those machines globally. South American hydrogen programs, African green ammonia plants, European synthetic fuel facilities, they all need electrolyzers. Most of those machines will ship from one country. The end game. Every technology discussed so far still has one constraint. It needs energy input. Solar needs sun, wind needs wind. Even liquid air storage is just shifting energy in time, not creating it. There is one technology that, if it works, removes that constraint permanently. China's East Reactor, experimental advanced superconducting tokamak, set a new world record this year for sustained plasma stability, surpassing what physicists call the Greenwald limit, a threshold in plasma density that defines the boundary of what a controlled fusion reaction can sustain. It held that condition longer than any machine on Earth has managed before. Fusion is not ready to power cities. Anyone claiming otherwise isn't doing analysis. They're selling something. The engineering distance between a record-breaking plasma duration and a grid-connected power plant is still measured in decades of work. But here's the honest framing that most coverage misses. Fusion doesn't need to arrive soon to matter now. The investment patterns around it are themselves a signal. When a country commits serious capital and serious scientific infrastructure to fusion research, it's communicating a planning horizon that most Western governments don't operate on. China is building for 2050 and 2070, the way it built high-speed rail for 2030 in 2005. Fusion is the long bet underneath the short bets. The honest catch: none of this is frictionless. Synthetic fuel at 100 tons per year is not synthetic fuel at 100 million tons per year. Scaling industrial chemistry is not just multiplication. Every increase in volume introduces new engineering problems. Carbonology's 2027 target of 100,000 tons is ambitious. Whether the unit economics stay favorable at that scale is unproven. Green ammonia at room temperature has run for 50 days. 50 days is not 50 years. Long-duration industrial reliability is a different test than initial proof of concept, and the transition from works in a pilot to works in a global supply chain has killed more promising technologies than most people realize. And fusion is still, realistically, not a near-term grid technology. Pouring investment into it now is rational long-term strategy, but it cannot solve an energy security problem in this decade. The honest version of this story is, the foundation is being laid with real materials, real facilities, and real operating data. It is not finished. The gap between this works and this replaced oil is still significant, and the timeline for closing it is uncertain. What isn't uncertain is the direction. My take: here's what I actually think, having looked at all of it together. The pieces aren't individually revolutionary. Synthetic fuel has been a research concept for decades. Liquid air storage has existed in various forms since the 1970s. Ammonia as an energy carrier is well understood chemistry. What's different is that all of these are now simultaneously crossing from laboratory to factory floor, at a moment when one country controls 65% of the critical manufacturing hardware, has declared hydrogen a national infrastructure priority on par with oil and gas, and has a documented track record of taking impossible manufacturing problems and systematically solving them through scale. The more revealing data point isn't any single technology, it's the refinery. One of China's largest oil refining companies posted a profit decline of more than a third in 2025, not because people used less energy, but because alternatives started competing with it. and its response was to commit 800 million yuan to converting its oil facilities to synthetic fuel production. A company whose entire identity, infrastructure, and business model was built on oil is voluntarily rebuilding itself around something else. Companies don't do that because a trend is interesting. They do it because they've run the numbers and concluded the future is moving, whether they move with it or not. The world that ran on oil didn't announce its own ending. It just slowly started losing ground to something that was cheaper and harder to interrupt. That transition is further along than most people outside this space understand. And the country building the machines that power it, the electrolyzers, the fuel factories, the storage systems, is doing to energy what it already did to solar panels, becoming the supplier the rest of the world depends on, before the rest of the world fully understood what it was depending on. Which economy is most exposed when the geography of energy stops being relevant? Drop your honest take in the comments. I read every one. If you want to keep following this, the quiet moves, the overlooked technologies, the shifts that matter before the headlines catch up, subscribe to Eastern Engine and hit the notification bell. This is where the actual story is. Thanks for watching. See you in the next one.
China made history this year when it became the first nation to land a spacecraft on the far side of the moon, the Chang'e 4.
Over the past decade and a half, one country has quietly sent more spacecraft to the moon than any other nation on the planet. Not a single flagship mission. Not a one-off publicity launch. We are talking about a sustained campaign. Orbiters, landers, rovers, a robot designed to leap into the darkest craters imaginable, and a spacecraft that retrieved rock samples from a region no human has ever set foot on and carried them all the way back to Earth. And that is only the surface of it. Here's what makes this story genuinely gripping. China is not pursuing this because it wants to win a sprint to plant a flag. It is pursuing this because the moon may be holding something that could fundamentally reshape how humanity explores the entire solar system. Something frozen. Something ancient. Something that has been sitting in permanent darkness for billions of years, waiting to be discovered. By the end of this video, you are going to understand exactly why China keeps returning to the moon, what they are actually searching for, and why whoever cracks this problem first could end up shaping the future of space travel for generations. Let's get into it. Most nations that set their sights on the moon try to land on it as quickly as possible. China took a deliberately different path. Back in the early 2000s, Chinese space planners sat down and designed a roadmap intended to unfold over decades. This was not because they lacked the capability to move faster. It was a strategic choice. Every mission was engineered to teach them something specific they would need for the next one. Nothing was wasted. Nothing was rushed for the sake of headlines. The plan rested on 4 phases. First, orbit the moon and study it in detail. Second, land on it. Third, retrieve samples and bring them home. Each phase had to succeed completely before the next one began. It is the same logic you would use building a skyscraper. You do not install the glass before the steel frame is up, and you certainly do not start on the roof before the foundation is poured. The first mission launched in 2007, Chang'e, named after a moon goddess from Chinese mythology. The spacecraft orbited the moon for over a year and produced some of the most detailed lunar surface maps available at the time. There was no dramatic landing, no human drama, just clean, precise data that scientists and engineers could analyze for years and slowly convert into a workable plan. 3 years later, Chang'e 2 refined those maps even further. Researchers could now zoom into craters, ridges, and mountain ranges to determine exactly where a spacecraft could safely touch down without tipping over or sinking into loose soil. These missions never grabbed front-page attention the way a crude rocket launch would, but behind the scenes, they were building the blueprint that would guide everything to follow. And what followed genuinely changed what scientists thought they understood about the moon. In 2013, China made its first major leap. Chang'e 3 became the first spacecraft to perform a soft landing on the moon since the 1970s. Consider that for a moment. Nearly 4 decades had passed without a single controlled landing on the lunar surface. Then, quietly and precisely, China did it. The lander carried a small rover named Yutu, meaning Jade Rabbit. It rolled off onto the gray, dusty terrain and immediately got to work. Within days, Yutu found something unexpected in the rocks. For decades, virtually everything science knew about moon rocks came from the Apollo missions. A small group of astronauts had walked the lunar surface and returned with samples, and researchers had been studying those same specimens ever since. An entire understanding of the moon's composition had been built on that foundation. Textbooks were written, models were constructed, a complete scientific narrative was assembled. That narrative, it turned out, was incomplete. U2's instruments analyzed the soil and surrounding rocks and identified a type of volcanic rock that matched nothing in the Apollo collection. The chemical signature was different. The mineral arrangement was different. It was like discovering a completely unfamiliar recipe in a cookbook you assumed you had read cover to cover. Not a variation on a known dish, but something entirely new. The implications were significant. The moon is not a single uniform body. It is geologically complex, with regions that formed through different processes across different eras. There had been volcanic activity in areas no previous mission had ever examined. The regions Apollo had explored were just a small cluster of points on a vast map stretching across millions of square kilometers. The moon people thought they knew was only a fragment of the real picture, and the rest had never been studied up close at all, which raised an obvious question. If the areas already explored were still producing surprises, what might be hiding in the places no one had ever looked? The moon always shows Earth the same face. This is not coincidence. The moon rotates at exactly the rate that keeps one side perpetually facing us, while the far side points constantly away into deep space. You could observe the moon every night for your entire life and never glimpse the other side, not even with the most powerful telescope ever built. Landing on the far side was long considered nearly impossible. The instant a spacecraft touches down there, it loses all direct contact with Earth. No line of sight, no way to send commands, no way to receive data, no way to know if something has gone wrong. It would be like trying to communicate with someone sealed inside a soundproof room with no signal and no door to knock on. China solved this with remarkable elegance. Before launching the lander, they positioned a relay satellite in a carefully selected orbit beyond the moon, where it could maintain a view of both Earth and the lunar far side simultaneously. Signals could then bounce between the lander and Earth through this satellite, like a reliable messenger relaying messages between two parties who cannot see one another. Simple in concept, extraordinarily difficult to execute. In 2019, Chang'e 4 touched down inside the South Pole Aitken Basin, one of the largest impact craters in the entire solar system. It spans more than 2,500 kilometers across, roughly the size of Western Europe. Scientists believe it is so deep and so ancient that the original impact may have punched through the moon's outer crust, exposing material from deep within the lunar interior that had been buried since the moon first formed. Then in 2024, Chang'e 6 accomplished something even more astonishing. It did not merely land on the far side. It landed, collected roughly 2 kilograms of ancient rock and soil, sealed the material inside a container, launched a small rocket off the lunar surface into orbit, docked with a waiting spacecraft, transferred the cargo, and returned it all the way to Earth. Every single step had to function flawlessly, and none of them had ever been attempted from the far side before. The return samples were around 2.8 billion years old, and showed clear evidence of volcanic activity occurring far later than anyone had predicted. The moon's geological story did not go quiet as early as scientists had assumed. It ran longer and stranger than the textbooks ever captured. And yet, as extraordinary as all of this was, it still was not the main objective. The real prize sits at a completely different part of the moon. Step outside on a clear night and look at the moon. Now picture its very bottom, the South Pole. On Earth, the poles are frozen and ice-covered. On the moon, the South Pole is something far stranger. Because the moon barely tilts on its axis, sunlight strikes the South Pole at an extremely low angle, skimming across the surface almost sideways. Some craters near the pole are so deep that their walls block every ray of sunlight entirely. Not for a day, not for a season, but for over 1 billion years. No light has reached their floors since long before any life existed on Earth. Inside these craters, temperatures plunge to around -200 degrees Celsius, colder than the surface of Pluto, and among the coldest natural environments anywhere in the solar system. But that extreme cold is exactly what makes these craters so exciting. Scientists believe those permanently shadowed crater floors may be storing frozen water ice. Over billions of years, comets and asteroids carrying water repeatedly struck the moon. Most of that water evaporated or drifted off into space. But in these permanently dark craters, the water had nowhere to go. It simply stayed, frozen solid, perfectly preserved, like food left in the back of a freezer no one ever opens. Now consider what water actually represents in space. Water is made of oxygen and hydrogen. Oxygen is what astronauts breathe. Hydrogen is one of the most powerful rocket fuels ever developed. If you can extract that ice, split it into its components, and convert it into breathable air and usable fuel, the moon stops being just a destination. It becomes a supply depot, a fueling hub sitting right next to Earth, capable of sending spacecraft deeper into the solar system without hauling all that heavy, expensive fuel up from Earth's surface. Launching anything off Earth costs an enormous amount because our planet's gravity is so strong. The moon's gravity is only about 1/6 of Earth's, which means launching fuel from the moon would cost a fraction of what it costs from home. Future missions to Mars, to the moons of Jupiter, or beyond could stop at the moon, refuel, and continue onward. The moon could become humanity's first off-world supply station, and whoever builds it first gains a substantial head start on everything that comes after. This is why the South Pole matters so much, and why China keeps returning, mission after mission, year after year. To actually find and confirm that water ice, you cannot simply orbit overhead and make educated guesses. You have to enter those dark craters directly. But conventional rovers run on solar power, and no sunlight means no energy. Worse, wheels struggle on the sharp, jagged, unpredictable terrain inside a crater that has sat undisturbed for 1 billion years. China's solution is Chang'e 7, currently planned for launch in 2026. It is the most technically ambitious lunar mission the country has ever designed, and it includes something never used before in lunar exploration: a small robot capable of jumping. Rather than slowly rolling across the surface, this hopping probe can leap directly into permanently shadowed craters. It carries instruments designed to detect water molecules, identify hydrogen signatures, and analyze frozen deposits embedded in the ground. It enters, performs its work, and exits places that would disable a standard rover within minutes. Picture sending a nimble frog into a dark cave instead of trying to drive a car down into it. The full Chang'e 7 mission also includes an orbiter mapping the South Pole region from above and relaying signals, a lander touching down on stable terrain near the pole, and a rover studying soil composition and scouting targets for the hopping probe. All 4 components operate as a coordinated team, continuously sharing information with each other and with scientists on Earth. If Chang'e 7 returns with clear confirmation of substantial water ice deposits in those ancient craters, it would rank among the most important discoveries in the history of space exploration. Not only scientifically thrilling, but practically transformative, because it would demonstrate that much of what humanity needs to begin living and working beyond Earth is already there, waiting. Finding a resource and actually using it are 2 very different challenges. You cannot simply scoop up ice and declare a base established. You need technology that can survive with no oxygen, extreme temperature swings, constant radiation, and fine abrasive dust that works its way into every gap in every machine. You need systems that can operate for months or years without human intervention. Essentially, you need to learn how to build on the moon using the moon itself. That is the central goal of Chang'e 8, planned for around 2029. This mission focuses on what engineers call in situ resource utilization, using what is already present rather than shipping everything from Earth across hundreds of thousands of kilometers of empty space. One set of experiments will attempt to heat and compress lunar soil into solid building blocks. Think of it as baking bricks, except instead of clay from a riverbank, you are using the gray dust that blankets the lunar surface. Those bricks could form landing pads that reduce the dangerous dust clouds kicked up during rocket landings, build protective walls around habitats to shield against radiation, or pave routes for rovers. Other experiments will explore extracting oxygen directly from lunar minerals. The moon's soil is rich in oxygen, but it is chemically locked inside rocks rather than floating freely. The right process can break those bonds and release it. Some designs under consideration involve robotic 3D printers that use lunar soil as raw material to construct structures layer by layer. The same principle as a home 3D printer, but on a far larger and more serious scale. Autonomous machines could print walls, floors, and protective domes long before any human crew arrives. If these technologies prove themselves in the actual lunar environment, rather than just a laboratory, the entire economics of space construction shifts. The moon would effectively help build itself. Everything described so far feeds into one final objective: a permanent research station at the lunar South Pole. China calls it the International Lunar Research Station, or ILRS, and it ranks among the most ambitious space infrastructure projects any nation has seriously proposed. Construction is set to begin in the early 2036. Robotic missions will arrive first, delivering power units, communication systems, and laboratory modules. Machines will handle the difficult, dangerous early construction work long before any astronaut boards a rocket. Over several years, the station is intended to grow module by module until it can support human crews for extended stays. China has also invited other nations to participate, and the response has been notable, with numerous countries expressing interest in contributing experiments, technology, or personnel. This would not be a single nation's outpost, but a shared facility on another world. On the crewed side, China has been methodically testing the systems needed to land astronauts on the lunar surface before the end of this decade. The Long March 10 rocket, capable of lifting roughly 27,000 kilograms into lunar orbit, completed a key low-altitude test flight in early 2026. The Mengzhou crewed spacecraft passed a critical emergency abort test around the same time, demonstrating it can protect astronauts even if something goes wrong during launch. Each crewed lunar mission will require 2 rockets, one carrying the crew, the other carrying the lander. They rendezvous in lunar orbit, dock, ideal for astronomy, and its position makes it a natural first stop for missions heading deeper into space. The first group to build lasting infrastructure there will not simply win a competition, they may set the terms for how future missions beyond Earth are planned and executed for decades. And right now, mission by mission, rover by rover, China is laying that foundation on a surface that once seemed like a closed chapter in human history. The moon was never a finished story. It turns out it was only the introduction. NVIDIA once controlled almost the entire market for advanced artificial intelligence chips in China. Today, that position is unraveling. A new forecast from Bernstein estimates that NVIDIA's share of China's AI accelerator market could fall to just 8% in 2026, down from roughly 40% in 2025. Huawei, meanwhile, could rise to around 50%. That would represent one of the fastest reversals in the history of the semiconductor industry. But the headline needs an important qualification. NVIDIA has not already been measured at 8% across the full year. 8% is a forecast based on current sales restrictions, delayed approvals, government policy, and the rapid growth of Chinese alternatives. Still, the direction is unmistakable. NVIDIA once held about 95% of China's advanced AI chip market. Now Huawei and other domestic suppliers are taking the customers, software support, and infrastructure projects that NVIDIA once expected to dominate. The central question is no longer whether China can build an alternative AI hardware industry. It is whether NVIDIA can prevent that alternative from becoming permanent. How NVIDIA lost its near monopoly. NVIDIA's dominance was built on more than fast chips. Its graphics processors became the standard hardware for training artificial intelligence because developers already knew how to use them. The company's CUDA software platform gave researchers tools, libraries, and optimized code that made complex AI workloads easier to run. Chinese universities, startups, cloud providers, and internet giants built their systems around that ecosystem. When a company wanted to train a large model, NVIDIA was usually the safest choice. That created a powerful feedback loop. More customers attracted more developers. More developers created more software. More software made the hardware even more valuable. At one point, NVIDIA controlled approximately 95% of China's advanced AI accelerator market. Then Washington changed the rules. The United States introduced export controls designed to limit China's access to the most advanced computing hardware. The concern was that powerful AI chips could support military systems, cyber operations, surveillance, and other strategic capabilities. But those rules continued evolving. Chips that were permitted under one standard could later become restricted, and Chinese companies began asking whether dependence on an American supplier had become too risky. The H200 problem 1974 was NVIDIA's H200. But approval from the United States did not guarantee immediate access to the Chinese market. Chinese authorities also had reasons to slow or discourage purchases. Beijing wants domestic companies to use Chinese technology whenever possible. Allowing unlimited imports of NVIDIA hardware would weaken that strategy. So even when export permission existed, orders remained surrounded by uncertainty. This placed NVIDIA between two governments with opposing objectives. Washington wanted to control China's access to advanced chips. Beijing wanted to reduce reliance on American chips. NVIDIA wanted to sell. Chinese customers wanted computing power, but every transaction became a political decision. That uncertainty is one reason market share can collapse faster than product performance. A customer building a multi-year data center cannot plan around a supplier whose products may disappear after the next policy change. The safest chip is not always the fastest chip. Sometimes it is the chip that will still be available next year. How Huawei filled the gap. Huawei was ready to exploit that uncertainty. The company had already been forced to build domestic alternatives after American sanctions restricted its access to foreign technology. Its Ascend AI accelerators were initially viewed as weaker substitutes for NVIDIA hardware. They faced limitations in software support, manufacturing capacity, memory bandwidth, and developer familiarity. But the gap began narrowing. Huawei improved its chips. It expanded its software tools. It worked with Chinese cloud companies, model developers, universities, and state-backed projects. Most importantly, it offered a supply chain aligned with Beijing's long-term objective of technological self-reliance. Huawei does not need every individual chip to outperform NVIDIA's best product. It can compete at the system level. That means combining many accelerators, networking equipment, software, storage, and cooling into a complete computing platform. Huawei's Cloud Matrix and Atlas systems follow this approach. If one chip is less powerful, the company can connect more chips together. That increases electricity consumption and technical complexity, but it can still deliver useful computing capacity. For customers blocked from buying NVIDIA hardware, an available Huawei cluster can be more valuable than an unavailable NVIDIA server. This is the strategic advantage created by export controls. They do not automatically make Chinese chips better. They make Chinese chips necessary. DeepSeek changes the software question. Hardware is only part of the competition. The larger challenge for Huawei has always been software. NVIDIA's CUDA ecosystem contains years of optimized libraries, developer knowledge, and compatible applications. Moving a model from NVIDIA hardware to another platform can require significant engineering work. Code must be modified. Operators must be supported. Performance must be tuned. Unexpected numerical differences can appear. That creates switching costs. But China's AI industry is increasingly adapting. DeepSeek's latest flagship model was designed to operate on Huawei infrastructure. Other Chinese model developers are optimizing software for Ascend chips and domestic accelerators. This matters because every successful model weakens the assumption that serious AI development must begin with CUDA. Developers follow available infrastructure. If Chinese cloud providers deploy more Huawei systems, software teams will spend more time optimizing for Huawei. If more software runs well on Huawei, future customers will feel safer purchasing Huawei hardware. A new feedback loop begins. It is the same kind of ecosystem advantage that originally made NVIDIA dominant. The difference is that Huawei's ecosystem is being accelerated by government policy, supply restrictions, and the enormous purchasing power of China's technology companies. Market share estimates must be handled carefully. Different research firms measure different categories. Some count individual accelerator cards. Others estimate revenue. Some focus only on advanced training chips. Others include lower-end inference hardware and domestic products. That explains why the available figures appear inconsistent. IDC data reported earlier in 2026 estimated that NVIDIA shipped about 2.2 million accelerators in China during 2025 and held roughly 55% of the market. Bernstein estimated NVIDIA at closer to 40% in 2025 and projected a fall to 8% in 2026. Those numbers cannot be treated as identical measurements. But both sources point in the same direction. NVIDIA's share has fallen sharply from its former near monopoly. Domestic suppliers now represent a major part of the market. Huawei is the strongest of those suppliers, and current policy could push NVIDIA's position much lower. So the important story is not whether the exact number is 8%, 10%, or something higher. The important story is that NVIDIA may be losing the market structure that once protected its dominance. Can Huawei really take the lead? Huawei still faces major constraints. The company cannot freely access the world's most advanced semiconductor manufacturing equipment. Its chips are produced using Chinese manufacturing technology that remains behind the leading processes available to NVIDIA through Taiwan Semiconductor Manufacturing Company. That can reduce performance, energy efficiency, and production yield. Huawei also depends on advanced memory and packaging. China is improving in those areas, but supply remains limited. A large order does not matter if the company cannot manufacture enough reliable systems. Software compatibility is another obstacle. Independent research has found that emerging accelerator platforms can support fewer operations and produce more inconsistencies than NVIDIA hardware. For developers training frontier models, small software problems can become expensive delays. NVIDIA also remains ahead in global developer support, networking, systems engineering, and access to advanced manufacturing. So Huawei taking the lead in China would not mean Huawei has defeated NVIDIA worldwide. It would mean the Chinese market is being reorganized around availability, national policy, and domestic infrastructure. That is a different kind of victory. It is less about winning a benchmark and more about becoming the default supplier inside a protected strategic market. The role of China's other chip makers. Huawei is not the only beneficiary. Cambricon, More Threads, MetaX, Biren, and other Chinese companies are also developing AI accelerators. Some focus on training, others target inference, cloud computing, or specialized workloads. China wants multiple domestic suppliers because dependence on one national champion would create another vulnerability. Competition can also improve products faster. Customers can compare price, software, reliability, and energy use. Investors can fund different technical approaches. Cloud providers can avoid relying completely on Huawei. However, fragmentation creates problems. Different chips may require different software tools. Developers may need to maintain multiple versions of the same model. Standards may not be mature. The industry could waste resources recreating capabilities that CUDA already provides. China therefore faces a difficult balance. It wants competition among domestic chipmakers, but it also needs enough standardization to create a coherent ecosystem. Huawei currently has the scale, customer relationships, networking equipment, and political support to lead that process. The United States introduced export controls to slow China's AI progress. In the short term, the restrictions created real pain. Chinese companies struggled to secure top NVIDIA products, computing rental prices increased, smuggling became more expensive and risky. Some frontier research remained dependent on imported hardware, but the long-term effect may be more complicated. By limiting NVIDIA sales, Washington reduced the competitive pressure facing Huawei inside China. Chinese customers that might have preferred NVIDIA were pushed toward domestic alternatives. Those customers provided Huawei with revenue, testing data, software feedback, and large deployment opportunities. Every restricted NVIDIA sale became a potential training exercise for China's semiconductor industry. This does not mean export controls were useless. Without them, Chinese companies could have purchased much larger quantities of advanced American hardware. That may have accelerated model development and military applications. But the policy created a trade-off. Restricting access to current technology can encourage development of future alternatives. The harder Washington pushes NVIDIA out, the stronger the commercial foundation for Huawei may become. What this means for NVIDIA China remains too large for NVIDIA to ignore. Jensen Huang has estimated that the country's AI market could be worth tens of billions of dollars annually. Losing that market would reduce revenue, weaken NVIDIA's global developer network, and give competitors room to scale. It could also divide the global AI industry into separate ecosystems. One system would be centered on NVIDIA, CUDA, American cloud companies, and Western manufacturing partners. The other would be centered on Huawei, domestic Chinese software, local semiconductor production, and state-supported infrastructure. Once customers build data centers, train engineers, and optimize models for one ecosystem, switching becomes difficult. That is why market share today matters far beyond immediate chip sales. NVIDIA may still sell approved products into China. It may design new export-compliant chips. Political negotiations could reopen access. But even if restrictions ease, NVIDIA may discover that the customers have changed. Chinese companies are being encouraged to buy domestic hardware. Engineers are learning Huawei's software. Government projects are setting local content requirements. A market that once welcomed NVIDIA, by default, may now treat it as a temporary foreign option. My take. My take is that the projected 8% share is not proof that Huawei has built a better chip than NVIDIA. It is evidence that semiconductor markets are shaped by more than engineering. Policy, supply security, software ecosystems, manufacturing capacity, and national strategy can matter as much as raw performance. NVIDIA still leads the global AI accelerator industry. Its hardware remains essential for many frontier workloads. Its software advantage is enormous. Huawei still faces serious limitations in manufacturing, energy efficiency, and developer compatibility. But inside China, the competitive rules have changed. NVIDIA is no longer competing only against Huawei's chips. It is competing against China's desire to remove a strategic dependency. That is a much harder opponent. If Bernstein's forecast proves accurate, NVIDIA's share could fall from a near monopoly to 8% in only a few years, while Huawei captures roughly half of the market. Even if the final number is higher, the structural shift is already visible. Export controls opened the space. Huawei filled it. Chinese developers are adapting. And every new domestic deployment makes the old NVIDIA-centered market harder to restore. So what do you think? Did American export controls successfully slow China's AI development? Or did they create the conditions for Huawei to become NVIDIA's most important long-term competitor? Let me know your view in the comments. and subscribe to Eastern Engine for more grounded coverage of the chips, factories, and engineering decisions reshaping the global economy. Because NVIDIA may still lead the world, but in China, Huawei is building a market that NVIDIA may never fully recover. A normal solid-state drive has one job: store data. It receives files from the computer, places them inside flash memory cells, and returns them when requested. The controller organizes the traffic, corrects errors, and tries to keep the drive alive as thousands of writes gradually wear down the NAND. But a Chinese memory company believes the SSD should do much more than move data from one place to another. Longsys has introduced a 5-nanometer chip called the WM8500. The company that creates an extraordinary possibility. A drive containing 128 terabytes of physical flash could provide as much as 256 terabytes of effective storage. No additional NAND package, no second SSD, no magical new memory cell. The same physical drive simply stores certain data more efficiently. But capacity doubling is only the beginning. Longsys says the SPU can also move selected AI data out of expensive DRAM and into high-speed storage, reducing memory requirements by nearly 40% in one tested scenario. The company has even demonstrated a system built around AMD's Ryzen AI Max Plus 395, running a 397 billion parameter model locally. That sounds almost impossible for a compact machine. Yet the idea behind it is surprisingly simple. Instead of treating storage as a passive warehouse, Longsys wants the SSD to become an active participant in computing. The drive does not merely hold the data, it compresses it, sorts it, predicts when it will be needed, and in some cases, acts as an extension of system memory. If the technology works as described, the future SSD may not be measured only by how many terabytes it contains. It may be measured by how intelligently it uses every byte. The storage problem. AI created. For years, computer performance was discussed mainly in terms of processors. Faster CPU, faster GPU, more cores, higher clock speeds. But artificial intelligence has exposed a different bottleneck: memory. A large AI model may contain billions or hundreds of billions of parameters. Each parameter represents a numerical value learned during training. To run the model, those values must be stored somewhere and moved repeatedly into the processor. The calculations can be fast. Moving the data is often slower. Imagine owning a factory with thousands of extremely powerful machines. The machines can assemble products at incredible speed, but every component is stored in a warehouse several kilometers away. The machines spend less time working than waiting for deliveries. That is the AI memory problem. High-end data centers attack it with massive amounts of high-bandwidth memory, large pools of conventional DRAM, and extremely expensive storage systems. An ordinary PC cannot do that. Even a powerful workstation may have 64, 128, or 256 gigabytes of memory. A large model may require far more. So developers use a technique called offloading. Part of the model remains in fast DRAM. The rest is stored on an SSD and loaded only when needed. This makes larger models possible, but it introduces another problem. SSDs are much slower than DRAM. If the wrong data is requested at the wrong moment, the processor must wait. Longsys is trying to reduce that delay by making the drive itself more intelligent. From SSD controller to storage processor. Every SSD already contains a controller. The controller translates commands from the computer, decides where data should be written, manages bad memory cells, and performs error correction. Without it, NAND flash would be difficult to use reliably. But the traditional controller is largely a traffic manager. It moves data. The WM8500 is designed to process data too. Longsys says the SPU combines a conventional storage control engine with an intelligent processing engine on the same chip. That distinction matters. A normal controller asks, where should this file be placed? The SPU can ask additional questions. Can this file be compressed? Is it used frequently? Should it remain close to the processor? Can part of it be moved into a cheaper region of the drive? Will the system need it again soon? The company calls the software layer controlling these decisions ISA, or Intelligence Storage Agent. The SPU is the muscle. The ISA is the planner. Together, they turn the drive from a passive destination into something closer to a data assistant. The idea resembles what happened to graphics cards. A GPU was once a specialized component responsible mainly for drawing images. Over time, it became a general computing engine used for science, simulation, and artificial intelligence. Longsys is suggesting that storage controllers may follow a similar path. not by replacing CPUs or GPUs, by performing the data management work those processors should not have to do. How 128 terabytes becomes 256 terabytes. The headline number comes from lossless compression. Lossless means the original data can be reconstructed perfectly. Nothing is thrown away, nothing is blurred, nothing is approximated. A photograph saved as a low-quality image may use lossy compression, where some visual information is permanently removed. That can reduce file size dramatically, but the original cannot be recovered exactly. Lossless compression works differently. It searches for repeated patterns and replaces them with shorter instructions. Suppose a document contains the word semiconductor 10,000 times. Instead of storing every letter 10,000 times, a compression system can store the word once and then record where it repeats. The file becomes smaller. When it is read, the system reconstructs the full version. Longsys says the WM8500 performs this process directly inside the storage device. The computer sends data to the SSD. The SPU analyzes it. Compressible data is reduced before being written to flash. When requested, the SPU decompresses it before returning it to the host. To the operating system, the process can appear transparent. The user does not need to place files inside an archive manually. The drive handles it automatically. With an average 2-to-1 ratio on suitable workloads, 1 physical terabyte can store approximately 2 terabytes of original information. That is how 128 terabytes can provide up to 256 terabytes of effective capacity. But the phrase suitable workloads is essential. Not all data compresses equally. The files that refuse to shrink. Text compresses extremely well because language contains repetition. Source code also contains repeated words, structures, commands, and symbols. Databases may contain recurring values, empty fields, and predictable patterns. These are the kinds of workloads Longsys highlights. Video is different. Modern video files are already heavily compressed. A movie encoded with an efficient codec has already had most of its obvious redundancy removed. Trying to compress it again may save almost nothing. The same applies to JPEG photographs, compressed archives, and many encrypted files. Encryption deliberately makes data appear random. Random-looking data contains fewer predictable patterns for a compression engine to exploit. So a 128 terabytes drive will not always behave like a 256 terabytes drive. One user may see close to the full 2-to-1 benefit. Another may see only a small improvement. A data center filled with text logs, program code, and database records could benefit greatly. A media archive filled with compressed movies may not. This is not a flaw unique to Longsys. It is a basic limit of compression. You cannot repeatedly squeeze information forever. Eventually, the obvious repetition disappears. That is why the most honest description is not, Longsys created a physical 256 terabytes SSD. It created a 128 terabyte storage platform that may hold as much as 256 terabytes of uncompressed source data under favorable conditions. Still impressive, just not magic. Why put compression inside the drive? Computers have compressed files for decades. Operating systems can compress folders. Databases use compression. Servers use software tools to reduce storage needs. So why build dedicated compression hardware inside an SSD controller? Because compression requires computation. If the CPU performs it, processor time is consumed. Data must move through system memory, power is used. Other programs may slow down. A dedicated engine can perform the same task more efficiently. Think of a restaurant kitchen. The head chef can wash every plate personally. But that is probably not the best use of the most valuable worker in the building. A dedicated dishwasher handles the repetitive task while the chef focuses on cooking. The SPU attempts to do the same for data. The CPU and GPU focus on applications and AI calculations. The storage processor handles compression, caching, and movement. Longsys claims the process introduces no meaningful performance penalty. But that is one of the areas where independent testing will be important. Compression always requires work. The real question is whether the 5-nanometer engine can perform that work fast enough that the user barely notices. If the drive can compress at full interface speed, the savings could be substantial. If compression slows sustained writes or increases latency, the value becomes more complicated. Capacity is not useful if access becomes painfully slow. The 5nm chip at the center, the WM8500, is manufactured using a 5-nanometer process. That does not automatically make it revolutionary. Process node names are not direct measurements, and a smaller node does not guarantee better architecture. but 5-nanometer manufacturing provides a practical advantage. More processing logic can fit inside a compact controller while keeping power consumption manageable. Traditional SSD controllers already perform difficult tasks. They manage multiple NAND channels, calculate error correction codes, track wear, translate logical addresses, maintain caches, encrypt data, support PCI Express communication. Now add hardware compression, workload classification, predictive prefetching, and AI data scheduling. That requires more transistors, more processing, more memory, and careful power control. A storage controller cannot behave like a desktop CPU, consuming 100 watts. It lives inside a drive where heat can reduce performance and shorten flash memory life. The 5-nanometer process gives Longsys room to add intelligence without turning the SSD into a small oven. The WM8500 also supports PCI Express 5.0, allowing high-speed communication with the host system. That bandwidth matters because the entire concept depends on moving model data quickly enough to hide the difference between SSD and DRAM. The drive does not need to become as fast as DRAM. It needs to become fast and predictable, enough that software can plan around it. The second trick, using SSD as slower memory. Compression creates the headline. HLC may create the bigger long-term impact. Longsys calls it high-level cache. The idea is to use the SSD as an extension of DRAM. Computers already use virtual memory. When physical RAM becomes full, the operating system moves some data to storage. Historically, this was painful. Hard drives were so slow that a computer using large amounts of virtual memory could become nearly unusable. Modern SSDs are much faster. They are still far slower than DRAM, but the gap can be managed more intelligently. Not all data needs immediate access. Some information is hot. The processor uses it constantly. Some is warm. It may be needed soon. Some is cold. It exists in memory but is rarely touched. HLC attempts to identify those categories. Hot data remains in DRAM. Warm and cold data moves to the SSD. If the system predicts correctly, the processor sees little delay because required data is fetched before it is needed. This resembles organizing a workshop. The tools used every minute remain on the table. Tools needed occasionally sit in a nearby drawer. Tools rarely used go into storage. A badly organized workshop forces the worker to walk across the building constantly. A well-organized one keeps the right objects close at the right time. Longsys says HLC can reduce required DRAM capacity by nearly 40% in a tested 256,000 token scenario involving a 122 billion parameter workload. That does not mean every computer can remove 40% of its RAM. It means this particular architecture reportedly achieved that reduction under a specific AI workload. The 397 billion parameter demonstration. The most eye-catching demonstration involved AMD hardware. Longsys says it jointly optimized an intelligent agent system built around the Ryzen AI Max Plus 395 processor. That AMD chip is designed for powerful local AI systems, combining CPU cores, graphics resources, and a large unified memory architecture. Using the SPU and ISA system, Longsys reports that the machine successfully deployed a 397 billion parameter model locally. That figure requires context. Deployed does not necessarily mean the model ran at cloud data center speed. It does not tell us the exact precision used for the weights. It does not reveal the token generation rate. It does not tell us how much of the model remained in memory and how much was streamed from storage, but it demonstrates the direction. A model too large to fit entirely inside conventional system memory can still run if inactive sections remain on the SSD and are loaded intelligently. Many modern models use a mixture of experts architecture. An MOE model may contain hundreds of billions of total parameters, but only a fraction activates for each token. Imagine a company employing hundreds of specialists. One question requires a lawyer, another requires an engineer, a third requires an accountant. The company does not need every employee in the meeting room simultaneously. The ISA system attempts to keep currently active experts in fast memory while storing inactive experts on the SPU-equipped SSD. When the system predicts that a different expert will be needed, it begins loading that expert early. If the prediction is accurate, the data arrives before the model asks for it. The delay becomes less visible. That is intelligent prefetching. The KV cache problem. Large language models face another memory burden, called the KV cache. As a model processes a conversation, it stores information about previous tokens so it does not need to recalculate everything repeatedly. The longer the conversation, the larger the cache grows. A short prompt may be manageable. A document containing hundreds of thousands of tokens can consume enormous amounts of memory. Longsys says its system can move older or less active portions of the KV cache onto the SSD while keeping important sections in DRAM. Compression may reduce the space required further. Again, timing is everything. If the model suddenly needs an old section and the data has not been pre-fetched, inference can pause. The SSD becomes a bottleneck. If the scheduler correctly predicts future needs, the storage delay can overlap with computation. The model continues working while the next data block arrives. This is why the ISA software may matter as much as the WM8500 hardware. A fast drive with poor scheduling is still slow at the wrong moment. An intelligent scheduler can make slower storage feel faster by requesting data before the wait begins. Can this replace DRAM? No, at least not in performance-sensitive roles. DRAM operates with latency measured in tens of nanoseconds. NVMe SSD latency is usually measured in microseconds. A microsecond is 1,000 nanoseconds. That difference is enormous. Even a highly advanced SSD cannot become genuine system memory simply through clever software. It can, however, reduce the amount of expensive DRAM required. This distinction is important. The SPU does not replace the workbench. It makes the storage room more useful. The most frequently used tools remain on the workbench. The rest can move to an automated shelf that delivers them when requested. For AI systems, that can change economics. DRAM is expensive. High-capacity memory configurations increase device cost and power consumption. If a manufacturer can build a system with 96 gigabytes of DRAM that behaves like a larger memory machine under selected workloads, the savings could be meaningful. But the user experience depends on the workload. Interactive applications may be sensitive to small delays. Batch processing may tolerate them. Models with predictable expert activation may work well. Other architectures may not. One benchmark cannot answer every case. Could smart SSDs replace hard drives? Longsys also presents the SPU as a possible alternative to large-capacity hard drives. HDDs remain popular because they provide huge capacity at low cost. SSDs are faster, quieter, and more efficient, but large enterprise SSDs can be extremely expensive. Compression changes that calculation. If a 128 terabytes flash drive stores the same amount of suitable data as 256 terabytes of conventional capacity, its effective cost per stored terabyte falls. It may still cost more than hard drives, but total ownership includes more than purchase price. Hard drives use mechanical parts. They require more physical space. They consume energy. They produce vibration. They need cooling. They may fail differently. An SSD with intelligent compression could become attractive in environments where space, power, and access speed matter more than the lowest possible purchase price. However, flash endurance remains important. Compression may actually help by reducing the amount of data physically written to NAND. If 2 terabytes of original data compress to 1 terabyte, fewer flash cells need to be programmed. That could extend drive life. But only independent endurance testing can show how the complete system behaves under sustained heavy use. The SPU itself also creates new complexity. More intelligence means more firmware. More firmware means more opportunities for bugs. Storage errors are unforgiving. A graphics glitch is annoying. A corrupted database can be catastrophic. The questions Longsys still needs to answer. The company's claims are fascinating. They are not the same as a full independent review. We still need to know the sustained compression speed. Can the controller maintain performance when writing hundreds of gigabytes continuously? How does latency change when compression is active? What happens with data that compresses poorly? How much power does the SPU consume? How hot does the controller become? How consistent is the 2-to-1 ratio across real enterprise workloads? How does the system protect data if power fails during a compressed write? How many drives can operate together in a server? What is the cost compared with a conventional enterprise SSD? And perhaps most importantly, when can customers actually buy one at scale? A technology demonstration can show possibility. A commercial product must show reliability, support, firmware stability, and manufacturing volume. Storage buyers are conservative for a reason. They are trusting the drive with information that may be more valuable than the hardware itself. My take. My view is that the most important part of the WM8500 is not the headline capacity doubling. Compression is useful, but it depends heavily on the data. Some users may approach 2-to-1. Others may see far less. The deeper shift is architectural. Longsys is treating storage as a computing layer. For decades, the hierarchy was simple. The CPU computes, DRAM feeds the CPU. Storage waits. AI is breaking that arrangement because model sizes are growing faster than affordable memory capacity. The SPU offers another approach. Let the storage device perform part of the data work. Compress information before it consumes flash. Keep inactive model experts outside DRAM. Predict which data will be needed next. Move old KV cache entries into a lower-cost tier. None of those ideas individually eliminates the memory bottleneck. Together, they may make local AI systems far more capable. The risk is that intelligent storage becomes complicated storage. Prediction errors create delays, compression adds processing, firmware bugs create new failure modes, and company demonstrations may look better than mixed real-world workloads. Still, the direction makes sense. We are approaching a point where adding more raw storage and more raw DRAM cannot be the only solution. Efficiency must improve too. A 128 terabytes drive should not merely be a bigger bucket. It should understand how the bucket is being used. That is what the WM8500 is trying to become. Not just an SSD controller, a storage processor, a chip that turns capacity into something flexible, a chip that lets flash behave partly like memory, and under the right conditions, a chip that allows 128 physical terabytes to hold 256 terabytes of original data. The achievement is not that Longsys created storage from nothing. It is that the company may have found a better way to use what was already there. So what do you think? Would you trust a smart SSD that automatically compresses your files and manages part of your AI memory? Or would you prefer a simpler drive with predictable physical capacity and fewer layers of processing? Let me know your view in the comments. And if you want more grounded breakdowns of the chips, memory systems, and hidden hardware reshaping computing, subscribe to Eastern Engine, because the next storage revolution may not come from adding more flash. It may come from teaching the drive what to do with it. Have you ever wondered why NVIDIA keeps building faster and faster AI chips, yet the biggest AI companies still complain their systems are waiting around instead of actually computing? It turns out the biggest problem isn't always the GPU anymore. Sometimes, it's what connects them. And now China says it has built an AI network that moves information so quickly it could remove one of the largest bottlenecks in modern artificial intelligence. If that's true, it changes far more than benchmark scores. It changes how future AI supercomputers are designed, how much they cost to build, and who can compete in the global AI race. Today, we're breaking down why this network matters, why NVIDIA has spent years trying to solve the same problem, and why China's latest breakthrough has the entire semiconductor industry paying attention. When most people hear about AI hardware, they immediately think about GPUs. NVIDIA has become almost synonymous with artificial intelligence, because its graphics processors train and run many of the world's largest language models. Every headline talks about faster chips, more memory, more tensor cores, and larger AI clusters. But here's something many people don't realize. The bigger an AI system becomes, the less important the individual chip is compared to the speed at which thousands of chips communicate with each other. Imagine you own the fastest sports car in the world. It can reach incredible speeds in seconds, but then you place that car in the middle of a traffic jam where every road is clogged. Suddenly, it doesn't matter how powerful the engine is because it spends most of its time waiting. That's exactly what happens inside massive AI data centers. Thousands of incredibly powerful processors constantly need to exchange enormous amounts of information. If those connections become congested, the expensive GPUs sit idle waiting for data instead of performing calculations. That waiting time is incredibly expensive. Some of today's largest AI clusters cost hundreds of millions, sometimes even billions of dollars to build. Every second a GPU isn't fully utilized represents wasted money, wasted electricity, and slower AI development. This has become one of the biggest engineering challenges in modern computing. For years, NVIDIA has been attacking this problem with technologies like NVLink and InfiniBand. These aren't GPUs themselves, they're the highways connecting those GPUs together. The faster the highway, the more efficiently every processor can work. Building these high-speed connections has become almost as important as designing the chips themselves. Now China appears determined to solve this challenge from another direction. Rather than simply building faster processors, Chinese researchers and technology companies have been investing heavily in networking technologies specifically designed for artificial intelligence workloads. Their goal isn't just faster downloads or faster internet. Their goal is dramatically reducing the time it takes for thousands of AI accelerators to exchange data while training enormous neural networks. That sounds simple until you realize just how much information modern AI systems move every second. Training a cutting-edge language model isn't like downloading a movie. Imagine thousands of processors all solving different pieces of the same giant puzzle simultaneously. After each step, every processor needs to share what it learned with thousands of others before moving to the next calculation. This exchange happens millions of times during training. If even one part of that communication slows down, the entire system becomes less efficient. That's why networking has quietly become one of the most valuable technologies in artificial intelligence. The interesting part is that networking has traditionally received far less public attention than GPUs themselves. Headlines celebrate trillion-parameter models and record-breaking chips, but the infrastructure connecting everything together usually stays behind the scenes. Yet many engineers argue these connections are becoming just as important as compute power itself. China clearly recognizes this trend. Over the last several years, enormous investments have gone into domestic networking equipment, optical communication systems, advanced switching technologies, silicon photonics research, and ultra-fast data center architectures. Instead of relying entirely on imported networking ecosystems, Chinese companies have increasingly focused on building their own complete AI infrastructure stack. That strategy mirrors what we've already seen happen across semiconductors. First came investments in domestic chip manufacturing, then memory, then advanced packaging, then AI accelerators. More recently, optical communication and photonic technologies began receiving massive attention because engineers realized future AI systems would eventually hit limits not inside processors, but between them. This is exactly where the latest reports become so interesting. Instead of asking how to make a single GPU faster, researchers are asking something much bigger. What if every GPU could spend dramatically less time waiting? Even a relatively modest improvement in communication efficiency can produce surprisingly large improvements across enormous AI clusters. Think about a warehouse filled with thousands of workers. If every employee loses only 10 seconds waiting for supplies every hour, the total lost productivity becomes enormous. Now imagine eliminating most of that waiting time across an operation employing thousands of people. The overall improvement becomes much larger than those 10 seconds initially suggested. Large AI clusters behave similarly. Tiny communication improvements, repeated millions of times, can save extraordinary amounts of computation. This is why companies around the world are investing billions into networking technology. It's also why China's latest efforts have attracted international attention. Many analysts believe future AI competition won't simply revolve around who builds the fastest processor. Instead, it may depend on who builds the fastest complete system. That's a major difference. A complete AI system includes processors, memory, networking, storage, cooling, software, power management, manufacturing capability, and increasingly, optical communication. Whoever optimizes every layer gains advantages that individual component improvements alone can't match. China appears increasingly focused on this systems approach. Rather than chasing one spectacular headline after another, many recent projects fit together like pieces of a much larger strategy. You've probably noticed this pattern if you've watched several videos on this channel. First, there were domestic AI accelerators, then high-speed memory developments, then glass-based technologies, then advanced packaging, then ultra-fast optical fibers, then AI servers, then CPU breakthroughs, now networking. Individually, each story seems impressive. Together, they begin forming an ecosystem. That's important because AI isn't powered by isolated inventions anymore. It's powered by entire infrastructures. This also explains why many governments have started viewing artificial intelligence less like traditional software and more like national infrastructure. Countries aren't simply competing to build chatbots. They're competing to build entire computing ecosystems capable of supporting future industries. Healthcare, autonomous transportation, scientific research, drug discovery, manufacturing, defense applications, climate modeling, financial systems. Every one of these increasingly depends on artificial intelligence processing massive data sets at extraordinary speeds. And every one of those workloads depends on communication. The challenge becomes even greater as AI models continue growing. A decade ago, training systems containing millions of parameters seemed impressive. Today, billions have become common. Trillions are already appearing. Future systems may become even larger. As models expand, communication requirements grow dramatically. Moving that information efficiently becomes one of the defining engineering challenges of modern computing. That's why networking engineers have suddenly become some of the most valuable specialists in artificial intelligence. They're building invisible technologies that determine whether tomorrow's AI systems spend their time calculating or waiting. This is where optical communication enters the conversation. Traditional electrical connections eventually face physical limitations involving heat generation, signal degradation, and energy consumption. Optical communication offers an alternative by transmitting enormous amounts of information using light rather than conventional electrical signaling. China has invested heavily in this area. Recent announcements involving air-filled optical fibers, photonic devices, advanced optical switching, and integrated communication technologies all point toward one long-term objective: move vastly more information while consuming less energy. If successful, that combination becomes extremely attractive for AI infrastructure. Energy consumption has quietly become one of artificial intelligence's biggest challenges. Every new generation of larger AI clusters cost. Those economics matter enormously. The largest technology companies now spend billions constructing AI infrastructure. Even relatively small percentage improvements can translate into hundreds of millions of dollars over time. This explains why networking technologies have become strategic assets rather than supporting components. The companies that master them may gain advantages extending far beyond raw processor performance. And according to recent developments, China clearly wants to compete at every layer of that stack. So what exactly makes this reported AI network different from the traditional approach? Instead of treating networking as an accessory to AI hardware, the latest Chinese developments suggest networking is becoming the foundation around which future AI systems are designed. The objective isn't simply increasing raw bandwidth. Engineers are trying to reduce latency, improve synchronization between thousands of processors, eliminate communication bottlenecks, and make every computing node behave almost like part of one enormous machine. That distinction is incredibly important. Imagine trying to coordinate 10,000 people on a project. Communication is fairly easy. Now imagine coordinating 10,000 people who all need updated information every few milliseconds. Suddenly, communication itself becomes the biggest challenge. Modern AI clusters face exactly that problem. Every training cycle requires processors to exchange parameters, gradients, weights, and intermediate calculations. As clusters grow larger, the amount of communication grows even faster than the amount of computation. That's why networking has become one of the hottest areas in semiconductor research. Several Chinese companies have already demonstrated advanced AI servers, domestic switching equipment, optical interconnect technologies, and high-speed communication platforms. While each announcement might seem unrelated, together they point toward an effort to reduce dependence on foreign AI infrastructure. This also explains why Alibaba's recent 128-chip AI server attracted so much attention. Many people focused on the processors themselves, but the more interesting question was this: how efficiently do all 128 processors communicate? The same applies to China's no-GPU supercomputer projects, its photonic chip developments, and its advanced optical fiber demonstrations. These aren't isolated breakthroughs. They're pieces of a larger puzzle. If China successfully combines domestic processors, domestic memory, domestic networking, domestic packaging, and domestic manufacturing into one complete ecosystem, it becomes far less vulnerable to outside supply restrictions. That's a strategic advantage that extends well beyond artificial intelligence. It means researchers can continue building larger AI systems using technologies developed and manufactured within their own industrial ecosystem. For NVIDIA, however, this creates an interesting challenge. The company remains the global leader in AI hardware, and its networking technologies are among the most advanced in the world. NVIDIA doesn't simply sell GPUs anymore. It sells complete AI infrastructure, including networking, software, switches, communication libraries, and integrated systems. That's one reason NVIDIA has been so successful. Customers aren't buying individual chips, they're buying an entire AI platform. China appears to be pursuing a similar strategy, but using domestic technology wherever possible. Whether that ecosystem ultimately matches NVIDIA's performance remains an open question, but even approaching comparable performance would represent a significant achievement, especially considering how quickly China's AI hardware ecosystem has evolved over the past several years. Another reason this matters involves cost. Building one of today's frontier AI data centers requires staggering amounts of capital. GPUs represent only part of that expense. Networking equipment, optical transceivers, switches, storage systems, cooling infrastructure, electrical distribution, and physical construction account for enormous portions of the overall investment. If communication technologies become more efficient, companies may need fewer networking devices to achieve the same workload. If processors spend less time waiting, fewer processors may accomplish the same training task. If energy consumption drops, operational costs decrease year after year. Those savings compound across facilities containing tens of thousands of accelerators. Suddenly, communication improvements become financial improvements. That's exactly why investors closely watch networking announcements even when they don't generate the same headlines as new processors. Now consider another trend happening simultaneously: AI inference. Training enormous models receives most of the attention, but inference, actually running AI after it's trained, is becoming an even larger market. Billions of users interacting with AI assistants, image generators, autonomous vehicles, industrial robots, medical systems, and enterprise software require enormous infrastructure. Inference also benefits from faster communication, especially when requests must travel between multiple processors and memory systems almost instantly. Future AI won't exist inside one processor. It will exist across entire distributed computing environments. That's why networking matters for both training and deployment. There's also another technology quietly entering this discussion: silicon photonics. Instead of moving information using traditional electrical signals through copper connections, silicon photonics uses light traveling through optical pathways. Light experiences lower resistance, generates less heat, and can carry tremendous amounts of information simultaneously. Several countries are investing aggressively in this technology because many engineers believe future AI data centers will increasingly rely on optical communication rather than purely electrical connections. China has been especially active here. You've already seen stories on this channel involving glass chips, photonic manufacturing, air-filled fiber, optical communication, and integrated photonic devices. Viewed separately, each seemed like a fascinating breakthrough. Viewed together, they reveal a long-term direction. Replace communication bottlenecks with light. That doesn't happen overnight. Entire industries must adapt. Manufacturing changes, software changes, data center architecture changes. But once that transition begins, the performance gains can become substantial. It's similar to the transition from hard drives to solid-state storage. At first, only premium systems adopted SSDs. Eventually, they became standard because the performance difference was simply too significant to ignore. Networking may follow a similar path. The fastest future AI systems could increasingly rely on optical communication internally. Another fascinating aspect of China's strategy is diversification. Rather than betting everything on one technology, Chinese companies appear to be exploring multiple complementary directions simultaneously. Photonics, advanced packaging, novel memory, glass substrates, three-dimensional integration, domestic AI accelerators, optical networking, ultra-fast fiber. Each technology strengthens the others. That's important because AI performance rarely depends on one breakthrough anymore. Progress happens when dozens of improvements arrive together. Think about Formula One racing. Winning doesn't come from having only the strongest engine. Teams optimize aerodynamics, suspension, tires, brakes, fuel efficiency, weight distribution, driver strategy. Tiny gains across every category produce enormous advantages on race day. Artificial intelligence infrastructure works the same way. Every percentage improvement compounds. Better networking improves GPU utilization, better memory reduces weighting, better packaging shortens communication distances, better cooling allows higher sustained performance, better software coordinates everything more efficiently. Eventually, the combined improvement becomes much larger than any single breakthrough. That's exactly why complete AI ecosystems matter. Looking ahead, analysts expect competition to become even more intense. The next generation of AI models will almost certainly require even larger computing clusters. That means networking requirements will continue growing. Data movement will become even more critical. Energy efficiency will matter even more. Infrastructure spending will likely continue breaking records. Every company wants faster AI. Every government wants technological independence. Every cloud provider wants lower operating costs. Networking sits directly in the middle of all three goals. For viewers, the biggest takeaway isn't whether one country wins tomorrow. The real takeaway is understanding where the industry is heading. For years, headlines focused almost exclusively on processors. Now the conversation is expanding. Memory matters, packaging matters, cooling matters, optics matter, networking matters. And increasingly, the companies mastering every layer of the AI stack will likely shape the future of artificial intelligence. Whether China's latest AI networking technologies ultimately outperform competing solutions remains something the industry will continue evaluating as more systems are deployed and independently tested. Performance claims always require real-world validation across diverse workloads. But regardless of exact benchmark numbers, one conclusion is becoming increasingly difficult to ignore. The global AI race is no longer only about building faster chips. It's about building faster systems, complete systems, integrated systems, entire ecosystems capable of training, deploying, and scaling artificial intelligence more efficiently than ever before. That's why announcements involving networking may soon become just as important as announcements involving GPUs themselves. The future winners won't necessarily be those with the fastest individual processor. They may be the ones whose processors spend the least amount of time waiting. And if that's the direction artificial intelligence is heading, then today's networking breakthroughs may end up being remembered as some of the most important developments of this entire AI era. Because in the next generation of AI, speed won't just be measured inside the chip, it will be measured between them. If you enjoyed today's breakdown, don't forget to like the video, subscribe to the channel, and turn on notifications because every day we cover the biggest breakthroughs shaping China's technology race, from AI chips and memory, to photonics, robotics, semiconductors, quantum computing, and everything in between. Thanks for watching, and we'll see you in the next one. His name is Dong Hui. He is 39 years old. 6 years ago, a car accident left him paralyzed from the neck down. He couldn't move his fingers. He couldn't write. Something as ordinary as holding a pen had become completely impossible, and every specialist he'd seen told him the same thing in different words: this is permanent. Then surgeons placed a coin-sized chip between his skull and his brain. 11 months later, sitting in the courtyard of his home in China's Henan province, Dong Hui picked up a pen. Slowly, carefully, deliberately, he wrote his name. Then he wrote, "Thank you." Then he wrote the date. He later told journalists he was so overwhelmed that he missed a stroke in his own name. "I couldn't believe I was able to write again. I was so excited." That chip, the one that gave Dong Hui back his hands, just became the first invasive brain-computer interface in history to receive full commercial approval anywhere on Earth. Not a trial permit, not a research exemption, a product license. Available to real patients, covered by China's national health insurance. In production right now, scaling to meet demand. And here's the part that changes the entire story. While that was happening, Elon Musk's Neuralink, the most famous, most funded, most publicized brain chip project in the world, still has 21 people in an experimental trial. No commercial approval, no product license, no insurance coverage, anywhere. The race that everyone assumed Elon Musk would win, someone just crossed the finish line. And it wasn't him. To understand what just happened, you need to understand how this competition looked from the outside for the past several years. Neuralink was the story. Full stop. Elon Musk announced it, hyped it, described a future where paralyzed people would walk again, where blind people would see again, where the entire interface between human consciousness and computing would be reinvented. He is the most followed person on the planet. Every announcement got global coverage. Every trial update was front-page news. The assumption baked into almost every article written about brain-computer interfaces was simple. Neuralink leads, everyone else follows. Meanwhile, in Shanghai, a startup called Neuracle Technology was quietly doing something different. No celebrity CEO, no viral announcements, no promises about controlling computers with your thoughts or uploading your memories. Just a research team, a partnership with Tsinghua University, one of China's most prestigious technical institutions, and a singular focus on getting one specific device approved for one specific group of patients. The device was called Neo. It's roughly the size of a coin. It takes about 90 minutes to implant. It sits between the skull and the outer protective membrane of the brain, called the dura mater, with 8 sensors pressing gently against that membrane, without ever penetrating the brain tissue itself. Wireless signals travel from the implant to an external processor, which translates the brain's electrical activity into commands for a robotic glove, allowing patients with severe hand paralysis to perform basic grasping movements they hadn't been able to do in years. In March 2026, China's National Medical Products Administration gave it full commercial clearance. 36 clinical trials, 32 of them completed in a compressed window in 2025 alone. And then, approved. Not for trials, for hospitals, for patients, for production. The first invasive brain implant ever cleared for sale anywhere in the world. Here's the counterintuitive part of this story. Neo is not the most powerful brain chip ever built. It almost certainly isn't. Neuralink's N1 chip penetrates the brain's outer cortex directly, accessing neural signals closer to their source and potentially enabling finer, more precise control. Neuralink's long-term ambitions, restoring sight, enabling full-body movement, eventually merging human consciousness with computing, are technically more audacious than anything Neo currently does. So how did the less aggressive device win the regulatory race? Because less aggressive and commercially viable are not opposites. They're often the same thing. NEO's design is epidural. It sits on top of the brain's protective membrane, rather than inside the brain tissue itself. A researcher at the University of Technology, Sydney, speaking to MIT Technology Review, explained why that distinction matters enormously in a regulatory context. An epidural approach carries significantly lower risk of bleeding and lower risk of signal loss over time than electrodes that penetrate the cortex. When a regulator is evaluating a device for broad commercial use, not just in a handful of carefully selected trial participants, but in real hospitals with real patients who have varying health conditions, risk profile is everything. NEO didn't win because it outperformed Neuralink. It comes with coordinated funding, expedited regulatory pathways, and the kind of institutional alignment between researchers, companies, and government that compresses the timeline from lab to clinic in ways that are genuinely difficult to replicate in a system where commercial interests, regulatory bodies, and research institutions operate independently. Neuralink ran 32 of its 36 trials in a matter of months in 2025. That pace of clinical validation reflects a system operating in a different gear from what Neuralink has been navigating. The facts and the regulatory milestones are important, but there's a human being at the center of this story, and he deserves more than a footnote. Everything you do online is being watched: your provider, advertisers, even governments. NordVPN encrypts your connection, hides your location, and unlocks the open internet from anywhere. Grab the deal, link in the description. Dong Hui was paralyzed in 2018, 6 years of his life spent unable to use his hands. Then he saw something on television, a news report about another paralyzed man in China who had regained some movement through a brain-computer interface trial. He signed up for Neuralink's program in October 2023, 1 month after watching that report. The implant went in. The rehabilitation process began. Slowly, painstakingly, his brain learned to communicate with the device, and the device learned to interpret his brain. 11 months later, he wrote his name in his own courtyard. He also told journalists he hadn't expected it to work. He'd spent 6 years being told his condition was permanent. The moment he picked up that pen was the moment 6 years of that certainty collapsed. This is what NEO actually is, underneath all the regulatory language and competitive framing. It is a device that gave a man back the ability to write his own name, and it is now approved for use in a country of 1.4 billion people, covered by the National Health Insurance System, with more patients entering the program as production scales. The numbers behind that aren't just impressive, they're staggering. Hundreds of thousands of people in China live with the kind of spinal cord injury NEO is designed to treat. Here's the pattern that keeps appearing in technology, and it's directly relevant to everything covered on this channel. A technology is invented, usually in a Western lab, usually by researchers with enormous resources and high ambitions. For years, everyone watches that original team. They assume the leader stays the leader. They write articles about when the technology will mature, when it will become commercial, when it will change the world. All the attention stays focused on the most famous version of the thing, and then something else happens somewhere else. Quietly, methodically, without the celebrity or the headlines. A different team, with different priorities, in a different system, makes different design choices. And while everyone is watching the famous version, the less famous version crosses a threshold that matters. It happened with glass chips. The semiconductor industry was fixated on transistors and lithography while the substrate layer changed underneath everyone. It happened with diamond cooling. NVIDIA's CEO was flying to China while most of the world was still debating whether diamond was even practical. And now it's happening with brain chips. Neuralink has more press coverage than every other BCI company combined. And a startup most people have never heard of, built in Shanghai with funding from Tsinghua University and backing from China's National Technology Strategy, just became the first to put a commercially approved brain implant into a patient outside a clinical trial. The pattern isn't that the famous version is wrong or that the quiet version is always better. The pattern is that fame and leadership aren't the same thing. And in technology, the milestone that actually counts isn't who announced it first, it's who shipped it first. NEO is the first. It will not be the only. China has at least 2 more BCI devices behind NEO in the pipeline. Neuroxess and StairMed are both developing competing implants domestically. The Beijing Brain Institute's BEINA01 system is expected to reach market by 2028. Within the span of roughly 2 years, China could have multiple commercially approved brain implants operating in its healthcare system, each generation learning from the one before it, while the rest of the world is still working through regulatory trials. The advantage this creates isn't just about one device, it's about data. Every patient who receives Neo generates real-world performance data in a commercial healthcare setting. That data, how the implant performs over months and years, which patient profiles respond best, which failure modes appear, and how often, is exactly the kind of evidence that makes second-generation devices better. And it is the kind of evidence that regulators in other countries will eventually require before approving anything. China now has a head start not just in commercial approval, but in the accumulation of long-term, real-world safety and performance data. That compounding lead is far harder to close than a regulatory gap. It's the same dynamic as the glass substrate story, the same dynamic as the diamond chip story. Being first doesn't just mean you got there early, it means every subsequent year of operation makes you harder to catch. For Neuralink specifically, the competitive picture has shifted in a way that doesn't get fully acknowledged. Neuralink's technical ambitions remain larger. Its long-term vision, the idea of a general-purpose brain-computer interface that goes far beyond motor rehabilitation, hasn't changed, but it is now competing in a landscape where a rival has commercial approvals, insurance coverage, real patients, and accumulating real-world data, while Neuralink is still adding participants to a clinical trial. That's a different kind of pressure than it was 12 months ago. Here's what strikes me most about this story, and it's something I keep coming back to. Neuralink had everything: the money, the attention, the most famous founder in technology, a decade of runway, and Neo, a startup from Shanghai with a fraction of the profile, shipped first. Not because Neuralink is more talented than Neuralink's engineers, both teams are world-class, but because Neuralink made a device that was designed to clear regulatory hurdles rather than one designed to impress a keynote audience. They optimized for approval, not for ambition. And in the market for medical devices, approval is everything. The most powerful chip in the world is useless inside a lab. I think the Neuralink story is far from over. A device that actually penetrates the cortex and accesses finer neural signals will likely enable capabilities that Neo simply can't. But Neuralink now has to develop and prove those capabilities while a competitor is already in hospitals, already covered by insurance, already generating data, and already treating patients. That's a completely different race than the one Neuralink thought it was running. Here's my question for you, and I want your honest answer. Does this change how you think about Neuralink? Because here's the tension. Neo got to market first, but Neuralink's ambitions are larger. Is first to market in medicine the thing that matters most, or does the device with the higher ceiling eventually win regardless? Drop your actual opinion in the comments. This one I'm genuinely curious about. If you want to keep following these stories, the ones that rewrite which country leads in a technology that seems settled, subscribe to Eastern Engine and turn on notifications. Brain chips, diamond chips, glass chips, the substrate layer, the thermal layer, all of it connects. And all of it is moving faster than most people realize. Thanks for watching. See you in the next one. Apple wants China's RAM after a 98% price surge. MacBooks already cost more. Apple has spent decades building one of the strongest supply chains in technology. But this time, even Apple could not absorb the pressure. MacBook and iPad prices have already increased after the cost of memory and storage chips surged across the industry. Now Apple is reportedly asking Washington for political clearance to purchase DRAM from Changshin Memory Technologies, better known as CXMT, China's largest memory chip producer. The reported request does not mean a deal has been signed. It does not mean Chinese RAM is already inside new MacBooks. And it does not mean CXMT has replaced Samsung, SK Hynix, or Micron. But the fact that Apple is even considering this option reveals how extreme the memory shortage has become. DRAM prices reportedly rose by as much as 98% during the first quarter of 2026, with another sharp increase expected during the second quarter. The AI boom is consuming advanced memory, manufacturing capacity, packaging resources, and capital at a pace the consumer electronics industry did not expect. Why Apple raised prices? Apple normally avoids sudden price changes during a product cycle. The company prefers predictable pricing because customers compare models, retailers plan inventory, and the entire product lineup is carefully positioned around specific price points. That strategy changed when memory and storage costs climbed too quickly. The entry MacBook Neo rose from $599 to $699. A 512GB MacBook Air increased from $1,099 to $1,999. The 128GB iPad Air moved from $599 to $749. Other Mac, iPad, HomePod, and Apple TV products also became more expensive. Apple said the increases were unavoidable because the company could no longer protect customers from the speed and scale of the component cost surge. If Apple cannot fully contain memory inflation, smaller computer and smartphone manufacturers are likely facing even greater pressure. How AI created a memory shock. An AI accelerator is only as useful as the memory feeding it. Large models require enormous quantities of data to remain close to the processor. Training needs high bandwidth memory to keep thousands of computing units active. Inference also consumes memory because model weights must be read repeatedly while each new token is generated. This has made HBM one of the most valuable products in the semiconductor industry. Samsung, SK Hynix, and Micron are investing heavily in high bandwidth memory because it earns stronger margins than many conventional products. It uses DRAM manufacturing technology, advanced packaging, engineering talent, capital, and factory time that might otherwise support ordinary server, laptop, or mobile memory. When capacity is limited, they prioritize the customers and products offering the highest return. AI companies can justify paying more because a single accelerator system may cost tens or hundreds of thousands of dollars. A laptop maker cannot increase component costs indefinitely without damaging demand. Prices rise. Apple's new prices are one of the clearest signs that the AI memory shortage has moved beyond server rooms. Why CXMT suddenly matters. CXMT was founded in 2016. DRAM is one of the hardest semiconductor markets to enter because success depends on scale, yield, process control, reliability, and relentless cost reduction. A small process variation can reduce the number of usable chips produced from every wafer. CXMT began by supplying more conventional DRAM products for China's domestic market. Its early technology lagged the global leaders, but it continued expanding capacity, improving processes, and introducing newer generations of DDR and low-power memory. The company is now widely regarded as the world's fourth-largest DRAM supplier, although it remains far smaller than the top three. Apple does not need CXMT to be larger than Samsung. It needs another supplier capable of producing qualified memory at meaningful volume. Even a modest additional source can strengthen Apple's negotiating position and reduce dependence on a tightly concentrated supplier base. The shortage has transformed CXMT from a distant challenger into a potentially useful option. What Apple is reportedly asking for. According to reports, Apple has been lobbying the United States government for clearance to buy memory chips from CXMT. The company reportedly approached officials because CXMT appears on a Pentagon list of companies alleged to have links to China's military. That listing does not automatically create a universal legal ban on every commercial purchase. However, it creates political, reputational, and regulatory risk. A supplier that is permitted today could face tighter restrictions later. Apple could spend months qualifying a product, redesigning logistics, and negotiating contracts only to see new rules block the arrangement. That is why political clearance matters even if the transaction is not currently prohibited in the simplest legal sense. Apple wants confidence that it will not build part of its supply chain around a supplier that Washington later prevents it from using. The administration has not publicly approved the request. Apple and CXMT have not announced a supply agreement. For now, this is an attempt to create an option, not proof that the option will be used. Apple's qualification process. Supplying Apple is not as simple as offering a low price. Memory must meet strict requirements for performance, power consumption, heat, reliability, packaging, and long-term consistency. A chip may pass one laboratory test and still fail to qualify for mass production. Apple needs components that behave predictably across millions of devices. The supplier must maintain quality from one production batch to the next. It must provide enough volume on schedule. It must support Apple through product launches, regional demand changes, and unexpected factory disruptions. For MacBooks and iPads, power efficiency is especially important. Poor memory efficiency reduces battery life and creates additional heat. Reliability is equally important because defective memory can cause crashes, data corruption, or complete device failure. CXMT would need to prove that its products satisfy Apple's technical standards and that its factories can maintain those standards at scale. Apple may also require extensive audits, traceability, security controls, and contingency plans. Political permission would only open the door. Technical qualification would decide whether CXMT could walk through it. Why Samsung, SK Hynix, and Micron should pay attention. The established suppliers still dominate global DRAM. They possess larger factories, more advanced products, stronger customer relationships, and decades of manufacturing experience. CXMT does not threaten to replace them overnight. But Apple's interest would still carry major symbolic weight. Apple is one of the most demanding and visible electronics companies in the world. If CXMT qualified for even part of Apple's memory supply, other manufacturers would pay attention. A successful Apple contract could validate CXMT's reliability and production discipline. It could also give Apple more leverage during negotiations with current suppliers. Memory is a cyclical commodity business. Small changes in supply and demand can produce large price movements. Adding another credible supplier does not need to eliminate Samsung or Micron to affect the market. It only needs to weaken the assumption that buyers have no alternative. The possibility of CXMT entering Apple's supply chain could therefore influence pricing even before large shipments begin. Why China could benefit? For China, an Apple contract would be more than a commercial sale. It would demonstrate that a domestic memory producer had reached standards acceptable to one of the world's most influential device makers. That could strengthen confidence among Chinese computer, smartphone, server, and automotive companies. It could support CXMT's expansion and help the company improve through larger production volumes. Semiconductor manufacturing often becomes more competitive through repetition. Higher volume generates more process data. More data helps engineers find defects, improve yield, and lower cost. A major customer can therefore accelerate a supplier's development, but the relationship would also create dependence. CXMT would need to satisfy Apple's requirements, absorb pricing pressure, and invest heavily to support future products. Apple is famous for demanding lower costs while maintaining strict quality. Winning the business would be prestigious. Keeping it profitable would be another challenge. Could Chinese RAM lower MacBook prices? Possibly, but not immediately. Adding a supplier can improve competition and reduce procurement risk. If CXMT offers qualified memory at a lower price, Apple could reduce some of the pressure created by the shortage. However, Apple has already raised retail prices. Companies rarely reverse broad price increases quickly unless market conditions change dramatically. The memory market also remains tight. One supplier cannot instantly replace capacity across the industry. CXMT must serve domestic customers while expanding production and improving technology. Any Apple agreement would likely begin with limited volumes or selected products rather than the entire Mac lineup. There is also no guarantee that lower component costs would be fully passed to consumers. Apple could use savings to protect margins, invest in supply security, or avoid additional price increases. The most realistic short-term benefit would be preventing the situation from becoming worse. CXMT could give Apple another source of supply while the company waits for global memory capacity to catch up with AI demand. The political problem. This is where the technology story becomes complicated. Some American lawmakers are likely to oppose any arrangement with CXMT because of national security concerns and broader efforts to reduce dependence on Chinese technology. They may argue that allowing Apple to become a major customer would strengthen a strategic Chinese semiconductor company. Others may focus on supply chain resilience and consumer prices. Blocking an available supplier during a severe shortage could increase costs for American companies and customers. Apple must navigate both arguments. The company sells heavily in China, manufactures much of its hardware through Asian supply chains, and depends on global suppliers. At the same time, it is one of the most prominent American corporations and faces intense political scrutiny. A memory contract that looks economically sensible could still become politically impossible. That uncertainty may be the greatest obstacle. The honest catch. The headline is powerful, but several facts must remain separate. Apple reportedly wants clearance to buy from CXMT. Apple has not confirmed a signed contract. CXMT memory is not confirmed inside current MacBooks. The reported 98% increase refers to market pricing during a specific period, not the exact cost increase of every memory chip Apple buys. MacBook and iPad prices rose for multiple configurations, but iPhone prices had not yet increased at the time of the announcement. CXMT also remains behind the leading suppliers in advanced memory technology and total production scale. The story is not that Apple has abandoned Samsung, SK Hynix, and Micron. The story is that the shortage has become severe enough for Apple to explore a politically risky supplier it previously did not rely on. My take is that Apple's reported request is one of the clearest signs that AI has changed the value of memory. For years, DRAM was treated as a replaceable commodity purchased from a small group of established suppliers. Now memory is becoming strategic. AI companies are absorbing supply. Prices are rising fast enough to change retail products, and a Chinese manufacturer that once looked peripheral suddenly has leverage because it can add capacity. Apple may never complete the deal. Political pressure could stop it. CXMT could fail qualification. The shortage could ease before large shipments begin. But the request itself matters. It shows that supply security can become more important than old assumptions about which companies are acceptable suppliers. It also shows how AI infrastructure costs are spreading through the wider economy. Consumers buying laptops are now paying for competition happening inside data centers. So what do you think? Should Apple be allowed to buy memory from CXMT if the chips meet its technical standards? Or would the long-term strategic risk outweigh any short-term reduction in cost? Let me know your view in the comments. And subscribe to Eastern Engine for more grounded coverage of the chips, factories, and engineering decisions reshaping technology. Because Apple is not turning to Chinese memory out of curiosity. It is considering it because a 98% price surge has made the old supply chain too expensive to ignore. The global technology industry is facing a memory crisis. RAM prices have climbed sharply. Storage prices are under pressure. AI data centers are consuming enormous quantities of advanced memory. And Lenovo is now warning that the unusually cheap memory market of early 2025 may not return for a very long time. At the International Supercomputing Conference, the company reportedly described the situation as the new normal. One Lenovo executive even said that memory pricing may never be like it was last year. The word never was delivered with a smirk, so it should not be interpreted as a literal prediction that prices can never fall. But the larger warning was serious. Artificial intelligence has changed the economics of the memory industry. Samsung, SK Hynix, and Micron are directing more production toward high-margin memory for AI servers. New factories will take years to complete, and even when additional capacity arrives, AI demand may absorb much of it. But just as the traditional memory giants are warning that shortages could last for years, China is creating a new challenger. Changshin Memory Technologies, better known as CXMT, is rapidly expanding its production capacity, moving into server memory, signing major customers, and approaching the manufacturing scale of Micron. Some analysts believe CXMT could become one of the largest DRAM producers in the world by wafer capacity. The question is whether China's RAM giant can finally break the global memory shortage, or whether its chips will be absorbed so quickly by China's own AI industry that prices everywhere else remain painfully high. Why RAM prices are surging? To understand the crisis, we first need to understand what has changed. For decades, memory was one of the most cyclical parts of the semiconductor industry. When demand was strong, Samsung, SK Hynix, and Micron expanded production. Eventually, too much memory reached the market. Prices collapsed, manufacturers reduced investment, supply tightened again, then the cycle restarted. This created periods when computer builders could purchase large amounts of RAM for surprisingly low prices. Early 2025 was one of those periods. But the current cycle is different because artificial intelligence is consuming memory at a scale the industry did not previously expect. An ordinary consumer computer may contain 16 or 32 gigabytes of RAM. A powerful AI server can require several terabytes of conventional DRAM, along with large quantities of high-bandwidth memory attached directly to AI accelerators. Modern AI systems must constantly move enormous amounts of model data between processors and memory. Without enough memory bandwidth, even the fastest GPU spends time waiting for information. That has made memory one of the most valuable components inside an AI data center. The HBM problem. High bandwidth memory, or HBM, is a specialized form of DRAM. Instead of placing memory chips separately across a circuit board, manufacturers stack multiple layers of memory vertically and connect them using extremely dense electrical pathways. The result is much faster communication between the memory and an AI accelerator. HBM is essential for advanced processors from NVIDIA, AMD, and other AI chip designers. It is also far more profitable than ordinary consumer memory. That creates an obvious incentive. If a manufacturer can use factory space to produce expensive HBM for AI companies, why devote the same resources to lower-margin DDR4 or standard DDR5 for consumer computers? Samsung, SK Hynix, and Micron have therefore shifted investment and cleanroom capacity toward AI-related products. But this is not a simple conversion. HBM requires extra manufacturing steps, advanced packaging, and multiple memory dies. Producing a usable quantity of HBM can consume considerably more wafer capacity than producing a comparable amount of conventional memory. That means the AI boom does not only increase demand, it also changes which products memory companies choose to manufacture. Every wafer directed toward premium AI memory is capacity that cannot simultaneously produce ordinary RAM for laptops, gaming computers, smartphones, and lower-cost servers. The new normal IDC has described the current shortage as more than a temporary mismatch between supply and demand. It may represent a strategic reallocation of global semiconductor capacity. The largest memory manufacturers are increasingly prioritizing hyperscalers, AI server companies, and enterprise customers willing to pay higher prices. Consumer electronics manufacturers are forced to compete for what remains. This can affect far more than individual RAM kits. Memory represents a significant portion of the cost of a smartphone. It is also essential for laptops, desktop computers, game consoles, networking equipment, vehicles, and industrial systems. When memory prices rise, manufacturers have several options. They can increase the final price. They can reduce the amount of memory inside the product. They can delay upgrades, or they can accept lower profit margins. None of those options is good for consumers. IDC has warned that memory constraints could contribute to weaker PC and smartphone sales during 2026, especially in lower-cost product segments where manufacturers operate on thin margins. Why supply cannot respond quickly? Normally, high prices encourage companies to build more factories. That process is now happening. SK hynix has announced an enormous investment program covering new memory production and advanced packaging facilities. Samsung and Micron are also expanding. But semiconductor factories cannot be built overnight. A modern memory fab requires land, clean rooms, power infrastructure, specialized gases, water systems, lithography machines, deposition tools, inspection equipment, and thousands of trained workers. Construction can take several years. After that, the production line must be installed, calibrated, tested, and gradually increased toward full output. SK hynix's latest major NAND facility is not expected to begin production until close to the end of the decade. Some advanced packaging capacity could arrive earlier, but the broader point remains the same. The factories needed to solve today's shortage will not deliver their full output tomorrow. And by the time they are ready, AI demand may be much larger. Enter CXMT. This is where CXMT becomes important. CXMT was founded in 2016 with government support and has become China's leading producer of DRAM. For years, the company was considered far behind Samsung, SK hynix, and Micron. Its manufacturing technology was less advanced, its product range was narrower, its yields were weaker, and much of its business focused on supplying China's domestic market. But CXMT has expanded rapidly. It now produces memory for computers, smartphones, servers, and other electronic systems. Its publicly disclosed customers reportedly include Tencent, Alibaba Cloud, ByteDance, Lenovo, and Xiaomi. That customer list matters because it shows that CXMT is no longer supplying only low-end or experimental applications. China's largest cloud and technology companies are beginning to treat domestic memory as a strategic component of their infrastructure. The Tencent Agreement. The clearest evidence is a reported long-term agreement between CXMT and Tencent. According to people familiar with the arrangement, the contract is worth more than 20 billion yuan, or approximately $2.94 billion. It reportedly covers several years of server DRAM supply. Different sources describe the period as between 3 and 5 years. Neither CXMT nor Tencent publicly confirmed the details when the report appeared, so the agreement should not be described as an official joint announcement. Still, if accurate, the scale is significant. Tencent operates one of China's largest cloud computing and internet infrastructures. It needs memory for databases, gaming services, social platforms, cloud servers, and artificial intelligence workloads. A multi-billion-dollar commitment would provide CXMT with predictable demand and give Tencent greater protection from the global shortage. It would also provide CXMT with something equally valuable: experience. Supplying a large cloud company forces a memory manufacturer to improve reliability, quality control, product consistency, and customer support. Enterprise customers cannot tolerate large failure rates. Their servers may run continuously for years. A major agreement therefore becomes more than a sale. It becomes a large-scale test of whether CXMT can compete in serious data center environments. Approaching Micron's scale, CXMT's most important advantage may be capacity. Semi-analysis estimates that the company could reach approximately 350,000 wafer starts per month by the end of 2026. Micron is estimated at around 385,000. That does not mean CXMT has already caught Micron as a complete company. Wafer capacity is only one measurement. Micron still has advantages in manufacturing technology, product performance, high bandwidth memory, yields, global customer relationships, and revenue. A more advanced process can produce more memory bits from each wafer. A company with fewer wafers may therefore still ship more useful memory. But reaching close to Micron's physical wafer scale would still be a remarkable change. The global DRAM industry has historically been dominated by 3 companies. Samsung is the largest. SK Hynix is the second major leader, particularly in HBM. Micron is the primary American supplier. CXMT is now attempting to turn that 3-company structure into a 4-company market. Can CXMT break the oligopoly? Memory manufacturing requires enormous capital. This high barrier to entry helps Samsung, SK Hynix, and Micron maintain control over most global DRAM production. When only 3 suppliers dominate an essential product, the decisions made by those companies can affect the entire electronics industry. If all 3 prioritize HBM, conventional DRAM becomes tighter. If all 3 slow investment, prices rise. If all 3 expand aggressively, oversupply eventually returns. CXMT introduces another decision maker. A 4th large producer could increase competition and add capacity during periods when the established manufacturers remain disciplined. That is why investors and industry analysts watch Chinese memory expansion so carefully. China previously disrupted other industries by adding enormous manufacturing capacity. Solar panels, batteries, steel, and several electronics categories experienced major price declines after Chinese production scaled. Some observers believe memory could eventually follow the same pattern. If CXMT produces far more DDR5 and server DRAM than China needs, additional chips could enter export markets and place pressure on global prices. But that outcome is not guaranteed. Why CXMT may not save global buyers? China's own demand is enormous. Tencent, Alibaba, ByteDance, Baidu, Huawei, and other companies are constructing AI infrastructure. Chinese computer manufacturers need domestic memory. Smartphone makers want secure supplies. Government and state-backed projects are being encouraged to use Chinese components whenever possible. This means CXMT may expand quickly without creating a large surplus for the rest of the world. Its new capacity could be absorbed almost entirely inside China. Export restrictions create another complication. CXMT faces limits on access to some advanced American semiconductor equipment. That can make it harder to move toward the most advanced manufacturing processes. The company may be able to install more production lines while still trailing competitors in memory density, efficiency, and yield. More wafers do not automatically mean cheaper memory if each wafer produces fewer usable chips. CXMT also remains relatively weak in HBM. Semi-analysis estimates that only a small portion of its current capacity is allocated to high-bandwidth memory, although this is expected to increase. That means CXMT may provide meaningful relief for conventional DRAM before it becomes a major competitor in the most advanced AI memory category. And conventional DRAM is exactly where consumers need relief. The 2 possible futures. There are now 2 very different futures for the memory market. In the first scenario, AI demand remains extremely strong. Samsung, SK Hynix, and Micron continue prioritizing HBM and enterprise memory. CXMT expands, but its output is absorbed by China's own cloud companies and electronics manufacturers. New factories arrive slowly. Consumer RAM remains expensive. Prices fluctuate, but the ultra-cheap memory environment of early 2025 does not return. In the second scenario, CXMT expands faster than expected. Its yields improve. Its DDR5 products become more competitive. China's domestic demand is satisfied. CXMT begins exporting larger quantities or indirectly frees other suppliers to serve global customers. The established manufacturers respond by increasing production or reducing prices. Competition returns. RAM becomes more affordable. The difference between those outcomes may depend on whether AI infrastructure continues growing at the current pace. It will also depend on how much production CXMT can add without access to the newest foreign equipment. What prices may never recover really means. The title of this story needs context. Memory prices will not rise forever in a straight line. The semiconductor industry remains cyclical. Demand can weaken. Factories can overbuild. New technologies can increase the number of bits produced from each wafer. Prices will rise and fall. The warning from Lenovo is not that RAM can literally never become cheaper. It is that the old reference point may no longer be realistic. The extremely low prices seen during periods of heavy oversupply may become less common because AI companies are creating a new source of structural demand. Even when consumer demand falls, data center customers may continue purchasing enormous quantities of memory. That creates a stronger floor under the market. My take is that CXMT can weaken the global memory shortage, but it may not end Ramageddon quickly. The company's expansion is real. Its reported Tencent agreement is significant. Its estimated wafer capacity is approaching the physical scale of Micron, and its customer base now includes some of China's largest technology companies. But the same forces making CXMT powerful are also consuming its output. China wants domestic RAM because foreign supplies are expensive, politically uncertain, and strategically important. Every new CXMT wafer may already have a Chinese customer waiting for it. That means global consumers should not assume that Chinese expansion will immediately produce cheap RAM on Western store shelves. The larger impact may appear gradually. CXMT can reduce China's purchases from Samsung, SK Hynix, and Micron. Those suppliers may then have more capacity available for other customers. CXMT can also place competitive pressure on the established memory giants, forcing them to improve products, expand output, or reconsider pricing. The important change is that the global DRAM market may no longer be controlled entirely by the same three companies. A fourth major supplier is emerging. And during the worst memory shortage in years, that supplier may become one of the most strategically important semiconductor companies in China. So what do you think? Can CXMT expand fast enough to bring RAM prices back down? Or will AI data centers consume every new memory chip the industry can produce? Let me know your view in the comments. And subscribe to Eastern Engine for more grounded coverage of the chips, factories, and engineering decisions reshaping the global economy. Because Ramageddon may be the new normal, but China is building the one company that could eventually break it. There is a building in the city of Wuhan, China, that has its own weather. Every single morning, an artificial sun rises inside it. It climbs across a simulated sky, shifting color as the hours pass, pale blue at dawn, warm amber by midday, deep orange and violet toward evening. And then it sets. The tens of thousands of people inside, shopping, skiing, riding roller coasters, watching their children splash along an indoor lakeside beach, can glance upward and watch the whole cycle unfold in real time. This is Dream Plaza, and it is one of the most ambitious buildings operating anywhere on the planet today. The numbers alone are staggering. The complex covers nearly 800,000 square meters of floor space. The retail center by itself spans 370,000 square meters across 9 floors above ground and 4 below. But those figures only describe the shell. They tell you nothing about what was put inside it, or why, and that is the far more interesting story. Because Dream Plaza is not just big, it represents a completely different theory of what a building in the center of a modern city is even supposed to be. To understand why it exists, you first have to understand what it was built to escape. Almost every country that built shopping malls in the second half of the 20th century eventually watched them decline. The formula was always identical: a large enclosed space, anchor stores at either end, smaller shops filling the corridors between them, a food court somewhere in the middle, and a vast parking lot wrapped around the whole thing like a moat. For decades, this worked beautifully. People drove in, walked the corridors, and spent money. Then online shopping arrived, and the formula came apart. The question that broke the traditional mall was brutally simple. Why would anyone drive to a building, hunt for a parking space, walk to a store, and pay a marked-up price for something they could order from their couch and have delivered the next morning? Increasingly, the answer was that they wouldn't. Foot traffic dropped. Anchor tenants packed up and left. The corridors emptied out. Across much of the West, shopping centers became half-lit monuments to a retail model the world had quietly moved beyond. Chinese developers watched this happen, and rather than simply copying the format that was already dying, they studied the failure carefully. They traced it back to its root cause. The malls had stopped offering a reason to show up that couldn't be replicated by staying home. And from that, they drew a conclusion that seems obvious in hindsight, but that most Western developers were too invested in the old model to act on. People have never primarily left their homes in order to buy things. They leave to experience things, to be somewhere specific, to feel something, to do something that requires their body to physically be present in a place. You can buy almost anything online, but you cannot ski online. You cannot take your child on a roller coaster through a screen. You cannot feel the cold of manufactured snow on your face from your living room. That single insight became the foundation of everything Dream Plaza is. The decision was locked in at the very start of the design process, and it was irreversible. This would not be a place to buy things. It would be a place to be. The building itself would be the product. Start at the bottom. The indoor theme park occupying the lower floors is not a token entertainment corner. A few arcade machines and a carousel squeezed into leftover space near the escalators. It is a full-scale attraction featuring roller coasters, high-speed rides, and multi-sensory experiences designed for adults and children alike. It runs year-round, regardless of season, regardless of weather, regardless of whatever the city outside is doing. In Wuhan, that matters enormously. Summer temperatures there routinely climb past 35 degrees Celsius, and winters arrive with real force. A venue that depends on pleasant weather might work 3 months out of the year. A fully climate-controlled one earns repeat visitors every single weekend without exception. Move upward through the building, and the temperature starts to drop before you understand why. The snow park, among the first and largest indoor ski facilities in the region when it opened, keeps its floors below freezing around the clock. Families living in a city where natural snowfall is rare and unpredictable can ski, snowboard, or simply play in manufactured powder on any Tuesday in July. That jarring transition, going from a sweltering Wuhan summer to a genuine ski slope in the time it takes to ride a few escalators, is precisely the point. Dream Plaza is selling sensory experiences the city outside its walls simply cannot offer. You want winter? Winter is on the 4th floor. The dining and retail areas are arranged unlike a standard mall. Instead of corridors lined with shops on either side, optimized purely for storefront exposure, the spaces are organized as a series of distinct atmospheric environments, each one designed to feel genuinely different from the last. The design team built the concept around the idea of time travel and the 4 seasons. Moving through Dream Plaza is meant to feel like passing through different eras and different climates. Warm golden zones that evoke high summer, cool blue-toned spaces that recall deep winter, transitional passages that shift the light and mood and texture as you walk. The atmosphere isn't background decoration. It is the architecture. It is what people came for. Beyond the enclosed floors, the complex spills outward into curated open-air areas, a lifestyle and leisure zone designed for adults, and a children's lakeside precinct built around water, open-ended play equipment, and natural shapes. In a dense urban district where green space and real outdoor room for kids is scarce, this isn't a luxury add-on. For families living in surrounding high-rise apartments, it's what turns the building into part of their weekly routine rather than an occasional outing. Now, the sky. The centerpiece of Dream Plaza's central atrium is one of the boldest single design decisions in any commercial building currently operating on Earth. The building doesn't simply provide artificial lighting the way every other indoor space does, fixed overhead sources angled to flatter products and keep shoppers comfortable enough to linger. It provides an artificial sky. A dynamic overhead display system spans the full width of the atrium, simulating the complete arc of a day. It moves from pale early morning blue, through warm midday amber, into the deep orange and violet of late afternoon, and finally into a simulated night sky as the building's evening hours begin. The sun that crosses the interior isn't a spotlight. It is a calibrated system designed to reproduce the quality and character of natural daylight, the specific kind of light human biology uses to track time, regulate mood, and maintain the circadian rhythm that governs energy, sleep, and even appetite. This matters more than it first appears. Every large enclosed building, every shopping center, every airport, every windowless venue is quietly fighting the same biological reality. Human beings are profoundly sensitive to their light environment. When that environment stops signaling what time it is, people's relationship with the space starts to break down. They tire faster. They become subtly disoriented. They want to leave. The artificial sky is engineered to prevent exactly that. It gives the building a pulse, a rhythm, a sense of time genuinely passing, which makes spending hours inside feel less like confinement and more like inhabiting a real place. It's worth pausing on how counterintuitive this is. Casino designers famously stripped windows and clocks from gambling floors, deliberately severing guests from any sense of time to keep them inside longer. Dream Plaza did the precise opposite. It introduced a complete simulated day-night cycle into a building where every door opens onto another interior room. One approach traps you by making time vanish. The other holds you by making time feel real. Both work, but only one of them also earned an international award for Best Retail Interior Design. Wuhan deserves a closer look because it is far more significant a city than most people outside China realize. With a population of around 12 million, Wuhan is one of the largest urban centers in China's interior. It sits at the meeting point of the Han and Yangtze rivers, a geographic position that made it a critical trading hub for centuries and continues to make it one of China's most important logistics nodes today. Dozens of universities are based here, A major industrial and manufacturing base operates here. A fast-growing technology sector has taken root here. This is not a secondary city playing catch-up. It is a city that has spent decades building the infrastructure and institutional weight to compete at the very top of China's urban hierarchy. The Eastern District, where Dream Plaza was built, is the densest and most historically significant of Wuhan's three main urban cores. Dropping a building of this scale into that district was not the speculative gamble that defines so many Chinese megaprojects, where enormous structures rise on the urban fringe and then wait years for the surrounding population to catch up. Dream Plaza opened in an already dense, already commercially active neighborhood, surrounded by millions of existing residents with disposable income and a clear appetite for experiential spending. When it a specific reason, it breaks with conventional mall logic, not just in what it contains, but in how it expects people to move through it. Standard commercial architecture is built on one overriding principle: maximize exposure. Every shopper who enters should pass as many storefronts as possible. Corridors are kept straight so sightlines stretch further. Escalators are positioned to pull foot traffic through peripheral zones. Floor plans are arranged so the route to the supermarket or cinema runs through 3 departments you never intended to visit. Every decision is optimized to ensure the path to wherever you're going routes you past as many things you weren't planning to buy as possible. This is effective retail science, and it has driven billions in unplanned purchases for 60 years. But it is also, increasingly, the wrong approach for a generation that grew up in information-saturated environments and has become highly skilled at recognizing and resisting the feeling of being managed. Dream Plaza's internal geometry is curved, branching, and deliberately non-linear. There are no long, straight corridors. Routes turn unexpectedly into plazas, open into soaring double-height atriums, narrow into intimate passages, then expand again. Navigation isn't optimized for efficiency. It's optimized for surprise. The underlying assumption is no longer that you came to reach a specific destination. The assumption is that you came to see what happens next. The building rewards wandering. It withholds its best moments until you've earned them by moving through something else first. Here, the journey genuinely is the destination, in the most literal architectural sense. The four-season atmospheric concept pushes this even further. Stepping from a warm, gold-toned environment into a cool, wintry blue one acts as a sensory reset, a way of making an 800,000 square meter building feel like it holds multiple distinct worlds, rather than one endless commercial space. It's the difference between a building that is merely enormous and one that somehow feels larger than its own floor plan. Dream Plaza is extraordinary, but it is also, in ways its designers haven't fully resolved, a set of open questions wearing the clothing of a solution, and the same features that make it remarkable also make it, in certain respects, genuinely fragile. That fragility doesn't show up in the steel frame or the foundations, it shows up in the assumptions the entire project rests on. The first is environmental. Keeping a snow park below freezing in a city where summers exceed 35 degrees is an enormous continuous energy commitment. Running a dynamic artificial sky, a full-scale theme park, a cinema, climate-controlled retail across 13 floors, and an outdoor lakeside precinct, all at once represents an energy demand that would be striking even before you account for the tens of thousands of daily visitors, adding to the heating, cooling, and ventilation load on every system in the building. Detailed energy consumption figures haven't been published, so the true environmental math is genuinely unknown. It may turn out to be more efficient per visitor than a city full of smaller, scattered venues. It may not. For now, no one can say for certain. The second question is economic. The experiences that make Dream Plaza feel exceptional today were new in 2022. The ski slope was novel, the artificial sky was astonishing, the indoor roller coasters were reason enough to cross the city and spend a Saturday. But what are they in 2030? In 2035? The history of experiential venues is full of attractions that felt revolutionary at opening and felt tired within a decade. Keeping genuinely novel experiences alive isn't only a financial cost, it's a creative one. Dream Plaza will have to keep reinventing itself, keep adding fresh reasons to return, or risk the same slow attrition that killed the conventional mall it was designed to replace. The artificial sun will keep rising. The real question is whether people keep finding a reason to come watch it. The third question is the most thought-provoking, and it's one cities everywhere should probably be asking more openly. Dream Plaza is, among other things, a machine for not leaving. Everything a family might want for an entire day. Exercise, entertainment, food, play, shopping, spectacle, outdoor space sits inside a single set of walls. The incentive to engage with the rest of the city is reduced by exactly the degree to which Dream Plaza succeeds at replacing it. Cities aren't just collections of services and amenities. They're systems where people encounter one another in unplanned ways, where public space generates the kind of spontaneous social friction that builds community over time. A building that substitutes for the city, rather than serving it, raises a question urban planners haven't yet answered. What happens to the street when the building beside it becomes more appealing than the street itself? Here is the honest version of what Dream Plaza is. It is not a mall. It is not a theme park. It is not a hotel complex or a civic center or an entertainment district. It is the first generation of a new kind of building that doesn't yet have a widely agreed upon name, a type that will very likely define how the world's most ambitious cities approach their downtown cores for the next several decades. Every major city on Earth is wrestling with the same fundamental question. What do you build at the heart of a dense urban district when buying things online is easier than going to a store? When entertainment competes directly with the device in everyone's pocket? When the bar for what counts as a good enough reason to leave the house has risen to a level no urban planner 50 years ago would even recognize? The answer most Western cities have offered is to wait and see, to rezone incrementally and hope that coffee shops, farmers markets, and creative offices fill the void left by departing retailers. That answer largely isn't working. Dream Plaza's answer is the opposite. Build something a screen cannot replace. Build an environment so deliberately physical to the idea that time is passing, that this moment will end, and that there's nowhere else they'd rather spend it. Whether that answer holds for a generation is something 12 million people in Wuhan will decide with their feet, weekend after weekend, for years to come. For now, the artificial sun inside Dream Plaza rises every morning. And for now, people keep coming to stand beneath it. China has demonstrated a new way to turn seawater into drinking water using sunlight instead of electricity from the grid. Researchers built an outdoor system covering less than 1 square meter. Under natural sunlight, the prototype reportedly produced just over 20 liters of fresh water per day. That is enough to cover the basic daily drinking water needs of roughly 10 people. The collected water met international drinking water standards, and the researchers even used it to irrigate a small test field through complete crop growing cycles. But the most important part is not simply that sunlight can evaporate seawater. Humans have known that for thousands of years. The breakthrough is the material inside the device. Chinese researchers created a three-dimensional photothermal structure designed to absorb sunlight, concentrate heat at the water's surface, accelerate evaporation, and operate without being connected to the electrical grid. In laboratory testing, the material reached an evaporation rate of 38.14 kilograms of water per square meter every hour. That was more than 8 times the performance of the researchers' earlier flat design. The system also absorbed more than 90% of incoming sunlight and reportedly reduced the energy needed for evaporation by nearly 46%. If the technology can be scaled reliably, it could provide drinking water to islands, coastal villages, farms, and disaster zones where large desalination plants are too expensive or where electricity is unreliable. But can a small solar prototype really compete with industrial desalination? Or is this another impressive laboratory result that becomes far more difficult once engineers try to build it at useful scale? To answer that, we need to understand why turning seawater into drinking water remains so expensive. Why desalination needs so much energy. The ocean contains an almost unlimited supply of water. But seawater also contains salt, minerals, microorganisms, and other contaminants that humans cannot safely drink in large quantities. Removing those substances takes energy. The most common modern method is reverse osmosis. A desalination plant uses powerful pumps to force seawater through membranes containing extremely small pores. Water molecules pass through, while most dissolved salts are blocked. The process works well and is used in large facilities around the world, but it requires high pressure. Creating that pressure consumes electricity, and the plant also needs pre-treatment equipment, filters, pumps, membranes, monitoring systems, and maintenance. Another approach uses heat. Seawater is evaporated, leaving salt behind, and the water vapor is then condensed into clean liquid. This resembles the natural water cycle. The sun evaporates ocean water, clouds form, and fresh water returns as rain. Industrial thermal desalination can produce large amounts of water, but heating that much seawater consumes enormous quantities of energy. That is why researchers are interested in solar evaporation. Instead of heating an entire tank of water, a photothermal material absorbs sunlight and concentrates the heat only where evaporation happens. The goal is to generate water vapor while wasting as little energy as possible. How the Chinese material works. The new system uses a three-dimensional photothermal structure. Photothermal simply means that the material converts light into heat. A flat, dark surface can already do this. Leave a black object in direct sunlight and it becomes hot because it absorbs more light than a reflective surface. But a high-performance solar evaporator needs to do much more. It must absorb a wide range of sunlight. It must transfer heat into a thin layer of water instead of heating the entire reservoir. It must continuously pull fresh seawater toward the evaporation surface. It must allow water vapor to escape. And it must prevent salt from blocking the structure. The Chinese team developed a three-dimensional design with a much larger active surface than a conventional flat absorber. That extra surface area allows more water to interact with the heated material at the same time. The structure also helps confine heat near the evaporation zone. Instead of allowing thermal energy to spread into the bulk seawater, more of the captured sunlight is used directly to change liquid water into vapor. The researchers reported solar absorption of up to 90.2%. They also said the design reduced the effective energy required for evaporation by 45.7%. That does not violate physics or create energy from nothing. Water molecules still need energy to escape the liquid. The material changes how efficiently heat is delivered and may also alter the local interaction between water and the internal surfaces. The result is faster evaporation from the same amount of sunlight. The 38.14 kilogram result. The headline laboratory number was 38.14 kilograms per square meter per hour. Because 1 kilogram of water is approximately 1 liter, that sounds like the device could produce more than 38 liters of drinking water every hour from 1 square meter. But that interpretation would be misleading. The figure describes the measured evaporation rate under controlled test conditions. Evaporated water is not automatically collected drinking water. A complete system must capture the vapor, move it toward a cooler surface, condense it into liquid, and store it without contamination. Every step introduces losses. Laboratory illumination may also differ from changing outdoor sunlight. Clouds, wind, temperature, humidity, and the angle of the sun all affect real-world output. That is why the outdoor prototype is more important than the laboratory record. The real outdoor prototype. The researchers constructed a system with an active area of approximately 0.75 square meters. It was tested outside using natural sunlight rather than a controlled indoor lamp. The complete device produced 20.16 liters of fresh water in 1 day. That is far lower than multiplying the peak laboratory evaporation rate across 24 hours. But it is a much more meaningful figure because it represents water actually collected by a working outdoor system. 20 liters is not enough for the complete daily water use of 10 people. Cooking, washing, sanitation, and agriculture require far more. But it may cover basic drinking needs. That could matter in remote places where fresh water must currently be transported by truck or boat. A small village could use several modules. A disaster relief team could deploy portable systems where the power grid has failed. Coastal farms might use larger arrays to supplement irrigation water. The system would still depend on weather and sunlight, but it could operate without the continuous electricity demand of a conventional reverse osmosis plant. What no grid power really means. The device is sometimes described as electricity-free. That wording needs context. The system does not operate without energy. Its energy comes from sunlight. The photothermal material absorbs solar radiation and converts it into heat. The correct claim is that the prototype can produce water without being connected to an external electrical grid. That is an important difference. A reverse osmosis plant may require continuous electricity for pumps. A solar evaporator can operate passively during daylight. However, a larger commercial system might still use small pumps, sensors, fans, or automated controls. Electricity could also be useful for moving seawater, collecting water, cleaning equipment, or operating at night. The central advantage is not that electricity becomes forbidden. It is that the main energy-intensive step, evaporation, is driven directly by the sun. The salt problem. Salt is one of the biggest obstacles facing solar desalination. When water evaporates, dissolved salt remains behind. As evaporation continues, the water near the surface becomes increasingly concentrated. Eventually, salt crystals can form on the photothermal material. Those crystals block sunlight, restrict water movement, and damage performance. A laboratory device may work well for several hours and then become far less effective after days of salt accumulation. Any practical solar evaporator needs a way to manage concentrated brine. Some designs allow salt to diffuse back into the larger seawater reservoir. Others use channels that continuously circulate water through the structure. Some devices are periodically flushed, while others are designed so that salt crystallizes in a separate location where it can be removed. Long-term durability will be one of the most important tests for the Chinese system. The prototype must prove that it can operate through repeated wetting, drying, heating, and salt exposure without losing performance. Coastal seawater also contains biological material and minerals that may clog surfaces over time. Producing water for one successful demonstration is different from operating every day for several years. The farming test. The researchers did not stop after measuring the water in a container. They used the fresh water to irrigate a test field covering approximately 5 square meters. The system reportedly supported complete crop growing cycles. That experiment matters because agriculture is the world's largest user of fresh water. Many water-stressed regions are located near oceans, but seawater cannot be applied directly to most crops. Salt builds up in soil, damages roots, and eventually makes farmland unproductive. A modular solar desalination system could provide small quantities of fresh water for greenhouses, seedlings, or high-value crops. It would not immediately replace the enormous irrigation networks used for rice, wheat, or corn. Those systems move thousands or millions of liters. But it could be valuable for remote islands, desert communities, or small coastal farms where every liter of clean water is expensive. The cost claim. The researchers estimate that after roughly 2 years of operation, the cost of the produced water could fall below the price of commercial bottled water. That is a projection, not a confirmed market price. Bottled water is also an easier benchmark to beat than municipal tap water. Bottled water includes packaging, transport, storage, and retail profit. A large reverse osmosis plant may produce water at a much lower cost per liter than bottled water, especially when operated at enormous scale. The true economics will depend on the cost of the photothermal material, the condenser, supporting structure, maintenance, cleaning, lifetime, and installation. If the device needs frequent replacement, the water will be expensive. If it survives for years with little maintenance, the economics become much stronger. Local conditions will also matter. In a city with an established water network, the system may not compete with tap water. On an isolated island where bottled water arrives by boat, it could be far more attractive. Can it scale? Scaling is the central question. A 0.75 square meter prototype can be carefully assembled and monitored by researchers. A commercial system may need hundreds or thousands of square meters. Every module must distribute seawater evenly. Vapor must be collected efficiently. Condensation surfaces must remain cool enough to turn vapor back into liquid. Strong winds, storms, dust, salt spray, and biological growth must not destroy the equipment. The system must also dispose of concentrated brine responsibly. Large desalination plants return salty waste to the ocean, where it can damage local ecosystems if it is not properly diluted. A solar system produces less water per unit, but a large field of modules could still create a significant waste stream. Manufacturing is another challenge. The photothermal structure must be cheap enough to produce in large quantities. A material with excellent laboratory performance may rely on complicated fabrication steps that make commercial production too expensive. Engineers will need to simplify the design without losing the properties that created the high evaporation rate. Where it could be used first. The technology is most likely to succeed first in places where water is valuable and electricity is limited. Small islands are one obvious market. Many islands have abundant sunlight and seawater, but depend on imported fuel or bottled water. Remote coastal villages could use modular units for drinking and cooking. Disaster zones are another possibility. Earthquakes, floods, and storms can damage power lines and contaminate freshwater supplies. Portable solar desalination equipment could begin producing water without waiting for the electrical grid to be restored. Military bases, research stations, ships, and offshore facilities may also value systems that reduce dependence on transported water. Agriculture could become another market if the device is combined with water storage and efficient drip irrigation. But the technology is unlikely to replace giant municipal desalination plants immediately. Cities need reliable water every hour of the day, regardless of weather. Large reverse osmosis facilities already produce hundreds of millions of liters daily. Solar evaporation will probably begin as a supplement rather than a complete replacement. My take is that this is a promising water technology, but the 20-liter outdoor result matters more than the spectacular laboratory number. The researchers have shown that the material can move beyond a small indoor sample and produce usable freshwater under natural sunlight. That is an important step. The system could be especially valuable where transporting water is expensive and grid electricity is unavailable. But it is not yet proof that China has solved global water scarcity. The prototype is small. Long-term salt resistance still needs to be demonstrated. The manufacturing cost must fall. and larger systems must show that they can collect and condense vapor efficiently in real weather. Still, the concept attacks one of desalination's biggest problems directly. Instead of spending large amounts of electricity pushing seawater through membranes or heating enormous tanks, the system uses a carefully designed material to place solar heat exactly where evaporation occurs. The ocean provides the water. The sun provides the energy. The material connects the two. If China can turn that laboratory efficiency into durable mass-produced equipment, the technology could give remote communities a new source of drinking water without waiting for a power plant or a massive pipeline. So what do you think? Could sunlight-powered desalination become a practical solution for water-stressed coastal regions? Or will scaling, salt, and maintenance keep it limited to small installations? Let me know your view in the comments. And subscribe to Eastern Engine for more grounded coverage of the technologies, factories, and engineering decisions reshaping the global economy. Because China has not eliminated the cost of desalination, but it may have found a way to replace part of that cost with sunlight. China's memory crisis is spreading into a part of the semiconductor industry most people barely notice. A Chinese supplier called Generative Semiconductor has reportedly told distributors that prices across its entire NOR flash product portfolio will rise by 25% beginning July 6th. The increase applies not only to newly signed orders, but also to outstanding orders that have not yet been delivered. That is a major move for a component that usually receives far less attention than RAM. High bandwidth have already surged sharply during the first half of 2026. Artificial intelligence infrastructure is absorbing investment, factory space, and customer attention. Automotive and edge AI systems are demanding larger amounts of dependable embedded memory. And now one Chinese supplier is adding another 25% to its price list. The question is whether this is a temporary adjustment from one company, or whether the global memory shortage is moving into the overlooked chips that keep the world's electronics running. What NOR flash actually does. NOR flash is not the same as the DDR5 memory inside a gaming computer. It is also different from the NAND flash used inside an SSD or smartphone storage drive. The easiest way to understand NOR flash is to think of it as instruction memory. When a device powers on, it needs a trusted place to find the first code it will execute. That code may initialize the processor, check connected hardware, load safety settings, verify security keys, and prepare the operating system. NOR flash is well suited to that job because it keeps data when power is removed and allows fast, direct access to stored instructions. A vehicle may use NOR flash inside electronic control units, infotainment systems, driver assistance computers, cameras, radar modules, telematic systems, and digital instrument clusters. A network switch may use it to store boot firmware and configuration code. An industrial robot may depend on it for control software that must survive vibration, heat, and years of continuous operation. A product containing powerful processors and expensive sensors can still become unusable if its boot memory is missing, unreliable, or delayed. Why prices are rising now? Mature memory products such as NOR flash and SLC NAND are often manufactured on older process technologies. Those production lines remain useful, but they do not generate the same excitement or margins as advanced AI memory. Large semiconductor manufacturers are investing heavily in high-bandwidth memory, enterprise SSDs, advanced DRAM, and newer NAND products. Those categories are being purchased in enormous quantities by cloud companies building AI infrastructure. Factory equipment, engineering teams, capital budgets, and wafer capacity are therefore moving toward the products with the highest demand and profit. But suppliers have little incentive to build large amounts of new mature node capacity when investors and customers are focused on AI. Modern cars contain more electronic systems than ever. Digital cockpits, advanced driver assistance, connectivity, over-the-air updates, cameras, radar, battery management, and intelligent lighting all require firmware. Edge AI devices also need more local code because they process information near the user instead of sending everything to a distant cloud. As software grows more complex, manufacturers move toward higher density NOR flash products. That creates pressure on a market where supply is already becoming less flexible. The 25% increase. According to current industry reporting, Generative new prices take effect on July 6th. The increase covers the company's full NOR flash portfolio and applies to both new orders and undelivered existing orders. Normally, customers may assume that an accepted order protects them from a later price adjustment. Applying the new price to outstanding shipments suggests that the supplier sees the market tightening quickly enough to reset terms immediately. It does not mean every NOR flash manufacturer has raised prices by exactly 25%. It does not mean every chip buyer will pay the same amount. Large customers may have long-term contracts, negotiated allocations, or different product mixes, and a 25% increase in one component does not mean the final price of a car, server, or router will rise by 25%. The decision signals demand strong enough and availability limited enough to raise prices across an entire category without waiting for the next pricing quarter. A broader memory shock. TrendForce says contract prices for NOR Flash and SLC NAND rose by more than 100% during the first half of 2026. It expects additional increases during the second half because major new capacity is not arriving quickly. When demand suddenly rises, manufacturers can sometimes solve the problem by running existing factories harder or releasing inventory. That becomes difficult when the underlying production base is shrinking. Mature memory is not the highest growth destination for semiconductor investment. High-bandwidth memory can sell for far more than a small embedded flash chip. Enterprise SSDs are being purchased through large multi-year agreements. Advanced server memory is receiving priority because cloud companies are willing to pay to secure supply. The result is that mature products can become scarce, even when total global memory investment is rising. The industry is building more memory, but not necessarily the specific kinds every customer needs. Why cars are exposed. Automotive companies are especially vulnerable because they cannot replace a qualified memory chip overnight. A consumer gadget manufacturer may redesign a board or switch suppliers relatively quickly. A vehicle component must pass demanding validation for temperature, vibration, reliability, and long operating life. Changing one part can require new testing, software verification, documentation, and approval. Automakers also need predictable supplies for many years because vehicles remain in production and require replacement parts after sales end. This dependence gives approved suppliers more pricing power when capacity tightens. Driver assistance systems need firmware for sensors and processing units. Connected vehicles need secure boot functions and update mechanisms. Higher levels of automation can increase the number and complexity of electronic modules. A shortage of relatively inexpensive NOR flash can therefore interrupt production of a much more expensive vehicle. Factories were forced to slow or stop because one missing controller or memory device prevented an entire car from being completed. AI servers are next, but with context. The title says cars and AI servers are next. That does not mean NOR flash will replace HBM or become the largest memory cost inside an AI server. Servers, network switches, accelerators, storage controllers, power systems, and management boards all require firmware. As AI data centers expand, they install enormous numbers of devices that must boot, authenticate, communicate, and recover reliably. Every additional server rack contains many embedded systems. The amount of NOR flash per device may be modest, but the number of devices is growing rapidly. AI clusters depend on high-speed switches, optical modules, smart network cards, and management controllers. These systems use dependable code storage for startup, configuration, diagnostics, and updates. Edge AI hardware creates another source of demand. Cameras, robots, industrial computers, vehicles, and smart appliances increasingly run models locally. That requires more sophisticated firmware and often larger embedded memory capacities. So AI contributes to the shortage in two ways. It pulls investment toward premium memory such as HBM and enterprise NAND. At the same time, it increases demand for the smaller firmware chips used throughout the infrastructure. China's position. Giantech is not the largest memory company in the world. Samsung, SK Hynix, Micron, Kioxia, and other major suppliers control far larger portions of global memory production. But China has been expanding its presence in mature and embedded semiconductor categories. That matters because domestic customers want secure supplies for vehicles, communication systems, industrial equipment, and consumer electronics. Chinese technology companies are also trying to reduce dependence on foreign components where possible. A stronger domestic NOR flash industry can support that goal. Yet higher Chinese prices show that localization does not automatically mean cheap supply. Domestic manufacturers still respond to capacity, demand, equipment costs, yields, and market conditions. If Chinese automakers and electronics companies compete for the same limited output, prices can rise inside China even while production expands. The shortage could benefit suppliers through higher margins. It could also encourage investment in additional capacity. But new semiconductor output takes time. Equipment must be ordered, installed, qualified, and operated at acceptable yields. Customers must test the finished chips. The market may remain tight long before any new line reaches meaningful volume. Du Chu pays the final bill. The immediate buyers are distributors, module makers, electronics manufacturers, and system suppliers. They must decide whether to absorb the higher cost or pass it onward. For an expensive vehicle or server, one NOR flash chip may represent only a small fraction of the final price. Manufacturers may instead accept lower margins. They may negotiate with suppliers, reduce inventory, delay projects, or redesign future products around alternative parts. Smaller companies have fewer options. They purchase lower volumes, possess less negotiating power, and may not have second sources already approved. They could face longer delivery times or steeper price increases. The most serious risk is not the added cost of one chip, it is interruption. A missing component can delay an entire board, controller, machine, or vehicle. Companies may therefore pay a premium simply to guarantee allocation. This behavior can make the shortage worse because customers order earlier and hold more inventory than usual. What could end the shortage? Several developments could weaken the price surge. Demand for AI hardware could slow. Automotive production could weaken. Customers could reduce memory capacity or redesign products to use alternative devices. Manufacturers could reopen older lines, improve yields, or shift capacity back toward mature products. Chinese suppliers could expand faster than expected. But each solution has limits. Redesigns take time. Automotive qualification is slow. Building capacity is expensive. And suppliers may prefer to keep production disciplined rather than create another oversupply cycle. Memory companies remember what happens when too many factories chase temporary demand. Prices collapse, inventories rise, and expensive equipment sits underused. That history encourages caution. The market may eventually balance, but buyers should not assume prices will return quickly to previous lows. What this does not prove. One supplier's notice is not proof that every electronics category faces an immediate crisis. Generative increase must be separated from broader claims. We do not know the exact price paid by every customer. We do not know how much inventory distributors currently hold. We do not know whether competitors will match the full increase. And we do not know how long the new pricing will remain in place. The report is best understood as evidence that pressure has reached another memory category. NOR flash was once treated as a stable, mature component. Now it is being affected by the same forces reshaping DRAM, NAND, HBM, and enterprise storage. AI demand is changing investment priorities across the entire memory supply chain. My take is that the 25% increase matters less as an isolated number than as a warning. The memory supercycle is spreading outward. It began with the obvious products: HBM for accelerators, server DRAM, and enterprise SSDs. Now pressure is reaching the smaller chips that store the code required to start cars, routers, robots, and industrial systems. These devices are not glamorous. They do not appear in benchmark charts. Most consumers will never know which company made them. But modern hardware depends on them. Generative decision shows that mature memory can become strategically important precisely because the industry spent years treating it as ordinary. Supply is limited, qualification is slow, demand is becoming more sophisticated, and manufacturers are focusing investment elsewhere. That combination creates pricing power. The final impact may not be a dramatic 25% increase in the price of a car or server. It may appear as delayed production, smaller margins, redesigned products, and manufacturers paying more to secure guaranteed supply. China's domestic memory industry could eventually add enough capacity to ease the pressure. But today, one of its own suppliers is signaling that the shortage remains strong. So what do you think? Is the NOR flash increase another temporary spike? Or is it proof that the AI memory crisis is reaching every layer of modern electronics? Let me know your view in the comments. And subscribe to Eastern Engine for more grounded coverage of the chips, factories, and engineering decisions reshaping the global economy. Because the next hardware bottleneck may not be the processor everyone watches. It may be the tiny memory chip that tells that processor how to start. There is a country that most of the world rarely thinks about when the conversation turns to ambitious engineering. And yet, over the past few decades, this country has quietly been building some of the most surprising infrastructure projects on the planet. Projects that, in many cases, barely register in international headlines. We are talking about the largest shopping complex on Earth, a railway network spanning 15,000 kilometers, an underground metro system so visually striking that travelers stop walking just to look at the ceilings, a car manufacturing industry that ranks among the 15 largest in the world, and perhaps the most audacious project of all, an effort to take seawater from the ocean and move it hundreds of kilometers inland to transform desert into livable land. That country is Iran. And whatever your views on its politics, the scale of what its engineers have built is genuinely worth understanding. This video is going to walk through these projects one by one, and some of them get more remarkable the deeper we go. Let's start with the one that sounds most unbelievable. When people think of the world's biggest malls, they usually picture Dubai or the United States. The actual record holder sits next to Chitgar Lake in northwest Tehran. Iran Mall covers nearly 2 million square meters across 7 enormous floors, making it the largest shopping complex in the world by total area, larger even than the famous Dubai Mall. The construction effort required more than 25,000 workers and over 1,000 contractors. At one point during the build, crews poured concrete continuously for 6 straight days, setting a Guinness World Record for the largest continuous concrete pour. But the scale is not really the interesting part. The interesting part is what is inside. The complex houses 12 cinemas, including IMAX screens, a full Olympic-sized ice rink, a 2,000-seat theater, a luxury hotel, a convention center, and rooftop sports courts. It also contains a library holding over 45,000 books and manuscripts, a mirror hall constructed from an estimated 38 million individually crafted mirror pieces, and a traditional bazaar designed to echo the historic markets of Isfahan, Shiraz, and Tabriz. The intention was never to build a simple shopping destination. It was a global architectural sensation, designed by an architect who was only in her 20s when she conceived it. Layla Aragian was a young Iranian architect when she looked at a busy highway cutting between 2 parks in Tehran and asked a deceptively simple question. What if a bridge could become part of the natural landscape rather than just passing over it? The result was the Tabiat Bridge. Tabiat means nature in Persian, and the structure lives up to the name. It stretches 270 meters in length and rises 40 meters above the highway below, with 3 full levels containing walking paths, cafes, seating areas, and open viewing platforms offering panoramic views of Tehran and the snow-capped Alborz Mountains. 3 large supporting columns hold the structure up, deliberately shaped to resemble trees with branches spreading outward to echo the surrounding parks. The engineering is serious. Roughly 2,000 tons of steel and 14,000 individually cut components, designed to withstand earthquakes above magnitude 7 and built to last a century. The bridge has won several of the most prestigious architecture awards in the world, including the Aga Khan Award for Architecture. In its first year alone, around 4 million people visited, and most of them did not come to cross from one park to the other. They came simply to experience the structure itself. Iran's railway story stretches back nearly a century and connects to one of the most impressive engineering legacies in the region. The country operates a railway network spanning roughly 15,000 kilometers, one of the largest in the Middle East. That network moves tens of millions of tons of freight and tens of millions of passengers every year. And its foundations are remarkably old. The original Trans-Iranian Railway was constructed between 1927 and 1938. It crossed 2 mountain ranges and 4 distinct climate zones, requiring 174 major bridges and 224 tunnels to complete. It is now recognized as a UNESCO World Heritage Site, a testament to engineering ambition that predates most modern construction technology. What is striking about Iran's infrastructure culture is the speed of repair when something goes wrong. There are documented cases of major railway bridges being restored to operational status within a matter of days, rather than the months such work typically takes elsewhere. A civilization with thousands of years of building history tends to approach repair and reconstruction with a particular kind of practiced efficiency. Beneath the streets of Tehran sits a transportation system that very few people outside Iran are aware of, and it ranks as the largest metro network in the Middle East. More than 3 million passengers ride the Tehran metro every single day. The system includes over 310 kilometers of track and more than 160 stations, with trains arriving every 3 minutes during peak hours. The expansion plans are ambitious. By 2040, the network is projected to reach 500 kilometers of track and 330 stations across 11 lines. But what makes the system genuinely remarkable is the design of the stations themselves. Many of them feel less like subway platforms and more like underground galleries, featuring Persian mosaics, intricate geometric ceilings, detailed artwork, and grand halls that prompt passengers to pause and look around. The system is also impressively modern in its features: fully accessible stations, smart card and QR code ticketing, dedicated carriages, and comprehensive security infrastructure. In 2022, Iran unveiled its first fully domestically manufactured metro train set, certified to meet European safety standards, with passenger service beginning in 2024, and the fare for a ride of any distance remains remarkably low by international standards. One station in particular drew worldwide attention when it opened in October 2025. The Maryam-e-Moghada station, named in honor of the Virgin Mary, the mother of Jesus in Christian tradition, was built with an architectural style that blends Persian geometric design with church-inspired elements. The station features vaulted arches, a large decorated dome, religious frescoes, and sculptures referencing Christian iconography. It took roughly a decade to complete, and when photographs of the station spread online, they captured global interest precisely because of the cultural blend it represented. A thoughtful piece of architecture, honoring a figure revered across multiple faith traditions. Iran's rail offering extends well beyond commuter transport. One of its premium long-distance services has earned a reputation that rivals luxury hotels. The Fadak Express is often described by Iranians not as a train but as a moving five-star hotel. It runs at speeds up to 200 kilometers per hour, connecting Tehran with Mashhad, Shiraz, and Qom. Its coaches were comprehensively redesigned under the supervision of a Swiss engineering firm, with upgraded air conditioning, electrical systems, and interiors built around a combination of Iranian aesthetics and high-end comfort. Each private compartment accommodates only 4 passengers and comes fully equipped with an entertainment system, charging outlets, and sound insulation effective enough that the movement of the train is barely audible. Meals are included in the ticket price, with catering quality compared to some of Iran's finest restaurants. The service offers 5 travel classes, ranging from economy to a premium tier that includes dinner and a hotel stay. The result has been a notable shift in traveler behavior. People who previously flew between Iranian cities began choosing the Fadak instead, not because it was cheaper, but because the overall experience was simply more pleasant. While Iran is rarely associated with car manufacturing in global conversation, the country has quietly developed an automotive sector that ranks among the largest in the world. Iran Khodro, commonly known as IKESO, was founded in 1962. Today, Iran ranks as roughly the 13th largest automobile producer globally, manufacturing more than 1.3 million vehicles annually. IKESO sits at the center of that production, and its vehicles are notable for being designed specifically for Iranian conditions rather than simply assembled from foreign designs. The Samand became Iran's national vehicle and was exported to countries including Venezuela, Belarus, and Azerbaijan. The Dena, named after a peak in the Zagros Mountains, featured a turbocharged engine producing around 150 horsepower. The Runa was developed as domestic intellectual property and proved successful enough to be adopted as a national vehicle in Tunisia. And in 2024, IKESO unveiled the Rira, including a fully electric variant. That last detail is worth pausing on, because Iran was experimenting with electric vehicle development as far back as 2010, well before electric cars became a mainstream topic across much of the region. Beyond passenger vehicles, the Baumann Group, founded in 1952, has built an export business in trucks and vans serving markets across multiple continents. One of Iran's most significant energy infrastructure projects involves a pipeline designed to connect it with neighboring Pakistan. The Iran-Pakistan gas pipeline, sometimes called the Peace Pipeline, was designed to carry natural gas from Iran's South Pars field, one of the largest natural gas fields on Earth, across roughly 2,700 kilometers to Pakistan. Iran completed its 1,100-kilometer section by 2012, on schedule using domestic engineers and technology. Pakistan's portion of the project, however, has faced extended delays for a range of complex political and economic reasons. The Iranian section sits ready, the gas is available, and the two neighboring countries have a clear complementary need, one with abundant gas supply, the other with significant energy demand. Many regional energy analysts have noted that if the obstacles to completion were resolved, the project could become one of the more impactful energy initiatives in the region, potentially supplying gas to millions of homes and supporting industrial activity. For now, the infrastructure on the Iranian side waits, a completed piece of engineering held back primarily by factors outside the realm of construction. Here is where Iran's ambition becomes genuinely remarkable, because the country faces a fundamental geographic challenge. A large majority of its territory is arid desert, and much of its rainfall occurs along coastal regions far from where tens of millions of people actually live. Iran's response has been to engineer its own water security on a massive scale. The country has constructed more than 600 dams, which at one point ranked it among the top 3 dam-building nations in the world. Collectively, these dams store an enormous volume of water, making Iran one of the largest water storage nations in its region. The flagship of this effort is the Karkhe Dam, the largest dam in Iran and one of the largest in the Middle East. It generates electricity, irrigates agricultural land, and manages billions of cubic meters of water, built largely through domestic engineering expertise. But storing water solved only part of the problem. The water existed. It was simply in the wrong place geographically. So Iran undertook one of its most ambitious projects yet, moving water from the sea to the dry interior. At the center of this effort is an interbasin water transfer system anchored by a large desalination network near Bandar Abbas. Built by Iranian engineers using domestic technology, the system draws water from the Persian Gulf and the Sea of Oman and pumps it through roughly 3,700 kilometers of pipelines to reach drought-affected provinces in the interior. To put that distance in perspective, it is longer than the distance from London to Cairo. The main desalination hub alone can produce around 1.5 million cubic meters of fresh water per day, with longer-term plans to serve tens of millions of people across dozens of facilities. A significant portion of the supporting infrastructure, including a major plant on Chesham Island, was constructed using domestically produced components, in part because importing certain parts was not an option, so Iranian engineers manufactured them locally. This is the project that gives the video its title. The idea of taking ocean water and forcing it hundreds of kilometers inland to make the desert livable sounds almost impossible. Iran is doing it. Moving and processing that much water requires enormous amounts of energy, and Iran's answer included nuclear power. The Bushehr nuclear power plant holds the distinction of being the first civilian nuclear facility in the Middle East. Its history is unusually long and complicated. Construction was initially started by a German firm in 1975, then abandoned after the political changes of 1979, and the site sat incomplete for decades. The plant was eventually completed with Russian assistance and connected to Iran's power grid in 2011, more than 3 decades after work first began. Since then, it has produced tens of billions of kilowatt-hours of electricity. 2 additional units are currently under construction, and Iran has set a long-term goal of significantly expanding its nuclear generation capacity over the coming decades. The story of Bushehr is, in many ways, a microcosm of Iran's broader infrastructure approach. Projects that take a very long time, face repeated setbacks, and get completed anyway. What strikes me most about all of these projects, when you lay them out together, is the underlying pattern. Iran's engineering culture seems to operate on a principle of self-sufficiency that has produced genuinely impressive results, regardless of external constraints. When parts could not be imported, engineers manufactured them domestically. When a needed technology was not available, the country developed its own version. The Tabiat Bridge, the desalination pipelines, the domestically built metro trains, the car industry. Across all of these, there is a consistent theme of building capability internally, rather than waiting for external solutions. I find that fascinating from a pure engineering standpoint, because necessity-driven innovation often produces solutions that are more creative and more durable than projects developed under comfortable conditions. Iran has thousands of years of building history behind it, and that long-term perspective shows up in how the country approaches construction, patiently, ambitiously, and with an apparent willingness to attempt things others consider impractical. Whether these projects reach their full potential will depend on many factors that extend well beyond engineering. But the work itself, viewed purely as feats of construction and design, deserves far more recognition than it typically receives. My question for you is this: which of these projects surprised you the most? The world's largest shopping complex, the museum-like metro stations, or the effort to pipe ocean water across the desert? Let me know in the comments, because I genuinely did not expect some of these to exist before researching this, and I am curious whether you felt the same. If you enjoy deep dives into the engineering and infrastructure stories that most media overlooks, please subscribe to Eastern Engine and turn on notifications. We cover the projects reshaping the world with the depth and curiosity they deserve. There is a lot more coming, and you do not want to miss it. For more than a century, copper has quietly powered the modern world. Every major electrical grid, every data center, every factory, and nearly every computer has relied on copper to move electricity and information from one place to another. It became so essential that most people never stopped to question it. Copper was simply the material everything depended on. But today, something unexpected is happening. As artificial intelligence grows at an incredible pace, the technology that carried us into the digital age is beginning to show its limits. AI systems are becoming so powerful that moving data between thousands of processors has become almost as difficult as performing the calculations themselves. In many of the world's largest AI data centers, chips spend valuable time waiting for information instead of processing it. The processors are getting faster every year, but the connections between them are struggling to keep up. That has created one of the biggest engineering challenges of the AI era. Now, researchers and technology companies around the world are racing to solve it, and one